All right, this is CS50, Harvard University's Introduction to the Intellectual Enterprises of Computer Science and the Art of Programming, back here on campus in beautiful Sanders Theater for the first time in quite a while. So welcome to the class. My name is David May. So my name is David Malin, and I took this class myself some time ago, but almost didn't. It was sophomore fall, and I was sitting in on the class, and I was a little curious, but didn't really feel like the field for me. I was definitely a computer person, but computer science felt like something altogether. And I only got up the nerve to take the class ultimately because the professor at the time, Brian Kernahan, allowed me to take the class pass-fail initially. And that is what made all the difference. I quickly found that computer science is not just about programming and working in isolation on your computer. It's really about problem solving more generally. And there was something about homework, frankly, that was like actually fun for perhaps the first time in, 19 years. And there was something about this ability that I discovered along with all of my classmates to actually create something and bring a computer to life, to solve a problem and sort of bring to bear something that I'd been using every day but didn't really know how to harness, that's been gratifying ever since. And definitely challenging and frustrating. Like to this day, all these years later, you're going to run up against mistakes, otherwise known as bugs in programming, that just drive you nuts and you feel like you've hit a wall. But the trick really is to give it enough time, to take a step back, take a break when you need to. And there's nothing better, I dare say, than that sense of gratification and pride, really, when you get something to work. And in a class like this, present, ultimately, at term's end, something like your very own final project. Now, this isn't to say that I took to it 100% perfectly. In fact, just this past week, I looked in my old CS50 binder, which I still have from some 25 years ago, and took a photo of what was apparently the very first program that I wrote and submitted and quickly received -2 points on. But this is a program that we'll soon see in the coming days that does something quite simply like print hello CS50, in this case, to the screen. And to be fair, I technically hadn't really followed the directions, which is why I lost those couple of points. But if you just look at this, especially if you've never programmed before, you might have heard about programming languages, but you've never typed something like this out, undoubtedly it's going to look cryptic. But unlike human languages, frankly, which were a lot more sophisticated, a lot more vocabulary, a lot more grammatical rules, programming, once you start to wrap your mind around what it is and how it works and what these various languages are, it's so easy, you'll see, after a few months of a class like this, to start teaching yourself subsequently other languages as they may come in the coming years as well. So what ultimately matters in this particular course is not so much where you end up relative to your classmates, but where you end up relative to yourself when you began. And indeed, you'll begin today. And the only experience that matters ultimately in this class is your own. And so consider where you are today. Consider perhaps just how cryptic something like that looked a few seconds ago. And take comfort in knowing just some months from now, all of that will be within your own grasp. And if you're thinking that, OK, surely the person in front of me, to the left, to the right behind me, knows more than me, that's statistically not the case. 2/3 of CS50 students have never taken a CS course before, which is to say you're in very good company throughout this whole term. So then what is computer science? I claim that it's problem solving. And the upside of that is that problem solving is something we sort of do all the time. But a computer science class, learning to program, I think kind of cleans up your thoughts. It helps you learn how to think more methodically, more carefully, more correctly, more precisely. Because honestly, the computer is not going to do what you want unless you are correct and precise and methodical. And so as such, there's these sort of fringe benefits of just learning to think like a computer scientist and a programmer. And it doesn't take all that much to start doing so. This, for instance, is perhaps the simplest picture of computer science, sure, but really problem solving in general. Problems are all about taking input, like the problem you want to solve. You want to get the solution, aka output. And so something interesting's got to be happening in here, when you're trying to get from those inputs to outputs. Now, in the world of computers specifically, we need to decide in advance how we represent these inputs and outputs. We all just need to decide whether it's Macs or PCs or phones or something else, that we're all going to speak some common language, irrespective of our human languages as well. And you may very well know that computers tend to speak only what language, so to speak? Assembly 1, but binary 2 might be your go-to. And binary, by implying 2, means that the world of computers has just 2 digits at its disposal, 0 and 1. And indeed, we humans have many more than that, certainly not just zeros and ones alone, but a computer indeed only has zeros and ones, and yet somehow they can do so much. They can crunch numbers in Excel, send text messages, create images and artwork and movies and more. And so how do you get from something as simple as a few zeros, a few ones, to all of the stuff that we're doing today in our pockets and laptops and desktops? Well, it turns out that we can start quite simply. If a computer were to want to do something as simple as count, well, what could it do? Well, in our human world, we might count doing this, like 1, 2, 3, 4, 5, using so-called unary notation, literally the digits on your fingers, where one finger represents one person in the room, if I'm, for instance, taking attendance. Now, we humans would typically actually count 1, 2, 3, 4, 5, 6, and we'd go past just those 5 digits and count much higher using zeros through nines. But computers somehow only have these zeros and ones. So if a computer only somehow speaks binary, zeros and ones, how does it even count past the number 1? Well, here are 3 zeros, of course. And if you translate this number in binary, 0, 0, 0, to a more familiar number in decimal, we would just call this 0. Enough said. If we were to represent with a computer the number 1, it would actually be 0, 0, 1, which, not surprisingly, is exactly the same as we might do in our human world, but we might not bother writing out the 2 zeros at the beginning. But a computer now, if it wants to count as high as 2, it doesn't have the digit 2, and so it has to use a different pattern of zeros and ones, and that happens to be 0, 1, 0. So this is not 10 with a 0 in front of it. It's indeed 0, 1, 0 in the context of binary, and if we want to count higher now than 2, we're going to have to tweak these zeros and ones further to get 3. And then if we want 4, or 5, or 6, or 7, we're just kind of toggling these zeros and ones, aka bits for binary digits, that represent, via these different patterns, different numbers that you and I, as humans, know, of course, as the so-called decimal system, 0 through 9, dec implying 10 digits, those zeros through 9. So why that particular pattern? And why these particular zeros and ones? Well, it turns out that representing one thing or the other is just really simple for a computer. Why? At the end of the day, they're powered by electricity. And it's a really simple thing to just either store some electricity or don't store some electricity. Like, that's as simple as the world can get, on or off, 1 or 0, so to speak. So in fact, inside of a computer, a phone, anything these days that's electronic pretty much, is some number of switches, otherwise known as transistors. And they're tiny. You've got thousands, millions of them in your Mac or PC or phone these days. And these are just tiny little switches that can get turned on and off. And by turning those things on and off in patterns, a computer can count from 0 on up to 7 and even higher than that. And so these switches, really, you can think of being as like switches like this. Let me just borrow one of our little stage lights here. Here's a light bulb. It's currently off. And so I could just think of this as representing, in my laptop, a transistor, a switch representing 0. But if I allow some electricity to flow, now I, in fact, have a 1. Well, how do I count higher than 1? I, of course, need another light bulb. So let me grab another one here. And if I put it in that same kind of pattern, I don't want to just do this. That's sort of the old finger counting way of unary, just 1, 2. I want to actually take into account the pattern of these things being on and off. So if this was 1 a moment ago, what I think I did earlier was I turned it off and let the next one over be on, aka 0, 1, 0. And let me get a third bit, if you will, and that feels like enough. Here is that same pattern now, starting at the beginning with 3. So here is 0, 0, 0. Here is 0, 0, 1. Here is 0, 1, 0, aka in our human world of decimal, 2. And then we could, of course, keep counting further. This now would be 3. And dot, dot, dot. If this other bulb now goes on, and that switch is turned, and all 3 stay on, this again was what number? OK, so 7. So it's just as simple, relatively, as that, if you will. But how is it that these patterns came to be? Well, these patterns actually follow something very familiar. You and I don't really think about it at this level anymore, because we've probably been doing math and numbers since grade school or whatnot. But if we consider something in decimal, like the number 123, I immediately jump to that. This looks like 123 in decimal. But why? It's really just 3 symbols, a 1, a 2 with a bit of curve, a 3 with a couple of curves that you and I now instinctively just assign meaning to. But if we do rewind a few years, that is 123 because you're assigning meaning to each of these columns. The 3 is in the so-called ones place. The 2 is in the so-called tens place. And the 1 is in the so-called hundreds place. And then the math ensues quickly in your head. This is technically 100 times 1 plus 10 times 2 plus 1 times 3, aka 100 plus 20 plus 3. And there we get the sort of mathematical notion we know as 123. Well, nicely enough, in binary, it's actually the same thing. It's just these columns mean a little something different. If you use 3 digits in decimal, and you have the ones place, the tens place, and the hundreds place, well, why was that 1, 10, and 100? They're technically just powers of 10. So 10 to the 0, 10 to the 1, 10 to the 2. Why 10? Decimal system, dec, meaning 10. You have 8 and 10 digits, 0 through 9. In the binary system, if you're going to use 3 digits, just change the bases if you're using only zeros and ones. So now it's powers of 2. 2 to the 0, 2 to the 1, 2 to the 2, aka 1 and 2 and 4, respectively. And if you keep going, it's going to be 8's column, 16's column, 32, 64, and so forth. So why did we get these patterns that we did? Here's your 0, 0, 0, because it's 4 times 0, 2 times 0, 1 times 0, obviously 0. This is why we got the decimal number 1 in binary. This is why we got the number 2 in binary, because it's 4 times 0 plus 2 times 1 plus 1 times 0. And now 3, and now 4, and now 5, and now 6, and now 7. And of course, if you wanted to count as high as 8, to be clear, like, what do you have to do? What does a computer need to do to count even higher than 7? Add a bit, add another light bulb, another switch. And indeed, computers have standardized just how many zeros and ones or bits or switches they throw at these kinds of problems. And in fact, most computers would typically use at least 8 at a time. And even if you're only counting as high as 3 or 7, you would still use 8 and have a whole bunch of zeros. But that's OK, because the computers these days certainly have so many more, thousands, millions of transistors and switches, that's quite OK. All right, so with that said, if we can now count as high as 7, or frankly, as high as we want, that only seems to make computers useful for things like Excel, like number crunching. But computers, of course, let you send text messages, write documents, and so much more. So how would a computer represent something like a letter, like the letter A of the English alphabet? If at the end of the day, all they have is switches. Any thoughts? Yeah. OK, so we could represent letters using numbers. OK, so give me, what's a proposal? What number should represent what?
Say if you were starting at the beginning of the alphabet, you could say 1 is A, 2 is B, 3 is C.
Perfect. Yeah, we just all have to agree somehow that one number is going to represent one letter. So 1 is A, 2 is B, 3 is C, Z is 26, and so forth. Maybe we can even take into account uppercase and lowercase. We just have to agree and sort of write it down in some global standard. And humans indeed did just that. They didn't use 1, 2, 3. Turns out they started a little higher up. Capital A has been standardized as the number 65. And capital B has been standardized as the number 66. And you can kind of imagine how it goes up from there. And that's because whatever you're representing ultimately can only be stored at the end of the day as zeros and ones. And so some humans in a room before decided that capital A shall be 65, or really this pattern of zeros and ones inside of every computer in the world. 0, 1, 0, 0, 0, 0, 0, 1. So if that pattern of zeros and ones ever appears in a computer, it might be interpreted then as indeed a capital letter A, 8 of those bits at a time. But I worry, just to be clear, we might have now created a problem. It might seem, if I play this naively, that, OK, how do I now actually do math with the number 65, if now Excel displays 65 as an A, let alone B's and C's? So how might a computer do as you've proposed, have this mapping from numbers to letters, but still support numbers? It feels like we've given something up. Yeah?
By having a prefix for letters?
By having a prefix? OK, so we could perhaps have some kind of prefix, like some pattern of zeros and ones. I like this, that indicates to the computer, here comes another pattern that represents a letter. Here comes another pattern that represents a number or a letter. So not bad. I like that. Other thoughts? How might a computer distinguish these two? Yeah? Indeed, and that's spot on. Nothing wrong with what you suggested, but the world generally does just that. The reason we have all of these different file formats in the world, like JPEG and GIF and PNGs and Word documents, .docx and .excel files and so forth, is because a bunch of humans got in a room and decided, well, in the context of this type of file, or really more specifically, in the context of this type of program, Excel versus Photoshop versus Google Docs or the like, we shall interpret any patterns of zeros and ones as being maybe numbers for Excel, maybe letters in like a text messaging program or Google Docs, or maybe even colors of the rainbow in something like Photoshop and more. So it's context dependent. And we'll see when we ourselves start programming, you, the programmer, will ultimately provide some hints to the computer that tells the computer, interpret it as follows. So similar in spirit to that, but not quite as standardized with these prefixes. So this system here actually has a name, ASCII, the American Standard Code for Information Interchange. And indeed, it began here in the US, and that's why it's actually a little biased toward A's through Z's and a bit of punctuation as well. And that quickly became a problem. But if we start simply now in English, the mapping itself is fairly straightforward. So if A is 65, B is 66, and ... suppose that you received a text message, an email from a friend, and underneath the hood, so to speak, if you kind of looked inside the computer, what you technically received in this text or this email happened to be the numbers 72, 73, 33, or really the underlying pattern of zeros and ones. What might your friend have sent you as a message if it's 72, 73, 33? Hey, close. Hi. It's indeed hi. Why? Well, apparently, according to this little cheat sheet, H is 72, I is 73. It's not obvious from this chart what the 33 is. But indeed, this pattern represents hi. And anyone want to guess, or if you know what 33 is? Exclamation point. And this is frankly not the kind of thing most people know, but it's easily accessible via a nice user-friendly chart like this. So this is an ASCII chart. When I said that we just need to write down this mapping earlier, this is what people did. They wrote it down in a book or in a chart. And for instance, here is our 72 for H. Here is our 73 for I. And here is our 33 for exclamation point. And computers, Macs, PCs, iPhones, Android devices just know this mapping by heart, if you will. They've been designed to understand those letters. So here I might have received hi. Technically, what I've received is these patterns of zeros and ones. But it's important to note that when you get these patterns of zeros and ones in any format, be it email or text or a file, they do tend to come in standard lengths with a certain number of zeros and ones altogether. And this happens to be 8 plus 8 plus 8. So just to get the message hi, exclamation point, you would have received at least, it would seem, some 24 bits. But frankly, bits are so tiny, literally and mathematically, that we don't tend to think or talk generally in terms of bits. You're probably more familiar with bytes. B-Y-T-E-S is a byte, is a byte, is a byte. A byte is just 8 bits. And even those, frankly, aren't that useful. If we do out the math, how high can you count if you have 8 bits? Anyone know? Say again? Higher than that, unless you want to go negative. That's fine. 256, technically 255. Long story short, if we actually got into the weeds of all of these zeros and ones and we figured out what 1111, 1111 mathematically adds up to in decimal, it would indeed be 255, or less if you want to represent negative numbers as well. So this is useful because now we can speak not just in terms of bytes, but if the files are bigger, kilobytes is thousands of bytes, megabytes is millions of bytes, gigabytes is billions of bytes, terabytes are trillions of bytes, and so forth. We have a vocabulary for these increasingly large quantities of data. The problem is that if you're using ASCII, and therefore 8 bits, or 1 byte per character, and originally only 7, you can only represent 255 characters. And that's actually fine, or 256 total characters, including 0. And that's fine if you're using literally English in this case, plus a bunch of punctuation. But there's many languages in the world that need many more symbols, and therefore many more bits. So thankfully, the world decided that we'll indeed support not just the US English keyboard, but all of the accented characters that you might want for some languages. And heck, if we use enough bits, zeros and ones, not only can we represent all human languages in written form, as well as some emotions along the way, we can capture the latter with these things called emojis. And indeed, these are very much in vogue these days. You probably send and or receive many of these things any given day. These are just characters, like letters of an alphabet, patterns of zeros and ones that you're receiving that the world has also standardized. For instance, there are certain emojis that are represented with certain patterns of bits, and when you receive them, your phone, your laptop, your desktop displays them as such. And this newer standard is called Unicode. So it's a superset of what we called ASCII, and Unicode is just a mapping of many more numbers to many more letters, or characters more generally, that might use 8 bits for backwards compatibility with the old way of doing things with ASCII, but they might also use 16 bits. And if you have 16 bits, you can actually represent more than 65,000 possible letters, and that's getting up there. And heck, Unicode might even use 32 bits to represent letters and numbers and punctuation symbols and emojis, and that would give you up to 4 billion possibilities. And I dare say one of the reasons we see so many emojis these days is we have so much room. I mean, there's got room for billions more, literally. So in fact, just as a little bit of trivia, has anyone ever received this decimal number, or if you prefer binary now, has anyone ever received this pattern of zeros and ones on your phone in a text or an email, perhaps this past year? Well, if you actually look this up, this esoteric sequence of zeros and ones happens to represent face with medical mask. And notice that if you've got an iPhone or an Android device, you might be seeing different things. In fact, this is the Android version of this most recently. This is the iOS version of it most recently. And there's bunches of other interpretations by other companies as well. So Unicode, as a consortium, if you will, has standardized the descriptions of what these things are. But the companies themselves, manufacturers out there, have generally interpreted it as you see fit. And this can lead to some human miscommunications. In fact, for like literally, embarrassingly, like a year or two, I started being in the habit of using the emoji that kind of looks like this, because I thought it was like, woo, happy face or whatever. I didn't realize this is the emoji for hug, because whatever device I was using sort of looked like this, not like this, and that's because of their interpretation of the data. This has happened too when what was a gun became a water pistol in some manufacturers' eyes. And so it's an interesting dichotomy between what information we all want to represent and how we choose ultimately to represent it. Questions then on these representations of formats, be it numbers or letters or soon more? Yeah? And sorry, why is what so popular? Yeah, so we'll come back to this in a few weeks. In fact, there are other ways to represent numbers. Binary is one, decimal is another, unary is another, and hexadecimal is yet a fourth that uses 16 total digits, literally 0 through 9, plus A, B, C, D, E, F. And somehow you can similarly count even higher with those. We'll see in a few weeks why this is compelling. But hexadecimal, long story short, uses 4 bits per digit. And so 4 bits, if you have 2 digits in hex, that gives you 8. And it's just a very convenient unit of measure. And it's also human convention in the world of like files and other things. But we'll come back to that soon. Other questions? Do the lights on the stage supposedly say anything? Well, if we had thought in advance to use maybe 64 light bulbs, that would seem to give us 8 total bytes on stage. 8 times 8 giving us just that? Maybe. Good question. Other questions on zeros and ones? It's a little bright in here. No? Oh, yes? Where everyone's pointing somewhere specific. There we go. Sorry. Very bright in this corner. Oh, sure. And we'll come back to this in some form in the coming days, too, at a slower pace, too. We have, with 8 bits, 2 possible values for the first, and then 2 for the next, 2 for the next, and so forth. So that's 2 times 2 times 2. That's 2 to the 8th power total, which means you can have 256 total possible patterns of zeros and ones. But as we'll see soon, computer scientists, programmers, software often starts counting at 0 by convention. And if you use one of those patterns, 0, 0, 0, 0, 0, 0, 0, 0, to represent the decimal number we know is 0, you only have 255 other patterns left to count as high as, therefore, 255. That's all. Good question. All right, so what then might we have besides these emojis and letters and numbers? Well, we, of course, have things like colors and programs like Photoshop and pictures and photos. Well, let me ask the question again. How might a computer, do you think, knowing what you know now, represent something like a color? Like, what are our options if all we've got are zeros and ones and switches? Yeah. RGB. When RGB indeed is this acronym that represents some amount of red and some amount of green and blue. And indeed, computers can represent colors by just doing that. Remembering, for instance, this dot, this yellow dot on the screen that might be part of any of those emojis these days. Well, that's some amount of red, some amount of green, some amount of blue. And if you sort of mix those colors together, we can indeed get a very specific one. And we'll see in just a moment just that. So indeed, earlier on, did humans only use 7 bits total. And it was only once they decided, well, let's add an 8th bit, that they got extended ASCII. And that was initially, in part, a solution to this same problem of not having enough room, if you will, in those patterns of zeros and ones to represent all of the characters that you might want. But even that wasn't enough. And that's why we've now gone up to 16 and 32 and long past 7. So if we come back now to this one particular color, RGB was proposed as a scheme, but how might this work? Well, consider, for instance, this. If we do indeed decide as a group to represent any color of the rainbow with some mixture of some red, some green, and some blue, we have to decide how to represent the amount of red and green and blue. Well, it turns out if all we have are zeros and ones, ergo numbers, let's do just that. For instance, suppose a computer were using these 3 numbers, 72, 73, 33, no longer in the context of an email or a text message, but now in the context of something like Photoshop, a program for editing and creating graphical files. Maybe this first number could be interpreted as representing some amount of red, green, and blue, respectively. And that's exactly what happens. You can think of the first digit as red, second as green, third as blue. And so ultimately, when you combine that amount of red, that amount of green, that amount of blue, it turns out it's going to resemble this shade of yellow. And indeed, you can come up with numbers between 0 and 255 for each of those colors to mix any other color that you might want. And you can actually see this in practice. Even though our screens, admittedly, are getting really good on our phones and laptops such that you barely see the dots, they are there. You might have heard the term pixel before. Pixel's just a dot on the screen. And you've got thousands, millions of them these days, horizontally and vertically. And if I take even this emoji, which again happens to be one company's interpretation of face with medical mask, and zoom in a bit, maybe zoom in a bit more, you can actually start to see these pixels. Things get pixelated because what you're seeing is each of the individual dots that compose this particular image. And apparently, each of these individual dots are probably using 24 bits. 8 bits for red, 8 bits for green, 8 bits for blue in some pattern. And this program, or some other like Photoshop, is interpreting one pattern as white or yellow or black or some brown in between. And so if you look sort of awkwardly, but up close to your phone or your laptop or maybe your TV, you can see exactly this too. All right, well, what about things that we also watch every day on YouTube or the like, things like videos? How would a computer, knowing what we know now, represent something like a video? How might you represent a video using only zeros and ones? Yeah? Yeah, exactly. And to summarize, what video really adds is just some notion of time. It's not just one image. It's not just one letter or number. It's presumably some kind of sequence because time is passing. And so with a whole bunch of images, maybe 24, maybe 30 per second, if you fly them by the human's eyes, we can interpret them using our eyes and brain that there is now movement and therefore video. And similarly with audio or music, if we just came up with some convention for representing those same notes on a musical instrument, could we have the computer synthesize them too? And this might be actually pretty familiar. Let me pull up a quick video here, which happens to be an old school version of this same idea. You might remember from childhood. So granted, that particular video is an actual video of a paper-based animation, but indeed, that's really all you need is some sequence of these these images, which themselves, of course, are just zeros and ones because they're just this grid of these pixels or dots. Now, something like musical notes like these, those of you who are musicians might just naturally play these on physical devices, but computers can certainly represent those sounds too. And for instance, a popular format for audio is called MIDI. And MIDI might just represent each note that you saw a moment ago essentially as a sequence of numbers. But more generally, you might think about music as having notes, for instance, A through G, maybe some flats and some sharps. You might have the duration, like how long is the note being heard or played on a piano or some other device. And then just the volume, like how hard does the human in the real world press down on that key, and therefore how loud is that sound? It would seem that just remembering little details like that quantitatively, we can then represent really all of these otherwise analog human realities. So that then is really a laundry list of ways that we can just represent information. Again, computers or digital have all of these different formats, but at the end of the day, and as fancy as those devices and yours are, it's just zeros and ones, tiny little switches or light bulbs, if you will, represented in some way. And it's up to the software that you and I and others write to use those zeros and ones in ways we want to get the computers to do something more powerfully. Questions then on this representation of information, which I dare say is ultimately what problem solving is all about, taking in information and producing new via some process in between. Any questions out there? Yeah, in back.
Yeah, so we talked about how different file formats kind of allow you to interpret information differently. But how does a file format like .mp4 discriminate between audio and video within itself for its value?
So a really good question. There are many other file formats out there. You allude to MP4 for video, and more generally, these are these things called codecs and containers. It's not quite as simple when using larger files, for instance, in more modern formats, that a video is just a sequence of images. For instance, why? If you stored that many images for like a Hollywood movie, like 24 or 30 of them per second, that's a huge number of images. And if you've ever taken photos on your phone, you might know how many megabytes or larger even individual photographs might be. So humans have developed over the years fancier software that uses much more math to represent the same information more minimally, just using somehow shorter patterns of zeros and ones than our most simplistic representation here. And they use what might be called compression. If you've ever used a zip file or something else, somehow your computer is using fewer zeros and ones to represent the same amount of information, ideally without losing any information. And in the world of multimedia, which we'll touch on a little bit in a few weeks, there are both lossy and lossless formats out there. Lossless means you lose no information whatsoever. But more commonly, as you're alluding to one, is lossy compression, L-O-S-S-Y, where you're actually throwing away some amount of quality. You're getting some amount of pixelation that might not look perfect to the human, but heck, it's a lot cheaper and a lot easier to distribute. And in the world of multimedia, you have containers like QuickTime and other MPEG containers that can combine different formats of video, different formats of audio in one file. But there, too, do designers have discretion. So more in a few weeks, too. Other questions then on information here as well. Yeah? Exactly. I mean, back in the day, you might have heard of the expression a vacuum tube, which is like some physically large device that might have only stored some 0 or 1. Yes, it is the miniaturization of hardware these days that has allowed us to store as many and many more zeros and ones much more closely together. And as we've built more fancy machines that can sort of design this hardware at an even smaller scale, we're just packing more and more into these devices. But there, too, is a trade-off. For instance, you might know by using your phone or your laptop for quite a while, maybe on your lap, starts to get warm. And so there are these literal physical side effects of this where now some of our devices run hot. And this is why, like a data center in the real world might need more air conditioning than a typical place, because there are these physical artifacts as well. And in fact, if you'd like to see one of the earliest computers from decades ago, across the river here in now Alston, in the new engineering building, is the Harvard Mark I computer that will give you a better mental model of just that. Well, if we come back now to this first picture, being computer science or really problem solving, I dare say we have more than enough ways now to represent information, input and output, so long as we all just agree on something. And thankfully, those before us have given us things like ASCII and Unicode, not to mention MP4s, Word documents, and the like. But what's inside of this proverbial black box into which these inputs are going and the outputs are coming, well, that's where we get this term you might have heard too, an algorithm, which is just step-by-step instructions for solving some problem, incarnated in the world of computers by software. When you write software, aka programs, you are implementing one or more algorithms, one or more sets of instructions for solving some problem. And maybe you're using this language or that, but at the end of the day, no matter the language you use, the computer is going to represent what you type using just zeros and ones. So what might be a representative algorithm? Nowadays, you might use your phone quite a bit to make calls or send texts or emails, and therefore you have a whole bunch of contacts in your address book. Nowadays, of course, this is very digital, but whether on iOS or Android or the like, you might have a whole bunch of names, first name and or last, as well as numbers and emails and the like. And you might be in the habit of like scrolling through on your phone all of those names to find the person you want to call. It's probably sorted alphabetically by first name or last name, A through Z, or some other symbol. And this is frankly quite the same as we used to do, back in my day of CS50, when we just used a physical book. In this physical book might be a whole bunch of names alphabetically sorted from left to right, corresponding to a whole bunch of numbers. So suppose that in this old Harvard phone book, we want to search for John Harvard. We might, of course, start quite simply at the beginning here, looking at one page at a time. And this is an algorithm. This is like literally step by step looking for the solution to this problem. In that sense, if John Harvard's in the phone book, is this algorithm, page by page, correct, would you say? Yes. Like if John Harvard's in the phone book, obviously I'm eventually going to get to him. So that's what we mean by correct. Is it efficient? Is it well designed, would you say? No, I mean, this is going to take forever, even just to get to the J's or the H's, depending how this thing's sorted. All right, well, let me go a little faster. I'll start like 2 pages at a time. 2, 4, 6, 8, 10, 12, and so forth. Sounds faster. Is faster. Is it correct? OK, why is it not correct? Yeah. Exactly. If I start on an odd number of pages and I'm going 2 at a time, I might miss pages in between. And if I therefore conclude when I get to the back of the book there was no John Harvard, I might have just erred. This would be, again, one of these bugs. But if I try a little harder, I feel like there's a solution. We don't have to completely throw out this algorithm. I think we can probably go roughly twice as fast still. But what should we do instead to fix this? Yeah, I'm back. Nice. So I think what many of us, most of us, if we even use this technology anymore these days, we might go roughly to the middle of the phone book just to kind of get us started. And now I'm looking down. I'm looking for J, assuming first name, J Harvard. And it looks like I'm in the M section. So just to be clear, what should I do next? OK, and presumably it is. John Harvard would be to the left of this. So here's an opportunity to figuratively and literally tear this particular problem in half, throw half of the problem away. It's actually pretty easy if you just do it that way. The hard way is this way. But I've now just decreased the size of this problem really in half. So if I started with like 1,000 pages of phone numbers and names, now I'm down to 500. And already, we haven't found John Harvard, but that's a big bite out of this problem. And I do think it's correct, because if J is to the left of M, of course, he's definitely not going to be over there. And I think if I repeat this, again, dividing and conquering, if you will, here I might have gone a little too far. Now I'm in like the E section. So let me tear the problem in half again, throw another 250 pages away, and again repeat, dividing and conquering until finally, presumably, I end up with just 1 page of a phone book on which John Harvard's name either is or is not. But because of the algorithm you propose step by step, I know that he's not in anything I discarded. So dramatic as that might have been made out to be, it's actually just harnessing pretty good human intuition. Indeed, this is what programming's all about too. It's not about learning a completely new world, but really just how to harness intuition and ideas that you might already have and take naturally, but learning how to express them now more succinctly, more precisely, and using things called programming languages. Why is an algorithm like that, if I found John Harvard, better than ultimately just doing the first one or even the second and maybe doubling back to check those even pages? Well, let's just look at little charts here. Again, we don't have to get into the nuances of numbers, but if we've got like a chart here, XY plot, on the x-axis here I claim is the size of the problem. So measured in the numbers of pages in the phone book. So the farther you go out here, the more pages are in the phone book. And here we have time to solve on the y-axis. So the higher you go up, the more time it's going to be taking to solve that particular problem. So let's just arbitrarily say that the first algorithm, involving like n pages, might be represented graphically like this. No matter the slope, it's a straight line, because there's presumably a one-to-one relationship between numbers of pages and number of seconds, or number of page turns. Why? If the phone company adds another page next year because some new people move to town, that's going to require one additional page for me, 1 to 1. If, though, we use the second algorithm, flawed though it was, unless we double back a little bit to fix someone being in between, that's too going to be a straight line, but it's going to be a different slope, because now there's a 2 to 1 or a 1 to 2 relationship, because I'm going 2 pages at a time. So if the phone company adds another page, that's going to take me only, or another 2 pages, that's still only just one more step. And you can see the difference if I kind of draw this. If this is the phone book in question, this number of pages, it might take this many seconds on the yellow line to represent or to solve, to find someone like John Harvard. But of course, on the first algorithm, the red line, it's literally going to take twice as many steps. And what do the n's here mean? N is the go-to variable for a computer scientist or programmer, just generically representing a number. So if the number of pages in the phone book is n, the number of steps the second algorithm would have taken would be, in the worst case, n over 2. Half as many, because you're going twice as fast. But the third algorithm, actually, if you recall your logarithms, looks a little something like this. There's a fundamentally different relationship between the size of the problem and the amount of time required to solve it that technically is log base 2 of n, but it's really the shape that's different. And the implication there is that if, for instance, Cambridge and Alston, 2 different towns here in Massachusetts, merge next year, and there's just one phone book that's twice as big, no big deal for that third and final algorithm. Why? You just tear the problem one more time in half, taking one more byte. That's it. Not another 1,000 bytes just to get to the solution. And put another way, you could walk out way, way, way out here to a much bigger phone book, and ultimately, that green line is barely going to have budged. So this then is just a way of now formalizing and thinking about what the performance or quality of these algorithms might be. And before we now make one more formalization of the algorithm itself, any questions then on this notion of efficiency or now performance of ideas? Yeah? How many phone books have you got? A lot of phone books over the years, and if you or your parents have any more still somewhere, we could definitely use them because they're hard to find. Other questions? But thanks. Other questions here too? No? Oh, was that a murmur? Yes, over here. Sorry, say again? Oh, yeah, hopefully, and then we could, then we'd have a little something more to use here. So now, if we want to formalize further what it is we just did, we can go ahead and introduce this, a form of code, aka pseudocode. Pseudocode is not a specific language. It's not like something we're about to start coding in. It's just a way of expressing yourself in English or any human language succinctly, correctly, toward an end of getting your idea for an algorithm across. So for instance, here might be how we could formalize the code, the pseudocode for that same algorithm. Step 1 was pick up the phone book, as I did. Step 2 might be open to the middle of the phone book, as you proposed that we do first. Step 3 was probably to look down at the page, as I did. And step 4 gets a little more interesting, because I had to quickly make a decision and ask myself a question. If person is on page, then I should probably just go ahead and call that person. But that probably wasn't the case, at least for John Harvard, and I opened to the M section. And so there's this other question I should now ask. Else, if the person is earlier in the book, then I should tear the problem in half as I did, but go left, so to speak. And then not just open to the middle of the left half of the book, but really just go back to step 3. Repeat myself. Why? Because I can just repeat what I just did, but with a smaller problem, having taken this big bite. But if the person was later in the book, as might have happened with a different person than John Harvard, then I should open to the middle of the right half of the book, again go back to line 3. But again, I'm not going to get stuck doing something forever like this, because I keep shrinking the size of the problem. Lastly, the only possible scenario that's left If John Harvard is not on the page, and he's not to the left, and he's not to the right, what should our conclusion be? He's not there, he's not listed, and so we need to quit in some other form. Now, as an aside, it's kind of deliberate that I buried that last question at the end, because this is what happens all too often in programming, whether you're new at it or professional, just not considering all possible cases, corner cases, if you will, that might not happen that often. But if you don't anticipate them in your own code, pseudocode or otherwise, this is when and why programs might crash. Or you might see stupid little spinning beach balls or hourglasses, or your computer might reboot. Why? It's doing something sort of unpredictable if a human, maybe myself, didn't anticipate this. Like, what does this program do if John Harvard's not in the phone book? If I had omitted lines 12 and 13, I don't know. Maybe it would behave differently on a Mac or PC because it's sort of undefined behavior. And these are the kinds of omissions that, frankly, you're invariably going to make. Bugs you're going to introduce, mistakes you're going to make early on, and me too 25 years later. But you'll get better at thinking about those corner cases and handling anything that can possibly go wrong. And as a result, your code will be all the better for it. Now, the problem ultimately with learning how to program, especially if you've never had experience, or even if you do, but you learned one language only, is that they all look a little cryptic at first glance. But they do share certain commonalities. And in fact, we'll use this pseudocode to define those first. Highlighted in yellow here are what henceforth we're going to start calling functions. Lots of different programming languages exist, but most of them have what we might call functions, which are actions or verbs that solve some smaller problem. That is to say, you might use a whole bunch of functions to solve a bigger problem, because each function tends to do something very specific or precise. These then, in English, might be translated in code, actual computer code, to these things called functions. Highlighted in yellow now are what we might call conditionals. Conditionals are things that you do conditionally based on the answer to some question. You can think of them kind of like forks in the road. You go left or go right or some other direction based on the answer to some question. Well, what are those questions? Highlighted now in yellow are what we would call Boolean expressions, named after a mathematician last name Boole, that simply have yes, no answers. Or if you prefer, true or false answers. Or heck, if you prefer, 1 or 0 answers. We just need to distinguish one scenario from another. The last thing manifest in this pseudocode is what I might highlight now and call loops. Some kind of cycle, some kind of directive that tells us to do something again and again, so that I don't need a 1,000-line program to search a 1,000-page phone book. I can get away with a 13-line program, but sort of repeat myself inherently in order to solve some problem until I get to that last step. So this then is what we might call pseudocode. And indeed, there are other characteristics of programs that we'll touch on before long, things like arguments and return values, variables, and more. But unfortunately, in most languages, including some we will very deliberately use in this class and that everyone in the world these days still uses, is programs tend to look like this. This, for instance, is a distillation of that very first program I wrote in 1996 in CS50 itself, just to print something on the screen. And in fact, this version here just tries to print quote unquote hello world, which is, dare say, the most canonical first thing that most any programmer ever gets a computer to say, just because. But look at this mess. I mean, there's a hash symbol, these angled brackets, parentheses, words like int, curly braces, quotes, parentheses, semicolons, and backslashes. I mean, there's more overhead and more syntax and clutter than there is an actual idea. Now, that's not to say that you won't be able to understand this before long, because honestly, there's not that many patterns. Indeed, programming languages have typically a much smaller vocabulary than any actual human language. But at first, it might indeed look quite cryptic. But you can perhaps infer, I have no idea what these other lines do yet, but hello world is presumably, quote unquote, what will be printed on the screen. But what we'll do today, after a short break, and set the stage for next week, is introduce these exact same ideas in just a bit using Scratch. Something that you yourselves might have used when you're quite younger, but without the same vocabulary applied to those ideas. And the upside of what we'll soon do using Scratch, this graphical programming language from our friends down the road at MIT, it'll let us today start to drag and drop things that look like puzzle pieces that interlock together if it makes logical sense to do so, but without the distraction of hashes, parentheses, curly braces, angled brackets, semicolons, and things that are quite beside the point. But for now, let's go ahead and take a 10-minute break here. And when we resume, we will start programming. So this on the screen is a language called C, something that we'll dive into next week. And thankfully, this now on the screen is another language called Python that we'll also take a look at in a few weeks before long, along with other languages along the way. Today, though, and for this first week, week 0, so to speak, we use Scratch because, again, it will allow us to explore some of those programming fundamentals that will be in C and in Python and in JavaScript and other languages too, but in a way where we don't have to worry about the distractions of syntax. So the world of Scratch looks like this. It's a web-based or downloadable programming environment that has this layout here by default. On the left here, we'll soon see, is a palette of puzzle pieces, programming blocks that represent all of those ideas we just discussed. And by dragging and dropping these puzzle pieces or blocks over this big area and connecting them together, if it makes logical sense to do so, we'll start programming in this environment. The environment allows you to have multiple sprites, so to speak, multiple characters, things like a cat or anything else. And those sprites exist in this rectangular world up here that you can full screen to make bigger. And this here, by default, is Scratch, who can move up, down, left, right, and do many more things too. And within Scratch's world, you can think of it as perhaps a familiar coordinate system with x's and y's, which is helpful only when it comes time to position things on the screen. Right now, Scratch is at the default 0, 0, where x equals 0 and y equals 0. If you were to move the cat way up to the top, x would stay 0, y would be positive 180. If you move the cat all the way to the bottom, x would stay 0, but y would now be negative 180. And if you went left, x would become negative 240, but y would stay 0. Or to the right, x would be 240, and y would stay 0. So those numbers generally don't so much matter because you can just move relatively in this world, up, down, left, right. But when it comes time to precisely position some of these sprites or other imagery, it'll be helpful just to have that mental model of up, down, left, and right. Well, let's go ahead and make perhaps the simplest of programs here. I'm going to switch over to the same programming environment now for a tour of the left-hand side. So by default, selected here are the category in blue, motion, which has a whole bunch of puzzle pieces or blocks that relate to motion. And whereas Scratch, as a graphical language, categorizes things by the type of things that these pieces do, we'll see that throughout this whole palette, we'll have functions and variables and conditionals and Boolean expressions and more, each in a different color and shape. So for instance, moving 10 steps or turning one way or the other would be functions categorized here as things like motion. Under looks in purple, you might have speech bubbles that you can create by dragging and dropping these that might say hello or whatever for some number of seconds. Or you could switch costumes, change the cat to look like a dog or a bird or anything else in between. Sounds too, you can play sounds like meow or anything you might import or record yourself. And then there's these things Scratch calls events. And the most important of these is the first, when green flag clicked. Because if we look over to the right of Scratch's world here, this rectangular region has this green flag and red stop sign up above, one of which is for play, one of which is for stop. And so that's going to allow us to start and stop our actual programs when that green flag is initially clicked. But you can listen for other types of events. When the space bar is pressed or something else. When this sprite is clicked or something else. And here you already see a programmer's incarnation of things you and I take for granted every day now on our phones. Anytime you tap an icon or drag your finger or hit a button on the side, these are what a programmer would call events. Things that happen and are often triggered by us humans, and things that a program, be it in Scratch or Python or C or anything else, can listen for and respond to. Indeed, that's why when you tap the phone icon on your phone, the phone application starts up because someone wrote software that's listening for a finger press on that particular icon. And so Scratch has these same things too. Under control in orange, you can see that we can wait for 1 second or repeat something some number of times, 10 by default, but we can change anything in these white circles to anything else. There's another puzzle piece here, forever, which implies some kind of loop where we can do something again and again. And even though it seems a little tight, there's not much room to fit something there, Scratch is going to have these things grow and shrink however we want to fill similarly shaped pieces. And here's those conditionals. If something is true or false, then do this next thing. And that's how we can put in this little trapezoid-like shape some form of Boolean expression, a question with a yes, no, true, false, or 1, 0 answer, and decide whether to do something or not. You can combine these things too. If something is true, do this, else do this other thing. And you can even tuck one inside of the other if you want to ask 3 or 4 or more questions. Sensing, too, is going to be a thing. You can ask questions, aka Boolean expressions, like, is the sprite touching the mouse pointer, the arrow on the screen, so that you can start to interact with these programs? What is the distance between a sprite and a mouse pointer? You can do simple calculations just to figure out maybe if the enemy is getting close to the cat. Under operators, some lower level stuff like math, but also the ability to pick random numbers, which for a game is great, because then you can kind of vary the difficulty or what's happening in a game without the same game playing the same way every time. And you can combine ideas. Something and something must be true in order to make that kind of decisions before. Or we can even join 2 words together. It says apple and banana by default, but you can type in or drag and drop whatever you want there to combine multiple words into full, larger sentences. And then lastly down here, there's in orange things called variables. In math, we've obviously got x and y and whatnot. In programming, we'll have the same ability to sort of store in these named symbols, x or y, of values that we care about, numbers or letters or words or colors or anything ultimately. But in programming, you'll see that it's much more conventional not to just use simple letters like x and y and z, but to actually give variables full words or singular or plural words to describe what they are. And then lastly, if this isn't enough colors, blocks for you, you can create your own blocks. And indeed, this is going to be a programming principle we'll apply today and with the first problem set, whereby once you start to assemble these puzzle pieces and you realize, oh, would have been nice if those several pieces could have just been replaced by one had MIT thought to give me that one puzzle piece, you yourself can make your own blocks by connecting these all together, giving them a name, and boom, a new puzzle piece will exist. So let's do the simplest, most canonical programs here, starting up with control. And I'm going to click and drag and drop this thing here when green flag clicked. And then I'm going to grab one more, for instance, under looks. And under looks, I'm going to go ahead and just say something like, initially, not just hello, but the more canonical, hello, comma, world. Now, you might guess that in this programming environment, I can go over here now and click the green flag, and voila, hello, comma, world. So that's my first program, and obviously much more user-friendly than typing out the much more cryptic text that we saw on the screen that you, too, will type out next week. But for now, we'll just focus on these ideas, and in this case, a function. So what is it that just happened? This purple block here is say. That's the function. And it seems to take some form of input in the white oval, specifically hello, comma, world. Well, this actually fits the paradigm that we looked at earlier of just inputs and outputs. So if I may, if you consider what this puzzle piece is doing, it actually fits this model. The input in this case is going to be hello, comma, world in white. The algorithm is going to be implemented as a function by MIT called say. And the output of that is going to be some kind of side effect, like the cat and the speech bubble are saying hello, world. So already, even that simple drag and drop mimics exactly this relatively simple mental model. So let's take things further. Let's go ahead now and make the program a little more interactive so that it says something like hello, David, or hello, Carter, or hello to you specifically. And for this, I'm going to go under sensing. And you might have to poke around to find these things the first time around. And I've done this a few times, so I kind of know where things are and what color. There's this function here, ask what's your name, but that's in white, so we can change the question to anything we want. And it's going to wait for the human to type in their answer. And this function called ask is a little different from the say block, which just had this side effect of printing a speech bubble to the screen. The ask function is even more powerful in that after it asks the human to type something in, this function is going to hand you back what they typed in the form of what's called a return value, which is stored ultimately in, by default, this thing called answer. This little blue oval here called answer is, again, one of these variables that in math would be called just x or y. But in programming, we're saying what it does. So I'm going to go ahead and do this. Let me go ahead and drag and drop this block. And I want to ask the question before saying anything. But you'll notice that Scratch is smart, and it's going to realize I want to insert something in between. And it's just going to move things up and down. I'm going to let go and ask the default question, what's your name? And now if I want to go ahead and say hello, David or Carter, let's just do hello, comma, because I obviously don't know when I'm writing the program who's going to use it. So let me now grab another looks block up here, say something again. And now let me go back to sensing and now grab the return value represented by this other puzzle piece. And let me just drag and drop it here. And notice it's the same shape, even if it's not quite the same size. Things will grow or shrink as needed. All right, so let's now zoom out. let me go and stop the old versions, because I don't want to say hello world anymore. Let me hit the green flag, and what's my name? All right, David, enter. Huh. All right, maybe I just wasn't paying close enough attention. Let me try it again. Green flag, DAVID, enter. This seems like a bug. What's the bug or mistake, might you think? Yeah. Yeah, we kind of want to combine them in the same text box. And it's, it's technically a bug because this just looks kind of stupid. It's just saying David after I asked for my name. I'd like it to say maybe hello, then David, but it's just blowing past the hello and printing David. But let's put our finger on why this is happening. You're right for the solution, but what's the actual fundamental problem? In back? Perfect. I mean, computers are really darn fast these days. It is saying hello. All of us are just too slow in this room to even see it, because it's then saying David on the screen so fast as well. So there's a couple of solutions here, and yours is spot on. But just to poke around, you'll see the first example of how many ways in programming, be it Scratch or C or Python or anything else, that there are going to be to solve problems. And we'll teach you over the course of this weeks. Sometimes some ways are better relatively than others, but rarely is there a best way necessarily, because again, reasonable people will disagree. And what we'll try to teach you over the coming weeks is how to kind of think through those nuances. And it's not going to be obvious at first glance, but the more programs you write, the more feedback you get, the more bugs that you introduce, the more you'll get your footing with exactly this kind of problem solving. So let me try this in a couple of ways. Up here would be one solution to the problem. MIT anticipated this kind of issue, especially with first-time programmers. And I could just use puzzle piece that says, say the following for 2 seconds or 1 second or whatever, then do the same with the next word. And it might be kind of a bit of a pause. Hello, 1 second, 2 seconds, David. 1 second, 2 seconds, but at least it would look a little more grammatically correct. But I can do it a little more elegantly as you proposed. Let me go ahead and throw away one of these blocks, and you can just drag and let go, and it'll delete itself. Let me go down to operators, because this join block here is the right shape. And so even if you're not sure what goes where, just focus on the shapes first. Let me drag this over here, and it grew to fill that. Let me go ahead and say hello, comma, space. And now it could just say by default, hello, banana. But let me go back to sensing, drag answer. And that's going to drag and drop there. And so now notice we're sort of stacking or nesting one block on another so that the output of one becomes the input to another. But that's OK here. Let me go ahead and zoom out, hit stop, and hit play. All right, what's your name? DAVID, enter. And voila. Now it's presumably as we first intended. So, thank you. Thank you. No -2 this time. So consider that even with these, this additional example, it still fits the same mental model, but in a little more interesting way. Here's that new function, ask something and wait. And notice that in this case, too, there's an input, otherwise known henceforth as an argument or a parameter, programming speak, for just an input in the context of a function. And if we use our drawing as before to represent this thing here, we'll see that the input now is going to be, quote unquote, what's your name? The algorithm is going to be implemented by way of this new puzzle piece, the function called ask. And the output of that thing this time is not going to be the cat saying anything yet, but rather it's going to be the actual answer. So instead of the visual side effect of the speech bubble appearing, now nothing visible is happening yet thanks to this function. It's sort of handing me back like a scrap of paper with whatever I typed in written on it, so I can reuse DAVID one or more times even, like I did. Now, what did I then do with that value? Well, consider that with the subsequent function, we had this say block 2 combined with a join. So we have this variable called answer. We're joining it with that first argument, hello. So already we see that some functions like join can take not one, but 2 arguments or inputs, and that's fine. The output of join is presumably going to be hello, David, or hello, Carter, or whatever the human typed in. And that output, notice, is essentially becoming the input to another function, say, just because we've kind of stacked things or nested them on top of one another. But methodically, it's really the same idea. The input now are 2 things, hello, comma, and the return value from the previous ask function. The function now is going to be joined. The output is going to be hello David, but that hello David output is now going to become the input to another function, namely that first block called say, and that's then going to have the side effect of printing out hello David on the screen. So again, as sort of sophisticated as ours, as yours, as others' programs are going to get, they really do fit this very simple mental model of inputs and outputs, and you just have to learn to recognize the vocabulary and to know what kinds of puzzle pieces or concepts ultimately to apply. But you can ultimately really kind of spice these things up. Let me go back to my program here that just is using the speech bubble at the moment. Scratch, as an aside, has some pretty fancy interactive features too. I click the extensions button in the bottom left corner, and let me go ahead and choose the text-to-speech extension. This is using a cloud service. So if you have an internet connection, it can actually talk to the cloud or a third-party service. And this one's going to give me a few new green puzzle pieces, namely the ability to speak something from my speakers instead of just saying it textually. So let me go ahead and drag this. And now notice I don't have to interlock them if I'm just kind of playing around and I want to move some things around. I just want to use this as like a canvas temporarily. Let me go ahead and steal the join from here, put it there. Let me throw away the say block by just moving it left and letting go. And now let me join this in. So I've now changed my program to be a little more interesting. So now let me stop the old version. Let me start the new. What's your name? Type in David, and voila.
Hello, banana.
OK, -2, for real. All right, so what I accidentally threw away there, intentionally for instructional purposes, was the actual answer that came back from the ask block. That's embarrassing. So now if I play this again, let's click the green icon. What's your name? David. And now,
hello, David.
There we go. Hello, David. All right. Thank you. OK, so we have these functions then in place. But what more can we do? Well, what about those conditionals and loops and other constructs? How can we bring these programs to life so it's not just clicking a button and voila, something's happening? Let's go ahead and make this now even more interactive. Let me go ahead and throw away most of these pieces. And let me just spice things up with some more audio under sound. I'm going to go to play sound meow until done. Here we go. Green flag. OK. It's a little loud, but it did exactly do what it said. Let's hear it again. OK, it's kind of an underwhelming program eventually, since you'd like to think that the cat would just meow on its own, but I have to keep hitting the button. Well, this seems like an opportunity for doing something again and again. So all right, well, if I wanted to meow, 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 let me just grab a few of these. Or you can even right-click or control-click, and you can copy-paste even in code here. Let me play this now. All right, so now like it's not really emoting happiness in quite the same way. It might be hungry or upset. So you know what, let's slow it down. Let me go to control, wait 1 second in between, which might be a little less worrisome. Here we go, play. OK, so if my goal was to make the cat meow 3 times, I dare say this code or algorithm is correct. But let's now critique its design. Is this well designed? And if not, why not? What are your thoughts here? Yeah. Yeah, sure. Yeah. Yeah, so yeah, agreed. I could use forever or repeat, but let me push a little harder. But why? Like this works. I'm kind of done with the assignment. What's bad about it? Yeah, there's too much repetition, right? If I wanted to change the sound that the cat is making to like a different variant of meow or have it bark instead like a dog, I could change it from the drop down here apparently. But then I'd have to change it here, and then I'd have to change it here. And God, if this were even longer, that just gets tedious quickly. And you're probably increasing the probability that you're going to screw up and you're going to miss one of the drop downs or something stupid and introduce a bug. Or if you wanted to change the number of seconds you're waiting, you've got to change it in 2, maybe even more places. Again, you're just creating risk for yourself and potential bugs in the program. So I do like the repeat or the forever idea so that I don't repeat myself. And indeed, what I alluded to being possible, copy-pasting earlier, doesn't mean it's a good thing. And in code, generally speaking, when you start to copy and paste puzzle pieces or text next week, you're probably not doing something quite well. So let me go ahead and throw away most of these to get rid of the duplication, keeping just 2 of the blocks that I care about. Let me grab the repeat block for now. Let me move this inside of the repeat block. It's going to grow to fit it. Let me reconnect all this and change the 10 just to a 3. And now play. So better. It's the same thing. It's still correct. But now I've set the stage to let the cat meow, for instance, 4 times by changing one thing, 40 times by changing one thing. Or I could just use the forever block and just walk away, and it will meow forever instead. If that's your goal, that would be better. A better design, but still correct. But you know what? Now that I have a program that's designed to have a cat meow, wow, like why? I mean, MIT invented Scratch. Scratch is a cat. Why is there no puzzle piece called meow? This feels like a missed opportunity. Now, to be fair, they gave us all the building blocks with which we could implement that idea. But a principle of programming and really computer science is to leverage what we're going to now start calling abstraction. We have step-by-step instructions here, the repeat, the play, and the wait, that collectively implements this idea that we humans would call meowing. Wouldn't it be nice to abstract away those several puzzle pieces into just one that literally just says what it does, meow? Well, here's where we can make our own blocks. Let me go over here to Scratch under the pink block category here. And let me click Make a Block. And here I see a slightly different interface where I can choose a name for it. And I'm going to call it meow. And I'm going to keep it simple. That's it. No inputs to meow yet. I'm just going to click OK. Now, just going to clean this up a bit here. Let me drag and drop play sound and wait over here. And you know what? I'm just going to drag this way down here, because now that I'm done implementing meow, I'm going to literally abstract it away, sort of out of sight, out of mind, because now, notice at top left, there is a new pink puzzle piece called meow. And so at this point, I'd argue, it doesn't really matter how meow is implemented. Frankly, I don't know how ask or say was implemented by MIT. They abstracted those things away for us. Now I have a brand new puzzle piece that just says what it is. And this is now still correct, but arguably better design. Why? Because it's just more readable to me, to you. It's more maintainable when you look at your code a year from now for the first time, because you're sort of fondly looking back at the very first program you wrote. It says what it does. The function itself has semantics, which conveys what's going on. If you really care about how meow is implemented, you could scroll down and start to tinker with the underlying implementation details. But otherwise, you don't need to care anymore. Now, I feel like there's an even additional opportunity here for abstraction and to sort of factor out some of this functionality. It's kind of lame that I have this repeat block that lets me call the meow function, so to speak, use the meow function 3 times. Wouldn't it be nice if I could just call the meow function, aka use the meow function, and pass it an input that tells the puzzle piece how many times I want it to meow? Well, let me go ahead and zoom out and scroll down. Let me right-click or control-click on the pink piece here and choose Edit. Or I could just start from scratch, no pun intended, with a new one. And now here, rather than just give this thing a name meow, let me go ahead and add an input here. And I'm going to go ahead and type in, for instance, n for number of times to meow. And just to make this even more user-friendly and self-descriptive, I'm going to add a label, which has no functional impact. It's just an aesthetic. And I'm just going to say times, just to make it read more like English in this case, that tells me what the puzzle piece does. And now I'm going to click OK. And now I need to refine this a little bit. Let me go ahead and grab, under control, a repeat block. Let me move the play sound and wait into the repeat block. I don't want 10, and I also don't want 3 here. What I want now is this n that is my actual variable that Scratch is creating for me that represents whatever input the human programmer provides. Notice it snaps right in place. Let me connect this. And now, voila, I have an even fancier version of meow that is parameterized. It takes input that affects its behavior accordingly. Now I'm going to scroll back up because out of sight, out of mind. I just care that meow exists. Now I can tighten up my code, so to speak, use even fewer lines to do the same thing by throwing away the repeat block, reconnecting this new puzzle piece here that takes an input like 3, and voila, now we're really programming. Right? We've not made any forward progress functionally. The thing just meows 3 times. But it's a better design. And as you program more and more, these are the kinds of instincts you'll start to acquire so that, one, you can start to take a big assignment, a big problem set, something for homework even, that feels kind of overwhelming at first, like, oh my God, where do I even begin? But if you start to identify what are the sub-problems of a bigger problem, then you can start making progress. And I do this to this day, where if I have to tackle some programming-related project, it's so easy to like drag my feet or, oh, it's going to take forever to start. until I just start writing down like a to-do list. And I start to modularize the program and say, all right, well, what do I want this thing to do? Meowing. What's that mean? I got to have it say something on the screen. All right, I need to have it say something on the screen some number of times. Like literally a mental or written checklist, or pseudocode, if you will, in English on a piece of paper or text file. And then you can decide, OK, the first thing I need to do for homework to solve this real-world problem, I just need a meow function. I need to use a bunch of other code too, but I need to create a meow function. And boom, now you have a piece of the problem solved. Not unlike we did with the phone book there, but in this case, we'll have presumably other problems to solve. All right, so what more can we do? Let's add a few more pieces to the puzzle here. Let's actually interact with the cat now. Let me go ahead and now, when the green flag is clicked, let me go ahead and ask a question using an event here. Let me go ahead and say if, let's see, if the cursor, I want to do something like implement the notion of petting the cat. So if the cursor is touching the cat, like here, something like this, it'd be cute if like the cat meows, like you're petting a cat. So I'm going to ask the question when the green flag is clicked, if, let's see, I think I need sensing. So if touching mouse pointer, this is way too big, but again, the shape is fine. So there it goes, grew to fill. And then if it's touching the mouse pointer, that is, if the cat, to whom this script or this program, anytime I attach puzzle pieces, MIT calls them a script or like a program, if you will. Let me go ahead then and choose a sound and say play sound meow until done. All right, so here it is to be clear. When the green flag is clicked, ask the question, if the cat is touching the mouse pointer, then play sound meow. Here we go. Play. Huh. All right, let's try again. Play. Huh. I'm worried it's not Scratch's fault. Feels like mine. What's the bug here? Why doesn't this work? Yeah, and back? Yeah, who just turned? Yeah, the problem is the moment I click that green flag, Scratch asks the question, is the cat touching the mouse pointer? And obviously it's not, because the cursor was like up there a moment ago, and it's not down there. It's fine if I move the cursor down there, but too late. The program already asked the question. The answer was no, or false, or 0, however you want to think about it, so no sound was played. So what might the solution here be? I could move my cursor quickly, but that feels like never going to work out right. Other solutions here? Yeah, and way back? The forever loop. So I could indeed use this forever loop, because if I want my program to just constantly listen to me, well, let's literally do something forever, or at least forever as long as the program is running until I explicitly hit stop. So let me grab that. Let me go to Control. Let me grab the forever block. Let me move the if inside of this forever block, reconnect this, go back up here, click the green flag, and now, nothing's happened yet, but let me try moving my cursor now. So now, that's kind of cute. So now the cat is actually responding, and it's going to keep doing this again and again. And so now we have this idea of taking these different ideas, these different puzzle pieces, assembling them into something more complicated. And I could definitely put a name to this. I could create a custom block. But for now, let's just consider what kind of more interactivity we can do. Let me go ahead and do this by, again, grabbing a when green flag clicked. Let me go ahead and click the video sensing. And I'm going to rotate the laptop, because otherwise we're going to get a little inception thing here where the camera is picking up the camera is up there. So I'm going to go reveal to you what's inside the lectern here while we rotate this. And now that we have a non-video backdrop, I'm going to say this. Instead of the green flag clicked, actually, I'm going to say when the video motion is greater than some arbitrary measurement of motion, I'm going to go ahead and play sound meow until done. And then I'm going to get out of the way. So here's the cat, and we'll put him on top of there. Just OK. All right, and here we go. So my hand is moving faster than 50 something or other, whatever the unit of measure is. And thank you. So now we have an even more interactive version. But I think if I sort of slowly, right, it's completely creepy, but I'm not like exceeding the threshold until finally my hand moves as fast as that. And so here actually is an opportunity to show you something a former student did. Let me go ahead here and, OK, got to stop this. Let me go ahead and zoom out of this in just a moment. If someone would be comfortable coming up, not only masked but also on camera on the internet, thought we'd play one of your former classmates' projects here up on stage. Would anyone like to volunteer here and be up on stage? Who's that? Yeah, come on down. What's your name? Sahar. Sahar? All right, come on down. Let me get it set up for you here. All right. Let me go ahead and full screen this here. So this is Whack-A-Mole by one of your former predecessors. It's going to use the camera focusing on your head, which we'll have to position inside of this rectangle. And have you ever played the Whack-A-Mole game at an arcade? OK, so for those who haven't, these little moles pop up, and with a very fuzzy hammer, you sort of hit down. You, though, if you don't mind, are going to use your head to do this virtually. So let's line up your head with this red rectangle, if you could. We'll do beginner. All right, here we go. Sahar. Give it a moment. OK, come a little closer. And now hit the moles with your head. There we go. 1 point. 1 point. Nice. 15 seconds to go. There we go. Oh, yep, 1 point. Nice. 6 seconds. There we go. Quick. All right. A round of applause for Sahar. Thank you. So beyond having a little bit of fun here, the goal was to demonstrate that by using some fairly simple primitives, some basic building blocks, but assembling them in a fun way with some music, maybe some new costumes or artwork, you can really bring programs to life. But at the end of the day, the only puzzle pieces really involved were ones like the ones I just dragged and dropped, and a few more because there were clearly lots of moles. So the student probably created a few different sprites, not a single cat, but at least 4 different moles. They had some kind of graphic on the screen that showed Sahar where to position her head. There was some kind of timer, maybe a variable that every second was counting down. So you can imagine taking what looks like a pretty impressive project at first glance, and perhaps overwhelming to solve yourself. But just think about what are the basic building blocks and pluck off one piece of the puzzle, so to speak, at a time. And so indeed, if we rewind a little bit, let me go ahead here and introduce a program that I myself made back in graduate school when Scratch was first being developed by MIT. Let me go ahead and open here. Give me just 1 second. Something that I called back in the day Oscar time that looks a little something like this. If I full screen it and hit play. So you'll notice a piece of trash is falling. I can click on it and drag. And as I get close and close to the trash can, notice it wants to go in, it seems. And if I let go, 1 point. Here comes another. I'll do the same, 2 points. There's a sneaker falling from the sky, so another sprite of some sort. I can also get just a little lazy and just let them fall into the trash themselves if I want to. So you can see it doesn't have to do with my mouse cursor. It has to do apparently with the distance here. Let's listen a little further. I think there's some additional trash is about to make its appearance. Presumably there's some kind of variable that's keeping track of this score. OK, let's see what the last chorus here is. OK, and thus it continues. And the song actually goes on and on and on. And I do not have fond memories of implementing this and hearing this song for 10 straight hours. But it's a good example to just consider, how was this program composed? How did I go about implementing it the first time around? And let me go ahead and open up some programs now that I wrote in advance, just so that we could see how these things are assembled. Honestly, the first thing I probably did was probably to do something a little like this. Here is just a version of the program where I set out to solve just one problem first of planting a lamppost in the program. Right? I kind of had a vision of what I wanted. It evolved over time, certainly. But I knew I wanted trash to fall. I wanted a cute little Oscar the Grouch to pop out of the trash can and some other stuff. But wow, that's a lot to just tackle all at once. I'm going to start easy, download a picture of a lamppost, and then drag and drop it into the stage as a costume. And boom, that's version 1. It doesn't functionally do anything. I mean, literally, that's the code that I wrote to do this. All I did was use like the backdrops feature and drag and drop and move things around. But it got me to version 1 of my program. Then what might version 2 be? Well, I considered what piece of functionality, frankly, might be the easiest to pluck off next. And the trash can. That seems like a pretty core piece of functionality. It just needs to sit there most of the time. So the next thing I probably did was to open up, for instance, the trash can version here that looks a little something now like this. So this time I'll show you what's inside here. There is some code, but not much. Notice at bottom right, I changed the default cat to a picture of a trash can instead, but it's the same principle that I can control. And then over here, I added this code. When the green flag is clicked, switch the costume to something I arbitrarily called Oscar 1. So I found a couple of different pictures of a trash can, one that looks closed, one that looks partly open, and eventually one that has Oscar coming out. And I just gave them different names. So I said switch to Oscar 1, which is the closed one by default. Then forever do the following. If touching the mouse pointer, then switch the costume to Oscar 2, else switch to Oscar 1. That is to say, I just wanted to implement this idea of like the can opening and closing. Even if it's not exactly what I wanted ultimately, I just wanted to make some forward progress. So here, when I run this program, by clicking play, notice what happens. Nothing yet, but if I get closer to the trash can, it indeed pops open because it's forever listening for whether the sprite, the trash can in this case, is touching the mouse pointer. And that's it. That was version 2, if you will. And if I went in now and added the lamppost and composed the program together, now we're starting to make progress, right? Now it would look a little something more like the program I intended ultimately to create. What piece did I probably bite off after that? Well, I think what I did is I probably decided, let me implement one of the pieces of trash, not the shoe and the newspaper all at once. Let's just get one piece of trash working correctly first. And so let me go ahead and open this one. And again, all of these examples will be available on the course's website, so you can see all of these examples too. It's not terribly long. I just implemented in advance so we could flip through kind of quickly. Here's what I did here. On the right-hand side, I turned my sprite into a piece of trash this time, instead of a cat, instead of a trash can. And I also created, with Carter's help, a second sprite, this one a floor. It's literally just a black line, because I just wanted initially to have some notion of a floor so I could detect if the trash is touching the floor. Now, without seeing the code yet, just hearing that description, why might I have wanted this second sprite and this black line for a floor with the trash intending to fall from the sky? What might I have been thinking? Like, what problem might I be trying to solve? Yeah?
You don't want the first sprite to go through it.
Yeah, you don't want the first sprite to start at the top, go through, and then boom, like you completely lose it. Like that would not be a very useful thing, or it would seem to maybe eat up more and more of the computer's memory if the trash is just endlessly falling and I can't grab it. It might be a little traumatic if you try to get it and you can't pull it back out and you can't fix the program. And so I just wanted the thing to stop. So how might I have implemented this? Let's look at the code at left. Here I have a bit of randomness, like I proposed earlier, exists. There's this blue function called goToX, y that lets me move a sprite to any position, up, down, left, right. I picked a random x location, either here or over here, negative 240 to positive 240, and then a y value of 180, which is the top. And this just makes the game more interesting. It's kind of lame pretty quickly if the trash always falls from the same spot. Here's just a little bit of randomness, like most any game would have, that spices things up. And so now if I click the green flag, you'll see that it just falls. Nothing interesting is going to happen, but it does stop when it touches the black line, because notice what we did here. I'm forever asking the question, if the distance of the sprite, the trash, is to the floor is greater than 0, that's fine. Change the y location to by -3. So move it down 3 pixels, until the distance to the floor is not greater than 0. It is 0 or even negative, at which point it should just stop moving altogether. There's other ways we could have implemented this, but this felt like a nice, clean way that logically just made it make sense. And OK, now I got some trash falling. I got a trash can that opens and closes. I have a lamppost. Now I'm, a good 3 steps into the program. We're making progress. If we consider 1 or 2 final pieces, something like the dragging of the trash, let me go ahead and open up this version too. Dragging the trash requires a different type of question. Let me zoom in here. Here's the piece of trash. I only need 1 sprite, no floor here, because I just want the human to move it up, down, left, right. And the human's not going to physically be able to move it outside of the world. And if we zoom in on this code, the way we've solved this is as follows. We're using that and conjunction that we glimpsed earlier, because when the green flag is clicked, we're forever asking this question, or really these questions, plural, if the mouse is down and the trash is touching the mouse pointer, that's equivalent logically to clicking on the trash. Go ahead and move the trash to the mouse pointer. So again, it takes this very familiar idea that you and I take for granted every day on Macs and PCs of clicking and dragging and dropping. How is that implemented? Well, Mac OS or Windows are probably asking a question. Oh, for every icon, is the mouse down and is the icon touching the mouse? If so, go to the location of the mouse forever while that mouse button is clicked down. So how does this work in reality now? Let me go ahead and click on the play. Nothing happens at first, but if I click on it, I can move it up, down, left, right. It doesn't move thereafter. So I now need to kind of combine this idea of dragging with falling. But I bet I could just start to use just one single program. Right now I'm using separate ones to show different ideas. But now that's another bite out of the problem. And if we do one last one, something like the scorekeeping is interesting. Because recall that every time we dragged a piece of trash into the can, Oscar popped out and told us the current score. So let me go ahead and find this one. Oscar variables. And let me zoom in on this one. And this one is longer because we combined all of these elements. So this is the kind of thing that if you looked at it first glance, like, I have no idea how I would have implemented this from nothing, from scratch, literally. But again, if you take your vision and componentize it into these smaller bite-sized problems, you can take these baby steps, so to speak, and then solve everything collectively. So what's new here is this bottom one. Forever do the following. If the trash is touching Oscar, the other sprite that we've now added to the program, change the score by 1. This is an orange. And indeed, if we poke around, we'll see that orange is a variable, like an x or a y, but with a better name. Changing it means to add 1, or if it's negative, subtract 1. And then go ahead and have the trash go to pick random. What is this all about? Well, let me show you what it's doing, and then we can infer backwards. Let me go ahead and hit play. All right, it's falling. I'm clicking and dragging it. I'm moving it over, and I'm letting go. All right, let me do it once more. Letting go. Let me stop. Why do I have this function at the end called go to x and y randomly? Like, what problem is this solving here? Yeah, and way back. Yeah. Yeah, exactly. Even though the human perceives this as like a lot of trash falling from the sky, it's actually the same piece of trash just kind of being magically moved back to the top as though it's a new one. And there, too, you have this idea of reusable code. If you were constantly copying and pasting your pieces of trash and creating 20 pieces of trash, 30 pieces of trash, just because you want the game to have that many levels, probably doing something wrong. Reuse the code that you wrote, reuse the sprites that you wrote, and that would give you not just correctness, but also a better design. Well, let's take a look at one final set of building blocks that we can compose ultimately into something particularly interactive as follows. Let me go ahead and zoom out here, and let me propose that we implement something like some kind of maze-based game. And let me go ahead here. So I want to implement some maze-based game that looks at first glance like this. Let me hit play. It's not a very fun game yet, but here's a little Harvard shield, a couple of black lines, this time vertical instead of horizontal. But notice you can't quite see my hand here, but I'm using my arrow keys to go down, to go up, to go left, to go right. But if I keep going right, it's not going anywhere. And left, it eventually stops. So before we look at the code, how might this be working? What kinds of scripts, collections of puzzle pieces, might collectively help us implement this? What do you think? Perfect. Yeah, there's probably some question being asked if touching the black line, and it happens to be a couple of sprites, each of which is just literally a vertical black line. We're probably asking a question like, are you touching it? Or is the distance to it 0 or close to 0? And if so, we just ignore the up, down, left, or rather, we ignore the left or the right arrow at that point. So that works. But otherwise, if we're not touching a wall, what are we probably doing instead? Forever here. How is the movement working, presumably? Yeah, and back? Or are you scratching? OK, sure. Let's go on. Sorry, say it a little louder. Exactly. It's continually, forever looking or listening for the arrow keys, up, down, left, right. And if the up arrow is pressed, we're probably changing the y by a positive value. If the down arrow is pressed, we're probably going down by y and left and right accordingly. So let's actually take a quick look. If I zoom out here and take a look at the code that implements this, there's a lot going on at first glance. But let's see. First of all, let me drag some stuff out of the way, because it's kind of overwhelming at first glance, especially if you, for instance, were poking around online as for problem set 0 just to get inspiration. Most projects out there are going to look overwhelming at first glance until you start to wrap your mind around what's going on. But in this case, we've implemented some abstractions from the get-go to sort of explain to ourselves and to anyone else looking at the code what's going on. This is that program with the 2 black lines and the Harvard shield going up, down, left, and right. It initially puts the shield in the middle, 0, 0. It then forever listens for keyboard, as I think you were describing. And it feels for the walls, as I think you were describing. Now, how is that implemented? Don't know yet. These are custom blocks we created as abstractions to kind of hide those implementation details. Because honestly, that's all I need to know right now. But as aspiring programmers, if we're curious now, let's scroll down to the actual implementation of listening for keyboard. This is the one on the left. And it is a little long, but it's a lot of similar structure. We're doing the following. If the up arrow is pressed, then change by y by 1, go up. If the down arrow is pressed, then change y by -1, go down. Right arrow, left arrow, and that's it. So it just assembles all of those ideas, combines it into one new block, just because it's kind of overwhelming. Let's just implement it once and tuck it away. And if we scroll now over to the feel for walls function, this now is asking the question, as hypothesized, if I'm touching the left wall, change my x value by 1, sort of move away from it a little bit. If I'm touching the right wall, then move x by -1 to move a little bit away from it. So it kind of bounces off the wall. Just in case it slightly went over, we keep the crest within those 2 walls. All right, so then a couple of more pieces here to introduce. What if we want to actually add some kind of adversary or opponent to this game? Well, let me go ahead to maybe this one here, where the adversary in this game might, for instance, be designed to be bouncing, to stand in your way. If this is like a maze and you're trying to get the Harvard shield from the bottom to the top or vice versa, uh-oh, Yale is in the way, and it seems to be automatically bouncing back and forth here. Well, let me ask someone else. Hypothesize. How is this working? This is an idea you have. This is an idea you see. Let's reverse engineer in your head how it works. How might this be working? Yeah, in back? Yeah, so if the Yale symbol is touching the left wall or the right wall, we somehow have it bounce. And indeed, we'll see there's a puzzle piece that can do exactly that, technically off the edge, as we'll see. But there's another way we can do this. And let's look at the code. The way we ourselves can implement exactly that idea bounce is just with a little bit of logic. So here's what this version of the program's doing. It's moving Yale by default to 0, 0, just to arbitrarily put it somewhere, pointing it direction 90 degrees, which means just horizontally, essentially. And then it's forever doing this. If touching the left wall or touching the right wall, here's our translation of bounce. We're just turning 180 degrees. And the nice thing about that is we don't have to worry if we're going from right to left or left to right. 180 degrees is going to work on both of the walls. And that's it. After we do that, we just move one step, 1 pixel at a time, but we're doing it forever, so something is happening continually. And the Yale icon is bouncing back and forth. Well, one final piece here. What if now we want a more another adversary, a more advanced adversary down the road, for instance, to go and follow us wherever we are, such that this time we want the other sprite to not just bounce back and forth, but literally follow us no matter where we go. How might this be implemented on the screen? I bet it's another forever block, but what's inside? Yeah, forever point at the location of the Harvard shield and go 1 step toward it. This is just going to go on forever. If I just give up, at least in this version, notice it's sort of twitching back and forth because it goes 1 pixel, then 1 pixel, then 1 pixel. It's sort of in a frantic state here. We haven't finished the game yet, but if we see inside, we'll see exactly that. It didn't take much to implement this simple idea. Go to a random position, just to make it kind of fair initially, then forever point towards Harvard, which is what we called the Harvard crest spray. Move 1 step. Suppose we now wanted to make a more advanced level. What's a minor change I could logically make to this code just to make MIT even better at this? All right, change the number of steps to 2. So let's try that. So now they got twice as fast. Let me go ahead and just get this out of the way. Whoops, let me make it a fair fight. Green flag. All right, I unfortunately am still moving 1 pixel at a time, so this isn't going to end well. It caught up to me. And if we're really aggressive and do something like 20 steps at a time, click the green flag. Jesus. OK, so that's how you might then make your levels progressively harder and harder. So it's not an accident that we chose these particular examples here involving these particular schools, because we have one more demonstration we thought we'd introduce today. If we could get one other volunteer to come up and play what was called by one of your predecessors Ivy's hardest game. Let's see, Hugh in the middle. Do you want to come on up? What's your name? Say again? Come a little closer, actually, and say it. Sorry. Hard to hear here. All right. A round of applause here if we could, too. OK, sorry. What was your name? Celeste. Celeste. Come on over. Nice to meet you, too. So here we have on this other screen Ivy's hardest game, written by a former CS50 student. I think you'll see that it combines these same principles. The maze is clearly a little more advanced. The goal at hand is to initially move the Harvard crest to the sprite all the way on the right so that you catch up to him in this case. But you'll see that there's different levels and different levels of sophistication. So if you're up for it, you can use just these arrow keys, up, down, left, right. You'll be controlling the Harvard sprite. And if we could raise the volume just a little bit, we'll make this our final example. There we go. Clicking the green flag. All right, that's it for CS50. Welcome to the class. We'll see you next time. All right, so this is CS50, and this is week 1, the one in which you learn a new language, which is something we technically said last week, at least if you had never played with this graphical language known as Scratch before, which itself was a programming language. But today, as promised, we transition to something a little more traditional, a little more text-based, not puzzle piece or block-based, known as C. This is an older language. It's been around for decades, but it's a language that underlies so many of today's more modern languages, among them something called Python that we'll also come to in a few weeks' time. Indeed, at the end of this semester, the goal is for you to feel that you've not learned Scratch, you've not learned C, or even Python for that matter, but fundamentally that you've learned how to program. Unfortunately, when you learn how to program with a more traditional language like this, there's just so much distraction. Last week, I described all of the syntax, all of the weird punctuation that you see in this, like the hash symbol, these angled brackets, parentheses, curly braces, \n, and more. Well, today, we're not going to reveal what all of those little particulars mean, but by next week, will this no longer look like the proverbial Greek to you, a language that presumably you've never actually seen or typed before. But to do that, we'll explore some of the very same topics as last week. So recall that via Scratch and presumably via problem set 1, we took a look at things called functions that are actions or verbs. And related to functions were arguments like inputs. And related to some functions were return values like outputs. Then we talked a bit about conditionals, forks in the road, so to speak, Boolean expressions, which are just yes-no questions or true-false questions, loops, which let you do things again and again, variables, like in math, that let you store values temporarily, and then even other topics still. So if you were comfortable on the heels of problem set 0 and last week, realize that all of these topics are going to remain with us. So really today is just about acquiring all the more of a mental model for how you translate those ideas into presumably a very cryptic new syntax. A new syntax, frankly, that's actually more simple in some ways than your own human language, be it English or something else, because there's far fewer vocabulary words. There's actually far less syntax that you might have in, say, a typical human language. But you need to be, with these computer languages, all the more precise so that you're most ultimately correct. And ultimately, we'll see, too, your code is successful along a few other lines as well. So if you think about like the last time you kind of wandered around not really knowing what you were doing or encountered something new, might not have been that long ago, entering Harvard Yard for the very first time or Old Campus or the like, be it in Cambridge or New Haven. You know, you didn't really need to know how to do everything as a first year. You didn't need to know who everyone was, where everything was, how Harvard or Yale or anything else for that matter worked. You sort of got by day to day by just focusing on those things that matter. And anything you didn't really understand, you sort of turn a blind eye to until it's important. And that's indeed what we're going to do today. And really for the next several weeks, we'll focus on details that are initially important and try to wave our hands, so to speak, at details that, yeah, eventually we'll get to, might be interesting, but for now they might be distractions. And by distractions, I really mean some of that syntax to which I alluded earlier. So by the end of today, and really by the end of problem set 1, your first foray presumably into this language called C, you'll have written some code. And you'll be asking yourself, we'll be asking yourselves, just how good is that code? Well, first and foremost, per last week, be it in Scratch or phone book form, like code ultimately needs to be correct, to be well done, right? You want the problem to be solved correctly, so that one sort of goes without saying. And along the way, this term will provide you with tools and techniques, so you don't have to just sit there sort of endlessly trying an input, checking the output, trying another input, checking the output. There's a lot of automation tools in the real world and in this class and others like it that'll help facilitate you answering that question for yourself. Is my code correct according to our specifications or the like? But then something that's going to take more time, and you're probably not going to feel 100% comfortable with the first week, the first weeks, is just how well designed your code is. It's one thing to sort of speak English or write English, but it's another thing, or any language for that matter, but it's another thing to speak it or write it well. And we spent all these years in middle school, high school, presumably, writing papers and other documents, getting grades and feedback on them as to how well formulated your arguments were, how well structured your paper was, and the like. And there's that same idea in programming. It doesn't matter necessarily that you've just solved the a problem correctly. If your code is a complete visual mess, or if it's crazy long, it's going to be really hard for someone else to wrap their mind around what your code is doing, and indeed to be confident if it is correct. And honestly, you, the next morning, the next year, next time you look at that code, might have no idea what you yourself were even thinking. But you will if you focus too on designing good code, getting your algorithms efficient, getting your code nice and clean, and even making sure your code looks pretty, which would describe as a matter of style. So in the sort of written human world, having punctuation in the right place, capitalization and the like, the sort of way you write an essay, but not necessarily send a text message, relates to style, for instance. And so good style in code is going to have a few of these characteristics that are pretty easily taught and remembered, but you just have to start to get in the habit of writing code in a certain way. So these three axes, so to speak, correctness, design, and style, are really the overarching goals when writing code that ultimately is going to look like this. So this program we conjectured last week does what if you run it on a Mac or PC or somewhere else, presumably? What does it do? Yeah. It just prints hello world. And honestly, that's kind of atrocious that you need to hit your keyboard keys this many times with this cryptic syntax just to get a program to say hello world. So a spoiler, in a few weeks' time when we introduce other more modern languages like Python, you can distill this same logic into literally one line of code. And so we're getting there ultimately, but it's helpful to understand what it is that's going on here, because even though this is a pretty cryptic syntax, there's nothing after this week and really next week that you shouldn't be able to understand, even about something that right now looks a little something like this. So how do you write code? Well, I've given us sort of the answer to a problem. How do you print hello world on the screen? So what do I do with this code? Well, we're in the habit of typically writing things with like Microsoft Word or Google Documents. And yeah, I could open up Word or Google Docs or Pages or the like and just literally transcribe that character for character, save it, and boom, I've got a program. But the problem, per last week, is that computers only understand or speak what other language, so to speak? Yeah, so binary, zeros and ones. And so this obviously is not zeros and ones. So it doesn't matter if I put it in a Word doc, Google Doc, Pages file, or the like. The computer's not going to understand it until I somehow translate it to zeros and ones. And honestly, none of those tools that I rattled off are really appropriate for programming. Why? Well, they come with features like boldfacing and italics and sort of fluffy aesthetic stuff that has no functional impact on what you're trying to do with your code. And they don't have the ability, it would seem, to convert that code ultimately to zeros and ones. But tools that do have this capability might be called integrated development environments, or IDEs, or more simply, text editors. A text editor is a tool that a programmer uses perhaps every day to write their code. And it's a simple program. Here, for instance, a very popular one called Visual Studio Code, or VS Code. And at the top here, you see that I've actually created in advance, before class, a very simple empty file called hello.c. Why? Well, .c indicates by convention that this is going to be a file in which there is C code. It's not .docx, which would mean in this file is a Microsoft Word document, or .pages is a Pages file. This is .c, which means in this file is going to be text in the language called C. This number 1 here is just sort of an automatic line number that's going to help me keep track of how long or short this program is. And the cursor is just blinking there, waiting for me to start typing some code. Well, let me go ahead and type out exactly the same code. For me, it comes pretty comfortably from memory, so I'm going to go ahead and include something called standardIO.h. More on that later. I'm going to sort of magically type int main void, whatever that means. We'll come back to that later. One of these curly braces, and then a sibling there that closes the same. Then I'm going to hit tab to indent a few spaces, and then I'm going to type not print, but printf. Then hello, comma, world, \n, close quote, close parenthesis, semicolon. And I dare say this was essentially the very first program I wrote some 25 years ago. I wrote it to say, hi, CS50. Now it just says the more canonical, conventional hello world. But that's it. That's my very first program. And all I need to now do is maybe hit Command S or Control S to save the file. And voila, I am a programmer. The catch, though, is, like, OK, how do I run this? Like on your Mac or PC, how do you run a program? Well, usually double-click an icon. On your phone, you tap an icon. In this environment that we're using and that many programmers, dare say most programmers use, you don't have immediately a nice, pretty icon to double-click on. That's very user-friendly, but it's not very necessary, especially when you get more comfortable with programming. You're going to want to type commands because it's just faster than pointing and clicking a mouse. And you're going to want to automate things, which is a lot easier if it's all command or text-based as opposed to mouse and muscular movements. And so here, I have my program. It lives in this file called hello.c. I need to now convert it, though, to zeros and ones. Well, how do I go about doing this? And how am I going to get from those this so-called code, or source code, as it's conventionally called, to this, these zeros and ones that we'll now start calling machine code. The zeros and ones from last week can be used not only to represent numbers and letters, colors, audio, video, and more. It can also represent instructions to a computer, like print, or play a sound, or delete a file, or save a file. All the sort of basics of a computer somehow can be represented by other patterns of zeros and ones. And just like last week, it depends on the context in which these numbers are stored. Sometimes they're interpreted as numbers, like in a spreadsheet. Sometimes they're interpreted as colors. Sometimes they're interpreted as instructions, commands to your computer to do very low-level operations like print something on the screen. So fortunately, like last week's definition of like computer science, of problem solving, is a nice mental model for exactly the goal at hand. I have some input, aka source code. I want to output ultimately machine code, those zeros and ones. I certainly don't want to do this kind of process by hand. So hopefully there's an algorithm implemented by some special program that does exactly that. And those of you who do have some prior experience, this program might be called a compiler. So a few of you have indeed programmed before. Not all languages use compilers. C, in fact, is a language that does use a compiler. And so I just need to find myself on my computer somewhere, presumably, a so-called compiler, a program whose purpose in life is to convert one language to another. And source code, written textually in C, like we saw a moment ago, is source code. The machine code is the corresponding zeros and ones. So let me go back to this same programming environment called Visual Studio Code, or VS Code. This is typically a program you or any programmer on the internet can download onto their own Mac or PC and be on their way with whatever computer you own writing some code. A downside, though, of that approach is that all of us have slightly different versions of Macs or PCs. We have slightly different versions of operating systems. They may or may not be up to date. It's just sort of a technical support nightmare to create a uniform environment, especially for like an introductory class where everyone should ideally be on the same page so we can get you up and running quickly. And so I'm actually using a cloud-based version of VS Code, something that you only need a browser to access, and then you can be on any computer today or tomorrow. By the end of the semester, we're going to get you out of the cloud, so to speak, as best we can, and get you onto your own Mac or PC so that after this class, especially if it's the only CS class you ever take, you feel like you can continue programming in any number of languages, even with CS50 behind you. But for now, wonderfully, the browser version of VS Code should pretty much be identical to what the eventual downloadable version of the same would be. And you'll see in problem set 1 how to access this and how to get going yourself with your first programs. But I haven't mentioned this bottom part of the screen, And this is an area where we have what's called a terminal window. So this is sort of old school technology that allows you, with a keyboard, to interact with a computer, wherever it may be, on your lap, in your pocket, or even, in this case, in the cloud. So on the top-hand portion of this screen is my text editor, like tabbed windows, like in many programs where I can just create files and write code. The bottom of the screen here, my so-called terminal window, gives me the ability to run commands on a server that currently I have exclusive access to. So because I logged into VS Code with my account online, I have my own sort of virtual server, if you will, in the cloud, otherwise known as, in this context, a container. This has its own operating system for me, its own hard drive, if you will, where I can save and create files of my own separate from yours and vice versa. And it's at this very simple prompt, which is conventionally, but not always, abbreviated by a $, has nothing to do with currency. It just means type your commands here. This is where I'm going to be able to type commands like compile my source code into machine code. So it's a command line interface, or CLI, on top of an operating system that you might not have ever used or seen, but it's very popular, called Linux. Odds are almost all of us in this room are using Mac OS or Windows right now. But we're all going to start using an operating system called Linux, which is in a family of operating systems that offer not only this command line interface, but are used not just for programming, but for serving websites and developing applications and the like. And it's indeed a familiar and very powerful interface, as we'll see. So how do I go about making this file, hello.c, into a program? There's no icon to double click, but there is a command. I can type make hello at this $ prompt, go ahead and hit enter, and nothing appears to happen. But that's a good thing. And as we'll see in programming, almost always, if you don't see anything go wrong, that means everything went right. So this is going to be a rarity at first, but this is a good thing that it just seems to do nothing. But now, there is in the folder in my account on the cloud a file called hello. And it's a bit of a weird command, but you'll get familiar with it before long. Dot just means go into my current folder. /hello means run the program called hello in this current folder. So ./hello and then enter, and voila. Now I'm actually not just programming, but running my actual code. So what have I just done? Let me go ahead and do this. I'm going to go ahead and open up the sidebar of this program, and you'll see in problem set 1 how to do this. And this might look a little different based on your own configuration. Even the color scheme I'm using might ultimately look different from yours because it supports nice colorful themes. So you can have different colors and brightnesses depending on your mood or the time of day. What I've opened here, though, is what is called in VS Code Explorer. And this is just all of the files in my cloud account. And there's not many right now. There's only 2. One is the file called hello.c, and it's highlighted because I've got it open right there. And the other is a file called hello, which is brand new and was created when I ran that command. And what's now worth noting is that now things are getting a little more like Mac OS and Windows. Like on the left-hand side, you have a GUI, a graphical user interface. But on the bottom here, again, you have a CLI, command line interface. These are just different ways to interact with computers. And you'll get comfortable with both. And honestly, you're certainly familiar and comfortable with GUIs already. So it's the command line one with which we'll spend some time. Now, suppose that I just wanted to do something more than compile this program. Suppose I wanted to go ahead and remove it. Like, no, I made a mistake. I want to say hello CS50, not hello world. I could just hover up here like in any software, and I could right-click, and I could poke around, and there, delete permanently. So most of us might have that instinct on a Mac or PC. You right-click or control-click, and you poke around. But in a command line interface, let me do this instead. The command for removing or deleting a file in the world of Linux, this other operating system, is just to type rm for remove, and then hello, enter. It's a somewhat cryptic confirmation message, but this just means, are you sure? I'm going to go ahead and type Y for yes. And now when I hit enter, watch what happens at top left in the Explorer, the GUI, the graphical interface. Voila, it disappears. Right, not terribly exciting, but this just means this is a graphical version of what we're seeing here. And in fact, if you want to never use the GUI again, I'll go ahead and close it with a keyboard shortcut here. You can forever just type ls for list and hit enter, and you will see in the command line interface all of the files in your current folder. So anything you can do with a mouse, you can do with this command line interface, and indeed we'll see many more things that you can do as well. But the inventors of this and this operating system and its predecessors were very succinct. Like the command is rm for remove. The command is ls for list. It's very terse. Why? Because it's just faster to type. So before we forge ahead with making something more interesting than just hello world, let me pause here to see if there's questions on source code or machine code or compiler or this command line interface. Yeah. Really good question, and let me recap. If I were to make changes to the program, run it, and then maybe make other changes and try to rerun it, would those changes be reflected, even though I've reworded slightly? Well, let's do this. I already removed the old version, so let me go ahead and point out that if I do /hello now, I'm going to see some kind of error because I just deleted the file. No such file or directory, so it's not terribly user-friendly, but it's saying what the problem is. Let me go ahead and remake it by typing make hello. Now, if I type ls, I'll see not one but 2 files again. And one of them is even green with a little asterisk to indicate that it's executable. It's sort of the textual version of something you could double-click in our human world. So now, of course, if I run hello, we're back where I started, hello world. But now suppose I change it to hello, CS50, like I did years ago. Let me go ahead and save the file with Command S or Control S. Down here now, let me run /hello again, and voila. So let me ask someone else to answer that question. What's the missing step? Why did it not say hello CS50? Yeah. Yeah, so I didn't compile it again. So sort of newbie mistake. You're going to make this mistake and many others before long. But now let me go ahead and remake hello, enter. It's going to seemingly make the same program. But this time when I run it, it's hello CS50. All right, any other questions on some of these building blocks? And we'll come back to all the crazy syntax I typed before long. But for now, we're focusing on just the output. Yeah? When I keep running make, it creates a new version of the machine code. So it keeps changing the hello program in the hello file, and that's it. There's no make file per se. Good question. No. If I open up that directory, you'll see that there's just the one. And it doesn't matter how many times I run make hello, 3, 4, 5, it just keeps overwriting the original. So it's kind of like just saving in the world of Google Docs or Microsoft Word or the like. But there's an additional step today. We have to then convert my words to the computers, the zeros and ones. Yeah, in front. What happens if I run hello.c? So let me go ahead and do /hello.c, which is a mistake you'll invariably make early on, permission denied. So what does that mean? This is where the error messages mean something to the people who design the operating system, but it's a little cryptic. It's not that you don't have access to the file. It means that it's not executable. This is not something you have permission to run, but you do have permission to read or write it. That is, change it. Really good question. So if I have named my file hello.c, or more generally something.c, one of the things that make does is it automatically picks the file name for me. And we'll discuss this a bit more next week. Make itself is kind of the first of white lies today. Itself is not a compiler. It's a program that knows how to find and use a compiler on the system and automatically create the program. If I use, as we'll discuss next week, the actual compiler myself, I have to type a much longer sequence of commands to specify explicitly what do I want the name of my program to be. Make is a nice program, especially in week 1, because it just automates all of that for us. And so here we have now a program that very simply prints something on the screen. So let's now put this into the context of where we left off last time, in the context of Scratch and inputs and outputs. So we discussed last time, of course, functions and arguments. Functions, again, are those actions and verbs like say or ask or the like. And the arguments were the inputs to those functions, generally in those little white ovals that in Scratch you could type words or numbers into. We'll see, and all of the languages we're going to see this term have that same capability. And let's just start to translate one of these things to another. So for instance, let's put this same program in C in the context of Scratch. This is what hello world looked like last week in the form of one function. This week, of course, it looks like print, and then the parentheses, notice, are kind of deliberately designed in the world of Scratch to resemble that same shape. Even though this is a white oval, you kind of get that it's kind of evoking that same idea with the parentheses. Technically, the function in C, it's not called say. It's not even called print. It's called printf. The F stands for formatted, but we'll see what that means in a moment. But printf is the closest analogous function for say in the world of C. Notice if, though, you want to print something like hello world or hello CS50 in C, you don't just write the words as we did last week. You also had to add what, if you notice already what's missing from this version? Yeah, so the double quotes on the left and the right. So that's necessary in C whenever you have a string of words, and I'm using that word deliberately. Whenever you have multiple words like this, this is known as a string, as we'll see, and you have to put it in double quotes. Not single quotes, you have to put it in double quotes. There's one other stupid thing that we need to have in my C code in order to get this function to do something ultimately, which is what? Semicolon. So just like in our human world, you eventually got into the habit of using, at least in formal writing, periods. Semicolon is generally what you use to finish your thought in the world of programming with C. All right, so we have that function in place. Now, what does this really fit into in terms of the mental model? Well, functions take arguments, and it turns out functions can have different types of outputs. And we've actually seen both already last week. One type of output from a function can be something called a side effect. And it generally refers to something visual, like something appearing on the screen or a sound playing from your computer. It's sort of a side effect of the function doing its thing. And indeed, last week we saw this in the context of passing in something like hello world as input to the say function. And we saw on the screen hello world. But it was kind of a one-off. It's one and done. You can't actually do anything with that visual output other than consume it visually with your human eyes. But sometimes, recall last week, we had functions like the ask block that actually returned me some value. Remember the ask, what's your name? It handed me back whatever answer the human typed in. It didn't just arbitrarily display it on the screen. The cat didn't necessarily say it on the screen. It was stored instead in that special variable that was called answer, because some functions have not side effects but return values. They hand you back an output that you can use and reuse, unlike the side effect, which again displays and that's it. You can't sort of catch it and hold on to it. So in the context of last week, we had the ask block, and that had this special answer return value. In C, we're going to see in just a moment, we could translate this as follows. The closest match I can propose for the ask block is a function that we're going to start calling getString. String is, again, a word, a set of words, like a phrase or a sentence in programming. It, too, is a function insofar as it takes input. And pretty much, this isn't always true, but very often when you have a word in C followed by an open parenthesis and a closed parenthesis, it's most likely the name of a function. And we're going to see that there's some exceptions to that. But for now, this indeed looks like a function because it matches that pattern. If I want to ask the question, what's your name? Question mark. And I'm even going to deliberately put a space there just to kind of move the cursor a little bit over so that the human isn't typing literally after the question mark. So that's just a nitpicky aesthetic. This is perhaps the closest analog to just asking that question. But because the ask block returns a value, the analog here for getString is that it too returns a value. It doesn't just print the human's input. It hands it back to you in the form of a variable, aka a return value, that I can then use and reuse. Now, ideally, it would be as simple as this, literally saying answer on the left equals. And this is where things start to diverge from math and sort of our human world. This equal sign, henceforth, is not the equal sign. It is the assignment operator. To assign a value means to store a value in some variable. And you read these things, weirdly, right to left. So here is a function called getString. I claim that it's going to return to you whatever the human types in as their name. It's going to get stored over here on the left because of this so-called assignment operator. That, yes, is an equal sign, but it doesn't mean equality in this context. It makes things equal, but it does so by copying the value on the right into the thing on the left. Unfortunately, we're not quite done yet with C. And this is where, again, it gets a little annoying at first, whereas Scratch just let us express our ideas without so much syntax. In C, when you have a variable, you don't just give it a name like you did in Scratch. You also have to tell the computer in advance what type of value it is storing. String is one such type of value. Int for integer is going to be another. And there's even more than that that we'll see today and beyond. And this is partly an answer to the question that came up one or more times last week, which was, how does a computer distinguish this pattern of zeros and ones from this? Like, is this a letter, a number, a color, a piece of video? And I just claimed last week that it totally depends on the program. It depends on the context. And that's true. But within those programs, it often depends on what the human programmer said the type of the value is. This specifies it's a string, which means interpret the following zeros and ones that are stored in my program as words or letters more generally. If it said int for integer, it would be implying by the programmer, treat the following zeros and ones in my program as a number, an integer, not a string. So here's where this week, unlike with Scratch, which just kind of figures out what you mean, with C in a lot of languages, you have to be this pedantic and tell it what you mean. There's still one stupid thing missing from my code here. What's still missing here? Yeah? And we still need the stupid semicolon. And I'm sort of impugning it here because, honestly, these are the kinds of stupid mistakes you're going to make today, tomorrow, this weekend, next week, a few weeks from now, until you start to notice this and recognize it as well as you do English or whatever your spoken language is. Yeah, question. Good question. Suppose I mix apples and oranges, so to speak, and I try to put a string in an int or an int in a string. The compiler is going to complain. So when I run that make command, as I did earlier, it's not going to be nice and blissfully quiet and just give me another prompt. It's going to yell at me with, honestly, a very cryptic-looking error message until we get the muscle memory for reading it. Other questions? What happened to the \n? So we'll come back to that in just a moment, if we may, because I have deliberately omitted it here, but we did have it earlier, and we'll see the different behavior in a sec. Other questions? Yeah, not at all nitpicky. These are the kinds of things that just matter, and it's going to take time to recognize and develop this muscle memory. Everything I've typed here, except for the W at the moment, is lowercase. And the W is capitalized just because it's English. Everything else is lowercase. And this kind of varies by language and also context. So in many languages, the convention is to use all lowercase letters for your variable names. Other languages might use some capitals as well, but we'll talk about that before long. But this is the kind of thing that matters and is hard to see at first, especially when a little s doesn't look that different, when it's on your tiny laptop screen from a capital S, but you'll start to develop these instincts. All right, so besides this particular block, let's go ahead and consider how we can go about implementing this now in code. So let me switch back to VS Code here. This was the program I had earlier, and let me go ahead and undo my CS50 change, and this time just rerun make on hello with the original version with the \n. Enter, nothing bad seems to have happened, so /hello, enter, hello world. Now, if you're curious, this is a good instinct to start to acquire. What happens if I get rid of this? Well, I'm probably not going to break things too badly, so let's try. Let me go ahead now and do make hello. Still compiles, so it's not a really bad mistake. So let me go ahead and run /hello. What's the difference here? Yeah, what do you see that's different? Yeah, the $, my so-called prompt, stayed on the same line. Why? Well, we can presumably infer now that the \n is some fancy notation for saying create a new line, move the cursor, so to speak, to the next line. Notice that the cursor will move to the next line in my terminal window. If I keep hitting it, it just automatically, by nature of hitting enter, does it. But it'd be kind of stupid if when you run a program in this world, simple as it is, if like the next command is now weirdly spaced in the middle of the terminal with the $, it just looks sloppy, right? It's really just an aesthetic argument. And notice that it's not acceptable or correct to do this, to hit enter there. Let me go ahead and save that, though, and see what happens. Let me go ahead now and run make hello, enter. Oh, my God, like 4 errors. This is like, what, 10 lines of errors for like a 1-line program? And this is where, again, you'll start to develop the instincts for just reading this stuff. These kinds of tools, like the compiler tool we're using, were not designed necessarily with user friendliness in mind. That's changed over the decades, but certainly early on, it's really just meant to be correct and precise with its errors. So what did I do here? Missing terminating close quote character. Long story short, when you have a string in C, your double quotes just have to be on the same line, just because. Now, there's the slight white lie. There's ways around this, but the best way around it is to use this so-called escape sequence. To escape something means generally to put a \, and then a special symbol like N for new line. And this is just the agreed upon way that humans decades ago decided, OK, you don't just hit your enter key. You instead put \n, and that tells the computer to move the cursor to the new line. So again, kind of cryptic, but once you know it, like that's it. It's just another word in our vocabulary. So now let me transition to making my program a little more interactive. Instead of just saying hello world, let me change it like last week to say hello David, or whoever's interacting with the program. So I'm going to do string answer get string, quote unquote, what's your name? I'm not going to bother with a new line here. I could. This is now just a judgment call. I deliberately want the human to type their name on the same line, just because. And how do I now print this? Well, last week, recall, we used say, and then we used the other block called join. So the idea here is the same, but the syntax this week is going to be a little different. It's going to be printf, which prints something on the screen. I'm going to go ahead and say hello, comma, and let me just go with this initially, with the \n, semicolon. Let me go ahead and recompile my code. Whoops. Damn, doesn't work still. And look at all these errors. Like there's more errors than code I wrote. But what's going on here? Well, this is actually a mistake you'll see somewhat often, at least initially. And let's start to glean what's going on here. So here, if I look at the very first line of output after the $, so even though it jumped down the screen pretty fast, I wrote make hello at the $, prompt. And then here's the first error. On hello.c, line 5, technically character 5, but generally line is enough to get you going. There's an error. Use of undeclared identifier string. Did you mean standard in? So I didn't. And this is not an obvious solution at first, but you'll start to recognize these patterns in error messages. It turns out that if I want to use string, I actually have to do this. I have to include another library up here, another line of code rather, called CS50.h. We'll come back to what this means in just a moment. But if I now retroactively say, all right, what does standard I/O do for us up here? Before I added that new line, what is standard I/O doing? Well, if you think back to Scratch, there were a few examples with like the camera and with the the text to voice. Remember, I had to poke around in like the extensions button, and then I had to load it into Scratch. It didn't come natively with Scratch. C is quite like that. Some functions come with the language, but for the most part, if you want to use a function, an action or a verb like printf, you have to load that extension, so to speak, that more traditionally is called a library. So there is a standard I/O library, stdio, standard I/O, where I/O just means input and output, which means, just like in MIT's world, there was an extension for doing text to voice or for using your camera. In C, there's an extension, aka a library, for doing standard input and output. And so if you want to use any functions related to standard input and output, like text from a keyboard, you have to include standard IO.h. And then can you use printf. Same goes here. getString, it turns out, is a function that CS50 wrote some time ago. And as we'll see over the coming weeks, it just makes it way easier to get input from a user. C is very good with printf at printing output on the screen. C makes it really annoying and hard, as we'll see in a few weeks, to just get input from the user. So we wrote a function called getString, but the only way you can use that is to load the extension, aka load the library called CS50. And we'll come back in time, like why is it .h, why is it a hash symbol? But for now, standard I/O is a library that gives you access to printf and input and output related stuff. CS50 is a second library that provides you with access to functions that don't come with C that include something like getString. So with that said, we've now kind of teased apart at a high level what lines 2 and now 1 are doing. Let me go ahead and rerun make hello. Now it worked. So all those crazy error messages were resolved by just one fix. So key takeaway is not to get overwhelmed by the sheer number of errors. Let me now do /hello. And if I type in my name, what am I going to see? What do you think? Yeah, hello answer, because the computer is going to take me literally. And it turns out that if you just write hello, comma, answer all in the double quotes, you're really just passing English as the input to the printf function. You're not actually passing in the variable. And unfortunately in C, it's not quite as easy to plug things in to other things that you've typed. Remember in Scratch, there was not just the say block, but the join block, which was kind of pretty. It does, you can combine apples and oranges, or what was it, apple and banana. Then we changed it to hello, and then the answer that the human typed in. In C, the syntax is going to be a little different. You tell the computer inside of your double quotes that you want to have a placeholder there, or so-called format code. %s means, hey, computer, put a string here eventually. Then, outside of your quotes, you just add a comma, and then you type in whatever variable you want the computer to plug in at that %s location for you. So %s is a format code, which serves as a placeholder. And now the printf function was designed by humans years ago to figure out how to do the apple and banana thing of joining two words together. It's not nearly as user-friendly as it is in Scratch, but it's a very common paradigm. So let me try and rerun this now. Make hello. No errors. That's good. /hello. What's my name? David. If I type enter now it's hello, David. And the printf, here's the f in printf. It formats its input for you by using these placeholders for things like strings, represented again by %s. So a quick question then. If I focus here on line 7 for just a moment and even zoom in here, how many inputs is printf taking as a function? A moment ago, I'd admit that it was taking one input, hello world, quote unquote. How many inputs might you infer printf is taking now? 2. And it's implied by this comma here, which is separating the first one, quote unquote, hello, %s, from the second one, answer. And then just as a quick safety check here, why is it not 3? Because there's obviously 2 commas here. Why is it not actually 3 arguments or inputs? Exactly. The comma to the left is actually part of my English grammar. That's all. So same syntax. And again, here's where, again, programming can just be confusing early on because we're using the same special punctuation to mean different things. It just depends on the context. And so now is actually a good time to point out all of the somewhat pretty colors that have been popping up on the screen here. Even though I wasn't going to like a format menu, I wasn't bold-facing things, I certainly wasn't changing things to red or blue or whatnot. That's because a text editor like VS Code syntax highlights for you. This is a feature of so many different programming environments nowadays. VS Code does it as well. If your text editor understands the language that you're programming in, C in this case, it highlights in different colors the different types of ideas in your code. So for instance, string and answer here are in black, but getString, a function, is in this sort of nasty brown yellow here right now, but that's just how it displays on the screen. The string, though, here in red is kind of jumping out at me, and that's marginally useful. The %s is in blue. That's kind of nice because it's jumping out at me. And so it's just using different colors to make different things on the screen pop so you can focus on how these ideas interrelate. And honestly, when you might make a mistake. For instance, let me accidentally leave off this quote here. And now all of a sudden, everything, notice, if I delete the quote, the colors start to get a little awry. But if I go back there and put it back, now everything's back in place. What's another feature of this text editor? Notice when my cursor is next to this parenthesis, which demarcates the end of the inputs to the function, notice that highlighted in green here is the opening parenthesis. Why? It's just a visually useful thing, especially when you start writing more and more code, just to make sure your parentheses are lining up. And that's true for these curly braces over here on the left and the right. We'll come back to those in a moment. If I put my cursor there, you can see that these things correspond to one another. So it's nothing in your code fundamentally. It's just the editor trying to help you, the human, program. And you can even see it, though it's a little subtle. See these 4 dots here and these 4 dots here? That's my indentation. I'm configured VS Code to indent by 4 spaces, which is a very common convention. Anytime I hit the tab key, this too can help you make sure, once we have more interesting and longer programs, that everything lines up nice and neatly. All right, any questions then on printf or more? Yeah. Short answer, yes. Printf can handle more than one type of variable or value. %s is one. We're going to see %i is another for plugging in an integer. You can have multiple i's, multiple s's, and even other symbols too. We'll come back to that in just a little bit. Printf can take many more arguments than just these two. This is just meant to be representative. Yeah, over here. Can you declare variables within the printf? No. The only variable I'm using right now is answer, and it's got to be done outside the context of printf in this case. Good question. We'll see more of that before long. Yeah, in back. How do we download the CS50 library? So we will show you in problem set 1 exactly how to do that. It's automatically done for you in our version of VS Code in the cloud. If ultimately you program on your own Mac or PC, either initially or later on, it's also installable online. But if you want to ask that via online or afterward, we can point you in the right direction. But pset 1 will itself. Yeah. String is the type of the variable, or more properly, the data type of the variable. Int is another keyword I alluded to earlier. Haven't used it yet. Int for integer is going to be another type or data type of variable. Yeah. Good question. Could I go ahead and just plug in this function, kind of like we did in Scratch, getting rid of the variable altogether, and just do this, which recall is reminiscent of what I did in Scratch by plopping block on top of block on block? Am I answering that right? Can I put string in front of getString? No. You only put the word string in front of a variable that you want to make string. And even though I'm apparently answering the wrong question, let me go ahead and zoom out, save this, do make hello again. Seems to compile OK. If I run /hello, type in David, voila, that too works. And so actually, let's go down this rabbit hole for just a moment. Clearly, it's still correct, at least based on my limited testing. Is this better designed or worse designed? Let's open that question like we did last week, yeah? Yeah, I kind of agree with that. Reasonable people could disagree, but I do agree that this seems harder to read because, like, I start reading here, but wait a minute, getString is going to get used first, and then it's going to give me back a value. So yeah, it just feels like it was nicer to read top to bottom, I would say. Your thoughts? Yeah, and so this is useful if I only want to print out the person's name once. If I want to use it later in a longer program, I'm out of luck. And so I haven't saved it in a variable. So I think, long story short, we could sort of debate this all day long. But in this case, like, if you can make a reasonable argument one way or the other, like, that's a pretty solid ground to stand on. But invariably, reasonable people are going to disagree, whether first-time programmers or many years after that. So let's frame this one last example in the context of this same process of taking inputs and outputs. The functions we've been talking about all take inputs, otherwise now known as arguments or parameters, pretty much synonymous. That's just the fancy word for an input to a function. And some functions have either side effects, like we saw, printing something, saying something on the screen sort of visually or audibly, or they return a value which is a reusable value, like name or answer in this case. If we look then at what we did last time, in the world of Scratch last week, the input was what's your name, the function was ask, and the return value was answer. And now let's take a look at this block, which is honestly a more user-friendly version of what we just did with the %s. Last week we said say, then join, then hello and answer. But the interesting takeaway there was not how to say hello anything. It was the fact that in Scratch 2, the output of one function, like the green join, could become the input to another function, the purple say. The syntax in C is admittedly pretty different, but the idea is essentially the same. Here, though, we have hello, a placeholder, but we have to, in this world of C, tell printf what we want to plug in for that placeholder. It's just different, but that's the way to do it. When we get to Python and other languages later in the term, there's actually easier ways to do this, but this is a very common paradigm, particularly when you want to format your data in some way. All right, let's then take a step back to where we began, which was with that whole program, which had the include, and it had int, main, void, and all of this other cryptic syntax. This Scratch piece last week was kind of like the go-to whenever you want to have a main part of your program. It's not the only way to start a Scratch program. You could listen for clicks or other things, not just the green flag, but this was probably the most popular place to start a program in Scratch. In C, the closest analog is to literally write this out. So just like last week, if you were in the habit of dragging and dropping when green flag clicked, as a C programmer, the first thing you would do is, after creating an empty file, like I did with hello.c, you'd probably type int main void, open curly brace, close curly brace, and then you can put all of your code inside of those curly braces. So just like Scratch had this sort of magnetic nature to it, where the puzzle pieces would snap together, C, as a text-based language, tends to use these curly braces, one of them opened, the other one closed, and anything inside of those braces, so to speak, is part of this puzzle piece, aka main. So what was atop them? We went down this rabbit hole a moment ago with these things called header files, even though I didn't call them by this name. But indeed, when we have a whole program in Scratch, super easy. Just have the when green flag clicked and then say hello world. There's no special syntax. After all, it's meant to be very user-friendly and graphical. In C, though, you technically can't just put int main void printf hello world. You also need this because, again, you need to tell the compiler to load the library, code that someone else wrote, so that the compiler knows what printf even is. You have to load the CS50 library whenever you want to use getString or other functions like getInt, as we'll soon see. Otherwise, the compiler won't know what getString is. You just have to do it this way. The specific file name I'm mentioning here, standardIO.h, CS50.h, is what C programmers call a header file. We'll see eventually what's inside of those files, but long story short, it's like a menu of all of the available functions. So in CS50.h, there's a menu mentioning getString, getInt, and a bunch of other stuff. And in standardIO.h, there's a menu of functions, among which are printf. And that menu is what prepares the compiler to know how to implement those same functions. All right, let me pause here. Question? Not quite. A library provides all of the functionality we're talking about. A header file is the very specific mechanism via which you include it. And we'll discuss this more next week. For now, they're essentially the same, but we'll discuss nuances between the two next week. Yeah, the library would be standard IO. The library would be CS50. The corresponding header file is standardio.h, cs50.h. Indeed. Other questions? Yeah. Indeed. That too is on the menu. We'll come back to that. But the word string, incredibly common in the world of programming. It's not a CS50 idea. But in C, there's technically no such data type as string by default. We have sort of conjured it up to simplify the first few weeks. That's a training wheel that we'll very deliberately in a few weeks take away. And we'll see why we've been using getString and string, because C otherwise makes things quite more challenging early on, which then gets besides the point for us. Yeah? Yes, early on, you will have to use whatever's prescribed by the specification. That will include CS50's functions. Long story short, you referred, I think, a moment ago to another function called scanf. We won't talk about for a few weeks. Long story short, in C, it's pretty easy and possible to get input from a user. The catch is that it's really easy to do it dangerously. And C, because it's an older, lower level language, so to speak, that gives you pretty much all ultimate control over your computer's hardware, it's very easy to make mistakes. And indeed, that's too why we use the library, so your code won't crash unintendedly. All right, so with this in mind, we have this now mapping between the Scratch version and the other. Let me just give you a quick tour of some of the other placeholders and data types that we'll soon start seeing as we assemble more interesting programs. In the world of Linux, here is a non-exhaustive list of commands with which you'll get familiar over the next few weeks by playing with problem sets. We've only seen 2 of these so far, ls for list, rm for others. But I mention them now just so that it doesn't feel too foreign when you see them on screen or online in a problem set. CP is going to stand for copy. Make_dir is going to stand for make directory. MV is going to stand for move or rename. rmdir is going to be remove directory. And CD is going to be for change directory. And let me show you this last one here first, only because it's something you'll use so commonly. If I go back to my code here on the screen, I'm going to go ahead and reopen the little GUI on the left-hand side, the so-called Explorer, revealing that I've got 2 files, hello and hello.c. So nothing has changed since there. Suppose now that it's a few weeks into class and I want to start organizing the code I'm writing so that I have a folder for this week or next week, or maybe a folder for problem set 1, problem set 2. I can do this in a few ways. In the GUI, I can go up here and do what most of you would do instinctively on a Mac or PC. You look for like a folder icon, you click it, and then you name a folder like pset1, enter. Voila, you've got a folder called pset1. I can confirm as much with my command line interface by typing what command? How can I list what's in my folder? Yeah, so ls for list. And now I see hello, and it's green with an asterisk because that's my executable, my runnable program. Hello.c, which is my source code. And now pset1 with a slash at the end, which just implies that it's indeed a folder. All right, I didn't really want to do it that way. I'd like to do it more advanced. So let me go ahead and right-click on pset1, delete permanently. I get a scary irreversible error message, but there's nothing in it, so that's fine. Now I've deleted it using the GUI. But now let me go ahead and start doing the same thing from the command line. And if you're wondering how things keep disappearing, if you hit Control-L in your terminal window or explicitly type clear, it will delete everything you previously typed just to kind of clean things up. In practice, you don't need to be doing this often. I'm doing it just to keep our focus on my latest commands. If I do, what was the command to make a new directory? Yeah, so make_dir, make directory. Let me create pset1, enter, and notice at left, there's my pset1. If I want to get a little overzealous, plan for next week, here's my pset2 directory. Suppose now I want to open those folders, one on Mac or PC or in this GUI. I could double click on it like this, and you'd see this little arrow is moving. It's not doing anything because there's nothing in there, but that's fine. But suppose, again, I want to get more comfortable with my command line. Notice if I type ls now, I see all 4 same things. Let me change directories with cd space pset1, enter. And now notice 2 things will have happened. One, my prompt has changed slightly to remind me where I am, just to keep me sane so that I don't forget what folder I'm actually in. So here is just a visual reminder of what folder I'm currently in. If I type ls now, what should I see after hitting enter? Nothing, because I've only created empty folders so far, and indeed, I see nothing. If I wanted to create a folder called Mario for a program that might be called Mario this week, I can do that. Now if I type ls, there's Mario. Now if I do cd Mario, notice my prompt's going to change to be a little more precise. Now I'm in pset1/Mario. And notice what's happening at top left. Nothing now because these folders are collapsed. But if I click the little triangle, there I see Mario. Nothing's going on in there because there's no files yet. But suppose now I want to create a file called mario.c. I could go up here. I could click the little plus icon and use the GUI. Or I can just type code mario.c. Voila. That creates a new tab for me. I'm not going to write any code in here yet, but I am going to save the file. And now at top left, you'll see that mario.c appears. So at some point, you can eventually just close the Explorer, because again, it's not providing you with any new information. It's maybe more user-friendly, but there's nothing you can't do at the command line that you could do at the GUI. All right, but now I'm kind of stuck. How do I get out of this folder? In my Mac or PC world, I'd probably click the back button or something like that, or just close it and start all over. In the terminal window, I can do cd ... is a nickname, if you will, for the parent directory. That is the previous directory. So if I hit enter now, notice I'm going to close the Mario folder, aka directory, and now I'm back in pset1. Or if I want to be fancy, let me go back into Mario temporarily. If I type ls, there's mario.c, just to orient us. If I want to do multiple things at a time, I could do cd // which goes to my parent to my grandparent, all in one breath. And voila, now I'm back in my default folder, if you will. And one last little trick of the trade, if I'm in pset1/Mario, like I was a moment ago, and you're just tired of all the navigation, if you just type cd and hit enter, it'll whisk you away back to your default folder. And you don't have to worry about getting there manually. Recall a bit ago, though, that I was running hello as this, /hello. If ... refers to my parent, perhaps infer here syntactically, what does a single dot mean instead? It means this directory, your current directory. Why is that necessary? It just makes super explicit to the computer that I want the program called hello that's installed here, not in some random other folder on my hard drive, so to speak. I want the one that's right here instead. All right, so besides these commands, there's going to be others that we encounter over time. Those are kind of the basics. That allows you to sort of wean yourself off of a GUI, a graphical user interface, and start using more comfortably, with practice and time, a command line interface instead. Well, what about those other types now, back in the world of C? Those commands were not C. Those are just commands specific to a command line interface like in Linux, which again we're using in the cloud. It's an alternative to Mac OS and Windows. Back in the world of C now, we've seen strings, which are words. I mentioned int or integer, but there's others as well. In the world of C, we've seen string. We will see int. If you want a bigger integer, there's something literally called a long. If you want a single character, there's something called a char. If you want a Boolean value, true or false, there is a bool. And if you want a floating point value, a fancy way of saying a real number, something with a decimal point in it, that is what C and other languages call a float. And if you want even more numbers after the decimal point, that is more precision, you can use something called a double. That is to say, here's again an example in programming where it's up to you now to provide the computer with hints, essentially, that it will rely on to know that what is this pattern of zeros and ones? Is it a number, a letter? Is it a sound, an image, a color, or the like? These are the types of data types that provide exactly those hints. What are the functions that come in the menu that is the CS50 library? We talked about standard I/O, and that's just one function so far, printf. In the CS50 library, you can see that it follows a pattern. The CS50 library exists largely for the first few weeks of the class to make our lives easier when you just want to get user input. So if you want to get a string, like a word or words from the human, you use getString. If you want to get an integer from the user, you're going to use getInt. When you want to get any of those other data types, for the most part, you use get_something else. And they're indeed all lowercase by convention. What about printf? If we have the ability now to store different types of data, and we have functions with which to get different types of data, how might you go about printing different types of data? Well, we've seen %s for string, %i for integer, %c for char, %f for a float or a double, those real numbers I described earlier, and then %li for a long integer. So here's the first example of like inconsistencies. In an ideal world, it would just be %l, and we'd move on. It's %li instead in this case. That's printf and some of its format codes. What more might we do? Well, in C, as we'll see, no pun intended, there's a whole bunch of operators. And indeed, computers, one of the first things they did was a lot of math and calculation. So there's a lot of operators like these. Computers, and in turn C, really good at addition, subtraction, multiplication, division, and even the % sign, which is the remainder operator. There's a special symbol in C and other languages just for getting the remainder when you divide one number by another. There are other features in the world of C, like variables, as we've seen. And there's also what is sort of playfully called syntactic sugar that makes it easier over time to write fewer characters but express your thoughts the same. So just as a single example of this, consider this use of a variable last week. Here in Scratch is how you might set a variable called counter to 0. In C, it's going to be similar. If you want the variable to be called counter, you literally write the word counter, or whatever you want it to be called. You then use the assignment operator, aka equal sign, and you assign it whatever its initial value should be here on the right. So again, the 0 is going to get copied from right to left into the variable because of that single equal sign. But this isn't sufficient in C. What else is missing on the right-hand side instinctively now, even if you've never programmed in this before? Yeah, in front. A semicolon at the end, and one other thing I think is probably missing. Again? A data type. So what would you, if we can keep going back and forth here, what data type seems appropriate intuitively for a counter? Int, for integer. So indeed, we need to tell the computer when creating a variable what type of data we want, and we need to finish our thought with the semicolon. So there might be a counterpart there. What about in Scratch if we wanted to increment that counter variable? We had this very user-friendly puzzle piece last time that was change counter by 1, or add 1 to counter. In C, here's where things get a little more interesting and pretty commonly done. You might do this. Counter equals counter plus 1 with a semicolon. And this is where, again, it's important to note the equal sign, it's not equality. Otherwise, this makes no sense. Counter cannot equal counter plus 1, right? Like, that just doesn't work if we're talking about integers here. That's because the equal sign is assignment. So it can certainly be the case that you calculate counter plus 1, whatever that is. Then you update the value of counter from right to left to be that new value. This, as we'll see, is a very common thing to do in programming, just to kind of count upward for whatever reason. You can write this more succinctly. This code here is what we'll call syntactic sugar, sort of a fancy way of saying the same thing with fewer words or fewer characters on the screen. This also adds 1, or whatever number you type over here, to the variable on the left. And there's one other form of syntactic sugar we're going to start seeing too, and it's even more terse than this. That too will increment counter by 1 by literally changing its value by 1, or if you change it to minus minus, subtracting 1 from it. You can't do that with 2 and 3 and 4, but you can do it by default with just plus plus or minus minus, adding or subtracting 1. Yeah? So when you are changing a variable that already has been created, as we did with the code that looked like this, you no longer need to remind the computer what the data type is. Thankfully, the computer's at least as smart as that. It will remember the type of the data that you intended. Other questions or comments on this? All right, that's quite a lot. Why don't we go ahead and here take a 10-minute break, and we'll be back. We'll start writing some code. All right. So we are back. We've just looked at some of the basics of compiling, even if it doesn't quite feel that basic. But now let's actually start focusing really on writing more and more code, more and more interesting code, kind of like we dove into Scratch last week. So here I have VS Code open. I've closed the GUI. I'm going to focus more on my terminal window and my code editors. Many different ways I can create new files, but I want to create something called a calculator. So again, within this environment of VS Code, I can literally write the code command, which is VS Code specific, and it just creates a new file for me automatically. Or I could do that in the GUI. I'm going to go ahead and create this file called calculator.c, and I'm going to go ahead and include some familiar things. So I'm just going to go ahead and proactively include CS50.h, Standard IO.h, I'm going to go ahead from memory and do the int void main. More on that next week, why it's int, why it's void, and so forth. And now let me just implement a very simple calculator. We saw like some mathematical operators like plus and the like, so let's actually use this. So let me go ahead and first give myself a variable called x, sort of like grade school math or algebra. Let me go ahead then and get an int, which is new, but I mentioned this exists. And then let me just ask the user for whatever their x value is. The thing in the quotes is just the English or the string that I'm printing on the screen, so I could say anything I want. I'm just going to say x colon to prompt the user accordingly. Now I'm going to go ahead and get another variable called y. I'm going to get int again, and now I'm going to prompt the user for y. And I'm just very nitpickily using a space just to like move the cursor so it doesn't look too messy on the screen. And then lastly, let me go ahead and just print out the sum of x and y. In an ideal world, I would just say something like printf x plus y. But that is not valid in C. The first argument, recall, in printf has to be a string in double quotes. So if I want to print out the value of an integer, I need to put something in quotes here, maybe followed by a new line if I want to move the cursor as well. So again, we only glimpsed it briefly, but what do I replace these question marks with if I want a placeholder for an integer? Yeah, so %i, right? Just like %s was string, %i is integer. So I change this to %i. And now if I want to add x and y, for instance, super simple calculator, doesn't do much of anything other than addition of two integers, I think this works. And again, it looks definitely cryptic at first glance. Like it would be nice if programming weren't this cryptic. Other languages will clean this up for us. But again, if you focus on the basics, printf takes one input first, which is a format string with English or whatever language, some placeholders maybe. Then it takes potentially more arguments after the comma, like the value of x plus y. All right, let me go ahead now and make calculator, which again compiles my source code in C, pictured above, and converts it into corresponding machine code or zeros and ones. No error messages, so that's already good. Now I do /calculator. Let's do 1 + 1 and enter. Voila. Now I have the makings of a calculator. Now let's start to tinker with this a little bit. What if I instead had done this? Int z gets x plus y, and then plug in z here. If I rerun make calculator, enter, rerun /calculator, type in 1 + 1, still equals 2, and let me claim that it will work for other values as well. Which of these versions is better designed? If both seem to be correct at very cursory glance, is this version better, or is the previous one without the z? OK, so this one's arguably better because I've now got a reusable variable called z that I can not only print, but heck, if my program's longer, I can use it elsewhere. Counter thoughts? Yeah, debatable like before because it depends on my intent. And honestly, I think a pretty good argument can be made for the first version because if I have no intention of, as you note, using that that variable again, you know what? Maybe I might as well do this just because it's one less thing to think about. It's one less distraction. It's one less line of code to have to understand. It's just a little tighter. So here again, I think it does depend on your intention, but this feels pretty reasonable. And I think, as someone noted earlier, when I did the same thing with getString, that, yeah, maybe kind of crossed a line because getString and the what's your name inside of it was just so much longer. But x plus y, it's not that hard to wrap our mind around what's going on inside of the printf argument. So again, these are the kinds of thoughts that hopefully you'll acquire the instinct for. Not necessarily reaching the same answer as someone else, but again, the thought process is what matters here. All right, so how might I enhance this program a little bit? Let's just talk about style for just a moment. So x and y, at least in this case, are pretty reasonable variable names. Why? Because like that's the go-to variable names in math when you're adding two things together. So x and y seem pretty reasonable. I could have done something like, well, maybe my first variable should be called first number, and my next variable should be called second number. And then down here, I would have to change this to first number plus second number. Like this isn't really adding anything semantically to help my comprehension, but that would be one other direction we could have taken things. So if you have very simple ideas that are conventionally expressed with common variable names like x and y, totally fine here. What if I want to annotate this program and remind myself what it is it does? Well, I can add in C what are called comments. with a slash slash, 2 forward slashes, you can write a note to yourself, like prompt user for X. And then down here, I could do something like prompt user for Y, just to remind myself what I'm doing there. And down here, perform addition. Now, in this case, not sure these comments are really adding all that much, because in the time it took me to write and eventually read these comments, I could have just read the 3 lines of code. But as our programs get more sophisticated and you start to learn more syntax that honestly you might forget the next day, the next week, the next month, might be useful to have these sort of notes to self that remind you of what your code is doing, or maybe even how it is doing that thing. With these early programs, not really necessary, doesn't really add all that much to our comprehension, but it is a mechanism you have in place that can help you actually remind yourself or remind someone else what it is that's going on. Well, let me go ahead and rerun this again in this current version, make calculator. And here too, you might think I'm typing crazy fast. Not really. I'm hitting tab a lot. So it turns out that Linux, the operating system we're using here in the cloud, but actually Windows and Mac OS nowadays support this too, supports autocomplete. So if you only have one program that starts with CAL, you don't have to finish writing calculator. You can just hit tab, and the computer will finish your thought for you. The other thing you can do is if you hit up and keep going up, you'll scroll through your entire history of commands. So there, too, I've been saving some keystrokes by hitting up quickly rather than retyping the same darn thing again and again. So again, just another little convenience to make programming and interacting with the command line interface even faster. All right, let me go ahead and just make sure it's compiled in the current form. The comments have no functional impact. These green things are just notes to self. Let me run calculator with maybe, how about this? Instead of 1 plus 1, how about 1 billion? Let's do that again. 1 million, 1 billion, and another 1 billion. And that answer is 2 billion. All right, so that seems correct. Let's run this program one more time. How about 2 billion plus another 2 billion? Did you know that? So apparently it's not so correct. And clearly running 1 plus 1 was not the most robust testing of my code here. What might have gone wrong? What might have gone wrong? Yeah. Yeah, the computer probably ran out of space with bits. So it turns out with these data types we've been talking about, string and int and also float and char and those other things, they all use a specific and most importantly finite number of bits to represent them. It can vary by computer. Newer computers use more bits. Older computers tended to use fewer bits. It's not necessarily standardized for all of these data types. But in this case, in this environment, it is using 32 bits for an integer. That's a lot. With 32 bits, you can count pretty high. This is 64 light bulbs on the stage and could count even higher. An int is only using half of these, or we have 2 integers here on the stage. Now, if you think back to last week, we talked about 8 bits at one point. And if you have 8 bits, 8 zeros and ones, you can count as high as 256. Just a good number to generally remember as trivia. 8 bits gives you 256 permutations of zeros and ones. 32 gives you roughly how many, if anyone knows? It's 2 to the 32 power. So it's roughly 4 billion, 2 to the 32. If you don't know that, it's fine. Most programmers, though, eventually remember these kinds of heuristics. So it's roughly 4 billion. So that feels like enough. 2 billion plus 2 billion is exactly 4 billion. And that actually should fit in a 32-bit integer. The catch is that my Mac, your PC, and the like also like to support negative numbers. And if you want to support both positive and negative numbers, that technically means with 32-bit integers, you can count as high as roughly 2 billion positive or 2 billion negative in the other direction. That's still 4 billion, give or take, but it's only half as many in one direction or the other. So how could I go about implementing a correct calculator here? What might the solution be? Yeah, so not just li, which was for long integer. I have to make one more change, which is to the data type itself. So let me go back up here and change x from an int to a long, aka long integer. And then let me change y as well. And then let me change the format code per the little cheat sheet we had up a few minutes ago to li. Let me recompile the calculator. Seems to work OK. Let's rerun it. Now let's do 1 plus 1. That should obviously be the same. Now let's do 2 billion and another 2 billion, and cross our fingers this time, Now we're counting as high as 4 billion. And we can go way higher than 4 billion, but we're only kicking the can down the street a bit. Even though we're now using, with a long 64 bits, which is as long as this stage now, that's still a finite value. It might be a really big value, but it's still finite. And we'll come back at the end of today to these kinds of fundamental limitations, because arguably now, my calculator is correct for like millions, billions of possible inputs, but not all. And that's problematic if you actually want to use my calculator for any possible inputs, not just ones that are roughly less than, say, 2 billion, as in this case. Are any questions then on that? But it's really just a precursor for all the problems that we're going to have to eventually deal with later on. A good question. Yes, if we were still using Z, we would also have to change it to a long. Otherwise, we'd be ignoring 32 of the bits that had been added together via the longs. Good question. All right, so how about we spice things up with maybe not just addition here. How about something with some conditions? Let's start to ask some actual questions. So a moment ago, recall that we had just the declaration of variables. Now let's look back at something in Scratch that looked a little something like this. A bunch of puzzle pieces asking questions by way of these conditionals, and then these Boolean expressions here in green, maybe saying something like x is less than y. In C, this actually maps pretty cleanly. It's much cleaner from left to right than it was with printf and join. Here we have just code that looks like this. If, a space, 2 parentheses, and then x less than y, and then we have something like printf there in the middle. So here it's actually kind of a nice mapping. Notice that just as the yellow puzzle piece in Scratch is kind of hugging the purple puzzle piece, that's effectively the role that these curly braces are playing. They're sort of encapsulating all of the code on the inside. The parentheses represent the Boolean expression that needs to be asked and answered to decide whether or not to do this thing. And here's an exception to what I alluded to earlier. Usually, when you see a word and then a parenthesis, something, and then close parenthesis, I claim that's usually a function. And I still feel pretty good about that claim. But there are exceptions. And the word if is not a function. It's just a programming construct. It's a feature of the C language that similarly uses parentheses just for different purposes, for a Boolean expression. How about something like this? Last week, if you wanted to have a two-way fork in the road, go this way or that way, you can have if and else. In C, that would look a little something like this. And if we add in the printfs, it now looks quite like the same, but it adds, of course, the word else and then a couple of more curly braces. As an aside, in C, it's not strictly necessary to have curly braces if you have only one line of code indented underneath. For best practice, though, do so anyway, because it makes super clear to you and ultimately anyone else reading your code that you intend for just that one or more line of code to execute. How about this from last week? Here was a three-way fork in the road. If x is less than y, else if x is greater than or equal to, greater than y, else if x equals y. Now here's where you have some disparities between Scratch and C. Scratch uses an equal sign for equality, to compare two values. C uses a single equal sign for assignment, from right to left, minor difference between the two worlds. In C, we could implement the same code like this, the addition being just this additional else if, and if we add in the printfs, it looks a little something now like this. This is correct, both in the Scratch world and in the C world, but could someone make a claim that this is not, again, well designed? Exactly. We don't need the last if. We need the else, at least, but we don't need the last if because, at least in the world of comparing integers, it's either going to be less than, greater than, or equal to. There is no other case, so you can save a few seconds, if you will, of your program running, a blink of the eye, by only asking two questions and then inferring what the answer to the third must be just by nature of your own human logic here. Now, why is that a good thing? If, for instance, x and y happen to equal each other, I type in 1 and 1 for both values, either in Scratch or in the C world. In the case of this version, you're sort of stupidly asking three questions, all of which are going to get asked, even though the answer is no, no, yes. That is true, false, false, true. That seems to be unnecessary because if we instead optimize this code, get rid of the unnecessary if, and just do as you proposed logically, else print that x is equal to y. Now, if x indeed equals y, because they're both 1 or some other value, Now you're only going to ask 2 questions, so 2/3 as many questions, and then you're going to get your same correct result. So again, a minor detail, but again, the kinds of things you should be thinking about, not only as you write your code to be correct, but also write it to be well designed as well. All right, so why don't we go ahead and translate this into the context of an actual program here. I'll create a blank window here, and let's do something with like points on my own very first CS50 problem set. Let me go ahead and run code of points.c. That's just going to give me a new text file. And then up here, I'm going to do my usual, include cs50.h, include standardio.h, int main void. So a lot of boilerplate, so to speak, in these early programs. And now let's ask the user how many points did they lose on their most recent CS50 p set, to sort of evoke my photograph of my own very first p set last week where I lost a couple of points myself. So int points equals getInt. Then I'll ask a question in English like, how many points did you lose? Question mark space. And then once I have this answer, let's now ask some questions of it. So if points is less than 2, borrowing the syntax that we saw on the screen a moment ago, let's go ahead and print out something explanatory like, you lost fewer points than me, \n. All right, else if points greater than 2, which is again how many I lost, I'm going to go ahead and print out, you lost more points than me, \n. Else if, wait a minute, else seems to be sufficient logically here. I'm just going to go ahead and print out something like, you lost the same number of points as me, \n. So really just a straightforward application of that simple idea, but to like a concrete scenario here. So let me go ahead and save this. Let me go ahead and run make points, enter. No errors, that's good. Run points, and then how many points did you lose? How about it's 1 point? All right, you lost fewer points than me. How about 0 points? Even better. How about 3 points? And so forth. So again, we have the ability to express in C now pretty basic idea from last week in reality, which is this notion of conditionals and asking questions. There's something subtle here, though, that's maybe not super well designed, that someone might call a magic number. This is sort of programming speak for something I've done here. There's a bit of redundancy, unrelated to the if and the else if and the else. But is there something I typed twice, just to ask perhaps for the obvious? Exactly. I've hard-coded, so to speak, manually typed out the number 2 in 2 locations in this case that did not come from the user. So this is apparently, once I compile this, this is it. You're always comparing yourself to me in like 1996, which for better or for worse is all the program can do. But this is an example, too, of a magic number in the sense like, wait, where did that 2 come from? And why is it in 2 places? It feels like we are setting the stage for just a higher probability of screwing up down the road. Because the longer this code gets, suppose I'm comparing against 2 points elsewhere. 2, 3, 4, 5 places. Am I going to keep typing the number 2? Like, yeah, that's fine. It's correct. It's going to work. But honestly, eventually you're going to screw up and you're going to miss one of the 2s. You're going to change it to a 3 because maybe I did worse the next year, or 1, I did better. And you don't want these numbers to get out of sync. So what would be like a logical improvement to this design rather than hard coding the same number sort of magically in 2 or more places? Yeah, why don't I make a variable that I can use in there? So for instance, I could create a variable like this, another integer called mine, and I'm just going to initialize it to 2. And then I'm going to change mentions of 2 to this. And mine is a pretty reasonable name for a variable insofar as it refers to exactly whose points are in question. There's a risk here, though. Minor though it is, I could accidentally change mine at some point. Maybe I forget what mine represents and I do some addition or subtraction. So there's a way to tell the computer, don't trust me because I'm going to screw up eventually, by making a variable constant too. So a constant in a programming language, this did not exist in Scratch, is just an additional hint to the computer that essentially enables you to program more defensively. If you don't trust yourself necessarily to not screw up later, or honestly in practice, if you know that number should never change, make it constant and never think about it again. This tells the compiler to make sure that even you, later in your code, cannot change the number 2. And another convention in C and other languages, when you have a constant, it's often common to just capitalize the variable. Kind of like you're yelling, but it really just visually makes it stand out. So it's kind of like a nice rule of thumb that helps you realize, oh, that must be a constant. Capitalization alone does not make it constant. The word const does, but the capitalization is just a visual reminder that this is somewhere, somehow, a constant. So just a minor refinement. But again, we're sort of getting better at programming just by sort of instilling these kinds of heuristics. Questions then on conditionals in C or these constants? Yeah? Yeah, why do you not use a semicolon on like lines 9, 13? No good, like just because. Like this is the way the language was designed, and it's confusing early on. Generally speaking, when you're using conditionals, and eventually we'll see loops, there's no semicolons involved. For now, assume that semicolons usually finish your thought after a function. That's not 100% reliable of a heuristic, but it'll get you most of the way there. And just because. Left hand was not talking to right hand when some of these languages were designed. All right, so let's do something else. How about this? If I have the ability to ask something conditionally, is this thing true or is this other thing? Could I write a very simple program that does something basic like tells me if a number the human types is even or odd? Well, let me just get the framework for that in place. Let me go ahead and write code of parity as a fancy way of saying even or odd. And let me go ahead and include CS50.h, include standard IO.h, int main void. Again, more on those down the road. But for now, I'm going to go ahead and get a number, n, from the user by calling getInt and asking them for whatever n is. And then now I'm going to introduce some pseudocode. So here's the first example of a program, honestly, that I'm not really sure how to proceed. So let me just resort to some pseudocode using comments. Eventually, I'll get rid of this and write actual code. But if n is even, then print. Actually, let me just print that. Let me just go ahead and say printf, quote unquote, even, because I know how to use printf. Else, all right, I know how to printf odd, so let me just say printf, quote unquote, odd. So here, I've sort of taken a bite out of the problem, if you will. And let me go ahead and put in my little placeholders. I want to do some kind of condition. So if question marks now, let me go ahead and fill in the blanks here. Else, I'll put this here. So I think I'm OK now. I'm getting closer to solving this, but I still have this question mark here. How, using syntax we've seen, might I determine if n is even or odd? What do you think? Nice. There's this little operator I mentioned by name earlier, the remainder operator, that will let you do exactly that. If you divide any number by 2, that mathematical heuristic is going to tell you if it's even or odd based on whether there's a remainder of 0 or 1. And that's nice because the alternative would seem to be doing something stupid like if n equals 0, or n equals if n equals 2, or n equals 4, right? Your code would be infinitely long if you had to ask all possible questions. But if I do n divided by 2 and look at the remainder, it's a little cryptic, but this will indeed do the trick. So the percent sign is the remainder operator. It does numerator divided by denominator and returns not the result of that, but rather the remainder of that. So if you divide anything by 2, it's going to be a 0 or 1 remainder. And if indeed 2 divides into n evenly, giving you 0, then you're going to print even, else it's got to be odd. But there is something odd, pun intended, in this highlighted line. What is another new piece of syntax, apparently, besides the percent sign? What's a little off there? Yeah. Yeah, so that's not a typo. And I even caught myself verbally saying it a moment ago just because it's so ingrained. What must this mean here? Yeah. Yeah, if something's equivalent to the other. So now this is the equality operator. It's not assignment from right to left. And this one, too, is an example of, like, literally humans not really planning ahead, perhaps. Left hand not talking to right hand, in that someone decided, let's use the equal sign for assignment. And then some number of minutes or days later, people are like, damn, how do we now compare for equality? Well, let's just use 2. And if you think this is a little weird, in some languages like JavaScript, there's a third version where you use 3 equal signs. So again, it's humans that design these languages. So if you're ever frustrated by them, confused by them, admittedly, it might just not have been the best design. But we just kind of have to live with it ever since. So let me go ahead and zoom out here. Let me go ahead and make parity here. So make parity, and again, parity is just the name of my file, parity.c. /parity, type in a number like 2. That's indeed even. 4, that's indeed even. 3, that's indeed odd, and so forth. If we continue testing, presumably we'll get the same kinds of answers. How about something else? Let me go ahead now, and let me start copying and pasting some of this code, because admittedly it's getting a little tedious to keep typing out all of that boilerplate at the top. Let me create a program called agree.c. That's reminiscent of like any of those forms you have to agree to online with a checkbox or typing in yes or no or the like. So let me throw away all the guts of this main program and now ask something like this. Let me go ahead and prompt user to agree to something. I'm going to go ahead and say, how about get string, do you agree, whatever the question might be. And I want the human to type y or no, y or n for yes or no respectively. So if it's only a single character, actually, I can actually get by with just get char. Not used it before, but it was on our menu of functions from the CS50 library. And if I want to get the user's response, the return value should be a char also on the left. So now we've seen strings, ints, and now chars if we only care about a single letter. And now let's go ahead, check whether user agreed. So how about if c equals quote unquote y, then let me go ahead and inside of my curly braces print out agreed or some such sentence like that. Else, if they did not type C, or you know what, let's be explicit here just so they can't type Z or B or some random letter. Else if C equals quote unquote n for no, then let me go ahead and print out not agreed or something like that. And I'm just going to ignore the user if they don't cooperate and they type Z or B or something that's not Y or N. All right, let me go ahead now and compile this code, make agree, /agree. All right, do I agree? Yes, let's go with the default. OK, so that seems to work. No, I don't agree this time. That seems to work. How about my caps lock key is on, or I'm just really yelling, capital Y, it ignores me. Capital N, it ignores me. So obviously a bug, at least if I want to tolerate uppercase and lowercase, which is kind of reasonable. So what would be the possible solutions here, do you think? How do I solve this and tolerate both capital and lowercase? Maybe what's the simplest, most naive implementation? Yeah, so why not just ask 2 questions? Or you know what, even more simplistic based only on what we've seen before. Let me, if you will, let me just kind of copy and paste some of this code, change this to an else, whoops, not in caps, else if, quote unquote, capital Y, and then I bet I could do the same thing with n. But here too, just like with Scratch, as soon as you start to find yourself copy pasting, you're probably doing something wrong. And what you said verbally, if I may, was actually better because you're implying that I could just say something like or C equals capital Y, or down here, C equals capital N. The catch is you can't use the word or in C. It's actually 2 vertical bars. So you can express one question or another. You only need one of the answers to be yes or true, and you use 2 vertical bars. By contrast, just so you've seen it, if you wanted to check if something is equal to something and something else, you could use 2 ampersands. This logically would make no sense here, though. Certainly, what the human typed can't both be lowercase and uppercase. That just makes no sense. So in this case, we do want or. But that allows me to tighten my code up. I don't have to start copying and pasting whole branches. I can now ask 2 questions at once. Questions, then, on this variation. Really good question. Can you convert the input to all lowercase? Absolutely, you could. We don't have the capability yet. It turns out that's going to require, to be easy, another library, though we could do it ourselves knowing a little bit about ASCII or Unicode from last week. But yes, that would be an alternative, but more on that a different time. Other questions? Good question. Unfortunately, you have to be explicit in C. You can't just say this, even though that's kind of how you might think about it. You have to ask a complete question using the equality sign twice in this case. Let me ask a question now, too. It's not a typo. I deliberately used single quotes around all of my single letters here. Why might that be? Previously, we used double quotes for anything that looked like text. Yeah. Correct. String is double quotes for multiple characters, or even one technically, but yes. And single quotes for for single characters. Because my data type is different, I chose the simple route of just using a single char. In fact, this program won't work with YES or NO. That's not supported at the moment. More on that another time. I had to use single quotes because that's how C does it. If you're dealing with single characters, aka chars, use single quotes. If it's a string, even if it's one single character in a string, as though you're starting to write out a longer word or sentence, that would be double quotes. And we'll see why this is before long, too. But again, just sort of things to keep in mind whenever writing code in this particular language. Yeah, down here. So short answer, if I'm understanding correctly, this would be incorrect. And this would be even more incorrect. But if you don't mind, let me kick the can a couple of weeks on this as to why this doesn't work. The most pleasant way to do this would indeed be to do something like this. But even this is a slippery slope, because what if the user does something weird, like they capitalize just the Y? You can imagine this getting messy quickly. I like your idea earlier about just forcing everything to lowercase, just to standardize things. Unfortunately, you cannot compare strings for equality like this, for, again, reasons we'll come to before long. So for today, we're keeping it simple, even though arguably it's not nearly as user-friendly to only tolerate individual letters. And there's a question over here. On a US English keyboard, it's Shift and then the / key above return. But depending on your keyboard, it will vary. All right, so let's actually now look back at something we did a little bit of last week. Let me go ahead and open a file called meow.c, because recall that's what we had Scratch do initially. Let me include not the CS50 library this time, but just standard io.h, because I only want printf for this demo. Let me go ahead now and just print out meow. And then if I want the cat to meow 3 times like it did last week, meow, meow, meow. Save it, make meow, /meow, voila. Program is written. Correct, I claim. It ran, it compiled OK. But again, this was the beginning of our conversation last week of not being particularly well designed. And if someone wants to maybe point out the now obvious, like, why is this not well designed necessarily? Yeah, it's just repetition, right? Again, I literally resorted to copy paste. Like, that should be the signal that you're probably doing something wrong, or at best, just lazy of you in this case. So the solution, as you might glean from last week, is probably going to be one of those things called loops. So let's just take a look at some of the syntax for loops in C. But again, no new ideas. It's just some new syntax that'll take some getting used to. In Scratch, if you wanted to meow forever with something like this, there's not a forever keyword in C, so this one's a little weird to look at, but this is the best we can do. It turns out there is a keyword called while in C, and that kind of has the right semantics, because it's like while, like do something again and again. That's the best I can do. But just like an if condition or an else if condition, those took a Boolean expression in parentheses. A while loop also takes a Boolean expression in parentheses. So I have to ask a question. Now, if I want to do something forever, I could kind of stupidly just say while 2 is greater than 1, while 3 is greater than 2, or just something completely arbitrary. But that should rub you the wrong way, because like why 2 versus 1, why 3, like just if you want true, just say true. So it turns out in C, there are special keywords, true and false, that are literally true and false respectively. I could also put the number 1 for true and the number 0 for false, but most people would just say true to be explicit. So it's a little hackish, if you will, but very conventional. There's no forever keyword in C. If I want to then print meow forever, I'm going to just use something like printf here. So again, not perfect translation from one to the other, but absolutely possible in C. What about this? This is a little more common if you want to do something a finite number of times, like repeat 3. There's a few different ways we can do this in C. Here's one I would approach. And here's where C, like a lot of text-based languages, you kind of have to whip out that toolkit of all of the basic building blocks and think about, all right, how can I build a little machine in software that does something some number of times? Well, let me give myself a variable called counter, set it equal to 0. Let me create a loop whose Boolean expression is counter less than 3. The idea being here, why don't I just kind of count 1, 2, 3? So how do I implement this physicality in code? I give myself a variable, set it to 0, 0 fingers up. Now I ask the question, is counter less than 3? If so, go ahead and print out meow. And just intuitively, even if you've never seen C code or any code before Scratch, what more do I need to do? I've left room here for one more line of logic. Yeah? We have to increase counter. So I need code like I showed earlier, like counter equals counter plus 1. And so here's where like programming sometimes becomes a bit more like plumbing. Like you can't just say what you mean like you could in Scratch. You have to build a little sort of software machine that initializes a value, does something, increments it, checks it. And so it's kind of like this software-based machine, but together that's just using some familiar building blocks. But this is pretty common. Just like in Scratch, you might have used loops a bunch of times. Pretty common in C. So can we tighten this code up? This is correct, but here's some conventions that are popular. If you're going to count, just say I. A convention in programming with at least languages like C is just use I as an integer if all its purpose is to count from like 0 on up. Counter is not wrong. It's not bad. It's just it's more verbose than you need to be. Just call it I. You don't need more semantics than that. All right, what else can I do here? There's another opportunity to tighten up this code. Do you recall? Yeah. Yeah, that syntactic sugar that does nothing new, but it does it more succinctly. I can change this to either the intermediate format or the even tighter format of just I++. Now, this is pretty canonical. Like, this is how many people, most people, would implement something 3 times using a loop in C. Using a while loop, that is. Turns out that it's so common in C and other languages to do something finitely many times. There's a couple of ways to do it. In this model, to be clear, the logic, though, is that we start by initializing the variable, like I've highlighted here. We then ask the question, is I less than 0? If so, everything that's indented inside the curly braces gets executed, namely meow, then the update. Then the computer is going to have to recheck the condition to make sure that I hasn't gotten so big that it's greater than 3. But if not, it then does this again, and it does this again. And then it repeats, constantly checking the condition and executing what's in the block. Checking the condition and executing what's in the block. After 3 times of that, the condition is going to be false or a no answer. And that's it for the code. It just proceeds to whatever's down here, just like with Scratch. It jumps to the next blocks down below. All right, what's another way, though, to do this? Well, I've deliberately been counting from 0, and that's a programming convention, right? We started last week with all the light bulbs off, which was 0. So it's pretty reasonable to start counting at zeros, just like you would here, like no fingers are up. This is 0 fingers on your hand. But if you prefer, you could start counting at I equals 1. But then you don't want to do it while I is less than 3. You want to do I is less than or equal to 3. On most keyboards, there's no symbol for less than or equal to or greater than or equal to. So in C, you use 2 characters, less than and then an equal sign with no spaces in between. That just means less than or equal to. We could change it to set I to 2 and make this condition be less than or equal to 4. We could make this be 10 and less than or equal to 12. But again, just stick with the basics. Start at 0 and count on up would be the convention. Or if you prefer to count down, that's fine too. Set I to 3, and then do this so long as I is greater than 0, but you have to decrement instead of increment. So again, we could do this all day long. There's like literally an infinite number of ways to implement this idea, and that's why I keep emphasizing convention. Call the variable I for something like this, initialize it to 0 for something like this, and just generally count up unless you really prefer to count down. Again, just certain human conventions. All right. How about another way to do this? This is what's called a for loop in C. Also very common. It's not quite as straightforward in that it doesn't really read top to bottom in exactly the same way. This kind of has a lot more logic tucked into its first line, but it does exactly the same thing. What happens here is, notice that inside the parentheses next to the word for, there's 2 semicolons, which is another weird use of syntax. They're not at the end of the line. Now they're in the middle of the parentheses, but that's what the humans chose years ago. The first thing, before the semicolons, initializes your variable. Int I equals 0. The next thing is the condition that's going to constantly get checked every cycle through this loop. And the last thing is going to be what you do after each loop, which in this case is going to be count up. So again, if I rewind, we initialize I to 0. We then ask the question, is I less than 3? If so, execute what's inside of the loop. Then the computer does this. It does the update, incrementing I by 1. And then it's not going to blindly meow again. It's going to check again the condition, is I less than 3? Then it's going to meow if so. Then it might go ahead and increment I and check the condition again. So again, this does not read quite in the same simple fashion top to bottom. You kind of read it left to right and then jump around. But again, the initialization, the constant Boolean expression being checked, and the update after each time does the exact same thing as what we saw a moment ago in this while loop format. Which one is better? They're the same. I think most people would probably eventually use a for loop once comfortable, but just because is really the answer there. All right, any questions then on loops as we've translated them to C? Yeah? For loop and while loop can both be used to do exactly the same thing. There are subtle differences with issues of scope, which we'll discuss before long, where when you create a variable in a for loop, notice that it was, again, inside of those parentheses, which technically means it's only going to exist in these 4 lines of code. By contrast, with the while loop, I declared my variable outside of the loop. That variable is going to continue to exist elsewhere in my program. So that's one of the minor differences there. Good question. But you'll see some others over time. All right, so we claim then that it's better in some form to do this with loops. So let's actually jump back to the code. Let me go ahead and now re-implement meowing with a for loop, for instance. So how about for int I gets 0, I less than 3, I less than 3, I plus plus. Then inside my curly braces, let me go ahead and print out with printf, meow with a new line and a semicolon. So I did it pretty quickly just because I've long acquired the muscle memory. But if I now make meow, no errors there, run /meow, and I see meow, meow, meow. Well, let's do now what we did last week, which was to begin to make our own custom functions, if you will, by using our own in C. So here's where the syntax gets a little funky, but we'll explain over time what each of these keywords is doing. If I want to create a function called meow, because the authors of C did not create a function called meow decades ago, I need to give it a name, like meow. I need to specify if it takes any inputs. For now, I'm going to say no. And I'm going to explicitly say no by writing this special word void. It's also necessary when implementing a function in C, which was not necessary in Scratch, to specify what its return type is. But for now, I'm just going to say that meow is the name of the function. It takes no inputs, and that's what the void in parentheses means. And it does not return anything like ask did, or like getString, or getInt does. Meow's purpose in life is just to have side effects, visual side effects by printing something on the screen. So what is meow going to do? I'm going to have it quite simply say printf, quote unquote, meow, \n. And now, just like in Scratch, I can now just call a brand new function called meow. And here's where, too, if you really don't like the curly braces, technically speaking, you can get rid of them when there's only one line of code inside your loop. But again, stylistically, I would encourage you to preserve them to make super clear to yourself and others what it is that's going on. Let me go ahead and save this and do make meow. Whoops. Darn. All right, what did I do? Something stupid. Yeah, so 0 does not belong there. I meant to hit parenthesis. So let me rerun make meow. OK, fixed. My mistake. All right, it's still working OK. But recall what I did in Scratch, kind of out of sight, out of mind. And just to make a point, let me just kind of highlight this and move it way down in the file. Because again, like now that meow exists, it's an abstraction. I just know a meow function exists. I want to be able to use it. So let me scroll back up. My main function is the same. Let me go ahead and make meow again. And now, just by moving that function, I've created all these lines of errors. And let's look at the first. Again, the rule of thumb here, it's a little small, but it says meow.c in bold, which is the name of the file where the bug is. 5 is the line number, and 20 is the character. So line number is enough alone. Let's see. Oh, this is what happens when I scrolled up too far. Sorry, this is the error we're now looking at. Line 7. I was looking at the old error message from earlier before I fixed the 0. Meow C, line 7. All right. Apparently, C does not know what the meow function is. Implicit declaration of function meow is invalid in C99. Well, what does that mean? Declaration of function means your creation of a function. Like I'm declaring that meow exists, but I haven't apparently defined it yet. And then C99 is the version of C from the year 1999, which we generally use here. It's one of the more recent versions. So why is that the case? Can you infer from the mere fact that I just moved meow to the bottom of the file, which was fine in Scratch, but now is bad? Why is that? Yeah, C is just kind of old school. It reads your code top to bottom, and if it does not know what meow is when you first try to use it, it just freaks out and prints out these error messages. So the solution is quite simply, don't do that. Just leave it where it was. But you could imagine this getting a little annoying over time, if only because main is by name the main part of your program. And honestly, it would just be nice, honestly, if main were always at the top of your code. Because if you want to understand what a file is doing, it makes sense to just read it top to bottom. Well, there is a solution to this. You can put functions in different orders with main at the top, so long as you, and this is perhaps the only time copy-paste is appropriate, so long as you leave a little breadcrumb for the compiler at the very top of your file that literally repeats the return value, the name, and the arguments to that function, semicolon. This is, so to speak, declaring your function. And the real fancy way is this is a prototype. It's like, what is this thing going to look like? But the semicolon means I'm not going to deal with this yet. I'm going to actually define the function or implement it down below here. This is kind of a stupid detail. More recent languages get rid of this need. You can put your functions in any order. But again, if you just think about the basics of programming languages like this one here, and as you noted, it must just be reading your code top to bottom. So annoying, yes, but explained, yes, too. So let me go ahead and make meow once more time. /meow, still working OK. And let me make one final enhancement to this meow program here. Let me go ahead now and say something like this. Let me go ahead and say, all right, wouldn't it be nice if my meow function could do something for me some number of times? So suppose I want to do this. This meow function at the moment is going to meow 3 times. But suppose I want to meow n times, where n is just some number provided by the user. Well, just like in Scratch, custom functions can take inputs. I just presently am saying void. But if I change this to int n, thereby telling the compiler, hey, meow still doesn't return something, but it does take something as input. It takes an integer, and I want to call it n. So this is another way of declaring a variable, but a way of declaring a variable that gets handed into as input the function. So now if I tighten up main here, now I can actually do something really cool, just like in Scratch, which is this. If I now look at this code, let me zoom in here. Now my main program is really well written in the sense that it just says what it does, meow 3 times. This works, though, because I define meow is now taking an input, an integer called n, and then using n in my now familiar for loop. There's one change. You might have caught my one mistake. I also have to remind myself up here to make that change too. Again, this is one of the only redundancies or copy-paste that's sort of reasonable. But there I have now a better version. So let me go ahead and rerun this. Make meow, /meow, voila. So again, no change in correctness. But now, again, we're sort of modularizing our code. And heck, what you could do now, and this is just a tease of a feature down the road, those header files we talked about early, those libraries, this is the kind of modularization we're talking about. We, the staff, wrote a function called getString, getInt, and so forth. We put it in a file called CS50.c, and we put little breadcrumbs, specifically these things called prototypes, in CS50.h. So that when you all, as aspiring programmers, include CS50.h, you are sort of secretly telling the compiler at the very top of your code what the menu of available functions is. Why? Because in CS50.h is lines like these. Obviously not for meow, but for getString, getInt, and so forth. And in standardIO.h is the same lines of code for things like printf. So that's all that's going on there. It's just a way of telling the computer in advance what functions to expect. Are any questions then on these here? Correct. So if you don't mind, I want to continue to wave my hand at that detail for today. Indeed, int main void is a little weird because, like, what would the input to main be? We have no mechanism for providing input yet. And what does it mean for main to return anything? Like, who is it returning to? For another day, if we may. They're going to come into play, but that for now today is just something you should take at face value as necessary copy-paste to begin programs. So meow is a function that takes an input, the number of times to meow, but it didn't actually have a return value, hence the void. But what if we actually want to create our own function that not only takes 0 or more inputs as arguments, but also returns some value, maybe an int, maybe a float, maybe something else altogether? Well, it turns out in C, we can do that as well. Let me go ahead and create a new file here called discount. And let's implement a quick program via which we can discount some regular price by some percentage, as though there's a sale going on in a store. Let me go ahead and include our usual CS50.h, followed by standard IO at the top. Let me give myself int main void, as before. And inside of main, let's go ahead and do something simple. Let's give ourselves a float called regular, representing like the regular price of something in a store. Let's go ahead and get a float from the user, asking them what that regular price is. Then next, let's go ahead and declare a second variable, also a float, called sale, ultimately representing the sale price after some percentage discount off. And let's go ahead and simply calculate whatever regular is and say 15% off is a pretty good discount. So let's go ahead and discount regular, whatever it is, by 15%, which is equivalent, of course, to multiplying it with the asterisk by 0.85. Of course, if we're taking off 15%, we multiply the regular price by 0.85. Now let's go ahead and print out the results here. Let me go ahead and say printf, sale price, colon. Let me go ahead and use %f, but more specifically %.2f, because at least in US currency, we typically show cents to 2 decimal places, followed by a new line. And then let me go ahead and plug in the value of sale. All right, let's go down here and do make discount. Enter. So far, so good. /discount, and the regular price is maybe $100, so the sale price should be $85. So our arithmetic seems to be correct here. But let's fast forward now in time. Suppose that we find ourselves discounting a lot of prices in an application, maybe a website like Amazon where they're offering some kind of percentage discount. And it'd be nice to have a reusable function that just does this arithmetic for us, simple though it may be. So let's go ahead and modify discount this time to give ourselves our own function called discount, for instance, that takes an input, like the regular price that you want to discount, and then it also returns a value. It doesn't just print it out. It returns a value, namely a float that represents what the sale price is. So let me go down below main and go ahead and define a function that's going to return a float, because we're dealing with dollar amount still. The function is going to be called discount, and it's going to take one input, like the price that we want to discount. In here, I'm going to do something very simple. I'm going to say float sale equals whatever that price is times 0.85. And then I'm going to go ahead and return sale. Now, for that matter, I can actually tighten this up a bit. If I'm only declaring a variable to store a value that I'm then returning with this keyword return, I actually don't even need that variable. So I can delete this second line. And I can actually just go ahead and get rid of that variable altogether and immediately return whatever the arithmetic result is of taking the price input, the argument that's being passed in, times 0.85. So very simple function that simply does the discounting for me. As always, let me go ahead and copy paste, almost the only time it's OK to copy paste, the prototype of that function to the top of the file so that when compiling this code, main has already seen the word discount before. And now let me go into the code here. And instead of doing the math myself in main, let me presume that we have some function already in our toolkit called discount that lets me discount the regular price and return that value. And then down here, my code doesn't need to change. I'm still going to print out sale, the variable in which I'm storing that result. But notice what I've done here. I've sort of abstracted away the notion of taking a discount by creating my own function that takes a float called price or anything else as input. It does a little bit of math, simple though it is here, and then it returns a value. But notice that discount is not printing that value. It's literally using this other keyword called return so that I can hand back that value just like getString hands back a value, just like getInt hands back an integer without printing it for you, so that I, up here on line 9, can go ahead and store that value in a variable if I want, and then actually print it out. Let me go ahead now and recompile this code with make discount. Let me go ahead and do /discount. And let's, again, do $100. Sale price is going to be $85 as well. Now, it turns out that functions don't have to take just 0 or 1 argument as input. They can actually take 2 or 3 or more. So in fact, suppose we wanted to now enhance this version of my program and take in as input to the discount function, not just the price that I want to discount, but also the percentage off, thereby allowing us to support not just 15% off, but any number of percentage points off. Well, let me go up here and declare an int, say, and call it percent off. And let me ask the user for how many percentage points they want to take off. So I'm going to say percent off inside of the prompt here, get that int called percent off. And now, in addition to passing in regular as an input to the discount function, I'm also going to pass in percent off. But I need to tell the computer that it is taking now 2 arguments. And the way I do this is just with a comma down here in the function's own definition. Here is going to be a percentage argument, a second argument per the comma. And I'm now going to use that percentage in a slightly familiar way. I don't want to just do percentage like this, because, of course, that's going to increase the size of the total price. I actually need to do a little bit of real world math where if this is a percentage off, like the number 15 for 15 percentage points, I need to do like 100 minus that many percentage points, thereby giving me 100 minus 15, 85. And then I need to divide that by 100 in order now to give myself 0.85 times the price that was passed in. But if I go ahead now and save this, run, make discount one last time, I notice that I've actually got an error here. What have I done wrong? Well, I need to change that prototype too. And again, this is admittedly an annoying aspect of C that you have to maintain consistency here, but that's fine. I'm just going to go up here, change this to int percentage, spelling int correctly. And now let me retry compilation, make discount, crossing my fingers this time, worked OK, /discount, and voila, $100 and percent off, say 15 points, and voila, $85. Now, it's worth noting that I've deliberately returned the results of my math from this function. I haven't just done the math on the original variable that's being passed in. In fact, if we take a look at this second version, where discount is now taking a price argument and a percentage argument, notice that I'm not doing something like this. I'm not just saying price equals price times 100 minus percentage divided by 100 and leaving it at that. The problem there is that this variable price is going to be scoped to that discount function. And we'll encounter this again before long, but this notion of scope just refers to where in which a variable actually lives or exists or is accessible. So it turns out if I change price in the context of this discount function, that's not going to have a lasting effect. If I actually want to get the result back to the function that used the discount function, namely main, I actually do need to take this approach of actually returning the value explicitly so that ultimately I'm handing back the discounted price. All right, well, let's go ahead and how about let's just use these primitives in just a few different ways. How about a little game of yesteryear, Super Mario Brothers. And in the original Super Mario Brothers, and in bunches of variants in, so you have like these side-scrolling worlds that look like this, where there's some coins in the sky hidden behind these question marks. So let's just use this as a visual to consider how, in C, could I start to make something semi-graphical? Like not actual colors or fanciness. That feels like too much too soon. Just something like printing out some question marks. Well, if I go back over here, let me create that actual file that I alluded to earlier. So let me code up mario.c. Let me go ahead and include standard.io.h, int main void, again, which we'll continue to copy paste for today. And then let me just go ahead and do something simple like 1, 2, 3, 4, and a new line. All right, this is what we might call ASCII art, which just means graphics, but really just implemented with your keyboard. And if I make Mario and do /Mario, it's not nearly as engaging visually as this, but it's the beginning of this kind of map for a game. Well, if I wanted to now print out of those things dynamically, let me go back to my code here. And instead of printing out 4 all at once, I could do something like for int I get 0, I less than 4, I plus plus. And then inside here, I could just print out one of them at a time. Let me save that, make Mario, and at the risk of disappointing, so close, but I made a mistake. Just stupid aesthetic. The prompt is not on the new line. How could I move it? Yeah, I need an escape character, the \n, but should I put it here? OK, no, because that's going to put it after everyone, and it's going to make this thing vertical instead of horizontal. So logically, just like in Scratch, put it at the end of the loop. So something out here, and just print out, for instance, only quote-unquote new line. And now if I do make Mario again, /Mario, OK, we're back in business. But a little better designed in that now I'm not repeating myself multiple times. I'm doing this again and again. But let's do one other thing here with Mario. Let me go ahead and ask the user how many question marks or coins to print. The catch here is that there's another type of loop that's helpful for this, and it's called a do-while loop generally. A do-while loop is similar to a while loop, but it checks the condition last instead of first. Recall earlier on the slide, we had while, open parenthesis, close parenthesis, and I kept claiming that we checked whether I is less than whatever it was, 3 in advance, again and again. A do-while loop just inverts the logic so that you can actually do something like this. At the top of this program, I'm going to go ahead now and give myself a variable n, like this, of type integer, and then I'm going to do literally the following with the keyword do. N equals get int, and I'm going to ask the user for the width, like the number of $signs to print. And I'm going to do this while n is less than, say, 1. So this is a little cryptic, but the salient differences are the Boolean expression is now at the bottom of my block of code, not at the top. Now, why is this? Well, the difference here, if I make Mario, is, I need to add CS50.h because I'm now using getInt. If I now compile this version of Mario and do /Mario, a do-while loop is helpful when you want to do something no matter what first and then check some condition or some Boolean expression to see if maybe, in this case, the user cooperated. It would make no sense if the user typed in, say, 0, because like there's no work to be done. It'd be really weird if they said -100, because that makes no sense logically. So with this simple construct here, I am doing the following while n is less than 1. The implication is that as soon as n equals 1 or is bigger than 1, I'm going to break out of this loop, and I've got myself a variable called n containing essentially a positive value, 1 through 2 billion or so. And I can now use this, for instance, here. Change the 4 to an n, so now my program is completely dynamic. Let me go ahead and do make Mario, /Mario again, and I'll do 4. Still works. I'll do 40. Still works. And the difference here with the do-while is if something like this involves getting user input, well, there's no question to ask. Like, the user hasn't given you anything yet, so you have to do something first, then check and break out of the loop if the human has, for instance, cooperated in this case. Now, all right, well, why don't we escalate to something more like this in the same game, where your underground is Mario, and this is like a 2-dimensional wall that's popping up here. It looks like a 3x3, for instance, for the sake of discussion. And it's like made of bricks, so I'll use maybe hash symbols this time. Well, it turns out that we can nest, that is, combine some of these same ideas as follows. Let me go ahead now and change back to this code. And I'm going to keep the do-while loop from before. And I'm going to ask, though, this question, what's the size of this square? I'm going to assume it's like n by n. So 3 by 3, 4 by 4, whatever. So I'm just going to ask for the size of this square of bricks. And now, how do I do this? Well, I'm going to go ahead, for instance, and print out, how about for int I gets 0, I less than n, I plus plus. Let me just keep it simple and print out something like this. Just a single hash symbol, that is a brick, and a new line after it. All right, let's make Mario, run Mario of 3. OK, that's close to being it. I've got a column. All right, but I need it to be wider. So the solution last time was to get rid of the new line and then maybe put the new line here, out after the loop. All right, so let's do make Mario, /Mario, and type in 3, and All right, so I kind of need to combine these two ideas somehow. So how might we solve this problem? I want to print like rows and columns, not row or column. How do I do this? Yeah, add another loop in the for loop, right? If you use one loop conceptually to kind of count the rows from top to bottom, and then within each row, you then sort of typewriter style, old school typewriter, do like character, 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 character horizontally, I think we could do exactly what we want to achieve here. So how about this? Let me get rid of this line and get rid of this line for now. And let me just give myself another loop on the inside. And since I'm already using I, another reasonable convention here would be to say something like j. So j also gets 0. J is less than n. J plus plus. And now, what's going to happen? Let me go ahead and print out just one of these things at a time. And let me save and write. Let me run this. Let me see how close we are. Make Mario 3. OK, 3. That's clearly wrong, but I see 9 things there on the screen. So we're close. What's the one fix I need now to sort of move the old school typewriter head down to the next row when appropriate? What do you think? Yeah, I need one of these \n's, and probably, let me add some comments now to help everyone visualize what I've done. For each row, for each column, how about print a brick, just to kind of explain the logic. And so I add that because now, move to next row, I could do something like this with a \n. So here is where the comments, really my pseudocode, actually kind of illuminates the situation a bit. Let me go ahead and recompile Mario, /Mario 3. Now we're talking. It's not a perfect square just because these hash symbols are a little taller than they are wide, but that's just a font detail here. Now I've done something that's quite more akin to something like this. All right, so let me pause here and see if there are any questions. Again, the code's getting a little more complicated, but we're just building like more complicated programs like in Scratch with like familiar puzzle pieces, some variables, some loops, some conditionals. It's all the same as before. Yeah. Can you multiply strings in C? No. But ask that same question again in a few weeks when we get to Python, and the answer will be yes. Other questions? Yeah. In C, you must specify the return type, the name of the function, and the inputs or arguments to the function in that order. And if none of them are applicable, you write the word void. So same question as earlier. Let me kick that can a week or so, and we'll come back to that, and we'll see why. But for now, just take on faith that you need to do that with main, because main is a little special, similar to the when green flag is clicked. It, too, was a little special as well. Yeah? Yes, if you want to get out of a loop early, you could do this. So let me answer this question this way. An alternative to a do-while loop would be to do something like this. How about while true? So do the following forever. Let me go ahead and get an int from the user for the size of this thing. If n is greater than 0, that is a positive integer, then go ahead and use a new keyword called break. This is identical to what we just did. It's just a little longer. It's like a couple extra lines. A lot of them are blank. And so it's just an alternative. But a do while does the same thing, but a little tighter, if that's an answer to your question. All right, so let's now introduce, finally, a sequence of problems that I've kind of been brushing under the rug, though we did see a little bit of evidence of this earlier when we tried to add 2 billion and 2 billion, and it overflowed the number of bits in an int, so to speak. Let me go ahead and code up a program called calculator again, but I'm going to go ahead now and change us to floats. So I'm going to change x to a float, and I'm going to use getFloat. And a float, again, is just a floating point value, which is a fancy way of saying a real number with a decimal point in it. And down here, I'm going to go ahead and use %f for float. And I'm going to go ahead now and do one more thing. Instead of addition, I want to do something fancier like division. So divide x by y. And I'm going to give myself another third float called z, as we did at the beginning of today. And I'm going to print out z instead of x and y explicitly. So I'm going to go ahead now and do make calculator, /calculator, and let's do something like, 2/3. 2 divided by 3 is 0.66667. So that's what you would rather expect. Let me run it again. 1/10. All right, so 0.1 and a bunch of zeros. That, too, is what you would rather expect. But now let me get a little curious. It turns out that in C, you can modify the behavior of these format codes a little bit. By default, you get like 6 or so digits. Suppose that you want to get exactly 2 digits. You can more succinctly say 0.2 before the f and after the %. And this is the kind of thing that's hard to remember, but you Google it and you find that, OK, format code for floats uses 0.2 to do 2 decimal points. So let me do make calculator again. /calculator, how about 2/3, 0.67. So it handles the display of significant digits for us here. And now let me go ahead and do 1/10 and 0.10. So it's adhering to that. Well, maybe I really want a lot of precision, right? I've got a really powerful computer. Let me see 50 numbers after the decimal point. That's a lot of significant digits. Let me remake the calculator. Whoops, typo. Let me remake the calculator. Not Mario, calculator. And how about 2/3 again? Well, that's interesting. Pretty sure it's supposed to be like a 0.6 with like a line over it, right, in grade school math. All right, well, maybe that's just a bug. How about 1/10? OK, that's really getting funky. So what's going on? It seems that my program can not only not do addition very well, we eventually hit problems in the billions, we can't even do very precise numbers here. What's going on? Exactly. In a nutshell, the computer is approximating the answer using that many numbers after the decimal point. But the problem fundamentally is actually very similar to that integer overflow from before. And I'm using that now as a term of art. Integers can overflow if you're trying to use more bits than you actually have available to you. You sort of change them all to ones, and then you're out of bits, so to speak. Same thing here, but in a different context of floats. If you only have 32 bits, or heck, if we change to double and only have 64 bits, that's a lot of precision, but it's not infinite. And yet, pretty sure there's an infinite number of real numbers in the world, which is to say a computer with finite memory cannot possibly represent all possible numbers in the world because, again, there's not an infinite number of permutations of 32 or 64 bits. It might be a lot in the billions or more, but it's still finite. And so, indeed, this is the computer's closest approximation to what's actually going on there. And so this is an example of what we would actually generally call floating point imprecision. Floating point imprecision refers to the inability for computers fundamentally to represent all possible real numbers 100% precisely, at least by default in languages like C. Thankfully, in the world of scientific computing and so forth, there are solutions to this problem that just give you more digits, but the problem fundamentally is still going to be there. So there's a reason I changed x and y to floats. Let's see what would happen if we rewound a bit, and instead of using floats for x and y, again use, say, integers. So int x and int y, and let's go far back and use getInt as well, thereby giving us integers x and y. Let's still leave z as a float, because at the end of the day, we want to be able to handle fractions or floating point values. But let's go ahead now and print out this value of z, having changed x and y now to ints. Make calculator, / calculator, and let's do, say, 2 for the numerator, 3 for the denominator, and voila, it's not 0.666, and it's not even rounding oddly. It's just all zeros this time. So why is that? Well, it turns out that C, when dividing an integer by an integer, is always going to give you back an integer, an int. The problem is that floating point values don't fit in ints. Only the integral part to the left of the decimal point does. Everything at and beyond the decimal point itself gets thrown away, known as a feature in C called truncation. When dividing an integer by an integer, you get back an integer. But if you're trying to then store what's actually a floating point result in that integer, C is just going to throw away everything at and beyond the decimal point, leaving us with this case in just the 0 from what should have been 0.666666, and so forth. So let's see one more example, in fact. Let me go back to my terminal here. Let me do / calculator again, and let's do 4/3. This time it should be 1.33333, and so forth. But let's see. 4 divided by 3, both as integers, this time gives us 1.0000, but there too. The answer should be 1.333, but the floating point part is getting truncated or thrown away, leaving us with just 1. So how do we solve this? Well, certainly, we could just use floats from the get-go as I did. But if by nature of your program you only have access to integers or maybe even longs, for which the same problem would occur, what we can actually do is called type conversion. And we can explicitly tell the computer that we actually want to treat this int as though it's a floating point value. And we can do that for both x and y. So let me go back to my code here. And I have a couple of options, in fact. I can convert y to a float by doing this. I can cast y to a float by literally writing the type float inside of parentheses right before the y. And if I really want to be explicit, I can also do the same to x. But strictly speaking, it suffices to just change one or the other, not necessarily both. Let me go ahead now and do make calculator again, / calculator, and let's try 2 divided by 3. And now we're back to an answer that's closer to correct, but indeed we're still having some rounding issues there. Let's run it one more time for 4 divided by 3. There too, we're closer to the right answer at least, but we still have that floating point imprecision, but that's going to be another problem altogether to solve. And here in a little more detail is that issue of integer overflow, which is in the context of ints. Suppose that we think back last week when we had 3 bits, and we counted from like 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7. I think I asked the question, how would we count to 8? Someone proposed, well, we need a 4th bit. That's fine if you have a 4th bit, if you have access to another light bulb or transistor. If you don't, though, the next number after this is technically 1, 0, 0, 0. But if you don't have space for or hardware for that 4th bit, you might as well just be representing the number 0. So in the world of integers, if you're only using 3 bits, those 3 bits eventually overflow when you count past 7, because what should be 8 can't fit, so to speak, so it rolls back over to 0. And as arcane as this problem might seem, we humans have done this a couple of times. You might recall knowing about or reading about the Y2K problem, where a lot of people thought the world was going to end. Why? Because on January 1st of 2000, a lot of computers, presumably, were going to update their clocks from 1999 to the year 2000. The problem is, though, for decades, for efficiency, we humans were honestly in the habit of not storing years as 4 digits. Why? Because that's just a lot of space to waste, especially since like centuries don't happen that often. So a lot of computer systems, especially early on, when hardware was very expensive and memory was very tight, just stored the last 2 digits of any year. Problem, of course, on January 1st of 2000 is that 99 rolls over to 100, but if you don't have room for another digit, it's just 0, 0. And if your code assumes a prefix of 19, well, we just went from the year 1999 back to the year 1900. Thankfully, long story short, a lot of people wrote a lot of code in a lot of old languages and mostly warded off this problem, so the world did not end. The next time the world might end, though, is on January 19th, 2038. Now, that might feel like a long time away, but so did the year 2000 at one point. Why might clocks again break in today's modern computers in 2038, might you think? Indeed. So this refers to some number of seconds. So it turns out that the way computers generally keep track of time is they count the total number of seconds since the epoch, which is defined as January 1st, 1970. Why? It was just a good year to sort of start counting at when computers really came onto the scene. Unfortunately, most computers use 32 bits to count the number of seconds since January 1st, 1970, the implication of which is we can only count up to roughly 2 billion seconds. 2 billion seconds is going to happen in 2038, at which point 31 ones are going to roll over as follows. That number 2 billion, which is the max, because if you're representing positive and negative numbers, recall that you can only count as high as positive 2 billion or negative 2 billion, looks like this. This is roughly the number 2 billion in binary. It's all ones with 1 0 way over here. If I count 1 second past that 2 billion number, give or take, that means like, all right, I add 1, I carry the 1. It's just like 9s becoming 0s in decimal. If I keep this sort of simple animation, and I keep carrying the 1, carrying the 1, carrying the 1, 1 second after 2 billion seconds, give or take, I have this number in the computer's memory. So there's still 1 bit, that's a 1, all the way to the left. Unfortunately, that bit often represents negativity, whereby if that first bit is negative, that represents that the rest of this somehow represents a negative number. It's not negative 0. There's a fancier representation. But a very big positive number very suddenly becomes a very big negative number, and that number is roughly negative 2 billion. That means computers in 2038 on that date are going to accidentally think that it's been negative 2 billion seconds since January 1st, 1970, which is going to make computers potentially think it's 1901. So what is the solution to the 2038 problem, perhaps? Y2K was because we were using 2 digits for years. What about 2038? More bits. And thankfully, we're getting a little better at lessons learned here, and computers now are increasingly using 64 bits, and all of us will be long gone by the time we run out of that number of seconds. So it's someone else's problem many, many years from now. But that's really the fundamental solution. If you're running up against something finite, well, just kick the can further and just give yourself more bits. And frankly, because hardware is so much cheaper these days, computers are so much faster, it's not as big of a deal as it might have been decades ago. But that's indeed the solution. But this arises in very common contexts. In fact, let me go ahead and write a real quick program here called pennies. Right? You might think that just converting dollars to pennies in US currency might be simple. But let me go ahead and do this. In pennies.c, I'm going to go ahead and include CS50.h, and I'm going to include standard IO.h, int main void as my starting point. And now down here, I'm going to do this. I'm going to get a float called amount, and I'm going to ask the user for some amount of dollars, so a dollar amount. And I'm going to store that in a variable called amount. Then I'm going to simply convert that amount to pennies by doing, say, how about amount times 100? And then I'm going to go ahead and print out that the number of pennies is %i, because that's just an integer in pennies, \n, quote unquote, comma, pennies. All right. So if I didn't make any mistakes here, let me make pennies, /pennies, and suppose I have, say, 99 cents, so 0.99, that's 99 pennies. Suppose I have $1.23. That's pretty good. Suppose I have $4.20. There's that imprecision issue. And this isn't even that big of an amount. Now, not a big deal if, like, the cashier gives you 1 penny less than you're owed, but you can imagine this adding up. You can imagine this being worrisome for financial implications, for financial transactions, for scientific measurements and the like. My program can't even handle this. Well, there are some solutions here. And it looks like what's really happening if I print it out using the %f with a 0.50 or whatever to see more decimal points, presumably the computer is struggling to represent $4.20 precisely. It's probably storing $4.19.9999 something cents. So it's close, but it's not quite there. So I could at least solve this by rounding up, for instance. And it turns out there is a round function out there. And it turns out that it's in a library called the math library. And you would know this by looking at online documentation and the like, as we'll point you to. And if I now make pennies again and do /pennies, I can now do $4.20. And voila, now it's correct. So at least in this context, it seems like a solvable problem. But it's certainly something I need to be mindful of nonetheless. Unfortunately, even professional, full-time programmers over the years have not been particularly attentive to these kinds of details. And in a class like this, the goal is not just to teach you programming, but to really teach you what's going on underneath the hood, so to speak, so that you have a bottom-up understanding of how data is represented, how computers are manipulating it, so that you are not on the failing end of some program having some bug, and so that we as a society are not beholden to those kinds of mistakes too. And this happens, unfortunately, all of the time. This is a Boeing airplane that a few years ago needed to be rebooted after every 248 days. Why? Because this Boeing airplane software was using a 32-bit integer, counting up tenths of a second to keep track of something or other related to its electrical power. And unfortunately, after 248 days of the airplane being continuously on, which in the airline industry is apparently not uncommon to make every dollar count, keeping the planes up and running all the time, the 32-bit number would roll over, and the power would shut off on the airplane as a side effect because of sort of undefined behavior in that case. The temporary solution by Boeing at the time was apparently essentially sort of operating system style, well, have you rebooted your plane? And that was indeed the fix until they rolled out an actual software patch. This stuff really matters. And the more hardware we carry around and the more we as a society use these kinds of devices, the more of these problems we're going to run into down the road. That's it for CS50. We'll see you next time. This is CS50, and this is week 2. Now that you have some programming experience under your belt in this more arcane language called C, among our goals today is to help you understand exactly what you have been doing these past several days, wrestling with your first programs in C, so that you have more of a bottom-up understanding of what some of these commands do, and ultimately what more we can do with this language. So this, recall, was the very first program you wrote, I wrote in this language called C, much more textual, certainly, than the Scratch equivalent. But at the end of the day, computers, your Mac, your PC, VS Code doesn't understand this actual code. What's the format into which we need to get any program that we write? Just to recap. So binary, otherwise known as machine code, right? The zeros and ones that your computer actually does understand. So somehow we need to get to this format. And up until now, we've been using this command called make, which is sort of aptly named because it lets you make programs. And the invocation of that has been pretty simple. Make hello sort of looks in your current directory or folder for a file called hello.c implicitly. And then it compiles that into a file called hello, which itself is executable, which just means runnable, so that you can then do /hello. But it turns out that make is actually not a compiler itself. It does help you make programs, but make is this sort of utility that comes on a lot of systems that makes it easier to actually compile code by using an actual compiler, the program that converts source code to machine code on your own Mac or PC or whatever cloud environment you might be using. In fact, what make is doing for us is actually running a command automatically known as clang for C language. And so in fact, here, for instance, in VS Code is that very first program again, this time in the context of a text editor. And I could compile this with make hello, but let me go ahead and use the compiler itself manually. And we'll see in a moment why we've been automating the process with make. I'm going to run clang instead, and then I'm going to run hello.c. So it's a little different how the compiler's used. It needs to know explicitly what the file is called. I'll go ahead and run clang hello.c, enter. Nothing seems to happen, which generally speaking is a good thing because no errors have popped up. And if I do ls now for list, you'll see there is not a file called hello, but there is a curiously named file called a.out. This is a historical convention, stands for assembler output. And this is just the default file name for a program that you might compile yourself manually using clang itself. Let me go ahead now, though, and point out that that's kind of a stupid name for a program, even though it works. /a.out would work. But if you actually want to customize the name of your program, we could just resort to make, or we could do explicitly what make is doing for us, because it turns out some programs, among them make, support what are called command line arguments. And more on those later today. But these are like literally words or numbers that you type at your prompt after the name of a program that just influences its behavior in some way. It modifies its behavior. And it turns out, if you read the documentation for clang, you can actually pass a -o for output command line argument that lets you specify explicitly what do you want your outputted program to be called. And then you go ahead and type the name of the file that you actually want to compile from source code to machine code. Let me go ahead and hit enter now. Again, nothing seems to happen. And I type ls, and voila, now we still have the old a.out because I didn't delete it yet. And I do have hello now. So /hello, voila, runs hello world again. And let me go ahead and remove this file. I could, of course, resort to using the Explorer on the left-hand side, which I am in the habit of closing just to give us more room to see. But I could go ahead and right-click or control-click on a.out if I want to get rid of it. Or again, let me focus on the command line interface. And I can use, anyone recall, we didn't really use it much, but what command removes a file? rm. So rm for remove, rm, a.out, enter, remove regular file, a.out, y for yes, enter. And now if I do ls again, voila, it's gone. All right, so let's now enhance this program to do the second version we ever did, which was to also include CS50.h so that we have access to functions like getString and the like. And let me go ahead and do string name gets, getString, what's your name, question mark. And now let me go ahead and say hello to that name with our %s placeholder, comma name. So this was version 2 of our program last time that very easily compiled with make hello. But notice the difference now. If I want to compile this thing myself with clang using that same lesson learned, all right, let's do it. Clang -o hello, just so I get a better name for the program, hello.c. Enter. And a new error pops up that some of you might have encountered on your own. So it's a bit arcane here, and there's this mention of a cryptic looking path with temp for temporary there. But somehow my issue's in main, as we can see here. It somehow relates to hello.c, even though we might not have seen this language last time in class. But there's an undefined reference to getString, as though getString doesn't exist. Now, your first instinct might be, well, maybe I forgot CS50.h, but of course I didn't. That's the very first line of my program. But it turns out make is doing something else for us all this time. Just putting CS50.h, or any header file at the top of your code for that matter, just teaches the compiler that a function will exist. It sort of asks the compiler to trust that I will eventually get around to implementing functions like getString in CS50.h and standardio.h like printf therein. But this error here, some kind of linker command, relates to the fact that there's a separate process for actually finding the zeros and ones that CS50 compiled long ago for you, that the authors of this operating system compiled for you long ago in the form of printf. We need to somehow tell the compiler that we need to link in code that someone else wrote, the actual machine code that someone else wrote and then compiled. So to do that, you'd have to type -l CS50, for instance, at the end of the command. So additionally telling Clang that not only do you want to output a file called hello and you want to compile a file called hello.c, you also want to, quote unquote, link in a bunch of zeros and ones that collectively implement getString and printf. So now if I hit enter, this time it compiled OK. And now if I run /hello, it works as it did last week, just like that. But honestly, this is just going to get really tedious really quickly. Notice already, just to compile my code, I have to run clang-o, hello, hello.c, -lcs50. And you're going to have to type more things too. If you wanted to use the math library, like to use that round function, you would also have to do -lm typically to specify give me the math bits that someone else compiled. And the commands just get longer and longer. So moving forward, we won't have to resort to running Clang itself. But Clang is indeed the compiler. That is the program that converts from source code to machine code. But we'll continue to use make because it just automates that process. And the commands are only going to get more cryptic the more sophisticated and more featureful your programs get. And make, again, is just a tool that makes all that happen, so to speak. Let me pause there to see if there's any questions before then we take a look further under the hood. Yeah, in front. Sure, and let me come back to that in a moment. What does the -lcs50 mean? We'll come back to that visually in just a moment. But it means to link in the zeros and ones that collectively implement getString and printf. But we'll see that visually in a sec. Yeah, behind you. Really good question. How come I didn't have to link in standard I/O? Because I used printf in version 1. Standard I/O is just literally so standard that it's built in. It just works for free. CS50, of course, is not. It did not come with the language C or the compiler. We ourselves wrote it. And other libraries, even though they might come with the language C, they might not be enabled by default, generally for efficiency purposes. So you're not loading more zeros and ones into the computer's memory than you need to. So standard I/O is special, if you will. Other questions? Yeah. Oh, what does the -o mean? So -o is shorthand for the English word output. And so -o is telling Clang to please output a file called hello, because the next thing I wrote after the command line, recall, was clang -o hello, then the name of the file, then -lcs50. And this is where these commands do get and stay fairly arcane. It's just through muscle memory and practice that you'll start to remember, oh, what are the other commands what are the command line arguments you can provide to programs? But we've seen this before. Technically, when you run make hello, the program is called make. Hello is the command line argument. It's an input to the make function, albeit typed at the prompt, that tells make what you want to make. Even when I used rm a moment ago and did rm of a.out, the command line argument there was called a.out, and it's just telling rm what to delete. It is entirely dependent on the programs to decide what their conventions are, whether you use -this or -that. But we'll see over time which ones actually matter in practice. So to come back to the first question about what actually is happening there, let's consider the code more closely up. So here is that first version of the code again with standardio.h and only printf, so no CS50 stuff yet, until we add it back in and had the second version where we actually get the human's name. When you run this command then, there's actually a few things that are happening underneath the hood. And we won't dwell on these kinds of details. Indeed, we'll abstract it away, so to speak, by using make. But it's worth understanding, at least from the get-go, how much automation is going on so that when you run these commands, it's not magic. You actually do have this bottom-up understanding of what's going on. So when we say you've been compiling your code with make, that's a bit of an oversimplification. Technically, every time you compile your code, you're having the computer actually do 4 distinct things for you. And this is not 4 distinct things that you need to sort of memorize and remember every time you run your program what's happening. But it helps to sort of break it down into building blocks as to how we're getting from source code, like C, into zeros and ones. It turns out that when you compile, quote unquote, your code, technically speaking, you're doing 4 things sort of automatically and all at once. Pre-processing it, compiling it, assembling it, and linking it. Just humans decided, let's just call the whole process compiling. But for a moment, let's just consider what these steps are. So pre-processing refers to this. If we look at our source code here, version 2, that uses the CS50 library and therefore gets string, notice that we indeed have these include lines at top. And they're kind of special versus all the other code we've written because they start with hash symbols specifically. And that's sort of a special syntax that means that these are technically called preprocessor directives. A fancy way of saying they're handled special versus the rest of your code. In fact, if we focus on CS50.h, recall from last week that I provided a hint as to what's actually in CS50.h, among other things. Like, what was the one salient thing that I said was in CS50.h, and therefore why we were including it in the first place? So getString, specifically the prototype for getString. We haven't made many of our own functions yet, but recall that anytime we've made our own functions and we've written them like below main in a file, we've also had to somewhat stupidly copy paste the prototype of the function at the top of the file just to teach the compiler that this function doesn't exist yet. It does down there, but it will exist. Just trust me. So again, that's what these prototypes are doing for us. So therefore, in my code, if I want to use a function like getString, or printf for that matter, they're not implemented clearly in the same file. They're implemented elsewhere. So I need to tell the compiler to trust me that they're implemented somewhere else. And so technically, inside of CS50.h, which is installed somewhere in the cloud's hard drive, so to speak, that you all are accessing via VS Code, there's a line that looks like this. A prototype for the getString function that says the name of the function's getString. It takes one input or argument called prompt. And that type of that prompt is a string. GetString, not surprisingly, has a return value, and it returns a string. So literally, that line and a bunch of others are in CS50.h. And so rather than you all having to copy paste the prototype, you can just trust that CS50 figured out what it is. You can include CS50.h, and the compiler is going to go find that prototype for you. Same thing in standard IO. Someone else. What must clearly be in standard IO.h, among other stuff, that motivates our including standard IO.h too? Yeah. Printf, the prototype for printf. And indeed, I'll just change it here in yellow to be the same. And it turns out the prototype for printf is actually pretty fancy because, as you might have noticed, printf can take one argument, just something to print. 2, if you want to plug a value into it. 3 or more. So the ... just represents exactly that. It's not quite as simple a prototype as getString, but more on that another time. So what does it mean to pre-process your code? The very first thing the compiler, Clang in this case, is doing for you when it reads your code top to bottom, left to right, is it notices, ooh, here is hash include. Oh, here's another hash include. And it essentially finds those files on the hard drive, CS50.h, standard IO.h, and does the equivalent of copying and pasting them automatically into your code at the very top, thereby teaching the compiler that getString and printf will eventually exist somewhere. So that's the pre-processing step, whereby, again, it's just doing a find and replace of anything that starts with hash include. It's plugging in the files there so that you essentially get all the prototypes you need automatically. OK, what does it mean then to compile the result? Because at this point in the story, your code now looks like this in the computer's memory. It doesn't change your file. It's doing all of this in the computer's memory or RAM for you. But it essentially looks like this. Well, the next step is what's technically really compiling, even though, again, we use compile as an umbrella term. Compiling code in C means to take code that now looks like this in the computer's memory and turn it into something that looks like this, which is way more cryptic. But it was just a few decades ago that if you were taking a class like CS50 in its earlier form, we wouldn't be using C if it didn't exist yet. We would actually be using this, something called assembly language. And there's different types of or flavors of assembly language. But this is about as low level as you can get to what a computer really understands, be it a Mac or a PC or a phone, before you start getting into actual zeros and ones. And most of this is cryptic. I couldn't really tell you what this is doing unless I really thought it through carefully and rewound mentally years ago from having studied it. But let's highlight a few key words in yellow. Notice that this assembly language that the computer is outputting for you automatically still has mention of main, and it has mention of getString, and it has mention of printf. So there's some relationship to the C code we saw a moment ago. And then if I highlight these other things, these are what are called computer instructions. At the end of the day, your Mac, your PC, your phone actually only understands very basic instructions like addition, subtraction, division, multiplication, move into memory, load from memory, print something to the screen, like very basic operations. And that's what you're seeing here. These assembly instructions are what the computer actually feeds into the brains of the computer, the CPU, the central processing unit. And it's that Intel CPU or whatever you have that understands this instruction and this one and this one and this one. And collectively, long story short, all they do is print hello world on the screen, but in a way that the machine understands how to do. So let me pause here. Are there any questions on what we mean by preprocessing, which just finds and replaces the hash includes symbols, among others, and compiling, which technically takes your source code once preprocessed and converts it to that stuff called assembly language? Correct. Each type of CPU has its own instruction set. Indeed. And as a teaser, this is why, at least back in the day when we used to like install software from CD-ROMs or some other type of media, this is why you can't take a program that was sold for a Windows computer and run it on a Mac or vice versa, because the commands, the instructions that those two products understand are actually different. Now, Microsoft or any company could generally write code in one language like C or another, and they can compile it twice, saving a PC version and saving a Mac version. It's twice as much work, and sometimes you get into some incompatibilities. But that's why these steps are somewhat distinct. You can now use the same code and support even different platforms or systems if you'd want. All right, assembling. Thankfully, this part is fairly straightforward, at least in concept, to assemble code, which is step 3 of 4, that is just happening literally for you every time you run make or in turn clang. This assembly language, which the computer generated automatically for you from your source code, is turned into zeros and ones. So that's the step that last week I simplified and said when you compile your code, you convert it to source code, from source code to machine code. Technically, that happens when you assemble your code. But no one in normal conversations says that. They just say compile for all of these terms. All right, so that's assembling. There's one final step. Even in this simple program of getting the user's name and then plugging it into printf, I'm using 3 different people's code, if you will. My own, which is in hello.c, some of CS50's, which is apparently in hello.c, which is in CS50.c, which is not a file I've mentioned yet, but it stands to reason that if there's a CS50.h that has prototypes, turns out the actual implementation of getString and other things are in CS50.c. And there's a third file somewhere on the hard drive, so to speak, that's involved in compiling even this simple program. Hello.c, CS50.c, and by that logic, what might the other be? Yeah. Standard.io.c. And that's a bit of a white lie because that's such a big, fancy library that there's actually multiple files that compose it. But the same idea, and we'll take the simplification. So when I have this code now, and I compile my code here, I get those zeros and ones that end up taking hello.c and turning it effectively into zeros and ones that are combined with CS50.c, followed by standard.io.c as well. So let me rewind here. Here might be the zeros and ones for my code, the 2 lines of code essentially that I wrote. Here might be the zeros and ones for what CS50 wrote some years ago in CS50.c. Here might be the zeros and ones that someone wrote for standard.io decades ago. The last and final step is that linking command that links all of these zeros and ones together, essentially stitches them together into one single file called hello, or called a.out, whatever you name it. That last step is what combines all of these different programmers' zeros and ones. And my God, like now we're really in the weeds. Who wants to even think about running code at this level? You shouldn't need to, but it's not magic. When you're running make, there's just some very concrete steps that are happening that humans have developed over the years, over the decades, that sort of break down this big problem of source code going to zeros and ones, or machine code, into these very specific steps. But henceforth, you can call all of this compiling. Questions or confusion? Yeah? Sure. What does a.out signify? A.out is just the conventional default file name for any program that you compile directly with a compiler like Clang. It's just kind of a meaningless name, though. It stands for assembler output. And assembler might now sound familiar from this assembling process. It's just kind of a lame name for a computer program. And so we can override it by outputting something like hello instead. Yeah? So there are, to recap, there are other prototypes in those files, CS50.h, standard.io.h. Technically, they're all included atop your file, even though you, strictly speaking, don't need most of them. But indeed, they are there, just in case you might want them. And finally, any other questions? Yeah? Does it matter what order we're telling the computer to run? Sometimes with libraries, yes, it matters what order they are linked in together. But for our purposes, it's really not going to matter. It's just going to make is going to take care of automating that process for us. All right, so with that said, henceforth, compiling technically is these four things, but we'll focus on it just as a higher level concept, an abstraction, if you will, known as compiling itself. So another process that we'll now begin to focus on all the more this week, because invariably this past week you ran up against some challenges. You probably created your very first bugs or mistakes in a program. And so let's focus for a moment on actual techniques for debugging. As you spend more time this semester, in the years to come, if you continue to program, you're never, frankly, probably going to write bug-free code. Ultimately, your programs are just going to get more featureful, more sophisticated, and we're all just going to start to make more sophisticated mistakes. And to this day, I write buggy code all the time, and I'm always horrified when I do it up here, but hopefully that won't happen too often. But when it does, it's just a process now of debugging, trying to find the mistakes in your program. And you don't have to just stare at your code or sort of shake your fist at your code. There are actual tools that real-world programmers use to help debug their code and find these faults. So what are some of the techniques and tools that folks use? Well, as an aside, if you've ever bug in a program is a mistake. That's actually been around for some time. If you've ever heard this tale, some 50 plus years ago in 1947, this is actually an entry in a logbook written by a famous computer scientist named Grace Hopper, who happened to be the one to record the very first discovery of a quote-unquote actual bug in a computer. This is actually like a moth that had flown into, at the time, it was a very sophisticated system known as the Harvard Mark II computer, sort of very large, sort of refrigerator-sized type systems in which an actual bug caused an issue. The etymology of bug, though, actually predates this particular instance. But here you have, as any computer scientist might know, the example of the first physical bug in a computer. How, though, do you go about removing such a thing? Well, let's consider a very simple scenario from last time, for instance, when we were trying to print out various aspects of Mario, like this column of 3 bricks. Let's consider how I might go about implementing a program like this. And let me switch back over to VS Code here. And I'm going to go ahead and write a program. And I'm not going to trust myself, so I'm going to call it buggy.c from the get-go, knowing that I'm going to mess something up. But I'm going to go ahead and include standard.io.h. And I'm going to go ahead and define main as usual. So hopefully no mistakes just yet. And now I want to print those 3 bricks on the screen using just hashes for bricks. So how about for int I gets 0, I less than or equal to 3, I plus plus. Now inside of my curly braces, I'm going to go ahead and print out a hash followed by a \n, semicolon. All right, saving the file, doing make buggy, enter, it compiles. So there's no syntactical errors, like my code is syntactically correct, but some of you have probably seen the logical error already, because when I run this program, I don't get this picture, which was 3 bricks high. I seem to have 4 bricks instead. Now, this might be jumping out at you why it's happening, but I've kept the program simple just so that we don't have to actually find an actual bug. We can use a tool to find one that we already know about in this case. What might be the first strategy for actually finding a bug like this, rather than just staring at your code, asking a question, trying to sort of just think through the problem? Well, let's actually try to diagnose the problem more proactively. And the simplest way to do this now and years from now is honestly going to be used to use a function like printf. Printf is a wonderfully useful function, not for printing formatted strings and all that, but just looking inside the values of variables that you might be curious about to see what's going on. So you know what? Let me do this. I see that there's 4 coming out, but I intended 3. So clearly something's wrong with my I variables. So let me just be a little more pedantic. Let me go inside of this loop and just temporarily say something explicit like I is %i \n, and then just plug in the value of I. Right? This is not the program I want to write. It's the program I'm temporarily writing, because now I'm going to go ahead and say make buggy /buggy. And if I look now at the output, I have some helpful diagnostic information. I is 0, and I get a hash. I is 1, and I get a hash. 2, and I get a hash. 3, and I get a hash. OK, wait a minute. I'm clearly going too many steps, because maybe I forgot that computers are essentially counting from 0. And now, oh, it's less than or equal to. Now you see it. Right? Again, trivial example. But just by using printf, you can see inside of the computer's memory by just printing stuff out like this. And now once you've figured it out, oh, so this should probably be less than 3, or I should start counting from 1. There's any number of ways I could fix this, but the most conventional is probably just to say less than 3. Now I can go ahead and delete my temporary print statement, rerun make buggy /buggy, and voila, problem solved. All right, and to this day, I do this, like whether it's making a command line application or a web application or a mobile application, it's very common to use printf or some equivalent in any language just to poke around and see what's inside the computer's memory. Thankfully, there's more sophisticated tools than this. Let me go ahead and reintroduce the bug here. And let me go ahead and reopen my sidebar at left here. And let me go ahead now and recompile the code to make sure it's current. And I'm going to run a command called debug50, which is a command that's representative of a type of program known as a debugger. And this debugger is actually built into VS Code. And all debug50 is doing for us is just automating the process of starting VS Code's built-in debugger. So this isn't even a CS50 specific tool. We've just given you a debug50 command to make it easier to start it up from the get-go. And the way you run this debugger is you say debug50 space, and then the name of the program that you want to debug. So in this case, /buggy. So you don't mention your C file. You mention your already compiled code. And what this debugger is going to let me do is most powerfully walk through my code step by step. Because every program we've written thus far just kind of runs from start to finish, even if I'm not done sort of thinking through each step at a time. With the debugger, I can actually like click on a line number and say pause execution here. And the debugger will let me walk through my code one step at a time, 1 second at a time, 1 minute at a time at my own human pace, which is super compelling when the programs get more complicated and they might otherwise just fly by on the screen. So I'm going to click to the left of line 5 and notice that these little red dots appear. And if I click on one, it stays and gets even redder. And I'm going to now run debug50 on /buggy. And in just a moment, you'll see that a new panel opens on the left-hand side. It's doing some configuration of the screen. And now let me go ahead and zoom out just a little bit here so we can see more on the screen at once. And sometimes you'll see in VS Code that debug console opens up, which looks very cryptic. Just go back to terminal window if that happens, because that the terminal window is where you can still interact with your code. And let's now take a look at what's going on. If I zoom in on my buggy.c code here, you'll notice that we have the same program as before, but highlighted in yellow is line 5. Not a coincidence. That's the line I set a so-called breakpoint at. The little sort of red dot means break here, pause execution here, and the yellow line has not yet been executed. But if I now, at the top of my screen, notice these little arrows. There's one for play. There's one for this, which if I hover over it, says step over. There's another that's going to say step into. There's a third that says step out. I'm just going to use the first of these, step over. And I'm going to do this. And you'll see that the yellow highlight moved from line 5 to line 7 because now it's ready, but hasn't yet printed out that hash. But the most powerful thing here, notice, is at top left here. It's a little cryptic because there's a bunch of things going on that'll make more sense over time. But at the top, there's a section called variables. Below that, something called locals, which means local to my current function, main. And notice, there's my variable called I, and its current value is 0. So now, once I click step over again, watch what happens. We go from line 7 back to line 5. But look in the terminal window, one of the hashes has printed. But now it's kind of printed at my own pace. I can sort of think through this step by step. Notice that I has not changed yet. It's still 0 because the yellow highlighted line hasn't yet executed. But the moment I click step over, it's going to execute line 5. Now notice at top left, I has become 1. And nothing has printed yet because now highlighted is line 7. And so if I click step over again, we'll see the hash. And if I repeat this process at my own human comfortable pace, I can see my variables changing. I can see output changing on the screen. And I can just think about, should that have just happened? And I can pause and give thought to what's actually going on without trying to race the computer and figure it all out at once. I'm going to go ahead and just stop here because we already know what this particular problem is. And that just brings me back to my default terminal window. But this debugger, let me disable the breakpoint now so it doesn't keep breaking. This debugger will be your friend moving forward in order to step through your code, step by step at your own pace to figure out where something has gone wrong. Printf is great, but it gets annoying if you have to constantly add print this, print this, print this, print this, recompile, rerun it. Oh, wait a minute, print this, print this. Like the debugger just lets you do the equivalent, but automatically. Questions on then this debugger, which you'll see all the more hands-on over time. Questions on debugger? Yeah?
You were using like the step over feature. What do the other features in the debugger?
Really good question. We'll see this before long, but those other buttons that I glossed over, like step into and step out of, actually let you step into specific functions if I had any more than main. So if main called a function called something, and something called a function called something else, instead of just stepping over the entire execution of that function, I could step into it and walk through its lines of code one by one. So anytime you have a problem set you're working on that has multiple functions, you can set a breakpoint in main if you want, or you can set it inside of one of your additional functions to focus your attention only on that. And we'll see examples of that over time. All right, so what else? And what's the the sort of elephant in the room, so to speak, is actually a duck in this case. Why is there this duck and all of these ducks here? Well, it turns out a third genuinely recommended debugging technique is talking through problems, talking through code with someone else. Now, in the absence of having a family member or a friend or a roommate who actually wants to hear you talk about code of all things, generally programmers turn to a rubber duck or other inanimate objects if something animate is not available. And the idea behind rubber duck debugging, so to speak, is that simply by looking at your code and talking it through, OK, on line 3, I'm starting a for loop, and I'm initializing I to 0. OK, then I'm printing out a hash. Just by talking through your code step by step, invariably finds you having the proverbial light bulb go off over your head because you realize, wait a minute, I just said something stupid, or I just said something wrong. And this is really just a proxy for any other human, teaching fellow, teacher, friend, colleague. But in the absence of any of those people in the room, you're welcome to take on your way out today one of these little rubber ducks and consider using it for real anytime you just want to talk through one of your problems in CS50 or maybe life more generally. But having it there on your desk is just a way to help you hear illogic in what you think might otherwise be logical code. So printf, debugging, rubber duck debugging are just 3 of the ways you'll see over time to sort of get to the source of code that you will write that has mistakes, which is going to happen, but it'll empower you all the more to solve those mistakes. Are any questions on debugging in general or these 3 techniques? Yeah. What's the difference between step over and step into? At the moment, the only one that's applicable to the code I just wrote is step over, because it means step over each line of code. If, though, I had other functions that I had written in this program, maybe lower down in the file, I could step into those function calls and walk through them one at a time. So we'll come back to this with an actual example, but step into will allow me to do exactly that. In fact, this is a perfect segue to doing a little something like this. Let me go ahead and open up maybe another file here. Actually, we'll use the same, buggy, and we're just going to write one other thing that's buggy as well. Let me go ahead up here and include, as before, cs50.h. Let me include standardio.h. Let me do int main void. So all of this, I think, is correct so far. And let's do this. Let's give myself an int called I, and let's ask the user for a negative integer. This is not a function that exists technically yet, but I'm going to assume for the sake of discussion that it does. And then I'm just going to go ahead and print out with %i and a new line whatever the human typed in. So at this point in the story, my program, I think, is correct, except for the fact that getNegativeInt is not a function in the CS50 library or anywhere else. I'm going to need to invent it myself. So suppose in this case that I declare a function called getNegativeInt. Its return type, so to speak, should be int, because as its name suggests, I want to hand the user back an integer. And it's going to take no input to keep it simple. So I'm just going to say void there. No inputs, no special prompts, nothing like that. Let me now give myself some curly braces. And let me do something familiar perhaps now from problem set 1. Let me give myself a variable like n. And let me do the following within this block of code. Assign n the value of getInt, asking the user for a negative integer using getInt's own prompt. And I want to do this while n is less than 0, because I want to get a negative int from the user. And recall, from having used this block in the past, I can now return n as the very last step to hand back whatever the user has typed in, so long as they cooperated and gave me an actual negative integer. Now, I've deliberately made a mistake here. And it's a subtle, sort of silly mathematical one. But let me compile this program after copying now the prototype up to the top, just so I don't make that mistake again. Let me do make buggy, enter. And now let me do /buggy. I'll give it a negative integer like -50. That did not take. How about -5? Maybe it's 2. No. How about 0? All right, so it's clearly sort of working backwards or incorrectly here logically. So how could I go about debugging this? Well, I could do what I've done before. I could use my printf technique and say something explicit like n is %i, new line, comma I, comma n, just to print it out. Let me recompile buggy. Let me rerun buggy. Let me type in -50. OK, n is -50. So that didn't really help me at this point, because that's the same as before. So let me do this. Debug 50 /buggy. Oh, but I've made a mistake. So I didn't set my breakpoint yet. So let me go ahead and do this. And I'll set a breakpoint this time. I could set it here on line 8. Let's do it in main as before. Let me rerun debug 50 now on /buggy. That fancy user interface is going to pop up. It's going to highlight the line that I set the breakpoint on. Notice that on the left-hand side of the screen, I is defaulting at the moment to 0, because I haven't typed anything in yet. But let me go ahead now and step over this line that's highlighted in yellow. And you'll see that I'm being prompted. So let's type in my -50, enter. All right, and notice now that I'm stuck in that function. So, all right. So clearly, the issue seems to be in my getNegativeInt function. So OK, let me go ahead and stop this execution. My problem doesn't seem to be in main, per se. Maybe it's down here. So that's fine. Let me set my same breakpoint at line 8. Let me rerun debug 50 one more time. But this time, instead of just stepping over that line, let's step into it. So notice, line 8 is again highlighted in yellow. In the past, I've been clicking step over. Let's click step into now. And when I click step into, boom, now the debugger jumps into that specific function. And now I can step through these lines of code again and again. I can see what the value of n is as I'm typing it in. I can think through my logic. And voila, hopefully once I've solved the issue, I can exit the debugger, fix my code, and move on. So step over just goes over the line but executes it. Step into lets you go into other functions you've written. So, all right, so let's go ahead and do this. We've got a bunch of possible approaches that we can take to solving some problem. Let's go ahead and pace ourselves today, though. Let's take a 5-minute break here. And when we come back, we'll actually take a look at that computer's memory we've been talking about. See you in 5. All right. So let's Let's dive back in. And up until now, both by way of week 1 and problem set 1, for the most part, we've just translated from scratch into C all of these basic building blocks like loops and conditionals, Boolean expressions, variables, so sort of more of the same. But there are features in C that we've already stumbled across already, like data types, the types of variables that doesn't exist in Scratch, but that in fact does exist in other languages. In fact, a few that we'll see before long. So to summarize the types we saw last week, just recall this little list here. We had ints and floats and longs and doubles and chars. There's also bools and also string, which we've seen a few times. But today, let's actually start to formalize what these things are and actually like what your Mac and PC are doing when you manipulate bits as an int versus a char versus a string versus something else. And see if we can't put more tools into your toolkit, so to speak, so we can start quickly writing more featureful, more sophisticated programs in C. So it turns out that on most systems nowadays, though this can vary by actual computer, this is how large each of the data types typically is in C. When you store a Boolean value, a 0 or a 1, a true or a false or a true, it actually uses 1 byte. That's actually a little excessive because strictly speaking, you only need 1 bit, which is 1/8 of this size. But for simplicity, computers use a whole byte to represent a bool, true or false. A char, we saw last week, is actually only 1 byte or 8 bits. And this is why ASCII, which uses 1 byte, or technically only 7 bits early on, was confined to only 256 maximally possible characters. Notice that an int is 4 bytes, or 32 bits. A float is also 4 bytes, or 32 bits. But the things that we called long is literally twice as long. 8 bytes or 64 bits. And so is a double. A double is 64 bits of precision for floating point values. And a string for today, we're going to leave as a question mark, because we'll come back to that later today and next week as to how much space a string takes up. But suffice it to say, it's going to take up a variable amount of space, depending on whether the string is short or long. But we'll see exactly what that means before long. So here's a photograph of a typical piece of memory inside of your Mac or PC or phone. And odds are it might be just a little smaller in some devices. This is known as RAM, or random access memory. And each of these little black chips on this circuit board, the green thing, these little black chips are where zeros and ones are actually stored. Each of those stores some number of bytes, maybe megabytes, maybe even gigabytes nowadays. So let's actually focus on just one of those chips just to give us a sort of zoomed in version thereof. And let's consider the fact that even though we don't have to care exactly how this kind of thing is made, if this is like 1 gigabyte of memory for the sake of discussion, it stands to reason that if this thing is storing 1 billion bytes, 1 gigabyte, then we can number them kind of arbitrarily. Like maybe this will be byte 0, 1, 2, 3, 4, 5, 6, 7, 8. And then maybe way down here in the bottom right corner is byte number 1 billion. Right? We can just number these things, as might be our convention. So let's actually draw that graphically, not with a billion squares, but fewer than those. And let's just zoom in further and consider that, all right, at this point in the story, let's abstract away all the hardware and all the little wires and just think of memory is taking up, or rather, just think of data as taking up some number of bytes. So for instance, if you were to store a char in a computer's memory, which was 1 byte, it might be stored literally at this like top left-hand location of this black chip of memory. If you were to store something like an integer that uses 4 bytes, well, it might use 4 of those bytes. But they're going to be contiguous, back to back to back in this case. If you were to store a long or a double, you might actually need 8 bytes. So I'm just kind of filling in these squares to represent how much memory a given variable of some data type would take up, 1 or 4 or 8 in this case here. Well, from here, let's go ahead and just abstract away from all of the hardware and just really focus on memory as being a grid, or really like a canvas that we can paint any types of data onto that we want. At the end of the day, all of this data is just going to be zeros and ones, but it's up to you and I to sort of build abstractions on top of that, things like actual numbers and colors and images and movies and beyond. But we'll start lower level here first. Suppose I had a program that needs 3 integers, like a simple program whose purpose in life is to like average your 3 scores on an exam or some such thing. And suppose that your 3 scores were these, 72 and 73, not too bad, and 33, which was particularly low. Let's go ahead and write a program that actually does this kind of averaging for us. Let me go back to VS Code here. Let me open up a file called scores.c. And let me go ahead and implement this as follows. Let me include standard io.h at the top, int main void as before, And then inside of main, let me go ahead and declare score 1, which is 72. Give me another score, 73, and then a third score called score 3, which is going to be 33. And now I'm just going to use printf to print out the average of those things. And I can do this in a few different ways, but I'm going to just print out %f. And I'm going to do score 1 plus score 2 plus score 3 divided by 3, close parenthesis, semicolon. So just some relatively simple arithmetic just to compute the average of 3 scores if I'm curious like what my average grade is in the class with these 3 assessments. All right, let me go ahead now and do make scores. All right, so I've somehow made an error already, but this one is actually germane to a problem we hopefully won't encounter too frequently. What's going on here? So underlined is score 1 plus score 2 plus score 3 divided by 3. Format specifies type double, but the argument has type int. Well, what's going on here? Because the arithmetic seems to check out. Yeah.
So the computer is doing the math, but they basically gives out an integer value at the end. Because, well, all of a sudden there are integers, right? All of a sudden it's
Correct. And we'll come back to this in more detail. But indeed, what's happening here is I'm adding 3 ints together, obviously, because I defined them right up here. And I'm dividing by another int, 3. But the catch is, recall that C, when it performs math, treats all of these things as integers. But integers are not floating point values. So if you actually want to get a precise average for your score without throwing away the remainder, everything after the decimal point, it turns out in this case, we're going to have to, we're going to have to convert this whole expression somehow to a float. And there's a few ways to do this, but the easiest way for now, I'm just going to go ahead and do this up here. I'm going to change the divide by 3 to divide by 3.0, because it turns out, long story short, in C, so long as one of the values participating in an arithmetic expression like this is something like a float, the rest will be treated as, promoted to, so to speak, a floating point value as well. So let me now recompile this code with make scores, enter. This time it worked OK because I'm treating a float as a float. And let me do /scores, enter. All right, my average is 59.33333, and so forth. All right, so the math presumably checks out, floating point imprecision per last week aside. But let's consider the design of this program. Like, what is kind of bad about it? Or if we maintain this program longer term, are we going to regret the design of this program? What might not be ideal here? Yeah? Yeah, so in this case, I have hard-coded my 3 scores. So if I'm hearing you correctly, this program is only ever going to tell me this specific average. I'm not even using something like getInt or getFloat to get 3 different scores. So that's not good. And suppose that we wait later in the semester. I think other problems could arise. Yeah? I can't reuse the number because I haven't stored the average in some variable, which in this program, not a big deal. But certainly, if I wanted to reuse it elsewhere, that's a problem. And let's fast forward again a little later in the semester. I don't just have 3 test scores or exam scores. Maybe I have 4 or 5 or 6. Where might this take us? Yeah, I've sort of capped this program at 3. And honestly, this is just kind of bordering on copy-paste. Even though the variables, yes, have different names, score 1, score 2, score 3. Imagine doing this for like a whole grade book for a class, having score 4, 5, 6, 11, 10, 12, 20, 30. Like, that's a lot of variables. And you can imagine just how ugly the code starts to get if you're just defining variable after variable after variable. So it turns out there are better ways in languages like C if you actually want to have multiple values stored in memory that happen to be of the same data type. And so let's take a look back at this memory here to see what these things might look like in memory. Here's that grid of memory. And each of these, recall, represents a byte. So just to be clear, if I store score 1 in memory first, how many bytes will it take up? So 4, aka 32 bits. So I might draw score 1 as filling up this part of the memory. It's really up to the computer as to whether it goes here or down there or wherever. I'm just keeping the pictures clean, though, for today, from the top left on down. If I then declare another variable called score 2, it might end up over there, also taking up 4 bytes. And then score 3 might end up here. And so that's just representing what's going on inside of the computer's memory. But technically speaking, to be clear, per week 0, what's really being stored in the computer's memory are patterns of 0s and 1s. 32 total in this case, because 32 bits is 4 bytes. But again, it sort of gets boring quickly to think in and look at binary all the time. So we'll generally abstract this away as just using decimal numbers in this case instead. But there might be a better way to store not just 3 of these things, but maybe 4, maybe 5, maybe 10, maybe more, by declaring one variable to store all of them instead of 3 or 4 or 5 or more individual variables. And the way to do this is by way of something generally known as an array. An array is another type of data that allows you to store multiple values of the same type back to back to back. That is to say, contiguously. So an array can let you create memory for 1 int, or 2, or 3, or even more than that, but describe them all using the same variable name, the same one name. So for instance, if for one program I only need 3 integers, but I don't want to sort of messily declare them as score 1, score 2, score 3, I can actually do this instead. And this is today's first new piece of syntax, the square brackets that we're now seeing. This line of code here is similar to int score 1 semicolon, or int score 1 equals 72 semicolon. This line of code is declaring for me, so to speak, an array of size 3. And that array is going to store 3 integers. Why? Because the type of that array is an int here. The square brackets tell the computer how many ints you want, in this case 3. And the name is, of course, scores, which in English I've just deliberately pluralized now so that I can describe this array as storing multiple scores indeed. So if I want to now assign values to this variable called scores, I can do code like this. I can say scores bracket 0 equals 72, scores bracket 1 equals 73, and scores bracket 2 equals 33. The only thing weird there is admittedly the square brackets, which are still new. But we're also, notice, 0 indexing things. To 0 index means to start counting at 0. And we've talked about that before. Our for loops have generally been 0 indexed. Arrays in C are 0 indexed. And you do not have choice over that. You can't just start counting at 1 in arrays just because you prefer to. You'd be sacrificing one of the elements. You have to start in arrays counting from 0. So out of context, this doesn't necessarily solve a problem, but it definitely is going to once we have more than even 3 scores here. In fact, let me go ahead and change this program a little bit. Let me go back to VS Code here, and let me go ahead and delete these 3 lines here, and let me replace it with a scores variable that's ready to store 3 total integers. And then let me go ahead and initialize them as follows. Scores bracket 0 is 72 as before. Scores bracket 1 is going to be 73. Scores bracket 2 is going to be 33. Notice I do not need to say int before any of these lines because that's been taken care of already for me on line 5, where I already specified that everything in this array is going to be an int. Now down here, this code needs to change because I no longer have 3 variables, score 1, 2, and 3. I have 1 variable, but that I can index into. I'm going to here then do scores bracket 0 plus scores bracket 1 plus scores bracket 2, which is equivalent to what I did earlier, giving me back those 3 integers. But notice I'm using the same variable name every time. And again, I'm using this new square bracket notation to quote unquote index into the array, to get at the first int, the second int, and the third, and then to do it again down here. Now this program's still not really solving all of the problems we described. Like I still can only store 3 scores, but we'll come back to something like that before long. But for now, we're just introducing a new syntax and a new feature whereby I can now store multiple values in the same variable. Well, let's enhance this a bit more. Instead of hard coding these scores, as was identified as a problem, let's go ahead and use getInt to ask the user for a score. Let's then use getInt to ask the user for another score. Let's use getInt to ask the user for a third score, storing them in those respective locations. And now, if I go ahead and save this program, recompile scores, I've messed up here, but now these errors should be getting a little familiar. What mistake did I make? Let me give folks a moment. CS50.h. So yeah, that was not intentional, so still making mistakes all these years later. I need to include CS50.h. Now I'm going to go back to the bottom in the terminal window, make scores. OK, we're back in business, /scores. Now the program's getting a little more interesting. So maybe this year was better, and I got 100 and a 99 and a 98, and there my average is 99.0000. So now it's a little more dynamic. So it's a little more interesting, but it's still capping the number of scores at 3, admittedly. But now I've kind of introduced another sort of symptom of bad programming. There's this expression in programming, too, called code smell, where like something smells a little off. And there's something off here in that I could do better with this code here. Does anyone see an opportunity to improve the design of this code here if my goal still is just to get 3 scores from the user, but without it like smelling kind of bad? Yeah. Yeah, exactly. Those lines of code are almost identical. And honestly, the only thing that's changing is the number, and it's just incrementing by 1. We have all of the building blocks to do this better. So let me go ahead and improve this. Let me go ahead and delete that code. Let me go ahead now and have a for loop. So for int I gets 0, I less than 3, I plus plus. Then inside of this for loop, I can distill all 3 of those lines into something more generic, like scores bracket I equals getInt, and now ask the user just once via getInt for a score. So this is where arrays start to get pretty powerful. You don't have to hard code, that is literally type in all of these magic numbers like 0, 1, and 2. You can start to do it programmatically as you propose with a loop. So now I've kind of tightened things up. I'm now dynamically getting 3 different scores, but putting them in 3 different locations. And so this program ultimately is going to work pretty much the same. Make scores, /scores, and 100, 99, 98, and we're back to the same answer. But it's a little better designed too. If I really want to nitpick, there's something that still smells a little bit here. The fact that I have indeed this magic number 3 here that really kind of has to be the same as this number here. Otherwise, who knows what's going to go wrong? So what might be a solution per last week to kind of cleaning that code up further too? OK, so we could leave it up to the user's discretion. And so we could actually do something like this. Let me take this a few steps ahead. Let me say something like int n gets getInt, how many scores, question mark. Then I could actually change this to an n and then this to an end, and indeed make the whole program dynamic. Ask the human, how many tests have there been this semester? Then you can type in each of those scores, because the loop is going to iterate that many times, and then you'll get the average of 1 test, 2 tests, 3, oh, I lost another, or however many scores that were actually specified by the user. Yeah, question? How many bytes are used in an array? So the purpose of an array is not to save space. It's to eliminate having multiple variable names, because that just gets very messy quickly if you literally have score 1, score 2, score 3, ... score 99. That's literally like 99 different variables potentially that you could actually collapse into one variable that has 99 locations, if you will, at different indices or indexes, as someone would say. The index for an array is whatever's in the square brackets. So it's a good question. So if I'm using ints for everything. And honestly, we don't really need ints for scores, because I'm not really likely to get a 2 billion on a test anytime soon. And so you could actually use different data types. And that list we had on the screen earlier is not all of them. There's actually a data type called short, which is literally shorter than an int. You could actually technically use char in some form, or even other data types as well. Generally speaking, in the year 2021, these tend to be overly optimized decisions. Like everyone just uses ints, even though no one's going to get a test score that's 2 billion or more, because int is just kind of the go-to. Years ago, memory was expensive, and every one of your instincts would have been spot on because memory is so tight. But nowadays, we don't worry as much about it. Yeah? So what is the difference between dividing 2 ints and not getting an error, as you might have encountered in a program like cache, versus dividing 2 ints and getting an error like I did a moment ago? The problem with the scenario I created a moment ago was printf was involved. And I was telling printf to use a %f, but I was giving printf the result of dividing integers by another integer. So it was printf that was yelling at me. And I'm guessing in the scenario you're describing for something like cache, printf was not involved in that particular line of code. So that's the difference there. All right, so we now have this ability to create an array, and an array can store multiple values. What then might we do that's more interesting than just storing numbers in memory? Well, let's take this one step further. As opposed to just storing 72, 73, 33, or 100, 99, 98 at these given locations, because again, an array gives you one variable name, but multiple locations or indices therein, bracket 0, bracket 1, bracket 2, on up, if it were even bigger than that. Let's now start to consider something more modest, like simple chars. Chars being 1 byte each, so they're even smaller. They take up much less space. And indeed, if I wanted to say a message like hi, I could use 3 variables. If I wanted a program to print hi, H-I exclamation point, literally, I could, of course, store those in 3 variables, like C1, C2, C3. And let's just, for the sake of discussion, let's go ahead and whip this up real quickly. Let me create a new program here now in VS Code. This time I'm going to call it hi.c. And I'm not going to bother with the CS50 library here. I just need the standard IO one for now. Int main void. And then inside of main, I'm going to simply create 3 variables. And this is already, hopefully, striking you as a bad idea. But we'll go down this road temporarily with C1 and C2 and finally C3, storing each character in the phrase I want to print. And I'm going to go ahead now and print this in a different way than usual. Now I'm dealing with chars, and we've generally dealt with strings, which was easier certainly last week. But %c, %c, %c will let me print out 3 chars, and like C1, C2, and C3. So kind of a stupid way of printing out a string. So we already have a solution to this problem last week. But let's just poke around at what's actually going on underneath the hood here. So let's make hi, /hi, and voila. No surprise. But we, again, could have done this last week with a string and just 1 variable, or even 0 at that. But let's go ahead now and start converting these characters to their apparent numeric equivalents like we talked about in week 02. Let me go ahead and modify these %c's just to be fun to be %i's. And let me just add some spaces so that there are gaps between each of them. Let me now recompile hi. And let me rerun it. And just to guess, what should I see on the screen now? Any guesses? Yeah. The ASCII values. And it's intentional that I keep using the same word, hi, because it should be, hopefully, the old friends 72, 73, and 33, which is to say that C knows about ASCII or equivalently Unicode and can do this conversion for us automatically. And it seems to be doing it implicitly for us, so to speak. Notice that C1, C2, and C3 are obviously chars. But printf is able to tolerate printing them as integers. If I really wanted to be pedantic, I could use this technique, again known as typecasting, where I can actually convert one data type to another if it makes logical sense to do so. And at the end of the day, we saw in week 0, chars or characters are just numbers, like 72, 73, and 33. So I can actually use this parenthetical expression to convert, incorrectly, 3 chars to 3 integers instead. So that's what I meant to type the first time. There we go. Strike 2 today. So parenthesis int close parenthesis just says take whatever variable comes after this, C1 or C2 or C3, and convert it to an int. The effect is going to be no different here. Make hi and then rerunning, then running /hi still works the same. But now I'm explicitly converting chars to ints. And we can do this all day long. Chars to ints, floats to ints, ints to floats. Sometimes it's equivalent. Other times you're going to lose information. Taking a float to an int just intuitively is going to throw away everything after the decimal point, because after all, an int has no decimal point. But for now, I'm going to go ahead and rewind to the version of this that just did implicit type conversion or implicit casting, just to demonstrate that we can indeed see the values underneath the hood. All right, let me go ahead and do this now the week 1 way. This was kind of stupid. Let's just do printf, quote unquote. Actually, let's do this. String s equals quote unquote hi. And then let's go ahead and do a simple printf with %s, printing out s is there. So now I've rewound to last week where we began this story. But you'll notice that if we keep playing around with this, whoops, what did I do here? Oh, and let me introduce the CS50 library here. More on that before long. Let me go ahead and recompile, rerun this. We seem to be coding in circles here. Like I've just done the same thing multiple different ways. But there's clearly an equivalence then between sequences of chars and strings. And if you do it the real pedantic way, you have like 3 different variables, C1, C2, C3, representing HI exclamation point. Or you can just treat them all together like this, HI exclamation point. But it turns out that strings are actually implemented by the computer in a pretty now familiar way. What might a string actually be as of this point in the story? Where are we going with this? Let me try to look farther back. Yeah, and way back? Yeah. Yeah, a string might be, and indeed is, just an array of characters. So last week we just took for granted that strings exist. Technically, strings exist, but they're implemented as arrays of characters, which actually opens up some interesting possibilities for us. Because let me see if I can do this. Let me try to print out now 3 integers again. But if string s is but an array, as you propose, maybe I can do s bracket 0, s bracket 1, and s bracket 2. So maybe I can start poking around inside of strings, even though we didn't do this last week, so I can get at those individual values. So make high, /high, and voila, there we go again. It's the same 72, 73, 33, but now I'm sort of hopefully like wrapping my mind around the fact that, all right, a string is just an array of characters. And arrays, you can index into them using this new square bracket notation. So I can get at any one of these individual characters and, heck, convert it to an integer like we did in week 0, as I might. But let me get a little curious now, too. What else might be in the computer's memory? Well, let's toggle back to the depiction of these same things. Here might be how we originally implemented high with 3 variables, C1, C2, C3. Of course, that mapped to these decimal digits or equivalent, these binary values. But what was this looking like in memory? Literally, when you create a string in memory like this, string s equals quote unquote high, let's consider what's going on underneath the hood, so to speak. Well, as an abstraction, a string, it's HI exclamation point taking up, it would seem, 3 bytes, right? I've gotten rid of the bars there because if you think of a string as a type, I'm just going to use one big box of size 3. But technically, a string we've just revealed is an array, and the array is of size 3. So technically, if the string is called s bracket 0 will give you the first character, s bracket 1 the second, and s bracket 3 the third. But let me ask this question now. If this, at the end of the day, is the only thing in your computer, memory, and the ability, like a canvas, to draw zeros and ones or numbers or characters or whatever on it, but that's it. Like this is what your Mac and PC and phone ultimately reduce to. Suppose that I'm running a piece of software, like a text messenger, and now I write down by exclamation point. Well, where might that go in memory? Well, it might go here, B-Y-E. And then the next thing I type might go here, 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 and so forth. My memory just might get filled up over time with things that you or someone else are typing. But then how does the computer know if potentially B-Y-E exclamation point is right after H-I exclamation point, where one string ends and the next one begins? Right? All we have are bytes or zeros and ones. So if you were designing this, how would you implement some kind of delimiter between the two or figure out what the length of a string is? What do you think? OK, so the right answer is use a null character. And for those who don't know, what does that mean? Yeah, so it's a special character. Let me describe it as a sentinel character. Humans decided some time ago that, you know what, if we want to delineate where one string ends and where the next one begins, we just need some special symbol. And the symbol they'll use is generally written as \0. This is just shorthand notation for literally 8 0 bits. 0, 0, 0, 0, 0, 0, 0, 0. And the nickname for 8 0 bits in this context is null, N-U-L, so to speak. And we can actually see this as follows. If you look at the corresponding decimal digits, like you could do by just doing out the math or doing the conversion like we've done in code, you would see for storing high, 72, 73, 33, but then one extra byte that's sort of invisibly there, but that is all zeros. And now I've just written it as the decimal number 0. The implication of this is that the computer is apparently using not 3 bytes to store a word like high, but 4 bytes. whatever the length of the string is, plus 1 for this special sentinel value that demarcates the end of the string. So we might draw it like this instead. And this character is, again, sort of pronounced null, or written N-U-L. So that's all, right? If humans at the end of the day just have this canvas of memory, they just needed to decide, all right, well, how do we distinguish one string from another? Because it's a lot easier with chars individually. It's a lot easier with ints. It's even easier with floats. Why? Because per that chart earlier, every character is always 1 byte. Every int is always 4 bytes. Every long is always 8 bytes. How long is a string? Well, hi is 1, 2, 3 with an exclamation point. Bi is 1, 2, 3, 4 with an exclamation point. David is D-A-V-I-D 5 without an exclamation point. And so a string can be any number of bytes long. So you somehow need to draw a line in the sand to separate in memory one string from another. So what's the implication of this? Well, let me go back to code here. Let's actually poke around. This is a bit dangerous, but I'm going to start looking at memory locations past my string here. So let me go ahead and recompile make hi. Whoops. What did I do here? Oh, I forgot a format code. Let me add one more %i. Now let me go ahead and rerun make hi, /hi, enter. There it is. So you can actually see in the computer, unbeknownst to you previously, that there's indeed something else going on there. And if I were to make like one other variant of this program, let's get rid of just this one word, and maybe let's have 2. So let me give myself another string called t, for instance, just as common convention, with by exclamation point. Let me then go ahead and print out with %s, s, and let me also print out with %s, whoops, printf, print out t as well. Let me just recompile this program. And obviously, the this is what happens when I go too fast. All right, third mistake today. Close quote, as I was missing, make hi. Fourth mistake today, make hi, /hi. OK, voila. Now we have a program that's printing both hi and bi, only so that we can consider what's going on in the computer's memory. If s is storing hi, and apparently one bonus byte that demarcates the end of that string, bi is apparently going to fit into the location directly after. And it's wrapping around, but that's just an artist's rendition here. But bi, B-Y-E exclamation point, is taking up 1, 2, 3, 4, plus a 5th byte as well. Whew. All right, any questions on this underlying representation of strings? And we'll contextualize this before long so that this isn't just like, OK, who really cares? This is going to be the source of actually implementing things, in fact, for problem set 2, like cryptography and encryption and actually scrambling actual human messages. But some questions first.
So if normally if you were to like not use string, you would just make a character array. You have to declare how many characters there are, or you know how many characters are going to be there.
A good question, too. And let me summarize as if we were instead to use chars all the time, we would indeed have to know in advance how many chars you want for a given string that you're storing. How then does something like getString work? Because when CS50 wrote the getString function, we obviously don't know how long the words are going to be that you all are typing in. It turns out next 2 weeks from now, we'll see that getString uses a technique known as dynamic memory allocation, and it's going to grow or shrink the array automatically for you. But more on that soon. Other questions? Good question. Why are we using a null value? Isn't it wasting a byte? Yes. But I claim there's really no other way to distinguish the end of one string from the start of another unless we make some sort of notation, so to speak, in memory. All we have at the end of the day inside of a computer are bits. Therefore, all we can do is spend those bits in some creative way to solve this problem. And so we're minimally going to spend 1 byte to solve this problem here. Yeah? If you don't, how does the computer know to move to a next line when you have a \n? So \n, even though it looks like 2 characters, it's actually stored as just 1 byte in the computer's memory. There's a mapping between it and an actual number. And you can see that, for instance, on the ASCII chart from the other day. So would that be stored in the It would be. If I had put a \n in my code here, right after the exclamation point here and here, that would actually shift everything in memory because we would need to make room for a \n here and another one over here. So it would take 2 more bytes, exactly. Other questions?
So if I exclamation point is written in binary and it has to be 2 as 72, 73, 33. If we are to write those numbers in a string and convert them into binary, how would the computer know what's 72 and what's 8?
And what's the last thing you said? It's context sensitive. So if at the end of the day, all we're storing is these numbers like 72, 73, 33, recall that it's up to the program to decide based on context how to interpret them. And I simplified this story in week 0, saying that Photoshop interprets them as RGB colors. And iMessage, or a text messaging program, interprets them as letters. And Excel interprets them as numbers. How those programs do it is by way of variables like string and int and float. And in fact, later this semester, we'll see a data type via which you can represent a color as a triple of numbers, and red value, a green value, and a blue value. So we'll see other data types as well. Yeah?
Yeah, it seems easy enough to just add a null thing at the end of a word. So why do we have integers and long integers? Why can't we make everything variable in its data size?
Really interesting question. Why could we not just make all data types variable in size? And some languages, some libraries do exactly this. C is an older language, and so because memory was expensive, memory was limited, the reality was you gain benefits from just standardizing the size of these things. You also get performance increases in the sense that if you know every int is 4 bytes, you can very quickly, and we'll see this next week, jump from integer to another in memory just by adding 4 inside of those square brackets. You can very quickly poke around, whereas if you had variable length numbers, you would have to kind of follow, looking for the end of it. Follow. You would have to look at more locations in memory. So that's a topic we'll come back to. But it was generally for efficiency. And other question, yeah?
Why not store the null character at like position 0 and start indexing 21?
Good question. Why not store the... OK, same one. Why not store the null character at the beginning? You could... let's see. Why not store it at the beginning? You could do that. You could absolutely... Well, could you do this? If you were to do that at the beginning... Short answer, no. OK, now I retract that. No, because I finally thought of a problem with this. If you store it at the beginning instead, we'll see in just a moment how you can actually write code to figure out where the end of a string is. And the problem there is you wouldn't necessarily know if you eventually hit a 0 at the end of the string because it's the number 0 in the context of like Excel using some memory, or if it's the context of some other data type altogether. So the fact that we've standardized, strings as ending with null means that we can reliably distinguish one variable from another in memory. And that's actually a perfect segue now to actually using this primitive to building up our own code that manipulates these things at a lower level. So let me go ahead and do this. Let me create a new file this time called length. And let's just use this basic idea to figure out what the length of a string is after it's been stored in a variable here. So let's go ahead and do this. Let me include both the CS50 header and the standard IO header. Give myself int main void again here. And inside of main, let me go ahead and do this. Let me prompt the user for a string s. And I'll ask them for a string like their name here. And then let me go ahead and actually, let me name it more verbosely name this time. And now let me go ahead and do this. Let me iterate over every character in this string in order to figure out what its length is. So initially, I'm going to go ahead and say this. Int length equals 0, because I don't know what it is yet. So we're going to start at 0. And then while the following is true, while, do I want to do this? Let me change this to I, just for clarity. Let me go ahead and do this. While name bracket I does not equal that special null character. So I typed it on the slide as NUL, but you don't write NUL in code. You actually use its numeric equivalent, which is \0 in single quotes. While name bracket I does not equal the null character, I'm going to go ahead and increment I to I++. And then down here, I'm going to print out the value of I to see what we actually get. Printing out the value of I. All right, so what's going to happen here? Let me go ahead and run make length Fortunately, no errors. /length, and let me type in something like HI exclamation point, enter. And I get 3. Let me try by exclamation point, enter. And I get 4. Let me try my own name, David, enter. 5, and so forth. So what's actually going on here? Well, it seems that by way of this for loop, we are specifying a local variable called I, initialized to 0, because we're figuring out the length of the string as we go. I'm then asking the question, does location 0, that is I, in the name string, which we now know is an array, does it not equal \0? Because if it doesn't, that means it's an actual character like H or B or D. So let's increment I. Then let's come back around to line 9 and let's ask the question again. Now I equals 1. So does name bracket 1 not equal \0? Well, if it doesn't, and it won't if it's an I or a Y or an A based on what I typed in, we're going to increment I once more. Fast forward to the end of the story. Once I get to the end of the string, technically one space past the end of the string, name bracket I will equal \0. So I don't increment I anymore. I end up just printing the result. So what we seem to have here with some low-level C code, just this while loop, is a program that figures out the length of a given string that's been typed in. Let's practice our abstraction and decompose this into maybe a helper function here. Let me actually grab all of this code here, and let me assume for the sake of discussion for a moment that I could just call a function now called string length. And the length of the string is name that I want to get. And then I'll go ahead and print out, just as before, with %i, the length of that string. So now I'm abstracting away this notion of figuring out the length of a string. That's an opportunity for me to create my own function. If I want to create a function called string length, I'll claim that I want to take a string as input. And what should I have this function return as its return type? What should getString presumably return? Yeah. An int, right? An int makes sense. Float really wouldn't make sense because we're measuring things that are integers, in this case, the length of something. So indeed, let's have it return an int. I can pretty much use the same code as before. So I'm just going to paste what I cut earlier in the file. And the only thing I have to change here is the name of the variable. Because now this function, I decided kind of arbitrarily that I'm going to call it s, just to be more generic. So I'm going to look at s bracket I at each location. And I don't want to print it at the end. This would be a side effect. What's the line of code I should include here if I actually want to hand back the total length? Yeah. Say again? Return I in this case. So I'm going to go ahead and return I, not print it, because now my main function can use the return value stored in length and print it on the next line itself. I just need a prototype. So that's my one forgivable copy paste here. I'm going to rerun make length. Hopefully I didn't screw up. I didn't. /length. I'll type in hi. Whoops. I'll type in hi again. That works. I'll type in by again, and so forth. All right. So now we have a function that determines the length of a string. Well, it turns out we didn't actually need this all along. It turns out that we can get rid of my own custom string length function here. I can definitely delete the whole implementation down here because it turns out in a file called string.h, which is a new header file today, we actually have access to a function called, more succinctly, strlen, S-T-R-L-E-N, which literally does that. This is a function that comes with C, albeit in the string.h header file, and it does pretty much what we just implemented manually. So here's an example of, admittedly, a wheel we just reinvented, but no more. We don't have to do that. And how do you know what kinds of functions exist? Well, let me actually pop out of my browser here to a website that is a CS50's incarnation of what are called manual pages. It turns out that on a lot of systems, Macs and Unix and Linux systems, including the Visual Studio Code instance that we have in the cloud, there are publicly accessible manual pages for functions. They tend to be written very expertly in a way that's not very beginner friendly. So what we have here at manual.cs50.io is CS50's version of manual pages that have this less comfortable mode that give you a sort of cheat sheet of very frequently used helpful functions in C. And we've translated the sort of expert notation to things that a beginner can understand. So for instance, let me go ahead and search for string up at the top here. You'll see that There's documentation for our own getString function. But more interestingly, down here, there's a whole bunch of string-related functions that we haven't even seen most of yet. But there's indeed one here called strlen, calculate the length of a string. And so if I actually go to strlen here, I'll see some less comfortable documentation for this function. And the way a manual page typically works, whether in CS50's format or any other system, is you see typically a synopsis of what header files you need to use the function. So you would copy paste these couple of lines here. You see what the prototype is of the function so that you know what its inputs are, if any, and its outputs are, if any. Then down below you might see a description, which in this case is pretty straightforward. This function calculates the length of s. Then you see what the return value is, if any, and you might even see an example, like this one that we've whipped up here. So these manual pages, which are, again, accessible here, and we'll link to these in the problem sets moving forward, are pretty much the place to start when you want to figure out, has a wheel been invented already? Is there a function that might help me solve some problem set problem so that I don't have to really get into the weeds of doing all of those lower level steps as I've had? Sometimes the answer is going to be yes. Sometimes it's going to be no. But again, the point of our having just done this together is to reveal that even the functions you start taking for granted, they all reduce to some of these basic building blocks. At the end of the day, this is all that's inside of your computer, is zeros and ones. We're just learning now how to harness those and how to manipulate them ourselves. All right, any questions here on this? Any questions at all? Yeah. Good question. Is it so common that you would have to specify it or not? You do need to include its header files, because that's where all of those prototypes are. You don't need to worry about linking it in with -l anything. And in fact, moving forward, you do not ever need to worry about linking in libraries when compiling your code. We, the staff, have configured Make to do all of that for you automatically. We want you to understand that it is doing it, but we'll take care of all of the -ls for you. But the onus is on you for the prototypes and the header files. Other questions on these representations or techniques? Yeah? Oh, good question. If you were to have a string with actual spaces in it, that is multiple words, what would the computer actually do? Well, for this, let me go to ASCIIchart.com, which is just a random website that's my go-to for the first 127 characters of ASCII. This is, in fact, what we had a screenshot of the other day. And if you look here, it's a little non-obvious, but SP is space. If a computer were to store a space, it would actually store the decimal number 32, or technically the pattern of zeros and ones that represent the number 32. All of the US English keys that you might type on a keyboard can be represented with a number. And using Unicode, can you express even things like emojis and other languages? Yeah?
Are only strings followed by a null number? Or let's say we had a series of numbers, would each one of them be accompanied by a null?
Good question. Only strings are accompanied by nulls at the end, because every other data type we've talked about thus far is of well-defined finite length. 1 byte for char, 4 bytes for ints, and so forth. If we think back, though, to last week, we did end the week with a couple of problems. Integer overflow, because like 4 bytes, heck, even 8 bytes is sometimes not enough. We also talked about floating point imprecision. Thankfully, in the world of scientific computing and financial computing, there are libraries you can use that draw inspiration from this idea of a string. And they might use 9 bytes for an integer value, or maybe 20 bytes. You can count really high, but they will then start to manage that memory for you. And what they're really probably doing is just grabbing a whole bunch of bytes and somehow remembering how long the sequence of bytes is. That's how these higher level libraries work too. All right, this has been a lot. Let's take one more break here. We'll do like a 7-minute break here. And when we come back, we'll flesh out a few more details. All right. So we just saw strlen as an example of a function that comes in the string library. Let's start to take more of these library functions out for a spin, so we're not relying only on the built-ins that we saw last week. Let me go ahead and switch over to VS Code, and let me create a file called, say, string.h, just to kind of apply this lesson learned as follows. Let me go ahead and include CS50.h. Let me include standard.io.h, and this new thing, string.h as well at the top. I'm going to do the usual int main void here. And then in this program, suppose for the sake of discussion that I didn't know about %s for printf, or heck, maybe early on there was no %s format code, and so there was no easy way to print strings. Well, at least if we know that strings are just arrays of characters, we could use %c as a workaround, so to speak, a solution to that sort of contrived problem. So let me ask myself for a string s by using getString here, and I'll ask the user for some input. And then let me go ahead and print out, say, output. And all I want to do is print back out what the user typed. Now, the simplest way to do this, of course, is going to be like last week, printf %s, and plug in the s, and we're done. But again, for the sake of discussion, I forgot about, or someone didn't implement %s. So how else could we do this? Well, in pseudocode, or in English, like what's the gist of how we could solve this problem? Printing out the string s on the screen without using %s. How might we go about solving this? Just in English, high level. What would your pseudocode look like? Yeah? OK, so just print each letter, and maybe more precisely, like some kind of loop. Like let's iterate over all of the characters in s and print one at a time. So how can I do that? Well, for int I gets 0 is kind of the go-to starting point for most loops. I is less than, OK, how long do I want to iterate? Well, it's going to depend on what I type in, but that's why we have Sterling now. So iterate up to the length of s, and then increment I with ++ on each iteration. And then let's just print out %c with no new line, because I want everything on the same line, whatever the character is at s bracket I. And then at the very end, I'll give myself that new line just to move the cursor down to the next line so the $sign's not in a weird place. All right, so let's see. If I didn't screw up any of the code, make string, enter. So far, so good. String, and let me type in something like hi, enter. And I see output of hi 2. Let me do it once more with by, enter. And that works too. Notice I very deliberately and quickly gave myself 2 spaces here and 1 space here just because I literally wanted these things to line up properly, and input is shorter than output. But that was just a deliberate formatting detail. So this code is correct, which is a claim I've made before, but it's not well designed. Now, it is well designed in that I'm using someone else's library function. Like I've not reinvented a wheel. There's no line 15 or below. I didn't implement string length myself. So I'm at least kind of practicing what I've preached. But there's still an imperfection, a suboptimality. This one's really subtle, though. And you have to think about how loops work. What am I doing that's not super efficient? Yeah, and back? Yeah, this is a little subtle, but if you think back to the basic definition of a for loop, and recall when I highlighted things last week, what happens? Well, the first thing is that I gets set to 0. Then we check the condition. How do we check the condition? We call Sterling on s. We get back an answer like 3 if it's hi exclamation point. And 0 is less than 3, so that's fine. And then we print out the character. Then we increment I from 0 to 1. We recheck the condition. How do I recheck the condition? I call Sterling of s, get back the same answer, 3, compare 3 against 1. We're still good, so we print out another character. I gets incremented again. I is now 2. We check the condition. What's the condition? Well, what's the string length of s? It's still 3. 2 is still less than 3. So I keep asking the same question sort of stupidly because the string is presumably never changing in length. And indeed, every time I check that condition, that function is going to get called. And every time the answer for hi is going to be 3, 3, 3. So it's a marginal sort of suboptimality, but I could do better, right? Like don't ask multiple times questions that you can remember the answer to. So how could I remember the answer to this question and ask it just once? How could I remember the answer to this question? Let me see. Yeah, back there? So stored in a variable, right? That's been our answer most any time we want to keep something around. So how could I do this? Well, I could do something like this. Int maybe length equals Sterling of s. Then I can just change this function call, so to speak. And let me refix my spelling here. Let me fix this to be now comparing against length. And this is now OK, because now Sterling is only called once on line 9. And I'm reusing the value of that variable, aka length, again and again and again. So that's more efficient. Turns out that for loops actually let you declare multiple variables at once. So we can actually do this a little more elegantly. all in one line. And this is just now some syntactic improvement. I could actually do something like this. N equals strlen of s. And then I could just say n here. Or I could call it length. But heck, while I'm being succinct, I'm just going to use n for number. So now it's just a marginal change. But I've now declared two variables inside of my loop, I and n. I is set to 0. N is set to the string length of s. But now, hereafter, all of my condition checks are just I less than n, and n is never now changing. All right, so a marginal improvement there. Now that I've used this new function, let's use some other functions that might be of interest. Let me go ahead and write a quick program here that maybe like capitalizes the beginning of, changes to uppercase some string that the user types in. So let me go ahead and code a file called uppercase.c. Up here, I'll use my new friends, CS50.h and standard.io and string.h. So standard.io and string.h. So just as before, int main void. And then inside of main, what I'm going to do this time is let's ask the user for a string s using getString, asking them for the before value. And then let me go ahead and just print out something like after, so that it just so I can see what the uppercase version thereof is. And then after this, let me go ahead and do the following. For int I equals 0. Oh, let's practice that same lesson. So n equals the string length of s. I is less than n, I plus plus. So really nothing new really fundamentally yet. How do I now convert characters from lowercase if they are to uppercase? In other words, if I type in hi, hi in lowercase, I want my program now to uppercase everything to capital H, capital I. Well, how can I go about doing this? Well, you might recall that there is this ASCII chart. So let's just consult this real quick. On the ASCIIchart.com, we've looked at this last week. Notice that A, capital A, is 65. Capital B is 66. Capital C is 67. And heck, here's lowercase a, lowercase b, lowercase c, and that's 97, 98, 99. And if I actually do some math, there's like a distance of 32. Right? So if I want to go from uppercase to lowercase, I can do 65 plus 32 will give me 97. And that actually works out across the board for everything else. 66 plus 32 gets me to 98 or lowercase b. Or conversely, if you have a lowercase a and its value is 97, subtract 32 and boom, you have capital A. So, all right, there's some arithmetic here involved. But now that we know that strings are just arrays and we know that characters which are in those arrays are just binary representations of numbers, I think we can manipulate a few of these things as follows. Let me go back to my program here and first ask the question, if the current character in the array during this loop is lowercase, let's force it to uppercase. So how am I going to do that? If the character at s bracket I, the current location in the array, is greater than or equal to lowercase a and s bracket I is less than or equal to lowercase z. Kind of a weird Boolean expression, but completely legitimate. Because in this array s is a whole bunch of characters that the humans typed in, because that's what a string is. Greater than or equal to a might be a little nonsensical, because when have you ever compared numbers to letters? But we know from week 0, lowercase a is 97. Lowercase z is, what is it, 1? I don't even remember. What is that? 132, we know. And so that would allow us to answer the question, is the current letter lowercase? All right, so let me go ahead here and answer that question. If it is, what do I want to print out? I don't want to print out the letter itself. I want to print out the letter minus 32, right? Because if it happens to be a lowercase a, 97, 97 minus 32 gives me 65, which is uppercase a. And I know that just from having stared at that chart in the past. Else, if the character is not between little a and big A, I'm just going to print out the character itself by printing s bracket I. And at the very end of this, I'm going to go ahead and print out a new line just to move the cursor to the next line. So again, it's a little wordy, but this loop here, which I borrowed from our code previously, just iterates over the string, aka array, character by character through its length. This line 11 here is just asking the question if that current character, the ith character of s, is greater than or equal to little a and less than or equal to little z, that is between 97 and 132, then we're going to go ahead and force it to uppercase instead. All right, and let me go ahead and zoom out here for just a second. And sorry, I misspoke. 122, which is what you might have said. There's only 26 letters. So 122 is little z. Let me go ahead now and compile and run this program. So make uppercase, / uppercase, and let me type in high and lowercase, enter, and there's the capitalized version thereof. Let me do it again with like my own name in lowercase, and now it's capitalized as well. Well, what could we do to improve this? Well, you know what? Let's stop reinventing wheels. Let's go to the manual pages. So let me go here and search for something like, I don't know, lowercase. And there I go. I did some autocomplete here. Our little search box is saying that, OK, there's an isLower function. Check whether a character is lowercase. Well, how do I use this? Well, let me check isLower. Now I see the actual man page for this function. Now we see include ctype.h. So that's the header file I need to include. This is the prototype for isLower. It apparently takes a char as input and returns an int, which is a little weird. I feel like isLower should return true or false. So let's scroll down to the description and return value. It returns, oh, this is interesting, and this is a convention in C. This function returns a non-zero int if C is a lowercase letter, and 0 if C is not a lowercase letter. So it returns non-zero. So like 1, -1, something that's not 0 if C is a lowercase letter, and 0 if it is not a lowercase letter. So how can we use this building block? Let me go back to my code here. Let me add this file, include ctype.h. And down here, let me get rid of this cryptic expression, which was kind of painful to come up with, and just ask this: is lower s bracket I? That should actually work. But why? Well, is lower, again, returns a non-zero value if the letter is lowercase. Well, what does that mean? That means it could return 1, it could return -1, it could return 50 or -50. It's actually not precisely defined. Why? Just because. Like, this was a common convention to use 0 to represent false and use any other value to represent true. And so it turns out that inside of Boolean expressions, if you put a value, like a function call like this, that returns 0, that's going to be equivalent to false. It's like the answer being no, it is not lower. But you can also just, in parentheses, put the name of the function and its arguments and not compare it against anything, because we could do something like this. Well, if it's not equal to 0, then it must be lowercase, because that's the definition. If it returns a non-zero value, it's lowercase. But a more succinct way to do that is just a bit more like English. If it's is lower, then print out the character -32. So this would be the common way of using one of these is functions to check if the answer is true or false. OK, well, we might be done. OK. No, so it's not necessarily 1. It would be incorrect to check for 1 or -1 or anything else. You want to check for the opposite of 0, so not equals 0, or more succinctly, like I did by just putting it into parentheses. Let me see what happens here. So this is great, but some of you might have spotted a better solution to this problem a moment ago when we were on the manual pages searching for things related to lowercase. What might be another building block we can employ here? Based on what's on the screen here. Yeah. So to upper, there's a function that would literally do the uppercasing for me, so I don't have to get into the weeds of like -32 plus 32. I don't have to consult that chart. Someone has solved this problem for me in the past. And let's see if I can actually get back to it. There we go. Let me go ahead now and use this. So instead of doing s bracket I -32, let's use a function that someone else wrote and just say to upper s bracket I. And now it's going to do the solution for me. So if I rerun make uppercase and then do slowly dot uppercase, type in high, now it's working as expected. And honestly, if I read the documentation for to upper by actually going back to its man page or manual page, what you'll see is that it says if it's lowercase, it will return the uppercase version thereof. If it's not lowercase, it's already uppercase, it's punctuation, it will just return the original character, which means thanks to this function, I can actually tighten this up significantly, get rid of all of my conditional there, and just print out the to upper return value and leave it to whoever wrote that function to figure out if something's uppercase or lowercase. All right. Questions on these kinds of tricks? Again, it all reduces to like week 0 basics, but we're just building these abstractions on top. Yeah? Yes, unfortunately, no. There is no easy way in C to say, give me everything. That was for historically performance reasons. They want you to be explicit as to what you want to include. In other languages like Python, Java, one of which we'll see later this term, you can say, give me everything. But that actually tends to be best practice because it can actually slow down execution or compilation of your code. Yeah? Does to-upper accommodate special characters like punctuation? Yes. If I read the documentation more pedantically, we would see exactly that. It will properly hand me back an exclamation point, even if I passed it in. So if I do make uppercase here, and let me do uppercase, hi with an exclamation point, it's going to handle that too, and just pass it through unchanged. Yeah? Really good question, too. No, we do not have access to a function that at least comes with C or comes with CS50's library that will just force the whole thing to uppercase. In C, that's actually easier said than done. In Python, it's trivial. So stay tuned for another language that will let us do exactly that. All right, so what does this leave us with? There's just let's come full circle now to where we began today, where we were talking about those command line arguments. Recall that we talked about rm taking a command line argument, the file you want to delete. We talked about clang taking command line arguments that, again, modify the behavior of the program. How is it that maybe you and I can start to write programs that actually take command line arguments? Well, here is where I can finally explain why we've been typing int main void for the past week and just asking that you take on faith that it's just the way you do things. Well, by default in C, at least the most recent versions thereof, there's only 2 official ways to write main functions. You might see other formats online, but they're generally not consistent with the current specification. This, again, was sort of the boilerplate for the simplest function we might write last week. And recall that we've been doing this the whole time, void. What that void means for all of the programs I have written thus far and you have written thus far is that none of our programs that we've written take command line arguments. That's what the void there means. It turns out that main is the way you can specify that your program does, in fact, take command line arguments. That is, words after the command in your terminal window. If you want to actually not use getInt or getString, you want the human to be able to say something like, hello, David, and hit Enter, and just print hello, David on the screen. You can use command line arguments, words after the program name on your command line. So we're going to change this in a moment to be something more verbose, but something that's now a bit more familiar syntactically. If you change that void in main to be this incantation instead, int argc, comma, string argv, open bracket, close bracket, you are now giving yourself access to writing programs that take command line arguments. Argc, which stands for argument count, is going to be an integer that stores how many words the human typed at the prompt. The C automatically gives that to you. String argv stands for argument vector. That's going to be an array of all of the words that the human typed at the prompt. So with today's building block of an array, we have the ability now to let the humans type as many words or as few words as they want at the prompt. C is going to automatically put them in an array called argv, and it's going to tell us how many words there are in an int called argc. The int as the return type here we'll come back to in just a moment. Let's actually use now this definition to make maybe just a couple of simple programs, but in problem set 2 will we actually use this to control the behavior of your own code. Let me go ahead and code up a file called argv.0 just to keep it aptly named. Let me go ahead and include cs50.h. Let me go ahead and include, oops, that is not the right name of a program. Let's start that over. Let's go ahead and code up argv.c. And here we have include cs50.h, include standardio.h, int main not void. Let's actually say int argc string argv open bracket, close bracket. No numbers in between because you don't know in advance how many words the human's going to type at their prompt. Now let's go ahead and do this. Let's write a very simple program that just says, hello, David, hello, Carter, whoever the name is that gets typed, but not using getString. Let's instead have the human just type their name at the prompt, just like rm, just like clang, just like make. So it's just one and done when you hit enter. No additional prompts. Let me go ahead then and do this. Printf, quote unquote, hello, comma, and instead of world today, I want to print out whatever the human typed in. So let's go ahead and do this. argv bracket 0 for now. But I don't think this is quite what I want, because, of course, that's going to literally print out argv bracket 0 bracket. Then I need a placeholder. So let me put a %s here and then put that here. So if argv is an array, but it's an array of strings, then argv bracket 0 is itself a single string. And so it can be plugged into that %s placeholder. Let me go ahead and save my program. And let me go ahead and compile argv. So far, so good. Let me go ahead now and type in my name after the name of the program. So no getString. I'm literally typing an extra word, my own name, at the prompt. Enter. OK. It's apparently a little buggy in a couple of ways. I forgot my \n, but that's not a huge deal. But apparently, inside of argv is literally everything the humans typed in, including the name of the program. So logically, how do I print out hello David or hello so-and-so and not the actual name of the program? What needs to change here? Yeah. Yeah, so presumably index to 1 if that's the second thing I or whichever human has typed at the prompt. So let's do make argv again, /argv enter. Hello null. So this is another form of null. But this is user error now on my part. I didn't do exactly what I said I would. Yeah. Yeah, I forgot the parameter. So that's actually, I should probably deal with that somehow so that people aren't sort of breaking my program and printing out random things like null. But if I do say argv David, now you see hello David. I can get a little curious, like what's at location 2? Well, we can see make argv bracket /argv David, enter. All right, so just nothing is there. But it turns out in a couple weeks, we'll start really poking around memory and see if we can't crash programs deliberately, because nothing is technically stopping me from saying, oh, what's at location 2 million, for instance. We could really start to get curious. But for now, we'll do the right thing. But let's now make sure the human has typed in the right number of words. So let's say this. If argc equals 2, that is the name of the program and one more word after that, go ahead and trust that in argv1, as you proposed, is the person's name. Else, let's go ahead and just default here to something simple and basic, like, well, if we don't get a name from the user, just say hello world, like always. So now we're sort of programming defensively. This time the human, even if they screw up, they don't give us a name or they give us too many names, we're just going to say hello world because I now have some error handling here. Because again, argc is argument count, the number of words total typed at the command line. So make argv /argv. Let me make the same mistake as before. OK, I don't get this weird null behavior. I get something well defined. I could now do David. I could do David Malin, but that's not currently supported. I would need to alter my logic to support more than just 2 words after the prompt. So what's the point of this? At the moment, it's just a simple exercise to actually give myself a way of taking user input when they run the program. Because consider, it's just more convenient in this new command line interface world. If you had to use getString every time you compile your code, it'd be kind of annoying, right? You type make, then you might get a prompt. What would you like to make? Then you type in hello or cache or something else. Then you hit enter. It just really slows the process. But in this command line interface world, if you support command line arguments, then you can use these little tricks like scrolling up and down in your history with your arrow keys. You can just type commands more quickly because you can do it all at once. And you don't have to keep prompting the user more pedantically for more and more info. So any questions then on command line arguments, which finally reveals why we had void initially, but what more we can now put in main. That's how you take command line arguments. Yeah?
If you were to put, if you were to use argv and you were to put integers inside of it, would it still give you like a string? Would that still be considered a string or would it be considered like
Yes, if you were to type at the command line something like not a word, but something like the number 42, that would actually be treated as a string. Why? Because again, context matters. So if your program is currently manipulating memory as though it's characters or strings, whatever those patterns of zeros and ones are, they will be interpreted as ASCII text or Unicode text. If we therefore go to the chart here, that might make you wonder, well, then how do you distinguish numbers from letters in the context of something like chars and strings? Well, notice 65 is A, 97 is A, but also 49 is 1 and 50 is 2. So the designers of ASCII and then later Unicode realized, well, wait a minute. If we want to support programs that let you type things that look like numbers, even though they're not technically ints or floats, we need a way in ASCII and Unicode to represent even numbers. So here are your numbers. And it's a little silly that we have numbers representing other numbers. But again, if you're in the world of letters and characters, you got to come up with a mapping for everything. And notice here, here's the dot. Even if you were to represent 1.23 as a string or as characters, even the dot now is going to be represented as an ASCII character. So again, context here matters. All right, one final example to tease apart what this int is and what it's been doing here for so long. So I'm going to go ahead and add one bit of logic here to a new file that I'm going to call exit.c. So in exit.c, we're going to introduce something that are generally known as exit status. It turns out this is not a feature we've used yet, but it's just useful to know about, especially when automating tests of your own code, when it comes to figuring out if a program succeeded or failed. It turns out that main has one more feature we haven't leveraged, an ability to signal to the user whether something was successful or not. And that's by way of main's return value. So I'm going to go ahead and now modify this program as follows, like this. Suppose I want to write a similar program that requires that the user type a word at the prompt so that argc has to be 2 for whatever design purpose. If argc does not equal 2, I want to quit out of my program prematurely because I want to just insist that the user operate the program correctly. So I might give them an error message like missing command line argument \n. But now I want to quit out of the program. Now, how can I do that? The right way, quote unquote, to do that is to return a value from main. Now, it's a little weird because no one called main yet, right? Main just gets called automatically. But the convention is anytime something goes wrong in a program, you should return a non-zero value from main. 1 is fine as a go-to. We don't need to get into the weeds of having many different exit statuses, so to speak. But if you return 1, that is a clue to the system, the Mac, the PC, the cloud device, that something went wrong. Why? Because 1 is not 0. If everything works fine, like let's go ahead and print out hello, comma, %s, like before, quote unquote, argv bracket 1. So this is just a version of the program without an else. So this is the same as doing essentially an else here, like I did earlier. I want to signal to the computer that all is well. And so I return 0. But strictly speaking, if I'm already returning here, I don't technically need, if I really want to be nitpicky, I don't technically need the else because the only way I'm going to get to line 11 is if I didn't already return. So what's going on here? The only new thing here logically is that for the first time ever, I'm returning a value from main. That's something I could always have done because main has always been defined by us as taking an int as a return value. By default, main automatically, sort of secretly, returns 0 for you. If you've never once used the return keyword, which you probably haven't in main, it just automatically returns 0, and the system assumes that all went well. But now that we're starting to get a little more sophisticated with our code, and you know, the programmer, something went wrong, you can abort programs early. You can exit out of them by returning some other value besides 0 from main. And this is sort of fortuitous that it's an int, right? 0 means everything worked. Unfortunately, in programming, there are seemingly an infinite number of things that can go wrong. An int gives you 4 billion possible codes that you can use, aka exit statuses, to signify errors. So if you've ever on your Mac or PC gotten some weird pop-up that an error happened, sometimes there's a cryptic number in it. Maybe it's positive, maybe it's negative. It might say error code 123 or -49 or something like that. What you're generally seeing are these exit statuses, these return values for main in a program that someone at Microsoft or Apple or somewhere else wrote. Something went wrong. They are sort of unnecessarily showing you, the user, what the error code is, if only so that when you call customer support or submit a ticket, you can tell them what exit status you encountered, what error code you encountered. All right. Any questions then on exit statuses, which is the last of our new building blocks for now? Any questions at all? Yeah? No. The question is, can you do things again and again at the command line like you could with getString and getInt, which by default, recall, are automatically designed to keep prompting the user in their own loop until they give you a int or a float or the like. With command line arguments, no. You're going to get an error message, but then you're going to be returned to your prompt. And it's up to you to type it correctly the next time. Good question. Yeah? If you do not return a value explicitly, main will automatically return 0 for you. Like, that is the way C simply works. So it's not strictly necessary. But now that we're starting to return values explicitly, if something goes wrong, it would be good practice to also start returning a value for main when something goes right and there are no errors, in fact. So let's now get out of the weeds and contextualize this for some actual problems that we'll be solving in the coming days by way of problem set 2 and beyond. So here, for instance, is a problem that you might think back to when you were a kid, the readability of some text or some book, the grade level at which some book is written. If you're a young student, you might read at a first grade level or third grade level in the US. Or if you're in college, presumably you're reading at a university level of text. But what does it mean for text, like in a book or in an essay or something like that, to correspond to some kind of grade level? Well, here's a quote, a title of a childhood book: 1 fish, 2 fish, red fish, blue fish. What might the grade level be for a book that has words like this? Maybe when you were a kid, or if you have siblings still reading these things, what might the grade level of this thing be? Any guesses? Yeah. Sorry, again? Before grade 1 is in fact correct. So that's for really young kids. And why is that? Well, let's consider these are actually pretty simple phrases, right? 1 fish, 2 fish, red. I mean, there's not even verbs in these sentences. They're just nouns and adjectives and very short sentences. And so that might be a heuristic we could use when analyzing text. Well, if the words are kind of short, the sentences are kind of short, everything's very simple, that's probably a very young or early grade level. And so by one formulation, it might indeed be even before grade 1 for someone quite young. How about this? Mr. and Mrs. Dursley of number 4, Privet Drive, were proud to say that they were perfectly normal. Thank you very much. They were the last people you would expect to be involved in anything strange or mysterious because they just didn't hold with such nonsense. And onward. All right, what grade level is this book at? OK, I heard 3rd. 7th, 5th, OK, all over the place. But grade 7, according to one particular measure, and whether or not we can debate exactly what age you were when you read this, and maybe you're feeling ahead of your time or behind now. But here, we have a snippet of text. What makes this text assume an older audience, a more mature audience, a higher grade level, would you think? Yeah. Yeah, it's longer, different types of words. There's commas now and phrases and so forth. So there's just some kind of sophistication to this. So it turns out for the upcoming problem set, among the things you'll do is take as input texts like this and analyze them, considering, well, how many words are in the text? How many sentences are in the text? How many letters are in the text? And use those according to a well-defined formula to prescribe what exactly the grade level of some actual text, there's the 3rd, might actually be. Well, what else are we going to do in the coming days? Well, I've alluded to this notion of cryptography in the past, this notion of scrambling information in such a way that you can hide the contents of a message from someone who might otherwise intercept it, right? The earliest form of this might also be when you're younger and you're in class and you're passing a note from one person to another, from yourself to someone else. You don't want to just necessarily write a note in English or some other written language. You might want to scramble it somehow or encrypt it. Maybe you change the A's to a B and the B's to a C so that if the teacher snaps it up and intercepts it, they can't actually understand what it is you've written because it's encrypted. Now, so long as your friend, the recipient of this note, knows how you manipulated it, how you added or subtracted sort of letters to each other, they can decrypt it, which is to say reverse that process. So formally, in the world of cryptography and computer science, this is just another problem to solve. Your input, though, when you have a message you want to send securely, is what's generally known as plain text. There's some algorithm that's going to then encipher or encrypt that information into what's called ciphertext, which is the scrambled version that theoretically can get safely intercepted, and your message has not been spoiled unless that intercept actually knows what algorithm you used inside of this process. So that would be generally known as a cipher. These ciphers typically take, though, not one input, but two. If, for instance, your cipher is as simple as A becomes B, B becomes C, C becomes D, dot, 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 Z becomes A, you're essentially adding 1 to every letter and encrypting it. Now, that would be what we call the key. You and the recipient both have to agree, presumably before class in advance, what number you're going to use that day to rotate or change all of these letters by. Because when you add 1, they, upon receiving your ciphertext, have to subtract 1 to get back the answer. So for instance, if the input plain text is high, as before, and the key is 1, the ciphertext using this simple rotational algorithm, otherwise known as a Caesar cipher, might be IJ exclamation point. So it's similar, but it's at least scrambled at first glance. And unless the teacher really cares to figure out what algorithm are they using today or what key are they using today, it's probably sufficiently secure for your purposes. How do you reverse the process? Well, your friend gets this and reverses it by -1. So I becomes H, J becomes I, and things like punctuation remain untouched, at least in this scheme. So let's consider one final example here. If the input to the algorithm is UIJT XBT DT50, and the key this time is -1, such that now B should become A, and C should become B, and A should become Z. So we're going in the other direction. How might we analyze this? Well, if we spread all the letters out, and we start from left to right, and we start subtracting one letter, U becomes T, I becomes H, J becomes I, T becomes S, X becomes W, A was D, T. This was CS50. We'll see you next time. This is CS50, and this is already week 3. And even as we've gotten much more into the minutiae of programming and some of the C stuff that we've been doing is all the more cryptic looking, recall that at the end of the day, like everything we've been doing ultimately fits into this model. So keep that in mind, particularly as things seem like they're getting more complicated, more sophisticated. It's just a process of learning a new language that ultimately lets us express this process. And of course, last week we really went into the weeds of like how inputs and outputs are represented. And this thing here, a photograph thereof, is called what? This is what? RAM, I heard. Random access memory, or just generally known as memory. And recall that we looked at one of these little black chips that contains all of the bytes, all of the bits ultimately. It's just kind of a grid, sort of an artist's grid that allows us to think about every one of these memory locations as just having a number or an address, so to speak. Like this might be byte number 0, and then 1, and then 2, and then maybe way down here again, something like 2 billion if you have 2 gigabytes of memory. And so as we did that, we started to explore how we could use this canvas to create kind of our own information, our own inputs and outputs, not just the basics like ints and floats and so forth, but we also talked about strings. And what is a string as you now know it? How would you describe, in layperson's terms, a string? Yeah, over there. An array of characters. And an array, meanwhile, let's go there. How might someone else define an array in more familiar now terms? What would be an array? Yeah. An indexed set of things, not bad. And I think a key characteristic to keep in mind with an array is that it does actually pertain to memory. And it's contiguous memory. Byte after byte after byte is what constitutes an array. And we'll see in a couple of weeks' time that there's actually more interesting ways to use this same primitive canvas to stitch together things that are sort of two-directional even, that have some kind of shape to them. But for now, all we've talked about is arrays and just using these things from left to right, top to bottom, contiguously to represent information. So today, we'll consider still an array, but we won't focus so much on representation of strings or other data types. We'll actually now focus on the other part of that process of inputs becoming outputs, namely the thing in the middle, algorithms. But we have to keep in mind, even though every time we've looked at an array thus far, certainly on the board like this, you as a human certainly have the luxury of just kind of eyeballing the whole thing with a bird's eye view and seeing where all of those numbers are. If I asked you where a particular number is, like 0, odds are your eyes would go right to where it is, and boom, problem solved in sort of one step. But the catch is, with a computer that has this memory, even though you, the human, can sort of see everything at once, a computer cannot. It's better to think of your computer's memory, your phone's memory, or more specifically, an array of memory like this, as really being a set of closed doors, not unlike lockers in a school. And only by opening each of those doors can the computer actually see what's in there, which is to say that the computer, unlike you, doesn't have this bird's eye view of all of the data in all these locations. It has to much more methodically look here, maybe look here, maybe look here, and so forth, in order to find something. Now, fortunately, we already have some building blocks, loops, conditions, Boolean expressions, and the like, where you could imagine writing some code that very methodically goes from left to right, or right to left, or something more sophisticated that actually finds something you're looking for. And just remember that the conventions we've had since last week now is that these arrays are 0 indexed, so to speak. To be 0 indexed just means that the data type starts counting from 0. So this is location 0, 1, 2, 3, 4, 5, 6. And notice, even though there are 7 total doors here, the rightmost one, of course, is called 6, just because we've started counting at 0. So in the general case, if you had n doors or n bytes of memory, 0 would always be at the left, and n minus 1 would always be at the right. That's sort of a generalization of just thinking about this kind of convention. All right, so let's revisit the problem that we started the whole term off with in week 0, which was this notion of searching. And what does it mean to search for something? Well, to find information. And this, of course, is omnipresent. Anytime you take out your phone, you're searching for a friend's contact. Anytime you pull up a browser, you're Googling for this or that. So search is kind of one of the most omnipresent topics and features of any device these days. So let's consider how the Googles, the Apples, the Microsofts of the world are implementing something as seemingly familiar as this. So here might be the problem statement. We want some input to become some output. What's that input going to be? Maybe it's a bunch of closed doors like this, out of which we want to get back an answer. True or false? Is something we're looking for there or not? You could imagine taking this one step further and trying to find where is the thing you're looking for. But for now, let's just take one bite out of the problem. Can we tell ourselves true or false is some number behind one of these doors or lockers in memory? But before we go there and start talking about ways to do that, that is algorithms, let's consider how we might lay the foundation of like comparing whether one algorithm is better than another. We talked about correctness, and it sort of goes without saying that any code you write, any algorithm you implement had better be correct. Otherwise, what's the point if it doesn't give you the right answers? But we also talked about design. And in your own words, like, what do we mean when we say a program is better designed at this stage than another? How do you think about this notion of design now? Yeah, in the middle? OK, so easier to understand. I like that. Other thoughts? Yeah. Efficiency. And what do you mean by efficiency, precisely? Nice. It doesn't use up too much memory, and it isn't redundant. So you can think about design along a few of these axes, sort of the quality of the code, but also the quality of the performance. And as our programs get bigger and more sophisticated and and just longer, those kinds of things are really going to matter. And in the real world, if you start writing code not just by yourself but with someone else, getting the design right is just going to make it easier to collaborate and ultimately produce right code with just higher probability. So let's consider how we might focus on exactly the second characteristic, the efficiency of an algorithm. And the way we might talk about the efficiency of algorithms, just how fast or how slow they are, is in terms of their running time. That is to say, when they're running, how much time do they take? And we might measure this in seconds or milliseconds or minutes or just some number of steps in the general case, because presumably fewer steps, to your point, is better than more steps. So how might we think about running times? Well, there's one general notation we should define today. So computer scientists tend to describe the running time of an algorithm, or a piece of code for that matter, in terms of what's called big O notation. This is literally a capitalized O, a big O. And this generally means that the running time of some algorithm is on the order of such and such, where such and such we'll see is just going to be a very simple mathematical formula. It's kind of a way of waving your hands mathematically to convey the idea of just how fast or how slow some algorithm or code is without getting into the weeds of like, it took this many milliseconds or this many specific number of steps. So you might recall then from week 0, I even introduced this picture, but without much context. At the time, we just used this to compare those phone book algorithms. Recall that this red straight line was the first algorithm, one page at a time. The yellow line that's still straight differed how, if you recall. That line represented what alternative algorithm? Looking out and back. What is that second algorithm? Yeah, over there. 2 pages at a time, which was almost correct so long as we potentially double back a page if maybe we go a little too far in the phone book. So it had a potential bug, but arguably solvable. This last algorithm, though, was the so-called divide and conquer strategy, where I sort of unnecessarily tore the phone book in half, and then in half, and then in half, which, dramatic as that was unnecessarily, it actually took significantly bigger bites out of the problem, like 500 pages the first time, another 250, another 125, versus just 1 or 2 bytes at a time. And so we described its running time as this picture there, though I didn't use that expression at the time, running times. But indeed, time to solve might be measured just abstractly in some unit of measure, seconds, milliseconds, minutes, pages, via this y-axis here. So let's now slap some numbers on this. If we had n pages in that phone book, n just representing a generic number, the first algorithm here we might describe as taking n steps. Second algorithm we might describe as taking n divided by 2 steps, maybe give or take 1 if we have to double back, but generally n divided by 2. And then this thing, if you remember your logarithms, was sort of a fundamentally different formula, log base 2 of n, or just log of n for short. So this is sort of a fundamentally different formula. But what's noteworthy is that these first 2 algorithms, even though, yes, the second algorithm was hands down faster, I mean, literally twice as fast, when you start to zoom out, and if I increase my y-axis and x-axis, these first two start to look awfully similar to one another. And if we keep zooming out, zooming out, zooming out, as n gets really large, that is, the x-axis gets really long, these first 2 algorithms start to become essentially the same. And so this is where computer scientists use big O notation. Instead of saying specifically this algorithm takes n steps and this one n divided by 2, a computer scientist would say, each of those algorithms takes on the order of n steps, or on the order of n over 2. But you know what? On the order of n over 2 is pretty much the same when n gets really large as being equivalent to big O of n itself. So yes, in practice, it's obviously fewer steps to move twice as fast. But in the big picture, when n becomes a million, a billion, the numbers are already so darn big at that point that these are, as the shapes of these curves imply, pretty much functionally equivalent. But this one still looks better and better as n gets large because it's rising so much less quickly. And so here, a computer scientist would say that that third algorithm was on the order of, that is, big O of log n. And you don't have to bother with the base because it's a smaller mathematical detail that is also just in some sense a constant multiplicative factor. So in short, what are the takeaways here? This is just a new vocabulary that we'll start to use when we just want to describe the running time of an algorithm. To make this more real, if any of you have implemented a for loop at this point in any of your code, and that for loop iterated n times, where maybe n was the height of your pyramid, or maybe n was something else that you wanted to do n times, you wrote code, or you implemented an algorithm that operated in big O of n time, if you will. So this is just a way now to retroactively start describing with somewhat mathematical notation what we've been doing in practice for a while now. So here's a list of commonly seen running times in the real world. This is not a thorough list, because you could come up with an infinite number of mathematical formulas, certainly. But the common ones we'll discuss and you will see in your own code probably reduced to this list here. And if you were to study more computer science theory, this list would get longer and longer. But for now, these are sort of the most familiar ones that we'll soon see. All right, two other pieces of vocabulary, if you will, before we start to use this stuff. So this, a big omega, capital omega symbol, is used now to describe a lower bound on the running time of an algorithm. So to be clear, big O is on the order of, that is, an upper bound on how many steps an algorithm might take. On the order of so many steps. If you want to talk, though, from the other perspective, well, how few steps might my algorithm take? Maybe in the so-called best case, it'd be nice if we had a notation to just describe what a lower bound is. Because some algorithms might be super fast in these so-called best cases. So the symbology is almost the same, but we replace the big O with the big omega. So to be clear, big O describes an upper bound, and omega describes a lower bound. And we'll see examples of this before long. And then lastly, last one here, big theta is used by a computer scientist when you have a case where both the upper bound on an algorithm's running time is the same as the lower bound. You can then describe it in one breath as being in theta of such and such, instead of saying it's in big O and in omega of something else. All right, so out of context, sort of seemingly cryptic symbols, but all they refer to is upper bounds, lower bounds, or when they happen to be one and the same. And we'll now introduce over time examples of how we might actually apply these to concrete problems. But first, let me pause to see if there's any questions. Any questions here? Any questions? I see pointing somewhere. Where are you pointing to? Over here. There we go. OK, sorry. Very bright. Smaller n functions move faster. So yes, if you have something like n, that takes only n steps. If you have a formula like n squared, just by nature of the math, that would take more steps and therefore be slower. So the larger the mathematical expression, the slower your algorithm is, because the more time or more steps that it takes. You want your n function, so to speak, to be small, yes. And in fact, the holy grail, so to speak, would be this last one here, either in big O notation or even theta. When an algorithm is on the order of a single step, that means it literally takes constant time, 1 step or maybe 10 steps, 100 steps, but a fixed constant number of steps. That's the best, because even as the phone book gets bigger, even as the data set you're searching gets larger and larger, if something only takes a finite number of steps constantly, then it doesn't matter how big the data set actually gets. Questions as well on these notations? Yep, thank you for the pointing. This is actually very helpful. I'm seeing pointing this way. What is the input to each of these functions? It is an expression of how many steps an algorithm takes. So in fact, let me go ahead and make this more concrete with an actual example here, if we could. So on stage here, we have 7 lockers, which represent, if you will, an array of memory. And this array of memory is maybe storing 7 integers that we might actually want to search for. And if we want to search for these values, how might we go about doing this? Well, for this, why don't we make things interesting? Would a volunteer like to come on up? Have to be masked and on the internet if you are comfortable. Both of the, oh, there's someone putting their friend's hand up in back? Yes? OK, come on down. And in just a moment, our brave volunteer is going to help me find a specific number in the data set that we have here on the screen. So come on down, and I'll get things ready for you in advance here. Come on down. Nice to meet. And what is your name? Manira? Namira. Nice to meet. Come on over. So here we have for Namira 7 lockers or an array of memory. And behind each of these doors is a number. And the goal, quite simply, is given this array of memory as input to return true or false is the number I care about actually there. So suppose I care about the number 0. What would be the simplest, most correct algorithm you could apply in order to find us the number 0? OK, try opening the first one. All right, and maybe just step aside so the audience can see. I think you have not found 0 yet. OK, so keep the door open. Let's move on to your next choice. Second door, sure. Oh, go ahead, second door. Well, let's keep it simple. Let's just move from left to right, sort of searching our way. And what do you see there? Up 6, not 0. How about the next door? All right, also not working out so well yet, but that's OK. If you want to go on to the next, we're still looking for 0. All right, I see a 2. All right, not so good yet. Let's keep going. Next door. 2, 7, no. OK, next door. No, that's a 5. All right, very well done. OK. All right, so I kind of set you up for a fairly slow algorithm, but let me just ask you to describe what is it you did by following the steps I gave you. You went one by one to each character, and if you want to talk into here. So you went one by each character. And would you say that algorithm, left to right, is correct?
No.
No?
Or yes, in this scenario.
OK, yes in this scenario. Why are you hesitating? What's going
Because
through
it's
your
not
mind?
the most efficient way to do it.
OK, good. So we see a contrast here between correctness and design. I mean, I do think it was correct, because even though it was slow, you eventually found 0. But it took some number of steps. So in fact, this would be an algorithm. It has a name called linear search. And Namira, as you did, you kind of walked along a line going from left to right. Now, let me ask, if you had gone from right to left, would the algorithm have been fundamentally better?
Yes.
OK, and why?
Because the 0 is here in the first scenario. But then if it was like the 0's in the middle, it wouldn't have been.
Yeah, and so here's sort of where the right way to do things becomes a little less obvious. You would absolutely have given yourself a better result if you had just happened to start from the right, or if I had pointed you to start over there. But the catch is, if I asked her to find another number, like the number 8, well, that would have backfired. And this time, it would have taken longer to find that number because it's way over here instead. And so in the general case, going left to right, or heck, right to left, is probably as correct as you can get, because if you know nothing about the order of these numbers, and indeed, they seem to be fairly random. Some of them are smaller, some of them are bigger. There doesn't seem to be rhyme or reason. Linear search is about as good as you can do when you don't know anything a priori about the numbers. So I have a little thank you gift here, a little CS50 stress ball. A round of applause for our first volunteer. Thank you so much. Let's try to formalize what I just described as linear search, because indeed, no matter which end Namir had started on, I could have kind of changed up the problem to make sure that it appears to be running slow. But it is correct. If 0 were among those doors, she absolutely would have found it, and indeed did. So let's now try to translate what we did into what we might call, again, pseudocode, as from week 0. So with pseudocode, we just need a terse English-like or any language syntax to describe what we did. So here might be one formulation of what Namira did. For each door, from left to right, if the number is behind the door, return true. Else, at the very end of the program, you would return false by default. And now you got lucky, and by the 7th door, Namira had indeed returned true by saying, well, there is the 0. But let's consider if this pseudocode is now correct, an accurate translation. First of all, normally when we've seen ifs, we might see an if-else, and yet down here, return false is aligned with the 4. Why did I not indent the return false? Or put another way, why did I not do if number is behind door, return true, else return false? Why would that version of this code have been problematic? Way in back? OK, I'm not sure it's because of redundancy. Let me go ahead and just make this explicit. If I had instead done else, return false, I don't think it's so much redundancy that I'd be worried about. Let me bounce somewhere else. Yeah, in front.
Would you be returning false for the entire list after
Yeah, I would be returning false for, even though I'd only looked at, or Namir had only looked at one element, and it would have been as though if all of these doors were still closed, she opens this up and sees, nope, this is not 0, return false. That would give me an incorrect result, because obviously at that stage in the algorithm, she wouldn't have even looked through any of the other doors. So just the original indentation of this, if you will, without the else, is correct, because only if I get to the bottom of this algorithm, or this pseudocode, does it make sense to conclude at that point, once she's gone through all of the doors, that nope, there's in fact the number I'm looking for is in fact not actually there. So how might we consider now the running time of this algorithm? We have a few different types of vocabulary now. And if we consider now how we might think about this, let's start to translate it from sort of higher level pseudocode to something a little lower level, right? We've been writing code using n and loops and the like. So let's take this higher level pseudocode and now just kind of get a middle ground between English and C. Let me propose that we think about this version of the same algorithm as being a little more pedantic. For I from 0 to n minus 1, if number behind doors bracket I return true, otherwise, at the end of the program, return false. Now, I'm kind of mixing English and C here, but that's reasonable if the reader is familiar with C or some similar language. And notice this pattern here. This is a way of just saying in pseudocode, give myself a variable called I, start at 0, and then just count up to n minus 1. And recall, n minus 1 is not one shy of the end of the array. N minus 1 is the end of the array because, again, we started counting at 0. So this is a very common way of expressing this kind of loop from the left all the way to the right of an array. Doors, I'm kind of implicitly treating as the name of this array, like it's a variable from last week that I defined as being an array of integers in this case. So doors bracket I means that when I is 0, it's this location. When I is 1, it's this. When I is 7, or more generally 6, or more generally n minus 1, that's this location here. So same idea, but a translation of it. So now let's consider what the running time of this algorithm is. If we have this menu of possible answers to this question, how efficient or inefficient is this algorithm? Let's take a look in the context of this pseudocode. We don't even have to bother going all the way to C. How do we go about analyzing each of these steps? Well, let's consider this. This outermost loop here, for I from 0 to n minus 1, that line of code is going to execute how many times? How many times will that loop execute? Let me give folks this moment to think on it. How many times is that going to loop here? Yeah, over there. N times, right? Because it's from 0 to n minus 1. And if it's a little weird to think in from 0 to n minus 1, this is essentially the same mathematically as from 1 to n. And that's perhaps a little more obviously, more intuitively, n total steps. So I might just make a note to myself, this loop is going to operate n times. What about these inner steps? Well, how many steps or seconds does it take to ask a question? If the number you're looking for is behind doors bracket I, well, as Namina did, that's kind of like one step, right? She opened the door and boom. All right, maybe it's 2 steps, but it's a constant number of steps. So this is some constant number of steps. Let's just call it 1 for simplicity. How many steps or seconds does it take to return true? I don't know exactly in the computer's memory, but that feels like a single step, just return true. So if this takes 1 step, this takes 1 step, but only if the condition is true, it looks like you're doing a constant number of things n times, or maybe you're doing one additional step. So in short, the only thing that really matters here in terms of the efficiency or inefficiency of the algorithm is what are you doing again and again and again, because that's obviously the thing that's going to add up. Doing one thing or 2 things a constant number of times, not a big deal. But looping, that's going to add up over time because the more doors there are, the bigger n is going to be and the more steps that's going to take. Which is all to say, if you were to describe roughly how many steps does this algorithm take in big O notation, what might your instincts say? How many steps is this algorithm on the order of given n doors or n integers? Yeah? Say again? Big O of n. And indeed, that's going to be the case here. Why? Because you're essentially, at the end of the day, doing n things as an upper bound on running time. And that's, in fact, exactly what happened with Amina. She had to look at all n lockers before finally getting to the right answer. But what if she got lucky and the number we were looking for was not at the end of the array, but was at the beginning of the array? How might we think about that? Well, we have a nomenclature for this too, of course, omega notation. Remember, omega notation is a lower bound. So given this menu of possible running times for lower bounds on an algorithm, what might the omega notation be for Amina's linear search? Omega of 1, and why that? Right, because if just by chance she gets lucky and the number she's looking for is right there where she begins the algorithm, that's it. It's one step, maybe it's two steps if you have to like unlock the door and open it, but it's a constant number of steps. And the way we describe constant number of steps is just with a single number like 1. So the omega notation for linear search might be omega of 1, because in the best case, she might just get the number right from the get-go. But in the worst case, we need to talk about the upper bound, which might indeed be big O of n. So again, there's this way now of talking symbolically about best cases and worst cases, or lower bounds and upper bounds. Theta notation, just as a little trivia now, is it applicable based on the definition I gave earlier? OK, no, because you only take out the theta notation when those two bounds, upper and lower, happen to be the same for shorthand notation, if you will. So it suffices here to talk about just big O and omega notation. Well, what if we are a little smarter about this? Let me go ahead and sort of semi-secretly here rearrange these numbers. But first, how about one other volunteer? One other volunteer. To be comfortable with your mask and your being on the internet. How about over here? Yes, you want to come on down? All right, come on down. And don't look at what I'm doing, because I'm going to take your time, and don't look up this way, because I need a moment to rearrange all of the numbers. And actually, if you could stay right there before coming up, just an awkward few seconds while I finish hiding the numbers behind these doors for you. I will be right with you. Actually, if do you want to warm up the crowd for a moment, and I'll be right back? So you want to introduce yourself?
Yeah. Hi, guys. I'm Rave. Yeah.
All right. I think I am ready. Thank you for stalling there.
Of course.
And I didn't catch your name. What was your name?
I'm Rave.
Sorry?
Rave like a party.
Rave. OK,
Yeah.
Nice to meet you. Come on over. So Rave has kindly volunteered now, and I'm going to give you an additional advantage this time.
Okay.
Unbeknownst to you, I now took numbers behind the doors, but I sorted them for you. So they're not in the same random order like they were for Namina. You now have the advantage to know that the numbers are sorted from small to big.
Okay.
Given that, and given perhaps what we talked about in week 0 with the phone book,
Yes.
where might you propose we begin the story this time? With which locker?
To find 0.
Let's find number 6 this time. Let's make things interesting.
Okay. I'll start in the middle.
OK, so the middle, there's 7 total. So
Okay.
that would be right here. Go ahead,
Yes.
open that up. And you find, sadly, the number 5. So
Yes.
what do you know now?
I know to go up.
Okay.
Yeah, okay. Yep.
All right, so and just to keep it uniform, just like I did, I opened to the right half of the phone book.
Yes.
Let's keep it similar. Yeah.
All right.
All right, and a little too far, even though I know you wanted to go one over.
All good, all good.
And now we're going to go which direction?
Over here in the middle.
All right, and voila, the number 6. All right, so very nicely done. A little stress ball for you as well. Thank you again. So here we see, by nature of the locker door still being open, sort of an artifact of the greater efficiency, it would seem, of this algorithm, because now that Rave was given the assumption that these numbers are sorted from small on the left to large on the right, she was able to apply that same divide and conquer algorithm from week 0, which we're now going to give a name, binary search. And simply by starting in the middle and realizing, OK, too small, then by going to the right half and realizing, oh, went a little too far, then by going to the left half, which Rave able to find in just 3 steps instead of 7, the number 6 in this case that we were actually searching for. So you can see that this would seem to be more efficient. Let's consider for just a moment, is it correct if I had used different numbers but still sorted them from left to right, would it still have worked? this algorithm? You're nodding your head. Can I call on you? Like, why would it still have worked, do you think? Yeah, so long as the numbers are always in the same order from left to right, or heck, they could even be in reverse order, so long as it's consistent, the decisions that Rave was making, if greater than, else if less than, would guide us to the solution no matter what, and it would seem to take fewer steps. So if we consider now the pseudocode for this algorithm, let's take a look how we might describe binary search. So binary search we might describe with something like this. If the number is behind the middle door, which is where Rave began, then we can just return true. Else, if the number is less than the middle door, so if 6 is less than whatever's behind the middle door, then Rave would have searched the left half. Else, if the number is greater than the middle door, Rave would have searched the right half. Else, if there are no doors, and we'll see in a moment why I put this up top just to keep things clean, if there's no doors, what should Rave have presumably returned immediately if I gave her no lockers to work with? Just return false. But this is an important case to consider, because if in the process of searching by locker, we might have whittled down the problem from 7 doors to 3 doors to 1 door to 0 doors. And at that point, we might have had no doors left to search. So we have to naturally have a scenario for just considering if there were no doors. So it's not to say that maybe I don't give Rave any doors to begin with, but as she divides and divides and divides, if she runs out of lockers to ask those questions of, or a few weeks ago, if I ran out of phone book pages to tear in half, I too might have had to return false, as in this case. So how can we now describe this a little more like C, just to give ourselves a variable to start thinking and talking about? Well, I might talk about doors as being an array. And so if I want to express the middle door, I could just, in pseudocode, say doors bracket middle. I'm assuming that someone has done the math to figure out what the middle door is, but that's easy enough to do. And then doors, if the number we're looking for is less than doors bracket middle, then search doors 0 through doors middle minus 1. So again, this is a more pedantic way of taking what's a pretty intuitive idea, search the left half, search the right half, but start to now describe it in terms of actual indices or indexes, like we did with our array notation. The last scenario, of course, is if the number is greater than the doors bracket middle, then Rave would have wanted to search the middle door plus 1, so 1 over, through doors n minus 1. Through n minus 1. So again, just a way of sort of describing a little more syntactically what it is that's going on. So how might we translate this now into big O notation? Well, in the worst case, how many steps total might Rave's binary search algorithm have taken? Given 7 doors, or given more generically n doors, how many times could she go left or go right before finding herself with 1 or no doors left? What's the way to think about that? Yeah, in the middle? Log n. So there's log n again. And even if you're not feeling wholly comfortable with your logarithm still, pretty much in programming and in computer science more generally, anytime we talk about some algorithm that's dividing and conquering in half, in half, in half, or any other multiple, it's probably involving logarithms in some sense. And log base n essentially refers to the number of times you can divide n by 2 until you bottom out at just a single door, or equivalently 0 doors left. So log n. So we might say that indeed binary search is in big O of log n, because the door that Rave opened last, this one, happened to be 3 doors away. And actually, if you do the math here, that roughly works out to be exactly that case. If we add 1, it's sort of out of 7 doors, or roughly 8, we were able to search it in just 3 total steps. What about omega notation, though? Like in the best case, Rave might have gotten lucky. She opened the door, and there it is. So how might we describe a lower bound on the running time of binary search? Yeah. Say again? Omega of 1. So here, too, we see that in some cases, binary search and linear search, like they're pretty equivalent. And so this is why sometimes it's sometimes compelling to consider both the best case and the worst case, because honestly, in general, who really cares if you just get lucky once in a while and your algorithm is super fast? what you probably care about is what's the worst case? How long are my users? How long am I going to be sitting there watching some spinning hourglass or a beach ball trying to give myself an answer to a pretty big problem? Well, odds are you're going to generally care about big O notation. So indeed, moving forward, we'll generally talk about the running time of algorithms, often in terms of big O, a little less so in terms of omega. But understanding the range can be important depending on the nature of the data that you're going to actually be given here. All right, let me pause and see if there is any questions. Any questions here? Yes, thank you.
So this method is clearly more efficient, but it requires that the information is all like compiled in a certain order. How do you ensure that you can compile information in a particular order at scale?
Yeah, that's a really good question. And if I can generalize it, how do you guarantee that you can do this at scale? Which algorithm is better? I've sort of led us down this road of implying that Rave's second algorithm, binary search, is better because it's so much faster. It's log of n in the worst case instead of big O of n. But Rave was given an advantage when she came up here in that the doors were already sorted. And so that sort of invites the question, well, given a whole bunch of random data, either a small data set or heck, something Google size with millions, billions of pieces of data, should you sort it first from smallest to largest and then search? Or should you just dive right in and search it linearly? Like, how might you think about that? If you are Google, for instance, and you've got millions, billions of web pages, should they just go with linear search because it's always going to work, even though it might be slow? Or should they invest the time in sorting all of that data? We'll see how in a bit. And then search it more efficiently. Like, how do you decide between those options? Yeah, if you had to sort the data first, and we don't yet formally know how to do this, but obviously as humans we could probably figure it out, you do have to look at all of the data anyway. And so you're sort of wasting your time if you're sorting it only then to go and search it. But maybe it depends a bit more. Like, that's absolutely right. And if you're just searching for one thing in life, then that's probably a waste of time to sort it and then search it because you're just adding to the process. But what's another scenario in which you might not worry about that? Whereby it might make sense to sort it and then search. Yeah? Yeah, exactly. So if your problem is a Google-like problem where you have more than just one user who's searching for more than just one web page, probably you should incur the cost up front and sort the whole thing because every subsequent request thereafter is going to be faster, faster, faster because it's going to be Rave's algorithm of binary search, binary search, binary search that's going to add up to be way fewer steps than doing linear search multiple times. So again, kind of depends on the use case and kind of depends on how important it is. And this happens even in like real world context. I think back always to graduate school when I was writing some code to analyze some large data set. And honestly, it was actually easier at the time for me to write pretty inefficient, but hopefully correct code. Because you know what? I could just go to sleep for 8 hours and let it analyze this really big data set. I didn't have to bother writing more complex code to sort it just to run it more efficiently. Why? Because I was the only user, and I only needed to run these queries once. And so this was kind of a reasonable approach. Reasonable until I woke up 8 hours later and my code was incorrect. And now I had to spend another 8 hours rerunning it after fixing it. But even there, you see an example where what is your most precious resource? Is it time to run the code? Is it time to write the code? Is it the amount of memory the computer is using? These are all resources we'll start to talk about because it really depends on what your goals are. Any questions then on upper bounds, lower bounds, or each of these two searches, linear or binary? Yeah? When analyzing running time, does the sorting step count? If you want it to, if you actually do it. At the moment, it did not apply. I just gave Rave the luxury of knowing that the data was sorted. But if I really wanted to charge her for the amount of time it took to find that number 6, I should have added the time to sort plus the time to search. And in fact, that's a road we'll go down. Why don't we go ahead and pace ourselves as before? Let's take a 10-minute break here. And when we come back, we'll write some actual code. So we've seen a couple searches, linear search and binary search, which to be fair, we saw back in week 0. But let's actually translate at least one of those now to some code using this building block from last week where we can actually define an array if we want, like an array of integers called numbers. So let me switch over to VS Code here. Let me go ahead and start a program called numbers.c. And in numbers.c, let me go ahead here and how about let's include our familiar header file. So CS50.h. I'll include standard.io.h so that we can get input and print input if we want. And now I'm going to go ahead and give myself int main void. No command line arguments today, so I'll leave that as void. And I'm going to go ahead and give myself an array of, how about 7 numbers? So I'll call it int numbers 7. And then I can fill this array with numbers like numbers bracket 0 can be the number 4. And numbers bracket 1 can be the number 6. And numbers bracket 2 can be the number 8. And this is the same list that we saw with Namina a bit ago, where it was 4, then 6, then 8. But you know what? There's actually another syntax I can show you here. If you know in advance in a C program that you want an array of certain values, and you know, therefore, how many of those values you want, you can actually do this little trick using curly braces. You can say, don't worry about how big this is. It's going to be implicit by way of these curly braces. Here I can do 4, 6, 8, 2, 7, 5, 0. Close curly brace. So it's a somewhat new use of curly braces. But this has the effect of giving me an array called numbers, inside of which are a whole bunch of integers. How many? The compiler can infer it from whatever inside these curly braces. And it seems to be of size 1, 2, 3, 4, 5, 6, 7. And all 7 elements will be initialized with 4, 6, 8, 2, 7, 5, 0 respectively. So just a minor optimization code-wise to tighten up what would have otherwise been like 8 separate lines of code. Now let's go ahead and implement linear search, as we called it. And you can do this in a bunch of ways, but I'm going to do it like this. For int I gets 0, I is less than 7, I plus plus. Then inside of my loop, I'm going to ask the question, well, if the numbers at location I equals, as we asked of Namina, the number 0, then I'm going to go ahead and do something like printf found \n. And then I'm going to return 0 just because of last week's discussion of returning a value from main when all is well. I'm going to return 0 by convention just to signal that indeed I found what I'm looking for. Otherwise, on what line do I want to go and add a printf like not found and return something other than 0? Right? I don't think I want an else here per our pseudocode earlier. So on what line would you prefer I sort of insert a default scenario of not found and I'll return an error? Yeah, over here. At the Nice. So at the end of the for loop, because you want to give the program, or our volunteer earlier, a chance to go through all of the doors, all of the numbers. But if you go through the whole thing, through the whole loop, at the very end, you probably just want to conclude not found \n and then return something like +1 just to signify that an error happened. And again, this was a minor detail last week. Anytime main is successful, the programming convention is to return 0. That means all is well. And if something goes wrong, like you didn't find what you're looking for, you might return something other than 0, like +1, maybe +2, or even negative numbers if you want. All right, well, let me go ahead and save this. Let me do make numbers. Hopefully no syntax errors. All good so far. /numbers, enter. All right, and it's found, as I would hope it would be. And just as a little check, let's search for something that's definitely not there, like the number -1. Let me go ahead and recompile the code with make numbers. Let me rerun the code with /numbers, and hopefully, phew, OK, not found. So proof by example seems to be working correctly. But let's make things a little more interesting now. Right now, I'm using just an array of integers. Let me go ahead and introduce maybe an array of strings instead. And maybe this time I'll store a bunch of names, and not just integers, but actual strings of names. So how might I do this? Well, let me go back to my code here. I'm going to switch us over to maybe a file called names.c. And in here, I'll go ahead and include CS50.h. I'll include standard.io.h. And I'm going to go ahead and, for now, include a new friend from last week, string.h, which gives me some string-related functionality. Int main void, because I'm not going to bother with any command line arguments for now. And now if I want an array of strings, I could do something like this, string names bracket 7. And then I could start doing like before. Names bracket 0 could be someone like Bill. And names bracket 1 could be someone like Charlie, and so forth. But there's this new improvement I can make. Let me just let the compiler figure out how many names there are. And using curly braces, I'll do Bill, and then Charlie, and then Fred, and then George, and then Ginny, and then Percy, and then Ron, if there's the pattern there. All right, so now I have these 7 names as strings. Let's do something similar. So for int I gets 0, I is less than 7, as before, I++ as before. And inside of the loop, let's this time check for the string in question. And suppose we're searching for Ron arbitrarily. He is there, so we should eventually find him. Let me go ahead and say if names bracket I equals quote unquote Ron, then inside of my if condition, I'm going to say printf found, just like before. And I'm going to return 0, just because all is well. And I'm going to take your advice from the get-go this time. And at the end of the loop, print out not found, because if I get this far, I have not printed found, and I have not returned already. So I'm just going to go ahead and return 1, and after printing not found. All right, let me go ahead and cross my fingers as always, make names this time. And it doesn't seem to like my code here. This is perhaps a new error that you might not have seen yet in names.c line 11. So that's this line here, my if condition. Result of comparison against a string literal is unspecified. Use an explicit string comparison function instead. I mean, that's kind of a mouthful. And first time you see it, you're probably not going to know how to make sense of that. But it does kind of draw our attention to something being awry with the equality checking here, with equals and Ron. And here's where, again, we've been telling sort of a white lie for the past couple of weeks. Strings are a thing in C. Strings are a thing in programming. But recall from last week, I did disclaim there's no such thing as a string data type technically, because it's not a primitive in the way an int and a float and a bool are that are sort of built into the language. You can't just use equals to compare two strings. You actually have to use a special function that's in this header file we talked briefly about last week. In that header file was string length or strlang. But there's other functions instead as well. Let me, in fact, go ahead and open up the manual pages. And if we go to string.h, let me scroll down a bit. In string.h, you can perhaps infer what function will probably take the place of equals for today. What do we want to use? Yeah. So strcomp, strcmp, which apparently compares two strings. And if I click on that, we'll see more information. And indeed, if I click on strcomp, we'll see under the synopsis that, OK, I need to use the CS50 header file and string.h, as I already have. Here is its prototype, which is telling me that strcomp takes two strings, s1 and s2, that are presumably going to be compared. And it returns an integer, which is interesting. So let's read on. The description of this function is that it compares two strings case sensitively. So uppercase or lowercase matters, just FYI. And then let's look at the return value here. The return value of this function returns an int less than 0 if s1 comes before s2, 0 if s1 is the same as s2, or an int greater than 0 if s1 comes after s2. So the reason that this function returns an integer and not just a bool, true or false, is that it actually will allow us to sort these things eventually. Because if you can tell me if two strings come in this order, or they're the same, you need 3 possible return values. And a bool, of course, only gives you 2, but an int gives you like 4 billion, even though we just need the 3. So 0 or a positive number or a negative number is what this function returns. And the documentation goes on to explain what we mean by ASCII-betical order. Recall that capital A is 65, capital B is 66, and it's those underlying ASCII or Unicode numbers that a computer uses to figure out whether something comes before it or after it, like in a dictionary. But for our purposes now, we only care about equality. So I'm going to go ahead and do this. If I want to compare names bracket I against Ron, I use strcompare, or strcomp, names bracket I, comma, quote unquote Ron. So it's a little more involved than actually using equals, which does work for integers, longs, and certain other values. But for strings, it turns out we need to use a more powerful function. Why? Well, last week, recall what a string really is. It's an array of characters. And so whereas you can use equals for single characters, strcomp as we'll eventually see, is going to compare multiple characters for us. There's more logic there. There's a loop needed, and that's why it comes with the string library, but it doesn't just work out of the box with equals equals alone. That would literally be comparing two things, not two arrays of things. And we'll come back to this next week as to what's really going on under the hood. So let me go ahead and fix one bug that I just realized I made. I want to check if the return value of stir compare is equal to 0, because per the documentation, that meant they're the same. All right, let me go ahead and make names this time. Now it compiles /names, enter, found. And just as a sanity check, let's check someone outside the family. Searching now for Hermione after recompiling the code, after rerunning the code, and she's not, in fact, found. So here's just a similar implementation of linear search, not for integers this time, but instead for strings. The subtlety really being we need a helper function, stir compare, to actually do the legwork for us of comparing two arrays of characters. All right, questions on either of these implementations? Yeah, in the middle? Good question. If I had not fixed what I claimed was a mistake earlier, and I did this, and we saw an example of this last week, actually. If a function returns an integer, be it negative or positive or 0, when you get back 0, the expression, the Boolean expression, will be considered false. So 0 equals false always. If a function returns any positive number or any negative number, that's going to be interpreted as true, even if it's positive or negative, whether it's 1, -1, 2, -2. And so if I did this, this would be saying the opposite. So if I were to say this, if stir compare of names bracket I and Hermione, that's implicitly like saying this does not equal 0. Or it means sort of is true, but you don't want to check for true because, again, we're comparing integers here. So the reason I did 0 here in this case is that it explicitly checks for the return value that means they're the same. And yeah, follow up? Yes, you might not have seen this yet, but you can express the equivalent, because if you want to check if this is false, you can actually use an exclamation point, known as a bang in programming, that inverts the meaning. So false becomes true, true becomes false. So this would be another way of expressing it. This is arguably a worse design, though, because the documentation explicitly says you should be checking for 0 or a positive value or a negative value. And this little trick, while correct, and I think you can make a reasonable case for it, sort of hides that detail. And I would argue instead for the first way, checking for equals equals 0 instead. And if that's a little subtle, not to worry. We'll come back to sort of little syntactic tricks like that before long. Other questions on linear search in these two forms? Is there another hand? Or hands, two hands? No? OK, just holler if I missed. So let's now actually take this one step further. Suppose that we want to write a program that maybe implements something a little more like a phone book that has both names and numbers, and not just integers, but actual phone numbers. Well, we could escalate things like this. We could now have two arrays, one called names, one called numbers. And I'm going to use strings for the numbers now, the phone numbers, because in most communities, phone numbers might have dashes, pluses, parentheses. So something that really looks more like a string, even though we call it a phone number. Probably don't want to use an int lest we throw away those kinds of details. So let me switch back to VS Code here. And let's do one more program, this one in a file called phonebook.c. And now let me go ahead and do the same. Let me include CS50.h. Let me include standardio.h. And let me include string.h. I'm going to instead, again, do int main void. And then inside of my program, I'm going to give myself two arrays the efficient way this time. String names will be just two of us this time. How about Carter and me? And then I'll give myself, oops, typo already. If I want this to be an array, I don't have to specify the number. The compiler can count for me, but I do need the square brackets. Then for numbers, I'm again going to use a string array specifying with the curly braces that, how about Carter can be at 1, 617, 495, 1000. And how about my own number here, 1, 949, 468. Oh, pattern appearing, 2750. Will be mine. Why mine? Well, I've just kind of lined things up. So Carter's number is apparently first in this array, and I'm claiming that he'll be first in this array, respectively. David, will be the second in the names array, and second in the numbers array. If you want to have a little fun with programming, feel free to text or call me sometime at that number. So now let's actually use this data in some way. Let's go ahead and actually search for my own name and number here. So let me do for int I gets 0. There's 2 of us this time, so I less than 2. And then I plus plus as before. And now I'm going to practice what I preached earlier, and I'm going to use stir compare to find my name in this case. And I'm going to say if stir comp of names bracket I equals quote unquote David, and that equals 0, meaning they're the same, then just as before, I'm going to go ahead and print something out. But this time I'm going to make the program more useful, not just say found or not found. Now I'm implementing a phone book, like the Contacts app on iOS or Android. So I'm going to say something like quote unquote found %s \n, and then actually plug in numbers bracket I to correspond to the current names bracket I, and then I'll return 0 as before. And then down here, if we get all the way through the loop and David's not there for some reason, I'm going to print as before not found and then return 1. So let me go ahead and compile this with make phonebook /phonebook, and it seems to have found the number. So this code, I'm going to claim, is correct. It's kind of stupid because I've just made a phone book or a contacts app that only supports 2 people. They're only going to be me and Carter. This would be like downloading the contacts app on a phone, and you can only call 2 people in the world. There's no ability to add names or edit things. That, of course, could come later using getString or something else. But for now, for the sake of discussion, I've just hard-coded 2 names and 2 numbers. But for what it does, I claim this is correct. It's going to find me and print out my number. But is it well designed? Let's start to now consider if we're not just using arrays, but are we using them well? We started to use them last week, but are we using them well this week? And what might I even mean by using an array well or designing this program well? Any critiques or concerns with why this might not be the best road for us to be going down when I want to implement something like a phone book with pieces of information? It seems all too vulnerable to just mistakes. For instance, if I screw up the actual number of names in the names array such that it's now more or less than is in the numbers array, or vice versa, it feels like there's not a tight relationship between those pieces of data. And it just sort of is trusting on the honor system that anytime I use names bracket I, that it lines up with numbers bracket I. And that's fine. If you're the one writing the code, you're probably not going to really screw this up. But if you start collaborating with someone else, or the program's getting much, much longer, the odds that you or your colleagues remember that you're sort of just trusting that names and numbers line up like this is going to fail eventually. Someone's not going to realize that, and just the code is going to break, and you're going to start outputting the wrong numbers for names. Which is to say, it'd be much nicer if we could somehow couple these 2 pieces of data, names and numbers, a little more tightly together, so that you're not just trusting that these 2 independent variables, names and numbers, have this kind of relationship with themselves. So let's consider how we might solve this. A new feature today that we'll introduce is generally known as a data structure. In C, we have the ability to invent our own data types, if you will, data types that the authors of C decades ago just didn't envision or just didn't think were necessary because we can implement them ourselves. Similar to Scratch, just as you could create custom puzzle pieces, or in C you can create custom functions, so in C can you create your own types of data that go beyond the built-in ints and floats and even strings. You can make, for instance, a person data type, or a candidate data type in the context of elections, or a person data type more generically that might have a name and a number. So how might we do this? Well, let me go here and propose that if we want to define a person, wouldn't it be nice if we could have a person data type, and then we could have an array called people, and maybe that array is our only array with 2 things in it, 2 persons in it. But somehow those data types, these persons, would have both a name and a number associated with them. So we don't need 2 separate arrays. We need 1 array of persons, a brand new data type. So how might we do this? Well, if we want every person in the world, or in this program, to have a name and a number, we literally write out first those 2 data types. Give me a string called name, give me a string called number, semicolon after each. And then we wrap those 2 lines of code with this syntax, which at first glance is a little cryptic. It's a lot of words all of a sudden. But typedef is a new keyword today that defines a new data type. This is the C keyword that lets you create your own data type for the very first time. Struct is another related keyword that tells the compiler that this isn't just a simple data type like an int or a float renamed or something like that. It actually is a structure. It's got some dimensions to it, like 2 things in it or 3 things in it or even 50 things inside of it. The last word down here is the name that you want to give your data type. And it weirdly goes after the curly braces, but this is how you invent a data type called person. And what this code is implying is that henceforth, the compiler Clang will know that a person is composed of a name, that's a string, and a number, that's a string. And you don't have to worry about having multiple arrays now. You can just have an array of people moving forward. So how can we go about using this? Well, let me go back to my code from before where I was implementing a phone book. And why don't we enhance the phone book code a little bit by borrowing some of that new syntax. Let me go to the top of my program above main and define a type that's a structure or a data structure that has a name inside of it and that has a number inside of it. And the name of this new structure, again, is going to be called person. Inside of my code now, let me go ahead and delete this old stuff temporarily. Let me give myself an array called people of size 2. And I'm going to use the non-terse way to do this. I'm not going to use the curly braces. I'm going to more pedantically spell out what I want in this array of size 2. At location 0, which is the first person in an array, because you always start counting at 0, I'm going to give that person a name of quote unquote Carter. And the dot is admittedly one new piece of syntax today too. The dot means go inside of that structure and access the variable called name and give it this value Carter. Similarly, if I want to give Carter a number, I can go into people bracket 0 dot number and give that the same thing as before, +1, 617, 495, 1000. And then I can do the same for myself here. People bracket, where should I go? OK, 1, because again, 2 elements, but we started counting at 0. Bracket name equals quote unquote David. And then lastly, people bracket 1 dot number equals quote unquote +1. 949 468 2750. So now if I scroll down here to my logic, I don't think this part needs to change too much. I'm still, for the sake of discussion, going to iterate 2 times from I is 0 on up to, but not through 2. But I think this line of code needs to change. How should I now refer to the ith person's name as I iterate? What should I compare, quote unquote, David to this time? Let me see on the end here. Yeah, people bracket I dot name. Why? Because people is the name of the array. Bracket I is the ith person that we're iterating over in the current loop. First 0, then 1, maybe higher if it had more people. Then dot is our new syntax for going inside of a data structure and accessing a variable therein, which in this case is name. And so I can compare David just as before. So it's a little more verbose, but now arguably this is a better program because now these people are full-fledged data types unto themselves. There's no more honor system inside of my loop that this is going to line up, because in just a moment I'm going to fix this one last remnant of the previous version. And if I can call back on you again, what should I change numbers bracket I to this time? Dot number. Exactly. So gone is the honor system that just assumes that bracket I in this array lines up with bracket I in this other array. Now, why? There's only one array. It's an array called people. The things it stores are persons. A person has a name and a number. And so even though it's kind of marginal, admittedly, given that this is a short program, and given that this kind of made things look more complicated at first glance, we're now laying the foundation for just a better design, because you really can't screw up now the association of names with numbers, because every person's name and number is, so to speak, encapsulated inside of the same data type. And that's a term of art in CS. Encapsulation means to encapsulate, that is, contain related pieces of information. And thus, we have a person that encapsulates 2 other data types name, and number. And this just sets the foundation for all of the cool stuff we've talked about and you use every day. What is an image? Well, recall that an image is a bunch of pixels or dots on the screen. Every one of those dots has RGB values associated with it, red, green, and blue. You could imagine now creating a structure in C probably where maybe you have three values, three variables, one called red, one called green, one called blue. And then you could name the thing, not person, but pixel. And now you could store in C three different colors, some amount of red, some green, some blue, and collectively treat it as the color of a pixel. And you can imagine doing something similar perhaps for video or music. Music, you might have three variables, one for the musical note, the duration, the loudness of it. And you could imagine coming up with your own data type for music as well. So this is a little low level. We're just using like a familiar contacts application. But we now have the way in code to express most any type of data that we might want to implement or discuss ultimately. So any questions now on struct or defining our own types, the purposes for which are to use arrays, but use them more responsibly now in a better design, but also to lay the foundation for implementing cooler and cooler stuff per our week 0 discussion. Yeah? What's the difference between this and an object in an object-oriented language? So slight side note, C is not object-oriented. Languages like Java and C++ and others, which you might have heard of, programmed yourself, had friends program in, are object-oriented languages. In those languages, they have things called classes or objects, which are interrelated. And objects can store not just data, like variables. Objects can also store functions. And you can kind of sort of do this in C, but it's not sort of conventional. In C, you have data structures that store data. In languages like Java and C++, you have objects that store data and functions together. Python is an object-oriented language as well, so we'll see this issue in a few weeks. But let me wave my hands at it for now. Yeah? Yes, could you use this struct to redefine how an int is defined? Short answer, yes. We talked a couple of times now about integer overflow. And most recently, you might have seen me mention the bug in iOS and macOS that was literally related to an int overflow. That's the result of ints only storing 4 bytes or 32 bits, or even as long as 64 bits or 8 bytes, but it's finite. But if you wanted to implement some financial software or some scientific or mathematical software that allows you to count way bigger than a typical int or a long, you could imagine coming up with your own structure. And in fact, in some languages, there is a structure called big int, which allows you to express even bigger numbers. How? Well, maybe you store inside of a big int an array of values, and you somehow allow yourself to store more and more bits based on how high you want to be able to count. So in short, yes, we now have the ability now to do most anything we want in the language, even if it's not built in for us. Other questions? Could you define a name and a number in the same line? Sort of. It starts to get syntactically a little messy, so I did it a little more pedantically line by line. Good question. Over here. Prototypes, you have to, in C, you have to define anything you're going to use or declare anything you're going to use before you actually use it. So it is deliberate that I put it at the top of my code in this file. Otherwise, the compiler would not know what I mean by person when I first use it here on what's line 14. So it has to come first, or it has to be put into something like a header file so that you know, so you include it at the very top of your code. Other questions over here? Yeah. Yeah, good question. We'll come back to this later in the term when we talk about SQL, a database language, and storing things in actual databases. Generally speaking, even though we humans call things phone numbers, or in the US we have social security numbers, those types of numbers often have other punctuation in it, like dashes, parentheses, pluses, and so forth. You could not store any of that syntax or that punctuation inside of an int. You could only store numbers. So one motivation for using a string is just I can store whatever the human wanted me to store, including parentheses and so forth. Another reason for storing things as strings, even if they look like numbers, is in the context of like zip codes in the United States. Again, we'll come back to this, but long story short, years ago, actually, I was using Microsoft Outlook for my email client, and eventually I switched to Gmail. And this is like 10 plus years ago now. And Outlook at the time lets you export all of your contacts as a CSV file, comma, separated values. More on that in the weeks to come, too. And that just means I could download a text file with all of my friends and family and their numbers inside of it. Unfortunately, I opened that same CSV file with Excel, I think at the time, just to kind of spot check it and see if what's in there was what it was expected. And I must have instinctively hit like Command or Control S to save it. And Excel, at least, has this habit of sort of reformatting your data. If things look like numbers, it treats them as numbers. And Apple Numbers does this too. Google Spreadsheets does this too nowadays. But long story short, I then imported my mildly saved CSV file into Gmail. And now, 10 plus years later, I'm still occasionally finding friends and family members whose zip codes are in Cambridge, Massachusetts 22138, which is missing the 0, because we here in Cambridge are 02138. And that's because I treated, or I let Excel treat, what looks like a number as an actual number or int. And now leading zeros become a problem, because mathematically they mean nothing, but in the mail system, they do. Sending envelopes and such. All right, other final questions here. Yeah, so could I have used a 2D or two-dimensional array to solve the problem earlier of having just one array? Yes, but one, I would argue it's less readable, especially as I get lots of names and numbers. And two, that too is also kind of relying on the honor system. It would be all too easy to omit some of the square brackets in the two-dimensional array. So I would argue it too is not as good as introducing a struct. More on that down the road. Two-dimensional arrays just means arrays of arrays, as you might infer. All right, so now that we have this ability to store different types of data, like contacts in a phone book, having names and addresses, let's actually take a step back and consider how we might now solve one of the original problems by actually sorting the information we're given in advance, and considering, per our discussion earlier, just how costly, how time-consuming is that, because that might tip the scales in favor of sorting, then searching, or maybe just not sorting and only searching. It'll give us a sense of just how expensive, so to speak, sorting something actually is. Well, what's the formulation of this problem? It's the same thing as week 0. We've got input to sort. We want it to be outputted as sorted. So for instance, if we're taking unsorted input as input, we want the sorted output as the result. More concretely, if we've got numbers like these, 6, 3, 8, 5, 2, 7, 4, 1, which are just randomly arranged numbers, we want to get back out 1, 2, 3, 4, 5, 6, 7, 8. So we just want those things to be sorted. So again, inside of the black box here is going to be one or more algorithms that actually gets this job done. So how might we go about doing this? Well, just to vary things a bit more, I think we have a chance here for a bit more audience participation. But this time we need 8 people, if we may. All of you have to be comfortable appearing on the internet. OK, so this is actually quite convenient that you're all quite close. How about 1, 2, 3, 4, 5, 6, 7. Oh, OK, and someone volunteering their friend. Number 8. Come on down. Come on down. Oh, and if you could, I'm going to set things up. If you all could join Valerie, my colleague over there, to give you a prop to use here. We'll go ahead in just a moment and try to find some numbers at hand. In just a moment, each of our volunteers is going to be representing an integer. And that integer is initially going to be in unsorted order. And I claim that using an algorithm, step-by-step instructions, we can probably sort these folks in at least a couple of different ways. So they're in wardrobe right now, just getting their very own Harvard t-shirt with a jersey number on it, which will then represent an element of our array. Give us just a moment to finish getting the attire ready. They're being handed a shirt and a number. And let me ask the audience for just a moment, as we have these numbers up here on the screen, these numbers too are unsorted. They're just in random order. And let me ask the audience, how would you go about sorting these 8 numbers on the screen? How would you go about sorting these? Yeah, what are your thoughts? OK. OK. OK, so just to recap, you would start with one of the numbers on the end. You would look to the number to the right or to the left of it, depending on which end you start at. And if it's out of order, you would just start to swap things. And that seems reasonable. There's a whole bunch of mistakes to fix here, because things are pretty out of order. But probably if you start to solve small problems at a time, you can achieve the end result of getting the whole thing sorted. Other instincts, if you were just handed these numbers, how you might go about sorting them? How might you? Yeah, in the back? OK. I like that. So to recap there, find the smallest one first and put it at the beginning, if I heard you correctly. And then presumably you could do that again and again and again. And that would seem to give you a couple of different algorithms. And if you all are attired here, do you want to come on up if you're ready? We had some felt volunteers too. Come on over. So if you all would like to line yourselves up facing the audience in exactly this order. So whoever's number 0 should be way over here. And whoever's number 5 should be way over there. Feel free to distance as much as you'd like. And scooch a little this way if you could. OK. All right, and make a little more room. So 7, let's see, 5, 2, 7, 4, 4, hopefully 1. Yeah, keep him to the side. OK, 1, 6. And there we go, 3. Come on over, 3. He's looking for you. All right, so here we have an array of 8 numbers, 8 integers, if you will. And do you want to each say a quick hello to the group?
Hello, I'm Quinn. Go Canada.
Hi, everyone. I'm Agiad.
Hey, I'm Mitchell.
Hi, I'm Brett. And also, go Canada.
I'm Hannah. Go Apley.
Hi, I'm Matthew. Go Hulbert.
Hi, I'm Miriam. Go Winthrop.
Hi, I'm Celeste. Go Strauss.
Wonderful. Well, welcome all to the stage. And let's just visualize, perhaps organically, how you 8 would solve this problem. So we currently have the numbers 0 through 7 quite out of order. Could you go ahead and just sort yourselves from 0 through 7? OK, so what did they just do? Well, OK, yes, first of all, yes, very well done. How would you describe what they just did? Well, let's do this. Could you go back into that order on the screen? 5, 2, 7, 4, 1, 6, 3, 0. And could you do exactly what you just did again? Sort yourselves. All right. OK, yes, well done again. All right. So admittedly, there's kind of a lot going on because each of you, except number 4, are doing something in parallel all at the same time. And that's not really how a computer typically works. Just like a computer can only look at one memory location at one locker at a time, so can a computer only move one number at a time, sort of opening a locker, checking what's there, moving it as needed. So let's try this more methodically based on the 2 audience suggestions. If you all could randomize yourself again to 5, 2, 7, 4, 1, 6, 3, 0. Let's take the second of those approaches first. I'm going to look at these numbers. And even though I, as the human, can obviously see all the numbers, and I just kind of have the intuition for how to fix this, we've got to be more methodical, because eventually we've got to translate this to pseudocode and then code. So let me see. I'm going to search for, as you proposed, the smallest number. And I'm going to start from left to right. I could do it right to left, but left to right just tends to be convention. All right, 5 at this moment is the smallest number I've seen. So I'm going to sort of remember that in a variable, if you will. Now I'm going to take one more step. 2, OK, 2 I'm going to compare to the variable in mind, obviously smaller. I'm going to forget about 5 and only now remember 2 as the now smallest element. 7, nope, I'm going to ignore that because it's not smaller than the 2 I have in mind. 4, 1, OK, I'm going to update the variable in mind because that's indeed smaller. Now, obviously, we, the humans, know that's getting pretty small. Maybe it's the end. I have to check all values to see if there's something even smaller, because 6 is not, 3 is not, but 0 is. And what's your name again? Celeste. Celeste. Where should Celeste or number 0 go according to this proposed algorithm? All right, I'm seeing a lot of this. So at the beginning of the array, so before doing this for real, let's have you pop out in front. And could you all shift and make room for Celeste? Is this a good idea, to have all of them move, or equivalently move everything in the array to make room for Celeste and number 0 over there? No, probably not. That felt like a lot of work. And even though it happened pretty quickly, that's like 7 steps to happen just to move her in place. So what would be marginally smarter, perhaps? A little more efficient, perhaps? What's that? Swapping. What do you mean by swap? OK, replace two values. So if you want to go back to where you were, one step over, number 5, he's not in the right place. He's got to move eventually. So you know what? If that's where Celeste belongs, why don't we just swap 5 and 0? So if you want to go ahead and exchange places with each other, notice what's just happened. The problem I'm trying to solve has gotten smaller. Instead of being size 8, now it's size 7. Now granted, I moved 5 to another wrong location. But if these numbers started off randomly, it doesn't really matter where 5 goes until we get him into the right place. So I think we've improved. And now if I go back, my loop is sort of coming back around. I can ignore Celeste and make this a 7-step problem and not 8 because I know she's in the right place. 2 seems to be the smallest. I'll remember that. Not 7, not 4. 1 seems to be the smallest. Now, I know as a human, this should be my next smallest. But why intuitively should I keep going, do you think? I can't sort of optimize as a human and just say, number 1, let's get you into the right place. I still want to check the whole array. Why? Yeah. Maybe there's another 1, and that could be another problem altogether. Other thoughts? Yeah. There could be another 0, indeed. But I did go through the list once, right? And I kind of know there isn't. Your thoughts?
We don't know that every value is represented. So maybe, or maybe there's a map. You just don't know the kind of data you're looking for.
Yeah, I don't necessarily know what is there. And honestly, I only stipulated earlier that I'm using 1 variable in my mind. I could use 2, and remember the 2 smallest elements I've seen. I could use 3 variables, 4, but then I'm going to start to use a lot of space in addition to time. So if I've stipulated that I only have 1 variable to solve this problem, I don't know anything more about these elements because the only thing I'm remembering at this moment is number 1 is the smallest element I've seen. So I'm going to keep going. 6, nope. 3, nope. 5, nope. OK, I know that number 1, and your name was? Hannah is the next smallest element. I could have everyone move over to make room, but nope. 2, you know, even though you're so close to where I want you, I'm just going to keep it simple and swap you 2. So granted, I've made the problem a little worse, but on average, I could get lucky too and just pop number 2 into the right place. Now let me just accelerate this. I can now ignore Hannah and Celeste, making the problem size 6 instead of 8. So it's getting smaller. 7 is the smallest. Nope. Now 2 is the smallest. Still 2, still 2, still 2. So let's go ahead and swap 2 and 7. And now I'll just kind of orchestrate it verbally for you're about to have to do something. So we now have 4, 7, 6, 3, 5. OK, 3. Could you swap with 4? All right. Now we have 7, 6, 4, 5. OK, 4. Could you swap with 7? Now we have 6, 7, 5. 5. Could you swap with 6? And now we have 7, 6. 6. Could you swap with 7? And now, perhaps a round of applause. They've sorted themselves. OK. Hang on there 1 minute. So we'll do this one other approach. And my God, that felt so much slower than the first approach. But that's 1, because I was kind of providing a long voiceover. But 2, we were doing 1 thing at a time. Whereas the first time, you guys had the luxury of moving like 8 different CPUs, brains, if you will, were all operating at the same time. And computers like that exist. If you have a computer with multiple cores, so to speak, that's like having a computer that technically can do multiple things at once. But software typically, at least as we've written it thus far, can only do 1 thing at a time. So in a bit, we'll add up all of these steps. But for now, let's take one other approach. If you all could reorder yourselves like that, 5, 2, 7, 4, 1, 6, 3, 0. Let's take the other approach that was recommended by just fixing small problems and see where this gets us. So we're back in the original order. 5 and 2 are clearly out of order. So you know what? Let's just bite this problem off now. 5 and 2, could you swap? Now let me take a next step. 5 and 7, I think you're OK. There's a gap, yes, but that might not be a big deal. 7 and 4, problem. Let's have you swap. OK, 7 and 1, let's have you swap. 7 and 6, let's have you swap. 7 and 3, you swap. 7 and 0, you swap. Now let me pause for just a moment. Still not sorted, so I'm clearly not done. But have I improved the problem? Right? I can't cheat like before, or I can't optimize like before, because 0 is obviously not here, so Leslie's still way back there. So it's not like I've gone from 8 steps to 7 to 6 just yet. But have I made any improvements? Yes, in what sense is this improved? What's a concrete thing you could point to as better? Yeah. I've sorted the highest number, which is indeed 7. And conversely, if you prefer, Celeste is 1 step closer to the beginning. Now, worst case, Celeste is going to have to move one step on each iteration. So I might need to do this thing like n total times to move her all the way over. But that might work out OK. Let me see. 2 and 5, you're good. 5 and 4, swap you. 5 and 1, let's swap you. 5 and 6, you're good. 6 and 3, let's swap you. 6 and 0, let's swap you. 6 and 7, you're good. And I think now, notice that the high values, as you noted, are sort of bubbling up, if you will, to the end of the list. 2 and 4, you're good. 4 and 1, let's swap. 4 and 5, good. 5 and 3, swap. 5 and 0, swap. 5, 6, 7, of course, are good. So now you can sort of see the problem resolving itself. And let's just do this part now faster. 2 and 1. 2 and 4 are OK. 4 and 3. 4 and 0. All right. Now 1 and 2. 2 and 3. 3 and 0. And good. So we do have some optimization there. We don't need to keep going because those all are sorted. 1 and 2, you're good. 2 and 0. All right. Done. 1 and 0. And big round of applause in closing. OK. So, thank you all. We need the puppets back, but you can keep the shirts. Thank you for volunteering here. Feel free to make your way exit left or right. And let's see if, thanks to our volunteers here, we can't now formalize a little bit what we did on both passes here. I claim that the first algorithm our volunteers kindly acted out is what's called selection sort. And as the name implied, we selected the smallest element again and again and again, working our way from left to right, putting Celestia into the right place, and then continuing with everyone else. So selection sort, as it's formally called, can be described, for instance, with this pseudocode here. For I from 0 to n minus 1. And again, why this? This is just how we talk about arrays. The left end is 0. The right end is n minus 1, where in this case, n happened to be 8 people. So that's 0 through 7. So for I from 0 to n minus 1, what did I do? I found the smallest number between numbers bracket I and numbers bracket n minus 1. So a little cryptic at first glance, but this is just a very pseudocode-like way of saying find the smallest element among all 8 volunteers. Because if I starts at 0 and n minus 1 never changes because there's always 8, and 8 people, so 8 minus 1 is 7. This first says find the smallest number between numbers bracket 0 and numbers bracket 7, if you will. Then what do? Swap the smallest number with numbers bracket I. So that's how we got Celeste from over here all the way over there. We just swapped those two values. What then happens next in this pseudocode? I, of course, goes from 0 to 1. And that's the technical way of saying now find the smallest element among the 7 remaining volunteers, ignoring Celeste this time because she was already in the correct location. So the problem went from size 8 to size 7. And if we repeat size 6, 5, 4, 3, 2, 1 until boom, it's all done at the very end. So this is just one way of expressing in pseudocode what we did a little more organically in a formalization of what someone volunteered out in the audience. So if we consider then the efficiency of this algorithm, maybe abstracting it away now is a bunch of doors where the leftmost, again, is always 0. The rightmost is always n minus 1. Or equivalently, the second to last is n minus 2. The third to last is n minus 3, where n might be 8 or anything else. How do we think about or quantify the running time of selection sort? Big O of what? I mean, that was a lot of steps to be adding up. It's probably more than n, right? Because I went through the list again and again. It was like n plus n minus 1 plus n minus 2. Any instincts here? We got like the whole team in the orchestra now. Let me propose we think about it this way, with just a bit of formula's sake. So the first time, I had to look at n different volunteers. N was 8 in this case, but generically, I looked at all 8 numbers in order to decide who was the smallest. And sure enough, Celeste was at the very end. She happened to be all the way to the right. But I only knew that once I looked at all 8 or all n volunteers. So that took me n steps first. But once Celeste was swapped into the right place, then my problem was size n minus 1. And I had n minus 1 other people to look through. So that's n minus 1 steps. Then after that, it's n minus 2 plus n minus 3 plus n minus 4 plus dot, dot, dot until I had one final step. And it's obvious that I only have one human left to consider. So we might wave our hands at this with a little ellipsis and just say dot, dot, dot plus 1 for the final step. Now, what does this actually equal? Well, this is where you might think back on like your high school math or physics textbook that has a little cheat sheet at the end that shows these kinds of recurrences. That happens to work out mathematically to be n times n plus 1, all divided by 2. That's just what that recurrence, that series, actually adds up to. So if you take on faith that that math is correct, let's just now multiply this out mathematically. That's n squared plus n divided by 2, or n squared divided by 2 plus n over 2. And here's where we're starting to get annoyingly into the weeds. Like, honestly, as n gets really large, like 1,000,000 doors or integers or 1,000,000,000 web pages in Google's search engine, honestly, which of these terms is going to matter the most mathematically? If n is a really big number, is n squared divided by 2 the dominant factor, or is n divided by 2 the dominant factor? Yeah, n squared. I mean, no matter what n is, and the bigger it is, the bigger raising it to the power 2 is going to be. So you know what? Let's just wave our hands at this, because at the end of the day, as n gets really large, the dominant factor is indeed that first one. And you know what? Even the divided 2, as I claimed earlier with our 2 phone book examples, where the 2 straight lines, if you keep zooming out, essentially look the same when n is large enough. Let's just call this on the order of n squared. So that is to say, a computer scientist would describe bubble sort as taking on the order of n squared steps. That's an oversimplification. If we really added it up, it's actually this many steps, n squared divided by 2 plus n over 2. But again, if we want to just be able to generally compare 2 algorithms' performance, I think it's going to suffice if we look at that highest order term to get a sense of what the algorithm feels like, if you will, or what it even looks like graphically. All right, so with that said, we might describe bubble sort as being in big O, selection sort as being in big O of n squared. But what if we consider now the best case scenario, an opportunity to talk about a lower bound? In the best case, how many steps does selection sort take? Well, here we need some context. Like, what does it mean to be the best case or the worst case when it comes to sorting? Like, what could you imagine meaning the best possible scenario when you're trying to sort a bunch of numbers? The whole crew here again. Yeah. All right, they're already sorted, right? I can't really imagine a better scenario than I have to sort some numbers, but they're already sorted for me. But does this algorithm leverage that fact in practice? Even if all of our humans had lined up from 0 to 7, I'm pretty sure I would have pretty naively started here. And yes, Celeste happens to be here, but I only know she needs to be here once I've looked at all 8 people. And then I would have realized, well, that was a waste of time. I can leave Celeste be. But then what would I have done? I would have ignored her position, because we're solved one problem. I would have done the same thing now for 7 people, then 6 people. So every time I walk through, I'm not doing much useful work, but I am doing those comparisons because I don't know until I do the work that the people were in the right order. So this would seem to imply that the omega notation, the best case scenario even, a lower bound on the running time would be what then? A little louder? It's still going to be n squared, in fact, because the code I'm giving myself doesn't leverage or benefit from any of that scenario, because it just mindlessly continues to do this again and again. So in this case, yes, I would claim that the omega notation for selection sort is also big O of n squared. So those are the kinds of numbers to beat. It seems like the upper bound and lower bound of selection sort are indeed n squared. And so we can also describe selection sort, therefore, as being in theta of n squared. That's the first algorithm we've had the chance to describe that in, which is to say that it's kind of slow. I mean, maybe other algorithms are slower, but this isn't the best starting point. Can we do better? Well, there's a reason that I guided us to doing the second algorithm second, even though you verbally proposed them in a different order. This second algorithm we did is generally known as bubble sort. And I deliberately used that word a bit ago, saying the big values are bubbling their way up to the right, to kind of capture the fact that indeed this algorithm works differently, but let's consider if it's better or worse. So here we have pseudocode for bubble sort. You could write this too in different ways, but let's consider what we did on the stage. We repeated the following n minus 1 times. We initialized, at least even though I didn't verbalize it this way, a variable like I from 0 to n minus 2, and then I asked this question. If numbers bracket I and numbers bracket I plus 1 are out of order, then swap them. So again, I just did it more intuitively by pointing, but this would be a way with a bit of pseudocode to describe what's going on. But notice that I'm doing something a little differently here. I'm iterating from I of equals 0 to n minus 2. Why? Well, if I'm comparing two things, left hand and right hand, I'd still want to start at 0, but I don't want to go all the way to n minus 1 because then I'd be going past the boundary of my array, which would be bad. I want to make sure that my left hand, I, if you will, stops at n minus 2, so that when I plus 1 in my pseudocode, I'm looking at the last two elements, not the last element and then past the boundary. That's actually a common programming mistake that we'll undoubtedly soon make, but going beyond the boundaries of your array. So this pseudocode then allows me to say, compare everyone again and again, and swap them if they're out of order. Why do I repeat the whole thing n minus 1 times? Like, why does it not suffice just to do this loop here? Think what happened with Celeste. Why do I repeat this whole thing n minus 1 times? Yeah, and back? Indeed, and I think if I can recap accurately, think back to Celeste again, and I'm sorry to keep calling on you as our number 0. Each time through bubble sort, she only moved one step. And so in total, if there's n locations, at the end of the day, she needs to move n minus 1 steps to get 0 all the way to where it needs to be. And so this inner loop, if you will, where we're iterating using I, that just fixes some of the problems. But it doesn't fix all of the problems until we do that same logic again and again and again. And so how might we quantify the running time of this algorithm? Well, one way to see it is to just literally look at the pseudocode. The outer loop repeats n minus 1 times. By definition, it literally says that. The inner loop, the for loop, also iterates n minus 1 times. Why? Because it's going from 0 to n minus 2. And if that's hard to think about, that's the same thing as 1 to n minus 1, if you just add 1 to both ends of the formula. So that means you're doing n minus 1 things n minus 1 times. So I literally multiply how many times the outer loop is running by how many times the inner loop is running, which gives me sort of FOIL method n minus 1 squared. And I could multiply that whole thing out. Well, let's consider this just a little more methodically here. If I have n minus 1 on the outer, n minus 1 on the inner, let's go ahead and FOIL this. So n squared minus n plus 1. Combine like terms, n squared minus 2n plus 1. And now, which of these terms is clearly going to be dominant, so to speak? The n squared. So yes, even though minus 2n is a good thing because it's subtracting off some of the time required, plus 1 is not that big a thing. There's such drops in the bucket when n gets really large, like in the millions or billions certainly, that bubble sort 2 is on the order of n squared. It's not the same exactly as selection sort, but as n gets big, honestly, we're barely going to be able to notice the difference most likely. And so it too might be said to be on the order of n squared. And if we consider now the lower bound on bubble sort's running time, here's where things get potentially interesting. What might you claim is the running time of bubble sort in the best case? And the best case I claim is when the numbers are already sorted. Is our pseudocode going to take that into account? OK, n. Why do you propose n? Yes, and that's the key word. To summarize, in bubble sort, I do have to minimally make one pass, because if I don't look at all n elements, then I'm theoretically just guessing if it's sorted or not. Like, I obviously, intuitively, have to look at every element to decide yay or nay it's in the right order. And my original pseudocode, though, is pretty naive. It's just going to blindly go back and forth n minus 1 times again and again. And that's going to add up. But what if I add a bit of an optimization that you might have glimpsed on the slide a moment ago, where if I compare two people and I don't swap them, compare two people, don't swap them, and I go all the way through the list comparing every pair of adjacent people, and I make no swaps, it would be kind of not just naive, but stupid to do that same process again. Because if the humans have not moved, I'm not going to make any different decisions. I'm going to do nothing again, nothing again. So at that point, it would be stupid, very inefficient to go back and forth and back and forth. So if I modify our pseudocode with just an additional if condition, I bet we can speed this up. Inside of that same pseudocode, what if I say, hey, if no swaps, quit? like quit prematurely before the loops are finished running. One of the loops has gone through per the indentation here. But if I do a loop from left to right and I have made no swaps, which you can think of as just being one other variable that's plussing as I go, keeping track of how many swaps. If I've made no swaps from left to right, I'm not going to make any swaps the next time around either. So let's just quit at that point. And that is to say, in the best case, if you will, when the list is already sorted, the omega notation for bubble sort might indeed be omega of n, if you add that optimization, so as to short circuit all of that inefficient looping to do it only as many times as is necessary. All right, let me pause to see if there's any questions here. Yeah? Good question. If the running time of selection sort and bubble sort are both in big O of n squared, but selection sort's in omega of n squared, while bubble sort's in omega of n, which sounds better. I think if I may, should we just always use bubble sort? Yes, if we think that we might benefit over time from a lot of good case scenarios or best case scenarios. However, the goal at hand in just a bit is going to be to do even better than both of these. So hold that question further for a moment. Yeah? No. So yes, good question. So I say omega of n, but is it technically omega of n minus 1? Maybe, but again, we're throwing away lower order terms. And that's an advantage because we're not comparing things ever so precisely. Just like I plotted with the green and yellow and red chart, I just want to get a sense of the shape of these algorithms so that when n gets really large, which of these choices is going to matter the most. At the end of the day, it's actually perfectly reasonable to use selection sort or bubble sort if you don't have that much data, because they're going to be pretty fast. My God, our computers nowadays are 1 gigahertz, 2 gigahertz, 1 billion things per second, 2 billion things per second. But if we have large data sets, as we will later in the term, and as you might in the real world at the Googles of the world, then you're going to want to be more thoughtful. And that's where we're going today. All right, so let's actually see this visualized a little bit. In a moment, I'm going to change screens here to open up what is a little visualization tool that will give us a sense of how these things actually work and look at a faster rate than our humans were able to do here on stage. So here is another visualization of a bunch of numbers, an array of numbers. Short bars mean small numbers. Tall bars mean big numbers. So instead of having the numbers on their torsos, here we just have bars that are small or tall based on the magnitude of the number. Let me go ahead, and I've pre-configured this in advance to operate somewhat quickly. Let's go ahead and do selection sort by clicking this button. And you'll see some pink bars flying by, and that's like me walking left and right to select the next smallest number. And so what you'll see happening on the left of this array of numbers is Celeste, if you will, and all of the other smaller numbers are appearing on the left while we continue to solve the remaining problems to the right. So again, we no longer have to touch the smaller numbers here. So that's why the problem is getting smaller and smaller and smaller over time. But you can notice now visually, look at how many times we're retracing our steps. This is why things that are n squared tend to be frowned upon, if avoidable, because I'm touching the same elements again and again. When I was walking through, I kept pointing at the same humans again and again, and that adds up. So let's see if bubble sort looks or feels a little different. Let me re-randomize the thing, and let me now click bubble sort at the top. And as you might infer, there's other sorting algorithms out there, not all of which we'll look at, but here's bubble sort. Same pink coloration, but it's doing something different. It's 2 pink bars going through again and again, comparing the adjacent numbers. And you'll see that the largest numbers are indeed bubbling their way up to the right, but the smaller numbers, like our number 0 was, is only slowly making its way over. Here's a comparable. Here's the number 1, and it's going to take a while to get all the way to the left. And here, too, notice how many times the same bars are becoming pink. How many times the algorithm is retracing and retracing its steps. Why? Because it's only solving one problem at a time on each pass. And each time we do that, we're stepping through practically the whole array. And now, granted, I could speed this up even further if I really wanted to. But my God, this is only, what, like 50 or 60 elements, something like that? This is slow. Like, this is what n squared looks like and feels like. And now I'm just trying to come up with words to say until we get to the finish line here. Like, this would be annoying if this is the speed of sorting. And this is why I sort of secretly sorted the numbers for Rave in advance, because it would have taken us an annoying number of steps to get that in place for her. So those two algorithms are n squared. Can we do, in fact, better? Well, to save the best algorithm for last, let's take a shorter 5-minute break here. And when we come back, we'll do even better than n squared. All right. So the challenge at hand is to do better than selection sort and better than bubble sort. And ideally, not just marginally better, but fundamentally better. Just like in week 0, that third and final divide and conquer algorithm was sort of fundamentally faster than the other two. So can we do better than something on the order of n squared? Well, I bet we can if we start to approach the problem a little differently. The sorts we've done thus far, generally known as comparison sorts, and that kind of captures the reality that we were doing a huge number of comparisons again and again. And you kind of saw that in the vertical bars that were going pink as everything was being compared again and again. But there's this programming technique, and it's actually a mathematical technique, known as recursion, that we've actually seen before. And this is a building block or a mental model we can bring to bear on the problem to solve the sorting problem sort of fundamentally differently. But first, let's look at it in a more familiar context. A little bit ago, I proposed this pseudocode for the binary search algorithm. And notice that what was interesting about this code, even though I didn't call it out at the time, it's kind of cyclically defined. Like, I claim this is an algorithm for search, and yet it seems a little unfair that I'm using the verb search inside of the algorithm for search. It's like in English, sort of defining a word by using the word. Normally, you shouldn't really get away with that. But there's something interesting about this technique here, because even though this whole thing is a search algorithm, and I'm using my own algorithm to search the left half or the right half, the key feature here that doesn't normally happen in English when you define a word in terms of a word is that when I search the left half or search the right half, yes, I'm doing the same thing. I'm using the same algorithm, but the problem is by definition half as large. So this isn't going to be a cyclical argument in the same way. This approach, by using search within search, is going to whittle the problem down and down and down until hopefully one door or no doors remains. And so recursion is a programming technique whereby a function calls itself. And we haven't seen this yet in C, and we haven't seen this really in Scratch. But in C, you can have a function call itself. And the form that takes is like literally using the function's name inside of the function's implementation itself. We've actually seen this an opportunity for this once before, too. Think back to week 0. Here's that same pseudocode for searching for someone in an actual physical phone book. And notice these yellow lines here. We described those in week 0 as inducing a loop, a cycle. And this is a very procedural approach, if you will, because lines 8 and 11 are very mechanically, if you will, telling me to go back to line 3 to do this kind of looping thing. But really what that's doing in the binary search algorithm for the phone book is it's just telling me to search the left half or search the right half. I'm doing it more mechanically, again, by sort of telling myself what line number to go back to. But that's equivalent to just telling myself, go search the left half, search the right half. The key thing being the left half and the right half are smaller than the original problem. It would be a bug if I just said, search the phone book, search the phone book. Because obviously you never get anywhere. But if you search the half, the half, the half, problem gets smaller and smaller. So let's reformulate week 0's phone book code to be not procedural as here, but recursive, whereby in this search algorithm, aka binary search, formerly called divide and conquer, I'm going to literally use also the keyword search here. Notice among the benefits of doing this is it kind of tightens the code up, makes it a little more succinct, even though that's kind of a fringe benefit here. But it's an elegant way, too, of describing a problem by just having a function use itself to solve a smaller puzzle at hand. So let's now consider a familiar problem, a smaller version than the one you've dabbled with, this sort of pyramid, this half pyramid from Mario. And let's throw away the parts that aren't that interesting and just consider how we might, up until now, implement this in C code. This left-aligned pyramid, if you will. Let me go over here and let me create a file called, how about iteration.c. And in this file, I'm going to go ahead and include CS50.h, and I'm going to include standard in. standardIO.h. And the goal at hand is to implement in C a little program that just prints out this and exactly this pyramid. So no get string or any of that. We're just going to keep it simple and print exactly this pyramid of height 4 here. So how might I do this? Well, let me go ahead and in main, let me first ask the user for, well, we'll go ahead and generalize it. Let's go ahead and ask the user for heights. We're using getInt as before. And I'll store that in a variable called height. And then let me go ahead and simply call a function draw, passing in that height. So for the moment, let me assume that someone somewhere has implemented a draw function, and this then is the entirety of my program. All right, unfortunately, C does not come with a draw function. So let me go ahead and invent one. It doesn't need to return a value. It just needs to print something, a so-called side effect. So I'm going to define a function called draw that takes as input an int. I'll call it n for number, but I could call it anything I want. And inside of this, I'm going to go ahead and print out a left-aligned pyramid like this from top to bottom. The salient features here are that this is a pyramid, at least in this example, of height 4. And on height 4, the first row has 1 brick, the second row has 2, the third has 3, the fourth has 4. That's a nice pattern that I can probably represent in code. So how might I do this? Well, how about for int I gets, let me do it the old school way, 1, and then I is less than or equal to n, and then I++. So I'm going from 1 to 4, just to keep myself sane here. And then inside of this loop, what do I want to do? Well, let me keep it conventional. In fact, let me just change this to be the more conventional 0 to n, even though it might not be as intuitive, because now on row 0, I want 1 brick. On row 1, I want 2 bricks, ... On row 3, I want 4. So it's kind of offset now, but I'm being more conventional. So on each row, how many bricks do I want to print? Well, I think I want to do this. For int j, for instance, common to use j after I if you have a nested loop. Let's start j at 0 and do this so long as j is less than I plus 1. And then do j++. So why I plus 1? Well, again, when I equals 0, that's the first row, and I want 1 brick. When I equals 1, that's the second row, I want 2 bricks. And ... When I is 3, I want 4 bricks. So again, I have to add 1 to I to get the total number of bricks that I want to print on the screen. So inside of this nested for loop, I'm going to do printf of a hash with no new line. I'm going to save the new line for about here instead. All right, the last thing I'm going to do is copy and paste the prototype at the top of the file so that I can call this. And again, this is sort of now week 1, week 2. Wouldn't necessarily come to your mind as quickly as it might to mine after all this practice. But this is something reminiscent of what you yourselves did already for Mario, printing out a pyramid that hopefully in a moment is going to look like this. So let me go back to my code. Let me run make iteration. And let me do /iteration. I'll type in 4. And voila, seems to be correct. And let's assume it's going to work for other inputs as well. Oh, thank you. This is so this is indeed an example of iteration, doing something again and again. And it's very procedural. Like I literally have a function called draw that does this thing. But I can think about implementing draw in a somewhat different way that's kind of clever. And it's not strictly necessary for this problem, because this problem honestly is not that complicated to solve once you have practice under your belt. Certainly the first time around, probably significantly challenging. But now that you kind of associate, OK, row 1 with 1 brick, row 2 with 2 bricks, it kind of comes together with these for loops. But how else could we think about this problem? Well, this physical structure, these bricks, in some sense is a recursive structure. A structure that's defined in terms of itself. Now, what do I mean by that? Well, if I were to ask you the question, what does a pyramid of height 4 look like? You would point, of course, to this picture. But you could also kind of, cleverly say to me, well, it's actually a pyramid of height 3 plus 1 additional row. And here's that cyclical argument, right? Kind of obnoxious to do typically in English or in a spoken language, because you're defining one thing in terms of itself. What's a pyramid of height 4? Well, it's a pyramid of height 3 plus 1 more row. But we can kind of leverage this logic in code. Well, what's a pyramid of height 3? Well, it's a pyramid of height 2 plus 1 more row. Fine. What's a pyramid of height 2? Well, it's a pyramid of height 1 plus 1 more row. And then hopefully this process ends, and it does, because notice the pyramid is getting smaller and smaller. So you're not going to sort of have this sort of silly back and forth with me infinitely many times, because when we finally get to the base case, the end of the pyramid, fine, what is a pyramid of height 1? Well, it's a pyramid of no height plus one more row. And at that point, things just get negative. No pun intended. Things just would otherwise go negative. And so you can just kind of stop. The base case is when there is no more pyramid. So there's a way to sort of draw a line in the sand and say, stop, no more arguments. But this idea of defining a physical structure in terms of itself or code in terms of itself actually lets us do some interesting new algorithms. Let me go back to my code here. Let me go ahead and create one final file here called recursion.c that leverages this idea of this built-in self-referential nature. Let me include CS50.h. Let me go ahead and include standard.io.h, int main void. And then inside of main, I'm going to do the exact same thing. Int height equals get int, asking the user for height. And then I'm going to go ahead and call draw, passing in height. So that's going to stay the same. I even am going to make my prototype the same. Void draw int n semicolon. And now I'm going to implement void down here with that same prototype, of course. But the code now is going to be a little different. What am I going to do here? Well, first of all, if you ask me to draw a pyramid of height n, I'm going to be kind of a wise ass here and say, well, just draw a pyramid of n minus 1. Done. All right, but there's still a little more work to be done. What happens after I print or draw a pyramid of height n minus 1, according to our structural definition a moment ago? What remains after drawing a pyramid of height n minus 1, or 3 specifically? We need one more row of hashes. OK, so I can do that, right? I'm OK with the single loops. There's no nesting necessary here. I'm just going to do this. For int I gets 0, I is less than n, which is the height that's passed in, I plus plus. And then inside of this loop, I'm very simply going to print out a single hash. And then down here, I'm going to print out a new line at the very end. So that's good, right? I might not be as comfortable with nested loops. This is nice and simple. What does this loop do here on lines 17 through 20? It literally prints n hashes by counting from I equals 0 on up to, but not through, n. So that's sort of week 1 style syntax. But this is kind of trippy now, because I've somehow boiled down the implementation of draw into printing a row after just drawing the thing above it. But this is problematic as is, because in this case, my draw function, notice, is always going to call the draw function forever in some sense. But ideally, when do I want this cyclical process to stop? When do I want to not call draw anymore? Yeah. When n is 1, right? When I get to the top of the pyramid, when n is 1, or heck, when the pyramid's all gone and n equals 0, I can pick any line in the sand so long as it's sort of at the end of the process. Then I don't want to call draw anymore. So maybe what I should do is this. If n equals 0, there's really nothing to draw. So I'm just going to go ahead and return like this. Otherwise, I'm going to go ahead and draw n minus 1 rows and then one more row. And I could express this differently. I could do something like this, which would be equivalent. I could say something like, if n is greater than or equal to 0, then go ahead and draw the row. But I like it this way first. For now, I'm going to go with the original way, just to ask a simple question and then just bail out of the function if n equals 0. And heck, just to be super safe, just in case the user types in a negative number, let me also just check. If n is a negative number, also just return immediately. Don't do anything. I'm not returning a value because, again, the function is void. It doesn't need or have a return value. So just saying return suffices. But if n equals 1 or 2 or 3 or anything higher, it is reasonable to draw a pyramid of slightly shorter height, like instead of 4, 3, and then go ahead and print one more row. So this is an example now of code that calls itself within itself. Draw is calling draw. But this so-called base case ensures, this conditional ensures that we're not going to do this forever. Otherwise, we literally would do this infinitely many times, and something bad is probably going to happen. All right, let me go ahead and compile this code. Make recursion. OK, no syntax errors. / recursion, enter, height of 4, and voila. If only because some of you have run into this issue accidentally already, let me get rid of the base case here and let me recompile the code, make recursion. Oh, and actually now it's actually catching it. So the compiler is smart enough here to realize that all pass through this function will call itself, aka it's going to loop forever. So let me do the first thing. Suppose I only check for n equaling 0. Let me go ahead and recompile this code with make recursion. And now let me just be kind of uncooperative. When I run this program, still works for 4, still works for 0. What if I do like -100? Have any of you experienced a segmentation fault or core dump? OK, so no shame in this. Like, this means I have somehow touched memory that I shouldn't have. And in short, I actually called this function thousands of times accidentally, it would seem now, until the program just bailed on me because I eventually touched memory in the computer that I shouldn't have. That'll make even more sense next week. But for now, it's simply a bug. And I can avoid that bug in this context, probably not your own pset context, by just making sure we don't even allow for negative numbers at all. So with this building block in place, what can we now do in terms of those same numbers to sort? Well, it turns out there's a sorting algorithm called merge sort. And there's bunches of others too. But merge sort is a nice one to discuss because it fundamentally, we hope, is going to do better than selection sort and bubble sort. That is better than n squared. But the catch is it's a little harder to think about. In fact, I'll act it out myself with just these numbers on the shelf here rather than humans, because recursion in general takes a little bit of effort to wrap your mind around, typically a bit of practice. But I'll see if we can't walk through it methodically enough such that this comes to light. So here's the pseudocode I propose for this algorithm called merge sort. In the spirit of recursion, this sorting algorithm literally calls itself by using the verb sort in its pseudocode. So how does merge sort work? It sort of obnoxiously says, well, if you want to sort all of these things, go sort the left half, then go sort the right half, and then merge the two together. Now, obnoxious in what sense? Well, if I just asked you to sort something and you just tell me, well, go sort that thing and then go sort that thing, what was the point of asking you in the first place? But the key is that each of these lines is sorting a smaller piece of the problem. So eventually, we'll be able to pare this down into something that doesn't go on forever. Because, in fact, in merge sort, there's a base case too. There's a scenario where we just check, wait a minute, if there's only one number to sort, that's it. Quit then, because you're all done. So there has to be this base case in any use of recursion to make sure that you don't mindlessly call yourself forever. You've got to stop at some point. So let's focus on the third of these steps. What does it mean to merge two lists, two halves of a list, just because this is apparently going to be a key ingredient? So here, for instance, are two halves of a list of size 8. We have the numbers 2, and I'll call it out if you're at a bad angle, 2, 4, 5, 7, and 0, 1, 3, 6. Notice that the left half at the moment, 2, 4, 5, 7, is already sorted. And the right half, 0, 1, 3, 6, is also sorted as well. So that's a good thing, because it means that theoretically, I've sorted the left half already. I've sorted the right half already before we began. I just need to merge these two halves. What does it mean to sort two halves? Well, for the sake of discussion, I'm just going to turn over most of the numbers except for the first numbers in each of these halves. There's two halves here, left and right. At the moment, I'm only going to consider the leftmost element of each half. That is the one on the left here and the one on the left here. How do I merge these two lists together? Well, if I look at 2 and I look at 0, which one should presumably come first? The smaller one. So I'm going to grab the 0 and I'm going to put it into its own place on this new shelf here. And now I'm going to consider, as part of my iteration, the beginning of this list and the new beginning of this list. So I'm now comparing 2 and 1. Which one's smaller? I'm going to go ahead and grab the 1. Now I'm going to compare the beginning of the left list and the new beginning of the right list, 2 and 3. Of course, it's 2. Now I'm going to compare the beginning of the left list and the beginning of the right list, 4 and 3. It's, of course, 3. Now I'm going to compare the 4 against the beginning and end, it turns out, of the second list, 4, of course. Now I'm going to compare the beginning of the left list and the beginning of the right list, 5, of course. I'm realizing this is not going to end well because I left too much distance between the numbers, but that has nothing to do with the algorithm. 7 is the beginning of the left list. 6 is the beginning of the right list. It's, of course, 6. And at the risk of knocking all of these over, if I now make room for this element, we have hopefully sorted the whole thing by having merged together the two halves of the list. So in short, thank you. I'm a little worried that's just getting sarcastic now. But now we now have merged two half lists. We haven't done the guts of the algorithm yet, sort the left half and sort the right half. But I claim that that is how, mechanically, you merge two sorted halves. You keep looking at the beginning of each list, and you just kind of weave them together based on which one belongs first based on its size. So if you agree that that was a reasonable way to merge two lists together, let's go ahead and focus lastly on what it means to actually sort the left half and sort the right half of a whole bunch of numbers. And for this, I'm going to go ahead and order them in this seemingly random order. And I just have a little cheat sheet above so that I don't mess up. And I'm going to start at the very top this time. And hopefully, these will not fall down at any point. But I'm just deliberately putting them in this random order, 5, 2, 7, 4. And then we have 1, 6, 3, 0. 1, 6, 3, 0. Hopefully, this won't fall over. Here is now an array of size 8 with 8 integers. And I want to sort this. I could use selection sort and just go back and forth and back and forth. I could use bubble sort and just compare pairs, pairs, pairs. But those are going to be on the order of big O of n squared. My hope is to do fundamentally better here. So let's see if we can do better. All right, so let me look now at my code. I'll keep it on the screen. How do I implement merge sort? Well, if there's only one number, I quit. There's obviously not. There's 8 numbers, so that's not applicable. I'm going to go ahead and sort the left half of numbers. All right, here's the left half, 5, 2, 7, 4. How do I sort an array of size 4? Well, here's where the recursion kicks in. How do you sort a list of size 4? Well, there's the pseudocode on the board. I sort the left half of the list of size 4. So here we go. I have a list of size 4. How do I sort it? I sort the left half. All right, now I have a list of size 2. How do I sort this? Well, sort the left half. So here we go. Here's a list of size 1. How do I sort this? I think it's done, right? That's quit, right? If only one number, I'm done. The 5 is sorted. All right, what was the next step? You have to now rewind in time. I just sorted the left half of the left half of the left half. What do I now sort? The right half, which is 2. This is one element, so I'm done. So now at this point in the story, I have sorted, sort of idiotically, the 5 is sorted and the 2 is sorted. But what's the third and final step of this phase of the algorithm? Merge the two together. So here's the left, here's the right list. How do I merge these together? I compare the lists, and I put the 2 there. I only have the phi left, and I do that. So now we see some visible progress. But again, let's rewind. How did we get here? We started to sort the left half of the left half of the left half, then the right half. And now where are we? We've just sorted the left half of the left half. So what comes after sorting the left half of anything? Right half. All right, here's the sort of same nonsensical thing. Here's a list of size 2. Let's sort the left half. Done. Let's sort the right half. Done. What's the third step? Merge them together. So that's the 4, and that's the 7. What have I now done? In total, I've now sorted the left half of the original thing. So what happens next? Wait a minute. I have not done that. What have I done? I have sorted the left half of the left half, and I've sorted the right half of the left half. What do I now need to do, lastly? Merge those two lists together. So again, I put my finger on the beginning of this list, the beginning of this list. And if you want, I'll do the same thing when I merged last time to be clear what I'm comparing. 2 and 4, the 2 obviously comes first. What comes next? Well, the 4 comes next. What comes next? The 5 comes next. And then lastly, of course, the 7. Notice that the 2, 4, 5, 7 are now sorted. So the original left half is sorted. And now I'll do the rest a little faster because, my God, this feels like it takes forever. But I bet we're on to something here. What step remains next? I've just sorted the left half of the original. Sort the right half of the original. How do I sort this? I sort the left half of the right half. How do I sort this? I sort the left half of the left half. Done. I sort the right half of the left half. Done. Now I merge the two together. The 1 comes first. The 6 comes next. Now I sort the right half of the right half. What do? Sort the left half. Done. Sort the right half. Done. What do? Merge them together. So that's the third step of that phase. Now, where are we in the story? Oh my God. where are we in the story? We have sorted the left half of the right half and the right half of the right half. What comes next? Merge. So I'm going to compare, and I'm going to move those down just to make clear what I'm comparing, the beginning of both sublists. What comes first? Of course, the 0. What comes next? What comes next? The 1. What comes next? The 3. And then lastly comes the 6. All right, where are we in the story? We've now sorted the left half of the original and the right half of the original. What step remains? Merge. All right, so I'm going to make the same point. And this is actually literally what we did earlier, because I deliberately demoed those original numbers in this order, 2 and a 0. This comes out first. What comes next? 2 and 1. The 1 comes out next. What comes next? The 2 comes next. What comes next? The 3 comes next. What comes next? The 4. What comes after that? The 5. What comes after that? The 6. And lastly, this is when we run out of memory. The 7 over there is actually in place. OK. OK. So admittedly, a little harder to explain, and honestly gets a little trippy because it's so easy to forget about like where you are in the story, because we're constantly like diving into the algorithm and then backing back out of it. But in code, we could express this pretty correctly, and it turns out pretty efficiently. Because what I was doing, even though it's longer when I do it verbally, I was touching these elements a minimal amount of times. Right? I wasn't going back and forth in front of the shelf again and again. I was deliberately only ever merging the smallest elements in each list. So every time we merged, even though I was doing it quickly, my fingers were only touching each of the elements once. And how many times did we divide in half the list? Well, we started with all of the elements here, and there were 8 of them. And then we moved them 1, 2, 3 positions. So the height of this visualization, if you will, is actually log n. Right? If I started with 8, turns out if you do the arithmetic, this is log n height, because 2 to the 3 is 8. But for now, just trust that this is a log n height. And how wide is the shelf? Well, it's of width n, because there's n elements anytime they were on the shelf. So technically, I was kind of cheating this algorithm, because this is the first time I've needed shelves, right? With the human examples, we just had the humans and that's it, and only 8 of them. Here, I was sort of using more and more memory. In fact, I was using like 4 times as much memory, even though that was just for visualization's sake. Merge sort actually requires that you have some spare space, an empty array, to move the elements into when you're merging them together. But if I really wanted, and if I didn't have this shelf or this shelf, honestly, I could have just gone back and forth between the 2 shelves. That would have been sufficient. So merge sort uses more memory for this merging process. But the advantage of using more memory is that the total running time, if you can perhaps infer from that math, is what? The big O notation for merge sort, it turns out, is actually going to be n times log n. And even if you're a little rusty still on your logarithms, we saw in week 0, and again today, that log n is smaller than n. Right? That's a good thing. Any binary search was log n. That's faster than linear search, which was n. So n times log n is, of course, smaller than n times n, or n squared. So it's sort of lower on this little cheat sheet that I've been drawing, which is to suggest that its running time is indeed better or faster. And in fact, if we consider the best case running time, turns out it's not quite as good as bubble sort with omega of n, where you can just sort of abort if you realize, wait a minute, I've done no work. Merge sort, you actually have to do that work to get to the finish line anyway. So it's actually in omega and ultimately theta of n log n as well. So again, a trade-off there. Because if you happen to have a data set that is very often sorted, honestly, you might want to stick with bubble sort. But in the general case where the data is unsorted, n log n is sounding better than n squared. Well, what does it actually look or feel like? Give me a moment to just change over to our visualization here. And we'll see with this example what merge sort looks like depicted with now these vertical bars. So same algorithm, but instead of my numbers on shelves, here is a random array of numbers being sorted. And you can see it being done half at a time. And you see sort of remnants of the previous bars. Actually, that was unfair. Let me zoom out here. Let me zoom out so you can actually see the height here. let me go ahead and randomize this again and run merge sort. There we go. Now you can see the second array and where the values are going temporarily. And even though this one looks way more cryptic visualization-wise, it does seem to be moving faster, and it seems to be merging halves together, and boom, it's done. Let's actually see in conclusion what these algorithms compare to, and consider that moving forward as we write more and more code, the goal is, again, not just to be correct, but to be well designed. And one measure of design is going to indeed be efficiency. So here we have in final a visualization of 3 algorithms: selection sort, bubble sort, and merge sort from top to bottom. And let's see what these algorithms might look or sound like here. If we can dim the lights for dramatic effect. Selections on top, bubble on bottom, merge in the middle. Well, this is CS50, and already this is week 4. And recall that last week, week 3, we began to explore like the inside of a computer's memory a bit more. We talked about arrays, which were just chunks of memory back to back to back that really laid things out left to right, top to bottom. And this is actually a pretty common paradigm. Even if you're new to programming and certainly new to C, you've kind of seen this approach of just using memory in some way to lay things out, like images, for instance. So for instance, here is a photo taken of last week's front row, for instance. And this is kind of an opportunity to explore exactly what happens if we start to zoom in and zoom in and zoom in, because it seems like most any TV show, like CSI, whatever, or any movie that explores forensic information might have the investigators sort of zoom in on an image like this to see what the glint in someone's eye is, because that reveals like the license plate number of someone that just drove past, right? Something that's a little over the top there, but there's an opportunity here to speak to why that is so unrealistic. For instance, let's zoom on this puppet here's eye, and let's zoom in a little more to see what might be reflected. Let's zoom in a little more. And that's it. There's only finite amount of information if you have an image represented in this way using pixels, these dots on the screen as rows and columns, because if you're only using a finite amount of memory, then at the end of the day, you can only store a finite amount of information. And at least I don't really see in this grid here any glint of a license plate or something like that that you might otherwise see in Hollywood. So today we'll explore sort of these kinds of representations of how you might use memory in new and interesting ways to represent now very familiar things, but also start to explore what some of the limitations are of this representation. But consider, after all, that this doesn't need to be even as high resolution, as many pixels as something like this other image. You could imagine just doing something silly with Post-it notes like this. And if you think of an image as just having rows and columns, these rows otherwise known as scan lines, something we'll explore in the coming week, you could make this sort of fun smiley face by just using two different values, maybe a 0 and a 1, or yellow and purple, or vice versa, just to kind of make something come to life. Now, in practice, recall, we talked about storing not just a 0 or 1, but maybe an R, a G, and a B value, like 24 bits or 3 bytes in total. But we'll come back to that. That would just be a more involved image. But if for fun, if today you sort of want to tackle something passively in the background, if you go to this URL here, we've put together an opportunity to do a sort of a bit of pixel art. If you go to this URL here, that'll redirect you to a Google spreadsheet if you have a laptop with you today. That'll look a little something like this, which we've sort of organized in rows and columns. So if you'd like to go ahead and use Google Spreadsheet's colorization feature to color in those individual squares, if you'd like, see if you can't make something a little creative, and then email it to Carter, and we'll exhibit some of the best or favorites on the website thereafter. So let's transition then to something a little more familiar, images. And not all of you have used, presumably, Photoshop, but you're probably generally familiar with Photoshop as a program for editing and creating images or photos or the like. And here is a screenshot of Photoshop's color picker, via which you can change like what color you're going to draw with the paintbrush, or what color you're going to fill in with the paint bucket. It's representative of any kind of graphical tool. And there's kind of a lot of information in here, but there's perhaps some familiar terms now, R, G, and B. In fact, right now, this is Photoshop's way of saying you're about to fill in your background or foreground with the color black, and that appears to be represented with an R, a G, and a B value of 0, 0, 0, or alternatively, using a hash symbol and then 0, 0, 0, 0, 0, 0. And if some of you have already made web pages before and you know a little bit of HTML and CSS, you probably are familiar with this kind of syntax, like a hash symbol and then 6 or sometimes 3 digits thereafter. And if we look at a few different colors here, for instance, here might be the representation of white. Now the R, the G, and the B values went way up from 0 to 255, 255, 255. Or alternatively, it looks like Photoshop, and in turn web browsers, could represent that same color white with FF. And let's just do a few others. Here is red. And it turns out that red is a whole lot of red, 255, but no green, no blue. Or AKA FF0000. So there's perhaps a pattern here emerging. Here is green, 0, 255, 0. AKA 00, FF00, or lastly here, blue, which is no red, no green, but apparently a lot of blue, 255 again, AKA 0000, FF. Now, some of you, again, might have seen this notation before, these zeros and these Fs and all of the numbers and letters in between. But this is another form of notation. And in fact, we'll explore this today. Really is just a precondition for talking about some other concepts. But the ideas ultimately are really no different. What we're about to see is a different base system, not just binary, not just decimal, but something we're about to call hexadecimal. But first, recall that with RGB, we previously did the following. Any RGB value, red, green, blue, just combine some amount of red or green or blue. So here we have 72, 73, 33, which in the context of an email or a text, of course, said what a couple weeks back? Just hi with an exclamation point. But in the context of a Photoshop-like program, this might instead be representing collectively this shade of yellow, for instance, when you combine that much red, that much green, that much blue. So here is the same idea. If you've got a lot of red, no green, no blue, together that's going to give us red. If you've got no red, a lot of green, no blue, that's going to give us, of course, green. If you've got no red, no green, a lot of blue, that, of course, is going to give us blue. So there's a pattern emerging here where apparently 0, 0 is none, as always, and FF is apparently a lot. And it's maybe somehow equated with 255, at least per that Photoshop screenshot. Meanwhile, if we combine one last one, a lot of red, a lot of green, a lot of blue, that's actually going to give us a single white pixel like this. All right, so think back. Here was binary. In the world of binary, you had just 2 digits, 0 and 1. Could have been anything else, A or B, X or Y, but the world standardized on these numerals, 0 and 1. In our world's decimal system, of course, you have 0 through 9. As of today, though, we're going to start using hexadecimal sometimes in the context of images and also files, just because it's a convention. There's some conveniences to it, where now you're going to be able to count up to F in a notation called hexadecimal. From 0 through 9, then you keep going to A to B to C to D to E to F. The idea being each of these, even though it's weirdly a letter of the English alphabet, it's still just a single symbol. It's not 1 0 for 10 or 1 1 for 11. All 16 of these values, these digits, so to speak, are indeed still just single symbols. And that's a characteristic of just using this other notational system. So how do we get from 0 0 and FF to something like 0 and 255 respectively? Well, this hexadecimal system, aka base 16, just does the math from week 0 and really grade school a little bit differently. For instance, if you have a number that's got 2 digits, or hexadecimal digits as of today, the columns are just a little different. Instead of powers of 2 or powers of 10, which we saw for binary and decimal respectively, it's powers of 16. So if we just kind of do the math out, that's the 1's column, this is the 16's column, and so forth. Things get actually pretty big pretty quickly in this system. But now let's just consider how we would represent familiar numbers. If you've got 2 hexadecimal digits, for which these hashes are just placeholders, 0 0 is going to mathematically equal the decimal number you and I know, of course, as 0. Why? Same thing as week 0. 16 times 0 plus 1 times 0 is the number you and I know as 0. And we can count up from here. This in hexadecimal would be how a computer represents the number we know as 1. It would be 0, 1 in this case. This would be 2, 3, 4, 5, 6, 7, 8, 9. In decimal, we're about to go to 10. But in hexadecimal, to be clear, what comes next? So apparently A, so 0A, 0B, which is now 10 or 11 or 12, 13, 14, 15. So using hexadecimal is just kind of an interesting way of using single symbols now, 0 through F, to count from 0 through 15. And we'll see why it's 15 in a moment. But as soon as we get to F, anyone want to conjecture how in hexadecimal, aka hex, do we now count up one position higher? What comes after 0F in hexadecimal? So 1 0. It's the same kind of thing. Like once you're at the highest digit possible, F, or in our decimal world it would have been 9, you sort of add one more, and 9 wraps around to 0. Or in this case, F wraps around to 0. You carry the 1, and voila, now we're representing the number you and I know as 16. And we could keep going forever, literally. This could be 17, 18, 19, 20 in decimal. But let's just wave our hands at it and count as high as we can, dot, dot, dot. The highest we could count in hexadecimal with 2 digits just logically would be what in hexadecimal? Something, something. FF, I heard. So yes, that's the biggest digit possible. So FF is what we have. So how high can you count in hexadecimal if you've got just 2 of these digits? Well, it's the same math as always. 16 times F, aka 15. So that's 16 times 15 plus 1 times F, or 1 times 15. That gives us 240 plus 15 in decimal, the result of which, of course, now is 255. So this hexadecimal system you may have seen in the world of web pages, and if you haven't, we'll get to that in this class in a few weeks, or we just saw in the context of Photoshop, just has this sort of shorthand notation of counting as high as 255, but just calling it FF. Now, it's marginal, but that's like 50% savings of how many digits you need in order to count as high as 255, because in decimal, of course, 255 is 3 digits. In hexadecimal, you can count as high using just 2. And that difference is going to get magnified the bigger our numbers get. Let me stipulate for now, you're going to get more and more savings in terms of just how many symbols you need on the screen to represent bigger and bigger numbers than that. All right, let me pause here just to see if there's any questions thus far on what we've called hexadecimal, which again just gives us 0 through 9 as well as A through F. Any questions or confusion? And if it feels like we're lingering a bit much on arithmetic, we're not really going to see other notations besides this moving forward. These are sort of the go-to 3 in a programmer's world, typically. But there are some others. Yeah? Good question. Does hexadecimal require more storage or less storage than a decimal system? Theoretically, no, because this is just a way of representing information. And we'll see in a concrete example in a moment. But inside of the computer, at the end of the day, you're still storing bits. And using hexadecimals, not using more or fewer bits, think of this as how you might write it down on a piece of paper, just how many digits you're going to write, or on a computer screen, how many digits you're going to see at once. But it doesn't change how the computer is representing information, because all they're representing at the end of the day is zeros and ones. So in fact, let's go there. If this, a moment ago, FF, I claim was 255. Let's just rewind to week 0. And if we wanted to count to 255 in binary, that's as high as you can count, recall, with 8 bits. And there's only a few of these numbers that are useful to memorize. Like 255 is as high as you can count with 8 bits if you start at 0, because 2 to the 8th is 256. But if you start at 0, it's 0 through 255. So in binary, recall, if you have 8 bits, all of which were ones, and I won't do out the math pedantically here, but if I do this plus this plus this dot, 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 that's also going to give me 255. So this is what's interesting here about hexadecimal. It turns out that an upside of storing values in hexadecimal is that we're going to see the first F sort of represents the left half of all these bits, and the second F, in this case, represents the rightmost 4 of these bits. So it turns out hexadecimal is very useful when you want to treat data in units of 4. It's not quite 8, but units of 4, and that's not bad, which is why if you use 2 digits like I have thus far, 00, 0 or FF or anything in between, that's actually a convenient way of representing 8 bits in total. 1 hex digit for the first 4 bits, 1 hex digit for the second. And again, there's nothing new intellectually here per se. It's just a different way of representing the same story as before, zeros and ones. So in what context do we see this? Well, we talked about memory last week, and we're going to talk more about it this week. If this is my computer's RAM, random access memory, you can again think of each byte as having a number associated with it, like its address or location. This might be 0. This might be like 2 billion. And so in the past, I described these as just this, using decimal numbers. Here's byte 0, 1, 2, 3, 4, 5, 6, 7, 15, 16 would be here, and so forth. But it turns out in the world of memory, and thus today programming, people tend to count memory bytes using hexadecimal. Partly just by convention, but also partly because it's a little more succinct. And again, each digit represents 4 bits, typically. So what comes after F here? Well, if I think about the computer's memory, I normally might do after F, which is 15, 16, but instead 1, 0, 1, 1, 1, 2, 1, 3. This is not 10, 11, 12, 13, because I claim them in the context of hexadecimal now. As per the previous slide, we already started going into A's through F's. So you immediately see here a possible problem. Like, why is this now worrisome if all of a sudden you're seeing seemingly familiar numbers like 10, 11, 12, 13? We didn't really stumble across this problem when it was like all zeros and ones before. Yeah? Yeah, so if you're writing some code in C that's doing some math, you might accidentally, or the computer might accidentally confuse hexadecimal with decimal if they look in some context the same. I mean, any number on the board that doesn't have a letter is ambiguously hexadecimal or decimal at this point. And so how might we resolve this? Well, it turns out that what computers typically do is this. By convention, anytime you see visually 0x and then a number, that's a human convention of signaling to the reader that this is in fact a hexadecimal number. So if it's 0x10, that is not the number 10. That is the hexadecimal number 10, which, recall we said earlier, is how you count up to 16. And again, these are not the kinds of things to memorize. It's really just the system for how you think about these things. So henceforth today, we're going to start seeing hexadecimal in a bunch of contexts. When you write code, you might even write code using some hexadecimal. But again, it's just a different way of representing numbers, and humans have different conventions for different contexts. All right, so with that said, any questions now on this building block? But here on out, we'll start using it in some actual code. Any questions? Nothing so far? All right, so let's go ahead and consider maybe a familiar example, something involving code where I initialize a variable like n to a value like 50 in this case, and then let's start to tinker around with what's going on inside of the computer's memory. In a moment, I'm going to load up VS Code on my computer, and I'm going to go ahead and whip up a program that very simply assigns a value like the number 50 to a variable called n. But today, keep in mind that that variable n and that value 50 is going to be stored somewhere in my computer's memory. And it turns out today we'll introduce a bit more syntax so you can actually see where things are being stored. So let me click over to VS Code here. I'm going to create a program called address.c just to explore computers' addresses today. And I'm going to do an include standard io.h, int main void, as usual, no command line arguments for now. I'm going to declare that variable n equals 50. And then I'm just going to go ahead and print it out. So nothing very interesting, but I'll use %i, \n, and then comma n to print out that value. Nothing here should be very interesting to compile or run, but I'll do it just to make sure I didn't make any mistakes. Looks like, as expected, it simply prints out the number 50 like this. But let's consider then what this code is doing underneath the hood when it's actually run on your machine. So here we have that grid of memory. That variable n is an int. And if you think back, how many bytes typically do we use for an int? Yeah. 4. So 4 bytes or 32 bits. So if each of these squares represents 1 byte, then my computer somewhere in my memory or RAM is using 4 of these squares. Maybe it ends up over here just because there's other stuff being used elsewhere, for instance. Though I don't really know. And frankly, I don't really care where it ends up, just that it ends up somewhere. So the value 50 is stored here in a variable called n. Even though I've written it as decimal, just like in my code, let me again remind that this is 32 zeros and ones representing that 50. It's just going to be very tedious if we start writing everything in binary, so I'll use the more comfortable human decimal system. So that's what's going on inside of the computer's memory. So what if I actually wanted to start tinkering with its location, or maybe just knowing its location? Well, this variable n indeed has a name, n. That's a label of sorts for it. But at the end of the day, that 50 is technically at a specific address. And I'm going to make one up, 0x123. And it's 123 because I really don't care what it is. I just want an address for the sake of discussion. So way over here off screen might be byte 0. Way down here is byte 0x123. It's in hexadecimal notation just by convention. So how can I actually see where my variables are ending up in memory if I'm curious to do so? Well, let me go back to my code here. And let me actually change this just a little bit. Let me go ahead and introduce, for instance, another symbol here and another topic altogether, namely pointers. So a pointer is a variable that stores the address of some value, the location of some value, or more specifically, the specific byte in which that value is stored. So again, if you think of your memory as being a whole bunch of bytes, 0 at top left, 2 billion or whatever at bottom right, depending on how much RAM you have, each of those things has a location and an address. A pointer is just a variable storing one such address. So it turns out that in the world of C, there's a couple of new symbols we can use if we want to see what it is we're talking about here. And those two operators, as of today, are these. You can use the ampersand operator in C in a couple of ways. We already saw it very briefly to do ampersand, ampersand, to kind of and two Boolean expressions together in the context of a conditional. This is different. A single ampersand is the address of operator. So literally in your code, if you've got a variable like n or anything else, and you write ampersand n, C is going to figure out for you what is the address of that variable n in the computer's memory. And it's going to give you a number, otherwise known as the address of that. If you want to store that address in a variable, even though, yes, it's a number, like 0x123, you have to tell C in advance that you want to store not an int per se, but the address of an int. And the syntax for doing that, somewhat non-obviously, is to use an asterisk here, a star operator. And you say this when creating the variable. If you want p to be a pointer, that is the address of some other variable, you do int star p. And the star just tells the computer, this is not an integer per se. This is the address of something. That yes is an int, but we're just being more precise. So on the right-hand side, you have the address of operator. As always, with the equal sign, you copy from right to left. Because ampersand n is by definition the address of something, you have to store it in a pointer. And the way to declare a pointer is to specify the type of value whose address you're storing, and then use the star to indicate that this is indeed a pointer and not just a regular old int. So let's see this in practice. Let me go back to my own source code here. and let me make just a couple of tweaks. I'm going to leave n alone here, but I'm going to go ahead and initially just do this. Let me say int star p equals ampersand n. And then down here, I'm going to print out not n this time, but p, the variable p. And then even though, yes, it's just a number, and therefore I kind of sort of could use %i for integers, there's actually a special format code in printf for printing pointers or addresses, and that's %p. So now let's go ahead and recompile this, make address. So far, so good. /address, enter. And a little weirdly, but perhaps understandably now, the address in my computer's memory at which the variable n happened to be stored was not quite as simple as 0x123. This computer has a lot more memory, so technically it was stored at 0x7ffcb4578e5c. Now that has no special significance to me. It could have ended up somewhere else altogether, but this is just where in my computer, or technically the cloud server to which I'm connected using VS Code here, that just happens to be where n ended up. And strictly speaking, I don't even need to introduce this variable. I could get rid of p, and I could just say print not just n, but the address of n, and achieve the same thing. You don't need to temporarily store it in a variable. Let me just do make address again, /address, and now I see this address here. And notice if I keep running the program, it's actually moving around. There's other stuff presumably going on inside of the computer. Maybe it's actually randomizing it so it's not always at the same location. That can actually be a security feature underneath the hood. But this happens to be at that moment in time where that value is in memory, quite like our picture a moment ago. All right, so let me pause here to see if there's now any questions on what we just did. Yeah?
Is there any way to control where you are storing something in memory? And does it even matter or does it just matter that you can go in and locate it?
Really good question. Is there any way to control where something is in memory? Short answer is yes. And this is both the power and the danger of C. And we're going to do this today and make a few deliberate mistakes, because with this power of going to or getting the address of any variable, I could just arbitrarily right now write code that stores a value at like byte 2 billion or 0 or anything in between. But that also means potentially I could start kind of creepily looking around at all of the computer's memory, even at things that I didn't put there, maybe other programs, maybe other parts of programs. And indeed, this is a potential security threat. If suddenly you're able to just look anywhere you want in the computer's memory. Now, I'm overselling it a little bit because nowadays, in this decade, there are some defenses in place in compilers and in our operating systems that do hedge against this a little bit. But this is still a very frequent source of problems. And later today, we'll talk briefly about things called Stack Overflow, which is not just a website. It is a problem that you can encounter. Heap overflow and more generally buffer overflows. There's just so many things that can go wrong using this language called C. And if any of you have encountered a segmentation fault yet, I think we saw a few hands for that already, you touched memory that you shouldn't have. And odds are you did it most recently by going too far in an array, going to the left or negative in an array, or somehow looking at memory you shouldn't have. And we'll explain today why it is you were able to do that. Other questions on these primitives so far? Yeah, from Carter? Good question. Earlier we used star p. Let me rewind in time to the previous version of this code where I actually had a variable called p. Just like with variable declarations in the past, once you've declared a variable to be an int, a char, a bool, or an int star, aka a pointer, you don't thereafter keep using the word int or now the star. Once you've declared it, that's it. You only refer to it by name. And so it's very deliberate what I did here, saying that the type here is int star, that is a pointer to an int. But here I just said the name of the variable as always. I didn't repeat int, and I also didn't repeat star. But at the risk of kind of bending one's minds a little bit, there is unfortunately one other use for the star operator, and that's as follows. If you want to print out not the address of something, but what is at a specific address, you can actually do this. If I want to print out the integer via %i that is at that address, I can actually use the star here which technically contradicts what I just said, but it has a different function here, different purpose. So let me go ahead and do this in two different ways. I'm going to leave this line of code as is, but I'm going to add another line of code now that prints out what apparently will be an integer in a moment. So %i\n. And I could cheat and let me just do n for now. So there's really nothing special happening now. I'm just adding a sort of mindless printing of n. So make address, /address. There's the current address of n, and there's the value of n. But what's kind of cool about C here, too, is if you know that a value is at a specific address like p, there's one other use for this star operator, the asterisk. You can use it as the so-called dereference operator, which means go to that address. And so here what we actually have is an example of a pointer p, which is an address like OX123 or OX7FF and so forth. But if you say star p now, you're not redeclaring the variable, because I didn't mention int. You're going to that address in p. So let me recompile this now. Make address, /address. And just to be clear, what should I see? I'm first going to see the pointer itself, OX something. What's the second line of output I should presumably see now? Just shout a little louder. So I'm hearing 50. And that's true because if you figure out the address of n and print it in line 7, but then go to the address of n, aka p, that's indeed going to just show you the number n, the value of n again. All right, any questions now on this syntax? And I will concede, I think this is confusing. The fact that we use the star for multiplication, the fact that we use the star to declare a pointer, but then we use a star in a third way to dereference the pointer and go to the pointer. It's just confusing, honestly, but with practice comes comfort. Yeah? Good question. When you are using the ampersand operator to get the address of something, the onus is on you at the moment to know what you are getting the address of. Is it a string? Is it a char? Is it a bool? Is it an int? I wrote this code, so I know in line 6 that I'm trying to get the address of what is an integer. In line 8, you don't have to worry about that. Good question. Notice in line 8, I didn't tell the computer, other than the %i, what kind of address I'm going to. But I did already. In line 6, I told the compiler that p, now and forever, is going to be the address of an int. That's enough information in advance so that printf, or really the language C, still knows on line 8 that p is a pointer to an int. And that way, it will print out all 4 bytes at that address, not just part of it, and not more than those 4 bytes. Good question. Yeah, next to you. Do pointers have pointers? Yes. We won't sort of do this today by having pointers to pointers. But yes, you can use star, and then things get in. I'm sorry. We won't do that today, and we won't do that often. In fact, Python, another language, is just a couple of weeks away. So hang in there. Almost there. Question back here? Was there? That was amazing. Good. More verbal feedback like that is helpful as we forge into the more complicated stuff. Other questions? Yeah. What's the point of printing the address? Sure. What's the point of doing this? If you don't mind, let's get there in a moment. This is not the common use case, just printing out the address. Like, who really cares? At the moment, we care only for the sake of discussion. We're soon going to start using these addresses. So hang in there just a little bit for that one, too. But it will solve some problems for us before long. So let's actually just now depict what was going on inside of the computer's memory just a moment ago. So if I toggle back here, let me redraw my computer's memory, and let me plop into the memory n, which is storing in this program the number 50. Where is p in my computer's memory? Specifically, I don't know, and apparently it moves around each time I run the program. So for the sake of discussion, let's just propose that if 50 ended up at address OX123, I don't know, p ends up over here at address, at whatever address this is here. But notice a couple of curiosities now. If p is a pointer, it's the address of something. So the value in p should be an address, and I've indeed written it as such, 0x123. And technically, there's not an x there, there's not a 0 there, there's not even a 123 there per se. There's a pattern of bits that represents the address 0x123. But again, that's week 0. Don't care about binary day to day. So if this is p, and this I claimed was n, why is p so much bigger? Can someone conjecture here? Because it turns out whether n is an int or a char or a bool, which are different types, heck, even a long, it turns out that p is always going to take up 8 squares on the board. But why might that be? What might explain that? Yeah, thoughts? OK, fair. Maybe it's allocating 8 bytes because it doesn't know the type. Turns out that's OK, because an address is an address. It's really up to the programmer to use it as a string or a char or a bool. Other thoughts?
Maybe like the first chord for the actual numbers and the last chord, like some null thing where you say that, oh, well, where that pointer ends.
OK, possibly. It could be that pointers have some complexity, like a \n or something curious like that, like we talked about for strings. Turns out that's not the case. It turns out that pointers nowadays typically are, but not always, are 8 bytes, aka 64 bits, because you and I, our Macs, our Ps, heck, even our phones, have a lot more memory than they did years ago. Back in the day, a pointer might have only been 32 bits, or even only 8 bits, way back in the day. But consider 32 bits, because that was the norm for some time. How high can you count roughly if you've got 32 bits? What's the number we keep rattling off? 32 bits is roughly 2 to the 32. So it's 4 billion. And I keep saying it's 2 billion if you do negative. But in the world of memory, there's a reason I keep saying 2 billion bytes, 2 gigabytes. Because for a very long time, that was the maximum amount of memory a computer could have. Why? Because the pointers that the computers were using were only, for instance, 32 bits. And with 32 bits, depending on whether you allow for negatives or not, you can count as high as 2 billion roughly, or maybe 4 billion. But you know what? Your Mac, your PC, your phone could not have had 5 gigabytes of memory or 5 billion bytes of memory. You certainly couldn't have had what computers nowadays come with, which might be 8 gigabytes of memory, 16 gigabytes of memory. Why? Because with 4 bytes or 32 bits, you literally physically can't count that high, which means if I drew a picture of all of the memory, we would run out of numbers to describe them, which means like most of my memory would just be unusable. So pointers nowadays are 64 bits or 8 bytes. That's really big. I can't even pronounce how big that number is, but it's plenty for the next many years. And so we've drawn it that way on the board here. Now, let's just kind of abstract this away. Let's get rid of all the other bytes that are storing something or nothing else. And let's now start to abstract away this complexity, because the reality is, to your question earlier, what is this useful for? Or what do we actually care about these addresses? Generally, no. We're doing this so that you see there's no magic. We're just moving things around and poking around in memory. But what a person would typically do when talking about pointers would literally be to just point at something. Like, I really don't care what address n is at. So it suffices when drawing pictures on a whiteboard, having a discussion with another programmer, you just kind of draw an arrow from the pointer to the value in question, because neither you nor I probably care about the specifics of 0x whatever. So there's your pointer. It's literally an arrow. And we can kind of see this. So it turns out that these pointers, these addresses, are not that dissimilar to what we've done for hundreds of years in the form of a postal system. For instance, here's a post office. Here is a mailbox. And suppose that this is a mailbox labeled P. It's a pointer. And suppose there's another mailbox like way over there, which is just another byte of my computer's memory. What are we really talking about? Well, you store in a computer's memory values like the number 50 or the word like hi inside of your computer's memory at some location. But today, we can also use those same memory locations to store the address of things. For instance, if I open this up here and I see, OK, the value inside of this mailbox is not a number like 50. It's actually an address, 0x123. That's kind of like a pointer, sort of a breadcrumb leading from one location in memory to another. And in fact, would someone who's seated roughly over there, do you mind getting the mail over there? Any volunteers over in this section? Just need you to get to the mailbox before I do. Who's being volunteered? Oh, yes, please. Whoever is gesturing most wildly. Come on down. Sure. What's your name? Say again? Anfu? OK, come on up to the edge of the stage there. And just to be clear, if this is p, that is apparently n. But to make clear what we're talking about when we're storing ox whatever values, like ox123, that's essentially equivalent to my, maybe pulling out something like this and just abstractly pointing to your mailbox there, or if you prefer, pointing to the mailbox. OK, all right. Oh, thank you. All right. This is akin to me pointing at your mailbox. And if you want to go ahead and open your mailbox and reveal to the crowd what's inside your mailbox, labeled N. All right. Thank you. We have a CS50 stress ball for your trouble. Thank you for coming up. So that's just to put a visual on what it is we're talking about, because it can get very abstract, very cryptic quickly when we're talking about addresses and memory and drawing it like these little squares. But if you think about just walking into a post office or an apartment complex that's got a lot of mailboxes, those mailboxes essentially are a big chunk of memory. And each of those mailboxes has an address. This is apartment 1, 2, 3, apartment 2 billion. And inside of those mailboxes can go anything that can be represented as information. It could be a number like n or 50, or if you prefer, it could be a number that represents the address of another mailbox. And this is akin, really, if you've ever had an apartment or you and your parents have moved, to having a forwarding address. It's like having the post office in the US put some kind of piece of paper in your old mailbox saying, actually forward it to that other mailbox. That really is all a pointer is doing. At the end of the day, it's just a number, but it's a number being used in a different way. And it's the syntax that we've introduced, not just int, but int star, that tells the computer how to treat that number in this slightly different way. All right, any questions then on this? Yeah, in back. If I did int c and said it, can you say the code again? Once more? Equal to n. So let me actually type it out. If I give myself another line of code, tell me one last time what to type. Int is equal to n, like this. So this is OK. And I can't draw it quite quickly enough on the board here. But this would be like creating another 4 bytes somewhere in memory, maybe down here, that stores an identical copy of 50, because the assignment operator from right to left copies one value to another. So that would just add one more rectangle of size 4 to this particular picture, if I'm answering your question as intended. OK, so that is sort of week 1 style use of assignment operators before pointers. I could, though, start copying pointers. But again, we'll come back to some of that complexity. Any other questions here? Ah, good question. Short answer, no. To repeat for the camera, if I create a second variable like this, int c equals n, and I claim, without actually drawing it on the board, that this gives me another rectangle, the value of which is also 50, p does not get touched. And this is what's important and really characteristic of C. Nothing happens automatically for you. Like p is not going to be updated unless you update p in some way. So creating a third variable called C, even if you're copying its value from right to left, that has no effect on anything else in the program. A good question. So what have we seen that's perhaps now a little more explainable? Well, recall that we talked quite a bit last week about strings. And just to recap, in layperson's terms, like, what is a string as you now understand it? Say, let me take a specific hand here. What's a string? How about over here? OK, sure. Both of you are right. An array of characters. An array of characters. And I claimed or revealed last week that string is not technically a feature built into C. Like, it's not an official data type. But every programmer in most any language refers to sequences of characters, words, letters, paragraphs, as strings. So the vernacular exists, but the data type doesn't typically exist per se in C. So what we're about to do, if you will, for dramatic effect, is take off some training wheels today. The CS50 library, implemented in the form of the header file, cs50.h, we claim has had a bunch of things in it. Prototypes for getString, prototypes for getInt, and all of those other functions. But it turns out it also is what defines the word string in such a way that you all can use it these past several weeks. So let's take a look at an example of a string in use. Here, for instance, is a tiny bit of code that uses the word string, creating a variable called s, and then storing quote unquote high exclamation point. Let's consider what this looks like now in the computer's memory. I don't care about all the other bytes. Let's just focus on these. And this, per last week, is how high might be stored. HI exclamation point, and then one more, as someone already observed, that sentinel value, that null character, which just means 0 bits to demarcate the end of that string. Just in case there's something to the right of it, the computer can now distinguish one string from another. So last week, we introduced this new syntax. Well, if strings are just arrays of characters, you can then very cleverly use that square bracket notation and go to location 0 or 1 or 2, which are kind of sort of like addresses, but they're relative to the string, right? This could be at 0x123 or 0x456. But with this bracket notation, 0 is always the beginning of the string, 1 is the next, 2 is the next, and so forth. So that was our array syntax for indexing into an array. But technically speaking, we can go a little deeper today. Technically speaking, if high is starting at the address 0x123, then it stands to reason that I is at 0x124, exclamation points at 0x125, and the null is at 0x126. Now, I don't care about 123 per se, but even though this is hexadecimal, this is correct math. Even in hex, if you just add 1 when you start at 0x123, the next number is 4, 5, 6 at the end. I don't have to worry about A's, B's, and C's because I'm not counting that high in this example. So if that's the case, and my computer is actually laying out the word high in memory like that, well, what exactly is S? Right? What exactly is S if at the end of the day, HI exclamation point null are stored at these addresses? Like, where is S? Like, now that I've kind of taken off those training wheels and showed you where HI exclamation point null actually are, what happened to S? Well, S, as always, is actually a variable, right? Even in the code I proposed a moment ago, S is apparently a data type that, yes, doesn't come with C, but CS50's library makes it exist. S is a variable of type string. So where is S in this picture? Well, it turns out that S might be up here. Again, I'm just drawing it anywhere for the sake of this discussion. But S is a variable per that line of code. What S is storing, apparently, I claim, is 0x123. I actually don't really care about these addresses, so let's abstract that away. S is apparently, as of now, today, 1 week later, just a pointer to a character, specifically the first character in S. And this is kind of the last piece of the puzzle. Last week, we had this clever way of demarcating the end of a string. Well, it turns out that strings are represented in the computer's memory as a variable that is a pointer inside of which is the address of the first character in the string. So if S is points at the first character, and you can trust that \0 is at the end of the string, that's literally all you need to figure out where a string begins and ends. So what do I mean by this? Well, let's be a little more concrete. In terms of this picture, if I've started with this line of code here, it turns out all this time since week 1 that the word string has just semi-secretly been an alias for char star. I know, so char star. So why does this make sense? It's a little weird still, but if in our previous example, we were able to store the address of an integer by declaring a variable called p as int star p. Well, if as of now strings are just the address of the first character in a string, then probably a string is just a char star, because that means S is the address of a character, the very first character in the string. Now, the string might have 3 letters like it did, or 4, or even 100 if it's a long paragraph, but that's fine because you can trust that there's going to be that null character at the very end. So this is a general purpose way of representing strings using this new mechanism in C. So in fact, let me go ahead here and introduce maybe a couple of manipulations of this. Let me go back to my code here, and let's get rid of this integer stuff. And let's instead now do, for instance, this. Let me add in the CS50 library. So we'll include CS50.h for now. I'm going to go ahead and inside of main give myself a string S equals high exclamation point. I don't type the \0. C does that for me automatically by using my double quotes like this. Now let me just go ahead and print it. So this again is sort of week 1 style stuff where I'm just printing a string, no pointers yet. So let me do make address, enter, /address, and hopefully I see hi. So nothing new there. But let's start to peel back some of these layers here. Let me first of all get rid of the CS50 library for a moment. And let me change string to char star. And it's a little bit weird, but yes, the convention is to say char, a space, then the star, and then immediately thereafter the name of the variable. Strictly speaking, though, you might see textbooks or websites that do it like this or like this, but the canonical way is typically to do it like that. So now no more CS50 library, no more training wheels, if you will. I'm just treating strings for what they really are. Let me go ahead and do make address, enter. So far, so good, /address. And that too still works. So %s is a thing. That comes with printf because the word string is programmer terminology. But strictly speaking, C doesn't have a string data type. It's always been char star. So what this means now is I can start to kind of have some fun with these basic ideas, even though this is not purposeful other than for the sake of discussion. But if s is this, let me go back and give myself the CS50 library. Let's put those training wheels back on for just a moment so that I can do one manipulation at a time. Here's my string s, as before. Well, let me go ahead and declare a char called c. And let me store the first character in the string there, which is s bracket 0. And that should give me h. And then just for kicks, let me go ahead and do char star. Whoops. Let me go ahead and do char star p equals ampersand c and see what this actually prints for me. Let me go ahead and print out what p is here. So we're just playing around. So make address. So far, so good. /address. All right. So what have I just done? I've just created a char c and stored in it the letter h, which is the same thing as s bracket I. Then I'm saying, what's the address of c? And that's apparently 0x7ff whatever. So that's the address. But I technically didn't have to do that. Let me go ahead and do two things now. Instead of just printing p, let me go ahead and print out maybe s itself. Let me go ahead and do make address, enter. So far, so good. /address. And damn it, what did I do? Oh, shoot. I didn't want to do that. Oh, I really made a mess of this. What did I want to do here? That was supposed to be impressive, but it was the opposite. So let me turn it around. So if I intended to do this, why are lines 9 and 10 printing different values? Didn't really intend to go here, but let me try to save this. Why are we seeing different addresses? Namely, this address, 402004 for S, and then 0x7ff for P. Any thoughts? Yeah, over here. Correct. So if I really wanted to weasel my way out of this, this is a great answer to the previous question, which was about what if I introduce another variable c that's a copy of the value, and not in this case an int, but an actual char. Here I've made c be a copy of the character that's at the beginning of s, but that's indeed a copy. So if I were to draw it on the screen, that would give me a different rectangle in which this copy of h would actually be stored. So I didn't intend to do this, but what you're seeing is, yes, the address of s, and apparently that's at a pretty low address by default here. Then you're seeing the address of c, but even though each of them is h, I claim one is at a different address in memory. And this has always been happening. Anytime you created one variable or another, it was ending up here or here or here or somewhere else in memory. Now, for the first time, all we're doing is actually just poking around the computer's memory to see what is actually there. So let me actually back this up a little bit and do what I intended to do here, which was something like this. So if string s equals quote unquote hi, let's go ahead and give myself a pointer called p to the first character in s. All right. So now let me go ahead and print out the value of this pointer, %p, printing out p. So we're just going to do one thing at a time. So make address, enter, /address. There at the moment is the address of the first character in s. What I meant to do now was this. If I want to print out two things this time, let me print out not only what p is, but also what s itself originally is. Because if I claim that everyone from last week should be comfortable with s bracket 0 just representing the first character in s, by definition of strings being arrays of characters, then s, as of today, is itself the address of a character, the first one in s. So if I now do make address and do /address, this time I see the same exact things. Thank you. This is really like the lamest sort of thing to be applauding over. But what we're demonstrating here is that s is by definition the address of the first character in C. So if we borrow some of our mental model from last week, well, if s bracket 0 is the first character in C, doing the ampersand on that expression should be the same as s. Now, this isn't to say that we would kind of jump through these hoops all the time with this much syntax, but this is just to do proof by example that s is, in fact, as I claimed a moment ago, just the address of a character, not even multiple characters. It's the address of a single character. But the key thing is it's the address of the first character in the string. And per last week, we trust that C is going to look for that null character at the very end just to make sure it knows where the string actually ends. All right, a question came up over here. Correct. To summarize, on line 8, when I am using %p, that just means print a pointer value, so 0x something, I'm passing it s. Previously, when we used %s, printf knew to print not just the first character of s, but h, I, exclamation point, and then stop when it hits the \0. %p is different. %p tells the computer to go to that address, tells the computer to print that address on the screen. So this is where %s all this time has been powerful. The reason printf worked in week 1 and 2 and 3 was because printf was designed by some human years ago to go to the address that's being passed in, for instance s, and print out character after character after character until it sees the null character, \0, and then stop printing it. So you're getting a lot of functionality sort of for free from %s. Today, we're using something much simpler, %p, which just literally prints what s is. And the reason we don't do this in week 1 is just because this is like way too much to be interesting when all you want to print out is hi or hello world or the like. But now what we're really doing is revealing what's been going on this whole time. And let me make one other example here. Let me go ahead and get rid of this variable here. And let me just print out a few things to make this same point. I'm going to print out not just s, like I did here, but let's go ahead and print out the address of every character in s. So let's get the first letter in s and get its address. And I'm going to do copy paste for time's sake, but not something I would do frequently. So let me print out the address of the first character, the second character, the third, and actually even the fourth, which is the \0, by doing this. So when I compile this program, make address, /address, I should see 2 identical values and then additional values that are 1 byte away. In my diagram a moment ago, my addresses were arbitrarily 0x123, 124, 125, 126. Now it starts at, by chance, 0x402004, which is s. 0x402004 is the same thing as s because I'm just saying go to the first character and then get its address. Those are one and the same now. And then after that is 0x402005, 006, 007, because that is just like the diagram, go to the I, to the exclamation point, and to the null character. So all I'm doing now is using my newfound understanding of what ampersand does and what the star does, is I'm just kind of playing around. I'm poking around in the computer's memory, just to demonstrate there's no magic. It's all there very deliberately because I or printf or someone else put it there. Yeah? Really good observation. So it's indeed the case that hi, unlike 50, is kind of ending up at a very low address, not at the 0x7ff, wherever it was. That's actually because, long story short, strings are often stored in a different part of the computer's memory. More on that later today for efficiency. There's actually only going to be one copy of the word hi, an exclamation point, and the computer is going to tuck it at sort of the beginning of my memory. But other values like ints and floats and the like, they end up lower in memory by convention. But a good observation, because that is consistent here. All right, so a couple final details then on what's been going on here. Let me go ahead and claim that we implemented char star, or rather string, as a char star as follows. As of last week, we were writing this code. As of this week, we can now start writing this code because char star specifically, we invented in the CS50 library. But it turns out you've seen a way of inventing your own data types. Recall this thing here. We played around last time with data structures, or the struct keyword in C, and briefly the typedef keyword, which defines a type for you. And if I highlight what's interesting here, the way we invented a person data type last time was to define a person as having two variables inside of it, a structure that encapsulates a name and encapsulates a number. Now, even though the syntax is a little different today because of the star thing, notice that this could be a similar application of that idea. If I want to create a type called string, highlighted in yellow here, then I use typedef to make it defined to be char star. So this is literally all that has ever been in CS50.h. In addition to those prototypes of functions we've talked about, typedef char star string is a one-line code that brings the word string as a data type into existence. And that's all that's ever been there. But the star, the char star, is just too much in week one. We wait until this point to sort of peel back that layer. Are any questions then on what a string is, what star or the ampersand are doing? Yeah. Oh my God, massive spoiler. But yes, if that is that why when you compare two strings, as I briefly did, or almost did, problems arise. And in fact, yes, last week we used str compare, strcmp, for a very deliberate reason, because yes, the spoiler is I accidentally would have compared two addresses in memory, not the strings at those addresses. Other questions here? No? All right, well, before we give ourselves maybe a 10-minute break here, we have lots of pieces of paper. If anyone wants to come on up and play with this big stack of Post-its, if you want to make your own 8x8 grid of something to share with the class, if you're artistically inclined, come on up. Otherwise, let's take 10 minutes, and we'll return after 10. All right. So let's come back to this question of how we can start to use these pointers and these addresses ultimately in an interesting way. The goal ultimately next week is going to be to use these addresses to really stitch together more complicated data structures than just persons like last week, or candidates in the context of like an electoral algorithm, if you will, and actually really use our memory in the most versatile way to represent not just images, but maybe videos and other two-dimensional structures as well. But for now, let's come back to this address example, whittle it down to just a hi initially, and see what's going on again here underneath the hood. So let me re-add the CS50 library just so we use our synonym for a moment. That is the word string. And I'll redefine s as a string. And what I didn't mention before is that these double quotes that you've been using for some time are actually a little special. The double quotes are a clue to the compiler that what is between them is in fact a string, as we now know it, which means the compiler will do all the work of figuring out where to put the h, the I, the exclamation point, and even adding for you automatically a \0. And what the compiler will do for you too is figure out what address all four of those chars ended up at and store it for you in the variable s. So that's why it just kind of happens with strings without using ampersands or even stars explicitly. But the star at least has been there because, again, string is just synonymous now with char star. It's not really as readable, but it is now the same idea. So I'll leave string in place just to do something sort of week one style here for a moment. And let's go ahead and print out a few characters. So I'm going to use %c this time. And I'm going to print out s bracket 0. And then I'm going to print out s bracket 1. And s bracket 2, literally doing sort of week 3 style from last week, a printing of every character in s as though it were an array. So /address should give me hi exclamation point. And if I really want to get curious, technically speaking, I could print out one more location. And let me go ahead and recompile, make address, /address, and there is, it would seem, the \0. I'm not seeing 0. Because I didn't type literally the 0 char in ASCII. It's literally 8 0 bits, which are technically unprintable, if you will, in printf speak. And so what I'm seeing here is like a blank symbol that just means there is something else there. It's apparently all 8 0 bits. But they are there, even though we're not seeing them literally right now. Well, let's go ahead and peel back one of these layers. And let me go ahead and get rid of the CS50 library and get rid of, therefore, the word string, because again, henceforth, it's just char star. Nothing else is different. I'm going to now do make address, /address, and it's the same exact thing. And now let's just focus on the high rather than even worry about that. So I'm going to recompile it one last time. And now I have HI exclamation point. Well, it turns out that the array notation we used last week was technically some of this syntactic sugar, sort of a neat way to use syntax in a useful way. But we can see more explicitly today what the square brackets for a string is actually doing. Let me go ahead and do this. Let me adventurously say I want to print out not s bracket 0, but I want to print out whatever the first character of s is. So to be clear, what is s now? It's the address of a string. OK, but what is s really? S is the address of the first char in a string. And again, that's sufficient for defining a string because eventually the computer will see that there's a \n at the end of it. So s is specifically the address of the first character in a string. So that means, using my new syntax, if I want to print out that first character, I can print out *s, because recall that star is the dereference operator. When you don't repeat the word char, you don't repeat the word int, you just use the star here. That means go to that address. Similarly, if I, in my sort of newfound knowledge of how strings work, know that the h comes first, then the I right after it, then the exclamation point, then the \0, contiguously, 1 byte apart, I could kind of start to do some arithmetic. I could go to s plus 1 byte and print out the second character. And I could print out whatever's at s plus 2. In fact, doing what's generally known as pointer arithmetic, literally treating pointers as the numbers they are, hexadecimal or decimal, doesn't really matter. It's still just numbers. And go ahead and add 1 byte or 2 bytes to them to start at the beginning of a string and just kind of poke around from left to right. So this now is equivalent to what we did last week using square bracket notation, but now I'm re-implementing that same idea with this sort of lower level plumbing, understanding ampersands and stars now a little bit more. So if I remake this program and do /address, I should still see HI exclamation point. But what I'm really doing is just kind of demonstrating, hopefully, my sort of understanding of what really is going on in the computer's memory. Now, programmers who are maybe trying to show off might actually write this syntax. I think the more common syntax would be what we did last week. S bracket 0, S bracket 1. Why? It's just a little more readable. And like we don't need to sort of brag about or care about this underlying representation. The square brackets last week were an abstraction, if you will, on top of what is lower level math. But that's all that's going on underneath the hood. We're poking around from byte to byte to byte. All right, let me pause here, see if there's any questions on that one. Any questions on this? Let's do one more then, just to demonstrate that this is not even specific to strings. Let me go ahead and get rid of all of this, and let me give myself an array of numbers like I did last week. So if I'm going to declare all the numbers at once using this funky curly brace notation, I can do like 4, 6, 8, 2, 7, 5, 0. So 7 different numbers inside of an array that's automatically initialized like this. I don't, strictly speaking, need to say 7. The compiler's smart enough to figure out how many numbers I put with commas between them. And that just gives me an array containing 4, 6, 8, 2, 7, 5, 0. So it turns out I can print each of these numbers in the familiar way. I can do a printf of %i, \n, and I can print numbers bracket 0. And let me just do some quick copy paste just to print the first 3 of these. Theoretically, that should print out 4, 6, 8, and so forth. But I can do the same sort of manipulation, understanding what pointers now are using pointer arithmetic. So let me actually unwind this and just go back to one printf. And instead of printing numbers bracket 0 like I might have last week, let me just go and print out whatever is at that address. So asterisk numbers. Let me then print out the second digit, which is going to be whatever is at numbers plus 1. And then let me do this further and do whatever's at numbers plus 2. And if I really want to repeat this, let me do it 4 more times and do what's at location 3, 4, 5, and 6. And that's 7 total numbers because I started counting at 0. So let me just quickly run this. Make address, /address. There are those 7 digits being printed. But there's something subtle but also kind of useful here. Each of these digits, 4, 6, 8, 2, 7, 5, 0, is an int. Why? Because I made an array of integers. But think back. How big is a typical integer, have we claimed? 4 bytes, or 32 bits. So it's worth noting that I don't really need to worry about that detail. Notice that I did not do +4, +8, +12, +16, +20. Right? I, the programmer, strictly speaking, don't need to worry about how big the data type is. This is the power of pointer arithmetic. The compiler is smart enough to know that if you add 1 to this pointer, that is the same as saying go one more piece of data, not just 1 byte. So if it's an int, move 4. If it's a second int, move 8. If it's a third int, move 12. Pointer arithmetic sort of handles that annoying arithmetic for you. So you can just think of this as a number after a number after a number that are back to back to back, but not 1 byte apart, but 4 bytes apart. Which is only to say +1, +2, +3 works no matter the data type. Why? Because the compiler knows what type of data you're talking about. Now there's one other detail I should reveal here that I've kind of taken for granted. In the past, I was using double quotes to represent strings. And I claim that the compiler's smart enough to realize that, oh, if I have double quote hi, that means it's an array of hi exclamation point and then the \0. Notice this usefulness. It turns out that you can actually treat arrays as though the name of the array is itself a pointer. And this is actually going to be something useful in upcoming problems when we want to pass arrays around in the computer's memory. Notice that, strictly speaking, on line 5, there's no pointers going on. There's no star. There's no ampersand. There's nothing new there. And yet, instantly on line 7, I'm sort of pretending that it is the address. And this is actually OK. It turns out that an array really can be treated as the address of the first element in that array. The difference is that there's no secret \0 anywhere. Like, this is just part of the phone number here, the ending in 0. That's not like a special \0. So this is something we're going to take advantage of, too, before long. There's this sort of interrelationship between addresses and arrays that just generally allows you to treat one as though it is the other. But the math is taken care of for you. Or any questions then on this before we start to solve some bigger problems? Yeah? Potentially, if you go beyond the end of an array, you might get a segmentation fault. The problem is that that symptom is sometimes non-deterministic, which means that sometimes it will happen, sometimes it won't. It often depends on how far off the end of the array you actually go. You'll often not induce a segmentation fault if you just kind of poke a little too far, but if you go way too far, it quite likely will. But we'll give you a tool today, actually, for detecting and solving exactly that kind of situation. So let's go ahead now and do something a little different in code, but that actually comes back to that spoiler from earlier. Let me go ahead and create a program called compare.c. And in this program, I'm going to go ahead and allow myself the CS50 library, not so much for string, but so that I can actually use getInt still, which is way easier than the way we'll see that C normally lets you get input. Let me give myself standard io.h, do an int main void, not worrying about command line arguments today. And let me go ahead and get an int I using getInt and ask the human for the value of I. Then let me give myself an int j, ask the user for another int, calling it j. And then let me go ahead and kind of naively, but to your point earlier, if I equals j, then let's go ahead and print out something like same \n. Else, let's go ahead and print out different if they are not, in fact, the same. So that would seem to be a program that compares the value of two integers. All right, so let's go ahead and run make compare. So far, so good. /compare. OK, I will be 50. J will be 50. They're the same. Let's do it once more. I will be 50. J will be 42. They are different. So far, so good in this first version of comparison. But as you might see where I'm going with this, let's move away from integers. And let's actually change these things to strings. So I could do string s over here, get string s over here. Then I could do string t over here and get string over here, asking the user for t this time here. And then I can compare the two. If s equals t, and this is a common convention. If you've used s for string already, you can use t for the next one, at least for simple demonstrations like this. I'm going to compare the two, just like I did for ints, which worked great. Make compare. So far, so good. /address. sorry, wrong program. /compare. Let me go ahead and type in something like hi, exclamation point, and by, exclamation point, which of course should definitely be different. Let me run it again with hi, exclamation point, and hi, exclamation point. Huh, different. Maybe I messed up. Let's maybe do lowercase. Maybe that'll fix. But no, those two are different. So to come back to what I described as a spoiler earlier, what's the fundamental issue here, to be clear? Why is it saying different, even though I'm pretty sure I typed the same thing twice? Yeah. Yeah, this is where it's now useful to know that string has been an abstraction, a training wheel, if you will. And if we take that away, still use getString because that's convenient still. But if I change string to be char star, it's a little more explicit as to what S and what T are. S is a pointer to a char. That is the address of a char. T is a pointer to a char. That is the address of a char. Specifically, the first character in S and the first character in T, respectively. So if I'm comparing these two, it should stand to reason that they're going to be different. Why? Because S might end up here in memory, and T might end up here in memory. Each time I call getString, it is not smart enough or advanced enough to know that, wait a minute, you typed the same thing, I'm just going to hand you back the same address. That doesn't happen because we did not design getString that way. Each time I call getString, it returns, apparently, a different copy of the string that was typed in. A hi over here and a hi over here. They might look the same to the human, but to the computer, they are different chunks of memory, and therefore at different addresses. And here, too, we can reveal what is getString returning. Well, up until today, it was returning a string, so to speak. That's not really a thing. Technically, what getString has always been doing is returning the address of the first char in a string, and trusting that we put a \0 at the end of whatever the human typed in, and that's enough now for printf, for strlang, for you, to know where a string begins and ends. So getString has actually always returned a pointer. It has not returned a quote-unquote string per se. But there are functions that can solve this comparison for us. Recall that I could do something like this. I could actually go in here and I could, let's see, where was it? So if I include compare here and use it to pass in two values, S and T, let's see now what happens when I make compare. Implicitly declaring library function compare with type int, and well, there's a star. So you might have seen this error before, and you might have ignored most of it, but there's some evidence of stars or pointers going on here. It looks like I didn't include the string.h header file, so that's an easy fix. Include string.h, which, despite its name, does not create a data type called string. It just has string-related functions in it, like compare. Let's make compare again. Now it compiles, /compare. Now let's type in hi, exclamation point, and even the same thing again. These are now, oh, I used it wrong. OK, user error. That was supposed to be impressive, but it's the opposite. What did I do wrong? What did I do wrong? Here, yeah. Yeah. Yeah, it returns three different values. 0 if they're the same. Positive if one becomes before the other. Negative if the opposite is true. I just forgot that. So like I did last week correctly, if I want to compare them for equality, per the manual page, I should be checking for 0 as the return value. Now make compare, /compare, enter. Let's try it one last time. Hi and hi. OK, now they're in fact the same. And Justin, thank you. And indeed, not that it's returning same all the time. If I type in hi and then by, it's indeed noticing that difference as well. Well, let me go ahead and do one other thing here. Let's do one other thing. Let me go ahead now and just reveal more pictorially what's going on. Let's get rid of the string comparison, and let's just print these things out. The simple way to print this out would be with %s. And again, %s is special. Printf knows take in an address and start there. Print every character up until the \n. So let's just hand it s and do that. And then let's do one more, %s, t. This is, again, sort of a mix of week 1 and this week, because I got rid of the word string. I'm using char star, but I'm still using printf and %s in the same way. Let me go ahead and run compare now. And if I type hi and hi, I should see the same thing twice. So they look the same. But here now we have the syntax today to print out the actual addresses of these things. So let me just change the s to a p, because p means don't go to the address and print it. it means just print the address as a pointer. So make compare, / compare. And now let's type in hi and once more. And I should see indeed two slightly different addresses given in hexadecimal. One's got a B at the end, one's got an F at the end, and they are indeed a few bytes apart. So this is just confirming what our suspicions have actually been. So what does this mean perhaps in the computer's memory? Well, let's kind of take a look. I've zoomed out so I have a little more squares to look at once. Here might be S in memory when I do string S equals, or char star S equals. I get a variable that's of size 1, 2, 3, 4, 5, 6, 7, 8, because I claimed earlier that on modern systems, pointers are generally 8 bytes nowadays, so they can count even higher. And inside of the computer's memory also might be high. And I don't know where it ends up, so for the sake of discussion, it ended up down here. That's what was free when I ran the program. HI exclamation point \0. Maybe it ended up, for the sake of discussion, at 0x1, 2, 3, 4, 5, and 6. So to be clear, what is S storing once the assignment operator copies from right to left? What is S storing if I advance one more slide? Yeah. 0x123, the presumption being that if a string is defined by the address of its first char, and that address of its first char is 0x123, then that's indeed what should be in the variable S. And so technically, that's what's been happening with that assignment operator from right to left. GetString indeed returns a string, so to speak, but more properly, it returns the address of a char. What's been then copied from right to left using that assignment operator all these weeks is indeed that address. Now, technically, we don't really need to care about where these addresses are. It suffices to just think about them sort of referentially, but let's first consider where t might be. T is just another variable that I created on my second line of code. Maybe it ends up there, maybe somewhere else. For the sake of discussion, I'll draw it left and right. Where did the second word end up that I typed in? Well, suppose the second copy of hi ended up at 0x456, 457, 458, 459. What ended up in t? I'll pluck this one off myself. 0x456, presumably. And so this is now a pictorial representation of y. And let's abstract away everything else. When I compared s against t using equals, based on the picture, they're obviously not the same. One is over here, one is over here. And per a moment ago, one is 0x123, the other is 0x456. Yes, technically they're pointing at something that's the same, but that just reveals how stir compare works. Stir compare is apparently a function that takes in the address of a string as its argument and the address of another string as its argument. It goes to the first character in each of those strings respectively, and probably has like a for loop or a while loop, and just goes from left to right comparing, looking for the same chars left and right. And if it doesn't notice any differences, boom, it returns 0. If it does notice a difference, it returns a positive or a negative value. And that's very similar, recall, to how we implemented string length ourselves last week. I sort of used a for loop. I was looking for a \0. Stir compare is probably a little similar in spirit, looping from left to right, but comparing this time, not just counting. Are any questions then on string comparison and why it is that we use stir compare and not equals? Yeah? Do pointers have addresses? Yes. So we won't do that today, but I could actually use the ampersand operator on s or on t. That would give me the equivalent of a char star star that itself could be stored elsewhere in memory. That's where it ends. We don't sort of do that recursively forever. There's star and there's star star. But yes, that is a thing. And it's very often useful in the context of like two-dimensional arrays, which we haven't really talked about. But that is a feature of the language too, but not today. Good question. All right, so what might we now do to take things up a notch? Well, let's go ahead and implement a different program here that maybe tries copying some values just to demonstrate this. Let me open up a file called, how about copy.c. And I'm going to start off with a few includes. So let's include the CS50 library just so we have a way of getting user input. Let's include, how about standard IO as always. Let's preemptively include string.h and maybe one other in a moment. Let's do int main void as before. And then in here, let's get a string from the user and just call it s for simplicity. And heck, we can actually just call this char star if we want, or string, since we're using the CS50 library, but we'll come back to that. Let's now make a copy of s and do s equals t using a single assignment operator. And then let's check something like this. Let's go into the first character of t which is t bracket 0. And then let's uppercase it using that function that we've used in the past of toUpper, t bracket 0, semicolon. And actually, I should go back up here. If I'm using toUpper, or if you've used toLower, or isUpper, or isLower, might not remember this offhand, but it was in another header file called ctype.h. There was a bunch of helpful functions in that library as well. Now, at the very last line of the program, let's just print out what both s and t are by simply printing out %s for each of them. And t is %s also, not %t, of course. And let's see what happens here. So let me make copy. Oh my God, so many mistakes. What did I do wrong? Oh, OK, that was unintended. String t equals s, sorry. So I'm creating two variables, s and t respectively, and I'm copying s into t. Make copy, enter. There we go. /copy. And let's now type in, for instance, how about hi, exclamation point, in all lowercase this time. And now what gets printed? I don't think that's what I intended, so to speak here, because notice that I got s from the user, so that checks out. I then copied t into s, which looks correct. That's what we always use assignment for. Then I uppercased the first letter in t, but not s, at least in my code. Then I printed s and t, and then notice, apparently, both s and t got capitalized. So if you're sort of starting to get a little comfortable with what's going on underneath the hood, like what's the fundamental problem here? Why did both get capitalized? Why did both get capitalized? Yeah, over here. Yeah, they're representing the same address. So C is really literal. If you create another variable called t and you assign it the value of s, you are literally assigning it the value in s, which is like 0x123 or something like that. And so at that point in the story, both s and t presumably have a value of 0x123, which means they technically point to the same hi exclamation point in memory. Nowhere did I tell the computer to give me a copy of hi exclamation point per se. I literally said just copy s. So here's where an understanding of what s literally is kind of explains the situation. I'm only copying the pointers. So what actually went on in memory, let's take a look here at this grid. If I created s initially, maybe it ends up here, and I created hi in lowercase, and it ended up down here, then the address was, again, like 0x123, 4, 5, 6. 0x123 is what's in s. If then I create a second variable called t, and I call it a string, aka char star, maybe it again ends up here. But when I copy s into t by doing t equals s semicolon, that literally just copies s into t, which puts the value 0x123 there. So if we now abstract away all these numbers and just think about a picture with arrows, what we've drawn in the computer's memory is this. Two different pointers, but storing the same address, which means the breadcrumbs lead to the same place. And so if you follow the t breadcrumb and capitalize the first letter, it is functionally the same as copying changing the first letter in the version s as well. So what's the solution then to this kind of problem? Like, even if you have no idea how to do it in code, like, what's the gist of what I really intended, which is I want a genuine copy of s called t. I want a new hi exclamation point \0. What do I need to do to make that happen? Thoughts? So there is a function called strcpy, strcpy, which is a possible answer to this question. The catch with strcpy is that you have to tell in advance not only what the source string is, the one you want to copy, you also need to pass in the address of a chunk of memory into which you can copy the string. And here's one thing we haven't seen yet, and we need one more building block today, if you will. We haven't yet seen a way to create new chunks of memory and then let some other function copy into them. And for this, we're going to introduce something called dynamic memory allocation. And this is the last and most powerful feature perhaps today, whereby we're going to introduce two functions, malloc and free, where malloc means memory allocate, which literally does just that. It's a function that takes a number as input. How many bytes of memory do you want the operating system to find for you somewhere in that big grid? It's going to find it, and it's going to return to you the address of the first byte of contiguous memory back to back to back. And then you can do anything you want with that chunk of memory. Free is going to do the opposite. When you're done using a chunk of memory that malloc has given you, you can say free it. and that means you hand it back to the operating system, and then the operating system can use it for something else later. So this is actually evidence of a common problem in programming. If your Mac, your PC, has ever been in the habit of starting to get like really, really slow, or it's kind of slowing to a crawl, heck, maybe it even freezes, one of the possible explanations could be that the program you're running by Apple or Microsoft or whoever, maybe they're using malloc or some equivalent, asking the operating system, Mac OS or Windows, for give me more memory. I need more memory. The user's creating more images. The user's typing a longer essay. Give me more memory, more memory. If the program has a bug and never actually frees any of that memory, your computer might end up using all of the available memory. And honestly, humans are not very good at handling corner cases like that. Very often, programs, computers just freeze at that point or get really, really slow because they start trying to be creative when there's not enough memory left. So one of the reasons for a computer really slowing down might be calling malloc a lot or some equivalent, but never freeing it, which is to say you should always use these two functions in concert and free memory once you are done with it. So let me go ahead and do this in code and solve this problem properly. Let me go ahead and do this. Before I copy S into T using something like strcpy, I first need to get a bunch of memory from the computer. So to do that, let's make this super clear that we're dealing with pointers. So I'm going to change my strings to char stars for both S and T. And what I technically am going to store in T is the address of an available chunk of memory. To do that, I can ask the computer to allocate memory for me. And how many bytes? If I want to create a copy of HI exclamation point, I need how many bytes? Good, 4, because I need the H, the I, the exclamation point, and additional space for the \0. It's up to me to understand that and ask for it. It's not going to happen magically. Nothing does in C. So I could just naively type 4 there, and that would be correct if I type in HI exclamation point or any other 3-letter word or phrase. But to do this dynamically, I should probably do something like strlen of S plus 1. For the additional null character. Recall that string length does it in the sort of the English sense. It returns the length of the string you see. Plus 1 also takes into account the fact that I'm going to need that \n. Now let me do this old school style first. Let me go ahead and manually copy the string S into T first. So for int I equals 0, I is less than the string length of S, I plus plus. Then inside my for loop, I'm going to do T bracket I equals S bracket I. But actually, I want the null character too. So I want to do the length of the string plus 1 more. And heck, I think I learned an optimization last time. If I'm doing this again and again, I could really do n equals strlen of S plus 1, and then do I is less than n, just as a nice design optimization. I think this for loop will actually handle the process then of copying every character from S into every available byte of memory in T. Or I could get rid of all of that and take your suggestion, which is to use strcpy, which takes as its first argument the destination and its second argument the source. So copy from right to left in this case too. That's going to do all of that automatically for me as well. Now I think I'm good. I can now capitalize safely the first character in T, which is now a different chunk of memory than S. And then I can print them both out to see that one has not changed, but the other has. So make copy. All right, what did I do wrong? Implicitly declaring library function malloc ... So we've seen this kind of error before. What is, even if you don't know quite how to solve it, what's the essence of the solution? What do I need to do to fix this kind of problem involving implicitly declaring a library function? What did I forget? Yeah. I need to include the library. And I could look this up in the manual, or I know it off the top of my head. I just forgot it. There's another library we'll occasionally need now called standard lib, standard library, that contains malloc and free prototypes and some other stuff too. All right, let me just clear this away and do make copy one more time. Now I'm good. /copy, enter. All right, S, I'm going to type in high lowercase, T, and S. Now come back as intended. S is untouched, it would seem, but T is now capitalized. All right, any questions then on what we just did in code? Yeah. Indeed, there's a few improvements I want to make, so let me actually do those right now. Technically, I should practice what I preached And I should indeed, when I'm done with t, free t. Fortunately, I don't have to worry about how big t was. The computer remembers how many bytes it gave me, and it will go free all of them, not just the first. I should do free t. I don't need to do free s, and I shouldn't, because that is handled automatically by the CS50 library. S, recall, came from getString, and we actually have some fancy code in place that makes sure that at the end of your program's execution, we free any memory that we allocated, so we don't actually waste memory like I described earlier. But there's actually a couple of other things, if I really want to be pedantic, I should put in here. It turns out that sometimes malloc can fail. And sometimes malloc doesn't have enough memory available because maybe your computer's doing so much stuff, there's just no more RAM available. So technically, I should do something like this. If t equals null with 2 L's today, then I should just return 1 or something to say that there was a problem. I should probably print an error message too, but for now, I'm going to keep it simple. I should also probably check this. This is a little risky of me. If I'm doing t bracket 0, this is assuming that there is a letter there. But what if the human just hit enter at the prompt and didn't even type h, let alone hi exclamation point? What if there is no t bracket 0? So technically, what I should probably do here is, if the length of t is at least greater than 0, then go ahead and safely capitalize the first letter of it. And then at the very end, if all goes well, I can return 0, thereby signifying that indeed this thing was successful. So yes, these two functions, malloc and free, should be in concert. And so if you call malloc, you should call free eventually. But you did not call malloc for s, so you should not call free for s. All right, yeah, other question. Why did I do malloc plus 1? So malloc of string length of s plus 1. The string length is sort of the literal length of the string as a human would perceive it in English. So hi exclamation point, strlen gives me 3. But I know now, as of last week and this week, what a string technically is. And a string always has an extra byte. The onus is on me to understand and apply that lesson learned so that I actually give strcpy enough room for that trailing null character. And here's just an annoying thing. When we call the \0 NUL last week, it turns out that NULL is the same idea. It's also 0, but it's 0 in the context of pointer. So long story short, you never really write NUL. I've just said it, and we saw it on the screen. You will start writing NULL when you want to check whether or not a pointer is valid or not. And what I mean by that is this. If malloc fails and there's just not enough memory left inside of the computer for you, it's got to return a special value. And that special value is NULL in all capital letters. That signifies something went wrong. Do not trust that I'm giving you a useful return value. Other questions on these copies thus far? Yeah, over there. Good question. Will strcpy not work without malloc? You kind of need both in this case, because strcpy, by definition, if I pull up its manual page, needs a destination to put the copied characters. It's not sufficient just to say char star t semicolon. That only gives you a pointer. But I need another chunk of memory that's just as big as hi exclamation point \0. So malloc gives me a whole bunch of memory. And then strcpy fills it with hi exclamation point \0. So again, that's why we're sort of going down to this lower level, because once you understand what needs to be done, you now have the functions to do it. So let's actually consider what we just solved. So in this SNCS version of the program where I actually introduced malloc, t was initialized to the return value of malloc. And maybe the memory that I got back was here, 0x456, 457, 458, 459. I've left it blank initially because nothing is put there automatically by malloc. I just get a chunk of memory that is now mine to use as I see fit. I then assign t to that return value, which points t at the first address. Notice there's no \0. This is not yet a string. It's just a chunk of memory, 4 bytes, an array of 4 bytes. What strcpy eventually did for me was it copied the h over, the I over, the exclamation point over, and the \0. And if I didn't want to use strcpy, or I forgot that it existed, my for loop would have done exactly the same thing. All right, any questions then on these examples here? Any questions? Yeah? Good question. After malloc, if I had then still done just t equals s, it actually would have recreated the same original problem by just copying OX123 from s into t. So then I would have been left with a picture that looked like this a few steps ago. I would have, and I can't quite do it live, this arrow, if I did what you just described, would now be pointing over here. And so I wouldn't have fundamentally solved the problem. I would have just additionally wasted 4 bytes temporarily that I'm not actually using. Yeah? Do you always use malloc and strcpy together? Not necessarily. These are both solving 2 different problems. Malloc's giving me enough memory to make a copy. Strcpy's doing the copy. However, you could actually use an array if you wanted of characters, and you could use strcpy on that. And there's other use cases for strcpy. But thus far, it's a reasonable mental model to have that if you want to copy strings, you use malloc and then strcpy, or your own homegrown loop. Yeah? Say that once more. No, it will. Good question. If I hadn't, strcpy per its documentation will copy the whole string plus the null character at the end. It just assumes there will be one there. It's therefore up to you to pass strcpy a long enough chunk of memory to have room for that. If I only asked malloc for 3 bytes, that could have potentially created a memory problem whereby strcpy would just still blindly copy 1, 2, 3, 4 bytes, but technically it should have only touched 3 of those. You do not yet have access to the 4th one or the rights to it because you never asked malloc for it. Yeah. Correct. The number inside malloc, it's 1 argument, is the number of bytes you want back. Yes, the onus is on you, the programmer, to remember or frankly use a function to figure out how many bytes you actually need. That's why I did not ultimately type in 4 manually. I used strlength plus 1. So the plus 1 is necessary if you understand how strings are represented. But using strlang means that I can actually play around with any types of inputs, and it will dynamically figure out the length. So suffice it to say, there's so many ways already where you can start to break programs. Let's give you at least one tool for finding mistakes that you might make. And indeed, in upcoming problem sets, will you use this to find bugs in your own code? Not just using printf, not just using the built-in debugger, but another tool here as well. So let me go ahead and deliberately write a program called memory.c that has some memory-related errors. Let me include standard.io.h at the top, and let me include standard lib.h at the top, so I have access to malloc now. Let me do int main void, and then inside of main, let me do this. I want to allocate maybe, how about space for 3 integers. Why? Just for the sake of discussion. So I'm going to go ahead and do malloc of 3, but I don't want 3 bytes. I want 3 integers, and an integer is 4 bytes. So technically I could do this, 3 times 4, or I could do 12. But again, that's making certain assumptions. And if I run this program on a slightly different computer, ints might be a different size. So the better way to do this would be 3 times whatever the size is of an int. And this is just an operator you can use anytime if you just want to find out on this computer how big is an int, how big is a float or something else. So that's going to give me that much memory for 3 ints. What do I want to assign this to? Well, malloc returns an address. Pointers are addresses, so I'm going to create a pointer to an int called x and assign it the value. So what am I doing here? This is a little less obvious, but again, go back to basics. The right-hand side here gives me a chunk of memory for 3 integers. Malloc returns the address of the first byte of that chunk. How do I store the address of anything? I need a pointer. The syntax for today is type of data star. The type of data in question is 3 ints, so I do int star x. Again, it's kind of purposeless, only for sort of instructional purposes here. But this is equivalent now to having a chunk of memory of size 12 in total, presumably. So I can technically now do this. I can go into maybe the first location and assign it the number 72, like the other day. Second location, the number 73. And the third location, maybe the number 33. Now, I've deliberately made 2 mistakes here because I'm trying to trip over my newfound understanding or my sort of greenness with understanding pointers. One, I didn't remember that I should be treating chunks of memory as 0 indexed. malloc essentially returns an array, if you want to think of it as that. An array of 3 ints, or more technically, the address of a chunk of memory that could fit 3 ints. So I can use my square bracket notation, or I could be really cool and use pointer arithmetic, but this is a little more user-friendly. But I have made 2 mistakes. I did not start indexing at 0. So line 7 should have been x bracket 0. Line 8 should have been x bracket 1. And then line 9 should have been x bracket 2. So first mistake. The second mistake that I've made as a side effect is I'm also touching memory that I shouldn't. X bracket 3 would mean go to the 4th int in the chunk of memory that came back. I only asked for enough memory for 3 ints, not 4. So this is what's called a buffer overflow. I am accidentally, but deliberately at the moment, going beyond the boundaries of this array, this chunk of memory. So bad things happen, but not necessarily by just running your program. Let me go ahead and just try this. Make memory. And you'll see here that it compiles OK, /memory. And it actually does not segmentation fault, which comes back to that point of non-determinism. Sometimes it does, sometimes it doesn't. It depends on how bad of a mistake you made. But there's a program that can spot these kinds of mistakes. And I'm going to go ahead and expand my terminal window for a moment. And I'm going to run not just /memory, but a program called valgrind /memory. This is a command that comes with a lot of computer systems that's designed to find memory-related bugs in code. So it's a new tool in your toolkit today, and you'll use it with the coming problem sets. I'm going to run this now. Its output, honestly, is hideous. But there's a few things that will start to jump out and will help you with tools in the problem set to see these kinds of things. Here's the first mistake. Invalid write of size 4. That's on memory.c line 9 per my highlights. So let me go look at line 9. In what sense is this an invalid write of size 4? Well, I'm touching memory that I shouldn't. And I'm touching it as though it's an int. And an int is 4 bytes, size 4. So again, this takes some practice to get used to, the nomenclature here. But this is now a clue for me, the programmer, that not only did I screw up, but I screwed up related to memory. And so this is just kind of a hint, if you will. It's not going to necessarily tell you exactly how to fix it. You have to kind of wrestle with the semantics. But invalid write of size 4, oh, OK. So I should not have indexed past the boundary here. All right, so I shouldn't have done that. So let me go ahead then and change this to 0, 1, and 2 perhaps here. All right, so let me go ahead and recompile my code, make memory. /memory still doesn't seem to be broken, but it is technically buggy. Let me go ahead and run valgrind again. So valgrind of /memory, enter. And now there's less scary output now, but there's still something in there. Notice this. 12 bytes in 1 blocks, no regard for grammar there, are definitely lost in loss record 1 of 1. Super cryptic, but this is hinting at a so-called memory leak. The blocks of memory are lost in the sense that I malloced them. I asked for them, but I never, take a guess, freed them. I have a memory leak. And this is the arcane way of saying you've screwed up, you have a memory leak. So this is an easy fix, fortunately. Once I'm done with this memory, I just need to free it at the end. So now let me go ahead and rerun make memory. It still runs fine. So all the while I might have thought incorrectly my code is correct. But let me run valgrind one more time. Valgrind of /memory, enter. Now this is pretty good. All heap blocks were freed, whatever that means. No leaks are possible. And even though it's still a little cryptic, there's no other error here. And in fact, it's pretty explicit. Error summary, 0 errors from 0 contexts, ... So even though this is one of the most arcane tools we'll use, it's also one of the most powerful because it can see things that you, the human, might not, and maybe even that the debugger might not. It does a much closer reading of your code while it's running to figure out exactly what is going on. All right, any questions then on this tool? And we'll guide you after today with actually using this too. Just helps you find memory-related mistakes that you might now be capable of making. All right, let's do one other memory-related thing. Let me shrink my terminal window here. Let me create one other file here called garbage.c. So it turns out there's a term of art called garbage values in programming that we can reveal as follows. Let me include standardIO.h, and let me include, how about standardlib.h. And then let me give myself int main void. And then in this relatively short program, let me give myself like 3 ints using last week's notation, just int scores bracket 3 for like 3 quiz scores or whatever. Then let me go ahead and do for int I equals 0, I less than 3, I plus plus. Then let me go ahead and print out %i backslash n scores bracket I semicolon. That's it. This code, pretty sure, is going to compile and it's going to run. But what is my logical bug? I've sort of forgotten a step, even though the code that's written is not so wrong. Yeah? Yeah, I didn't provide the scores. So I didn't actually initialize the array called scores to have any scores whatsoever. What's curious about this, though, is that the computer technically doesn't mind. Let me go ahead and sort of playfully make garbage, enter. And it's kind of an apt description because what I'm about to see are so-called garbage values. When you, the programmer, do not initialize your code's variables to have values, sometimes who knows what's going to be there. The computer's been doing some other things. There's a bit of work that happens even before your code runs in the computer. So there might be remnants of past ints, char, strings, floats, anything else in there. And what you're seeing is those garbage values, which is to say you should never forget, as I just did, to initialize the value of some variable. And this is actually pretty dangerous. And there have been many examples of software being compromised because of one of these issues where a variable wasn't initialized. And all of a sudden, users, maybe, people on the internet in the context of web applications could suddenly see the contents of someone else's memory or remnants, maybe someone's password that had been previously typed in or some other value like a credit card number that had been previously typed in. There are different defense mechanisms in place to generally make this not so likely, but it's certainly very possible, at least in this kind of context, to see values that you probably shouldn't because they might be remnants from something else that used them. So this is to say, again, you sort of have this great power now to manipulate memory, but also now you have this great sort of hacking ability to poke around the contents of memory. And this is exactly what hackers sometimes do when trying to find ways to exploit systems. Are any questions here? No? All right, let's go ahead and take a quick 5-minute break. And when we come back, we'll build on these final topics. See you in 5. We are back. First, just a little programmer humor from XKCD, which hopefully now will make a little bit of sense to you. And what we'll also do next is take a look at a short 2-minute video that animates, with claymation, if you will, from our friends at Stanford, exactly what happens now if you have an understanding of what garbage values are and how they get there, and what happens then if you misuse them. It's one thing just to print them out, as I just did. It's another if you actually mistake a garbage value for a valid pointer, because garbage values are just zeros and ones somewhere, numbers, that is. But if you use that new dereference operator, the star, and try to go to a garbage value, thinking incorrectly that it's a valid pointer, bad things can happen. Computers can crash, or more familiarly, segmentation faults can happen. So allow me to introduce, if we could dim the lights for 2 minutes, our friend Binky from Stanford.
Hey, Binky, wake up. It's time for pointer fun. What's that? Learn about pointers? Oh, goody! Well, to get started, I guess we're going to need a couple pointers. Okay. This code allocates 2 pointers which can point to integers. Okay, well, I see the 2 pointers, but they don't seem to be pointing to anything. That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up's a separate step. Oh, right. I knew that. The pointees are separate. So, how do you allocate a pointee? Okay, well, this code allocates a new integer pointee, and this part sets x to point to it. Hey, that looks better. So make it do something. Okay, I'll dereference the pointer x to store the number 42 into its pointee. For this trick, I'll need my magic wand of dereferencing. Your magic wand of dereferencing? That's great. This is what the code looks like. I'll just set up the number and... Hey, look, there it goes. So doing a dereference on x follows the arrow to access its pointee, in this case to store 42 in there. Hey, try using it to store the number 13 through the other pointer, y. Okay, I'll just go over here to y and get the number 13 set up, and then take the wand of dereferencing and just... Whoa! Oh, hey, that didn't work. Say, Binky, I don't think dereferencing y is a good idea because, setting up the pointee is a separate step, and I don't think we ever did it. Good point. Yeah, we allocated the pointer y, but we never set it to point to a pointee. Very observant. Hey, you're looking good there, Binky. Can you fix it so that y points to the same pointee as x? Sure, I'll use my magic wand of pointer assignment. Is that going to be a problem like before? No, this doesn't touch the pointees. It just changes one pointer to point to the same thing as another. Oh, I see. Now y points to the same place as x. So wait, now y is fixed. It has a pointee. So you can try the wand of dereferencing again to send the 13 over. Okay, here goes. Hey, look at that. Now dereferencing works on y. And because the pointers are sharing that one pointee, they both see the 13. Yeah, sharing, whatever. So are we going to switch places now? Oh, look, we're out of time. But
It's from our friend Nick Parlante at Stanford. So let's consider what Nick did here as Binky. So here's kind of all the code together. These first couple of lines were not bad. And notice that in Stanford's code, they moved the stars to the left. That's fine. Again, more conventional might be this syntax here. These two lines are fine. It's OK to create variables, even pointers, and not assign them a value initially, so long as you eventually do. So we eventually do here with this line. We assign to x the return value of malloc, which is presumably the address of something. To be fair, we should really be checking for null as well, but that's not the biggest problem here. The biggest problem is not even this next line, which means go to the memory location in x and store the number 42 there. That's fine, because again, malloc returns the address of some chunk of memory. This chunk of memory is big enough for an int. X is therefore going to store the address of that chunk that's big enough for an int. Star x, recalls the dereference operator means go to that address and put 42 in it. It's like going to the mailbox and putting the number 42 in it instead of taking the number 50 out like we did before. But why is this line bad? This is where Binky sort of lost his head, so to speak. Why is this bad? Yeah. Exactly. We haven't yet allocated space for y. There's no mention of malloc. There's no assignment of y even to that same memory. So this would be go to the address in y. But if there is no known address in y, it is a so-called garbage value, which means go to some random address that you have no control over. And boom, that might cause what we've seen in the past perhaps as a segmentation fault. Now, this fortunately is the kind of thing that if you don't quite have the eye for it yet, Valgrind, that new tool, could help you find as well. But it's just another example of, again, the sort of upside and downside of having control now over memory at this level. All right, well, let's go ahead and do one other thing. Considering from last week that this notion of swapping was actually a really common operation. We had all of our volunteers come up. We had to swap a lot of things during bubble sort and even selection sort. And we just kind of took for granted that, the two humans would swap themselves just fine. But there needs to be code to do that if you actually implement bubble sort, selection sort, or anything that involves swapping. So let's consider some code like this. We'll keep it simple like last week and where we wanted to swap some values like int a and int b. For instance, here, void, because I'm not going to return a value, but I have a function called swap. So here, for instance, might be some code for this. But why is it so complicated here? Let's actually take a step back. Why don't we do this here? I think we have time for one more volunteer. Could we get someone to come on up? You have to be comfy on camera. And you're being asked to help with your friend. Oh, I'll go with the friend pointing. So whoever has their friend doing this here. No? Now they're pointing over here. Now literally an arm is being twisted. OK. Come on down. That backfired. Come on over. And what is your name? Marina. Yeah. Nice to meet you. Who were you trying to volunteer?
My friend Jessica.
OK. So here we have for Marina 2 glasses of liquid, orange and purple, just so that they're super obvious. And suppose that the problem at hand, like last week, is just to swap 2 values, like as though these 2 glasses represented 2 people, and we want to swap them. But let's consider these glasses to be like variables or location in an array. And you know what? I'd really like you to swap the values. So like orange has to go in there, and purple has to go in there. How would you do it? And we'll see if we can then translate that to code. OK, what, did you say it a little louder? All right, yeah, so presumably you're sort of struggling mentally with how you would do this without having an extra cup. So good foresight here. Let me go ahead, and we do have a temporary variable, if you will. So if I hand you this, how would you now solve this problem?
Well, I would go like that, but it's easy.
No, that's, oh, well, okay, go with your instincts. Okay. Sure, go ahead. Go to whatever your instincts are. Yeah, so strictly speaking, probably shouldn't have moved the glasses just because that would be like moving the array locations. So let's actually do it one more time, but the glasses now have to go back where they originally are. So how would you swap these now using this temporary variable? Okay, good. Otherwise, we'd be completely uprooting the array, for instance, by just physically moving it around. So you moved the orange into this temporary variable, then you copied the purple into where the orange was, and now presumably, excellent. The orange is going to end up where the purple once was. And this temporary variable, it's sort of some extra memory. It was necessary at the time, but not necessary ultimately. But a round of applause if we could. And thank you for doing that so well. So, right, the fact that it sort of instantly occurred to Mariana that like you need some temporary variable is a perfect translation to code. And in fact, this code here that we might glimpse now is reminiscent of exactly that algorithm, where A and B at the end of the day are the same chunks of memory. Just like the second time, the two glasses have to kind of stay put, even though we're physically lifting them, but they're going back to where they were. It's kind of like having two values, A and B, and you just have a temporary variable into which you copy A, then you change A with B, then you go and change B with whatever the original value of A was, because you temporarily stored it in this temporary variable, TMP. Unfortunately, this code doesn't necessarily work as intended. So let me go over to my VS Code here and open up a program called swap.c. And in swap.c, let me whip up something really quickly here with, how about include standard io.h, int main void. Inside of main, let me do something like int x gets 1, int y gets 2. Let me just print out as a visual confirmation that x is %i, y is %i, \n, plugging in x and y respectively. Then let me call a swap function that we'll invent in just a moment, swap x and y. And then let me print out again, x is %i, y is %i, \n, just to print out again what they are, because presumably I should see 1, 2 first, then 2, 1 the second time. Now, how is swap going to be implemented? Let me implement it exactly as on the screen a moment ago. So void swap int x, or let's call it int a for consistency, int b. But I could always call those anything I want. Int temp gets a gets b gets temp. So exactly as I proposed a moment ago, and exactly as Mariana really implemented it using these glasses of water. I need to now include my prototype as always, so nothing new there. And I'll just copy paste that up here. And now let's go ahead and run this. So make swap. So far, so good. Swap. X is now 1, y is 2. X is 1, y is 2. So there seems to be a bit of a bug here. But why might this be? This code does not, in fact, work, even though it obviously works in reality. Yeah? Good, and let me summarize. A and B do indeed have different addresses of x and y. And in fact, what happens when you call a function like this on line 11, calling swap, passing in x and y, you are calling a function by value, so to speak. And this is a term of art that just means you are passing in copies of x and y, respectively, and calling them a and b in the context of this function. But they're indeed copies. Now, technically, these names are local only. I could have called this x. I could have called this y. I could have changed this to x, this to y, this to x, and this to y. The problem would still remain. Just because you use the same names in one function as you do elsewhere, that doesn't mean they're the same. They just look the same to you. But indeed, swap is going to get copies of this x and y. And in this context, this scope, so to speak, x and y will be copies of the original. So for clarity, let me revert this back to a and b, just to make super clear that they're indeed different, albeit copies. But there's indeed a problem there. This function actually works fine. In fact, notice this. Let me go ahead and print out inside of this, printf, a is %i, b is %i, \n, and then I'll print a and b. And let me do that same thing at the beginning of this function before it does any work. Let me go ahead and rerun make swap. ./swap, and this is promising. Initially, x is 1, y is 2. A is 1, b is 2, a is 2, b is 1, but then nope, x is 1, y is 2. So if anything, I've confirmed that the logic is right, Mariana's logic is right, but there's something about C. There's something about using one function versus another that's actually creating a problem here. The fact that I'm passing in copies of these values is creating this problem. So what in fact is going on? Well, again, inside of your computer's memory, there's these little chips, and we've been talking about them abstractly. It's just this grid of memory locations. It turns out that your computer uses this memory in a pretty conventional way. It's not just kind of random where it just puts stuff wherever is available. It actually uses like different parts of the memory for different purposes. And you have control over a lot of it, but the computer uses some of it for itself. And let's go ahead and zoom out from this and consider that within your computer's memory, what a computer will typically do is actually store initially all of the zeros and ones that you compiled in the top of your computer's memory, so to speak. So when you compile a program and then you run it with / whatever, or on a Mac or PC, you double click on it, the computer first, the operating system first, loads all of your program zeros and ones, aka machine code, into just one big chunk of memory at the top, so to speak. Below that, it stores global variables. Any variables you have created in your program that are outside of main and outside of any functions, generally at like the top of your file. Globals tend to go at the top there. Then there's this chunk of memory that's generally known as the heap, and we saw that word briefly in Valgren's output. And then there's this other chunk of memory called the stack. And it turns out that up until this week, you were using the stack heavily. Anytime you use local variables in a function, they end up on the stack. Anytime you use malloc, that memory ends up on the heap. Now, as the arrow suggests, this actually looks like a problem waiting to happen, because if you use more and more and more heap and more stack, it's like, two things barreling down the tracks at one another. This does not end well. And that's actually a problem. If you've ever heard the phrase Stack Overflow or used the website, this is the origin of its name. When you start to use more and more and more memory by calling lots and lots of functions or using lots and lots of local variables, you use a lot of this stack memory. Or if you use malloc a lot and keep calling malloc, and never really or rarely calling free, you just use more and more memory. And eventually, these two things might overflow each other, at which point you're just kind of out of luck. The program will crash or something bad will happen. So the onus is kind of on you just to don't do that. But this is the design generally of what's going on inside of your computer's memory. Now, within that memory, though, there are certain conventions focusing on here the stack. And in fact, let me go over here with a marker and say that this represents like the bottom of my memory, ultimately. And so here, we have a whole bunch of wooden blocks, and each of these squares represents a byte of memory. And this, for instance, might represent 4 bytes altogether, good enough for an int or something like that. So in my original code that I wrote earlier, that is in fact buggy, what is in fact going on inside the swap function, we can kind of visualize it like this. When you run /swap, or any program for that matter, main is the first function to get called with a C program. And so I'm just going to label this bottom row of memory as main. And what were the 2 variables I had in main called in this code? Yeah. X and Y. And each of those was an int, so that's 4 bytes. So it's kind of deliberate that I reserved a chunk of wood here that's 4 bytes. So let me just call this x, and I'm just going to write the number 1 in this box here. And then I had my other variable y, and I'm going to put the number 2 there. What happens when main calls swap like it does in this code here? Well, it has 2 variables of its own, a and b. And a initially is 1, and b is initially 2. But it has a third variable, temp, which is a local variable in addition to the arguments a and b that are passed in. So I'm going to call this temp, TMP, over here. And what is the value of temp? Well, we have to look back at the code. Temp initially gets the value of a. All right, the value of a was 1. So temp initially gets 1. That's step 1 in my 3-line program. OK, a equals b. So that is assigned from the right to the left of the b into the a. So b is 2. A is this. So let me go ahead and erase this and just overwrite that. So at this moment in the story, you have 2 copies of 2. So that's OK, though, because the third line of code says temp gets copied into b. So what's temp? 1 gets copied into b. So let me overwrite this 2 with a 1. And now what happens? Now, unfortunately, the code ends. Swap doesn't actually do anything with the result. And the problem in C is that I could have had a return value. I could go in there and change void to int. But which one am I going to return? The A or the B? The whole goal is to swap two values, and it seems kind of lame if you can't write a function to do something as common per last week's sorting algorithms as swapping two values. But what really happens? Well, even though when this program starts running, main is using this chunk of memory at the bottom in the so-called stack, and the stack is just like a cafeteria, a stack of trays. It grows up like this. Here's main's memory on the stack. Here's the swap function's memory on the stack. It's using 3 ints instead of only 2. What happens when the function returns, whether it's void or not? The sort of recollection that this is swap's memory goes away, and garbage values are left. So adorably, we get rid of these values here. And there's still data there. Technically, the numbers 1, 1, and 2 are still there in the computer's memory, but they no longer belong to us because the function has now returned. So they're still in there. And this is kind of an example visually of why there's other stuff in memory, even though you didn't put it there necessarily. Sometimes you did put it there. But now, once swap returns, you only should be touching memory inside of main. But we've never actually copied one value into main. We haven't returned anything, and we haven't solved this fundamentally. So how could we do this? Well, what if we instead passed into swap not copies of x and y, calling them a and b? What if they passed in breadcrumbs to x and y, sort of a treasures map that will lead swap to the actual x and to the actual y? Today, we have that capability using pointers. So suppose that we use this code instead. There's a lot of stars going on here, which is a bit annoying, but let's consider what it is we're trying to achieve. What if we pass in not x and y, but the address of x and the address of y, respectively? Breadcrumbs, if you will, that will lead swap to the original values. Then what we do is we still give ourselves a temp variable, like an empty glass. It's still a glass, so we still call it an int. But what do we want to put into that temporary variable? We don't want to put a into it, because that's an address now. We want to go to that address, per the star, and put whatever's at that address. What do we then want to do? Well, we want to then copy into whatever's at location A. We want to copy over to location A's contents, whatever is at locations B's contents. And then lastly, we want to copy temp into whatever's at location B. So again, we're very deliberately introducing all of these stars because we don't want to change any of these addresses. We want to go to these addresses per the dereference operator and put values there or get values from. So what does this actually mean? Well, if I kind of rewind in this story and I go back here, I still have temp, although I'm going to delete its value to begin with. I still have B, and I still have A. But what's going to be different this time is how I use A and B. So let me finish erasing those. That's A on the left. This is B on the right. At this point in the story, we're rerunning swap with this new and improved version. And let's see what happens. Well, x is presumably at some address. Maybe it's like 0x123, as always. What then does A get when I'm using this code? The value of A is 0x123. What is the value of B? Maybe y is at 0x456. What goes in B? Well, I'm going to put 0x456. And then what am I going to do? Based on these 3 lines of code, I'm going to store in temp whatever is at the address in A. What is the address in A? That's this thing here. So I'm going to put 1 in temp. Line 2, I'm going to go to B. All right, B is 456. So I'm going to B. And I'm going to store 2 at whatever is at location A, and at location A is 1, 2, 3. So that's this. So what am I going to do? I'm going to change this one to a 2. Last line of code. Get the value of temp, which is 1, and then put it at whatever the location B is. So B, 4, 5, 6, go there, and change it to be the value of temp, TMP, which puts 1 here. That's it for the code. There's still no return value. Swap returns, which means these 3 temporary variables are sort of garbage values now. They can be reused by subsequent function calls. But now I've actually swapped the values of x and y, which is to say what came as naturally as the real world here for Mariana is not quite as simply done in C, because, again, functions are sort of isolated from each other. You can pass in values, but you get copies of those values. If you want one function to affect the value of a variable somewhere else, you have to, 1, understand what's going on, but 2, pass things in as by a pointer here. So if I go back to my code here, I need to make a few changes now. Let me get rid of these extra printfs. Let me go in and add all these stars. So I'm dereferencing these actual addresses here and here, and I've got to make one more change. How do I now call swap if swap is expecting an int star and an int star? That is the address of an int and the address of another int. What do I change on line 11 here? Yeah. Sorry, a little louder. Sorry, the address of operator. So up here on line 11, we do ampersand x and ampersand y. So that, yes, we're technically passing in a copy of a value, but this time the copy we're passing in is technically an address. And as soon as we have an address, just like when I held up the fuzzy finger, or the foamy finger, I can point at that address. I can go to that address and actually get a value from the mailbox or put a value into the mailbox if I even want. So let's cross our fingers now and do make swap, enter. Oh my God, so many mistakes. Oh, I didn't remember to change my prototype. So let me go way up here and add 2 more stars, because I made that change already. Make swap, / swap, and voila, now I have actually swapped. Thank you. Thank you, the 2 values. All right, so what more can we do here? Well, let me consider that all this time we've been deliberately using getString and getInt and getFloat and so forth, but for a reason. These aren't just training wheels for the sake of like making things easier. They're actually in place to make your code safer. And to illustrate this, let me go ahead and open up one other file here. How about a file called code scanf.c? It turns out that the old school way, the way in C really, of getting user input is via functions like scanf. And let me go ahead and include standard.io.h, int main void, and without using the CS50 library at all for strings or for any of those get functions, let me give myself an int called x. Let me just print out what the value of x is, even though it's going to be, or rather ask the user for the value by asking them for x. And I'm going to use a function called scanf that's going to scan in an integer using %i. And I'm going to store whatever the human types in at this location. And then I'm going to go ahead and, just so we can see what happened, I'm going to print out with %i whatever the human typed in as follows. All right, so line 8 is week 1 style code. Line 5 and 6 is week 1 style code. So the curiosity today is this new line. Scanf is another function in standard.io.h. And notice what I'm doing. I'm using the same syntax that I use for printf, which is kind of a little clue, a format code to tell scanf what it is I want to scan in, that is, read from the human's keyboard. And I'm telling it where to put whatever the human typed in. I can't just say x, because we run into the same darn problem as with swap. I have to give a little breadcrumb to the variable where I want scanf to put the human's integer. And so this just tells the computer to get an int. This is what you would have had to type essentially in week 1 just to get an int from the user. And there's a whole bunch of things that can go wrong still, but that's the cryptic syntax we would have had to show you in week 1. Let me go ahead and make scanf here. Oops. User error. Put the semicolon in the wrong place. Make scanf. Enter. Oh my God. Non-void doesn't return a value. Oh, thank you. Strike 2. OK. Make scanf. There we go. OK, so scanf, I'm going to type in a number like 50, and it just prints it back out. So that is the sort of traditional way of implementing something like getInt. The problem, though, is when you start to get into strings, things get dangerous quickly. Let me delete all of this and give myself a string s, although wait a minute, we don't call it strings anymore, char star to store a string. Then let me go ahead and just prompt the user for a string using just printf. Then let me go ahead and use scanf, ask them for a string this time with %s, and store it at that address. Then let me go ahead and print out whatever the human typed in just by using the same notation. So here, line 5 is the same thing as string s, but we've taken back that layer today, so it's char star s. This is just week 1. This is just week 1. Line 7 is new. Scanf will also read from the human's keyboard a string and store it at s. But that's OK, because s is an address. It's correct not to do the ampersand. It's not necessary. A string is and has always been a char star, aka string. The problem, though, arises as follows. If I do make scanf, oh my God, what did I do? Oh, I can't. OK, we have certain defenses in place with make. Let me do clang of scanf .c and output a program called scanf. All right, so I'm overriding some of our pedagogical defenses that we have in place with make. Let me now run scanf of this version, enter, and let me type in something like, how about hi again? Huh. So it didn't even store something, and it weirdly printed out null. This time it's in lowercase, but that is somewhat related. What did I fundamentally do wrong, though, here? Why is this getting more and more dangerous? And let me illustrate the point even more. What if I type in not just something like hello, which also doesn't work. What if I do like hello and make a really long string, enter? That still works. Can I do this again? Let's try again. All right, a really long, unexpectedly long string. This is the non-determinism kicking it. Enter. All right, damn it. I was trying to trigger a segmentation fault, but it wouldn't. But the point still remains. It's still not working. But what's the essence of why this isn't working and it's not storing my actual input? Yeah. We have to make space for it. So what we're missing here is malloc or something like that. So I could do that. I could do something like this. Well, let me let the human type in at least a 3-letter word. So I could do malloc of 3 plus 1 for the null character. So like, let me give them 4 characters. And let me go ahead and do make scanf. Whoops. Nope, sorry. Clang. I have to search. Nope. Damn it. Oh. Include standard lib.h. There we go. That gives me malloc. Now I'm going to recompile this with clang. Now I'm going to rerun it. And now I'm going to type in my first thing, hi. That now works. And let me get a little aggressive now and type in hello, which is too long. Still works, but I'm getting lucky. Let me try a hello. Damn it. That still works too. Sort of. But it actually, not quite. There's some weirdness going on there already. It turns out I could also do this. I could actually just say char star 4 and give myself an array of 4 characters. Let me try this one more time. So let me rerun clang /scanf. Hello, clearly exceeding the 4 characters. There we go. Thank you. All right, so the point here, though, is if we hadn't given you getInt, you would have had to use the scanf thing. Not a huge deal because it seemed to work. But if we hadn't given you getString, you would have had to do stuff like this, knowing about malloc already, or knowing about strings being arrays. And even now, there's a danger. If the human types in 5 letters, 6 letters, 100 letters, this code, like with the hello input, will probably just crash, which is bad. So getString also has this functionality built in where we have a fancy loop inside such that we allocate, using malloc, as many bytes as you physically type in. And we use malloc essentially every keystroke. The moment you type in H-E-L-L-O, we're sort of like laying the tracks as we go, and we keep allocating more and more memory so that we, theoretically, will never crash with getString, even though it's this easy to crash your code using scanf if you, again, did it without the help of a library. So where are we all going with this? Well, let me show you a few final examples that will pave the way for what will be problem set 4. Let me go ahead and open up from today's code, which is available on the course's website. For instance, a program like this called phonebook.c. And I'm just going to give you a quick tour of it that you'll see more details on in the context of pset 4 itself. We're going to introduce a few new functions you're going to see. You're going to see a function called fopen, which stands for file open. And it takes 2 arguments, the name of a file to open, like a CSV that you might manipulate in Excel or Google Spreadsheets or the like, comma, separated values. And then something like A for append, R for read, W for write, depending on whether you want to add to the file, just open it up, or change it. We're going to introduce you to a file pointer. You'll see that capital file, which is a little non-conventional, capital file is a pointer to an actual file on the computer's hard drive so that you can actually access something like a CSV file or, heck, even images. And we're going to see down below that you're also going to have the ability to write files as well, or print to files. You'll see functions like fprintf for file printf, or fwrite, file write, which now that you will begin to understand pointers, you'll have the ability to actually not only read files, text files, images, other things, but also write them out. In fact, for instance, just as a teaser here, JPEGs will be one of the things we focus on this week, where we give you a forensic image, and your goal is to recover as many photographs from this forensic image of like a digital camera as you possibly can. And the way you're going to do that is by knowing in advance that every JPEG in the world starts with these 3 bytes, written in hexadecimal, but these 3 numbers. And so in fact, just as a teaser, let me open up an example you'll see on the course's website for today. If I scroll through here, you'll see a program that does a little something like this. And again, more on this in if we could, hit the button. Oh, there we go. So here we have the notion of a byte. We're going to create for ourselves, we'll see a data type called byte, which is a common convention. This gives me 3 bytes. And you're going to learn about a function called fread, which reads from a file some number of bytes, for instance, 3 bytes. We might then use code like this. If bytes bracket 0 equals OXFF, and bytes bracket 1 equals 0xD8, and bytes bracket 2 equals 0xFF, all 3 of those bytes I just claimed represent a JPEG, you'll see an output like this. Let me go ahead and run this program as follows. Let me copy jpeg.c into my directory from today's distribution. Let me do make JPEG. And let me run JPEG on a file, which is available online, called lecture.jpg. And I claim, yes, it's possibly a JPEG. Well, what is that file? Let me open it up for us, called lecture.jpg. And here, for instance, is that same photo with which we began class, namely implemented as a JPEG. But what we're also going to do this week is start to implement our own sort of filters a la Instagram, whereby we might take images and actually run them through a program that creates different versions thereof. For instance, using a different file format called BMP, which is